Hi everyone. So in this lecture, we are going to start our next subject, that is digital electronics. Okay. So the motive of this lecture will be to understand the basic terms like what is analog signal, what is digital signal, what is the advantage of digital signals over analog signals, what is the meaning of pulse width, what is the meaning of time period, what is the meaning of frequency, what is known by data sequence, all kind of things. First, we will understand the basic terms. After that, we will study about digital blocks. So what are the fundamental digital blocks? How do we build a digital system? So from the next lecture onwards, we will build that digital system. So this is just a fundamental lecture, might be a 30 minutes or 40 minutes video only. So let's start. The first question is, these four waveforms are given. You need to tell me which is analog signal and which is digital signal. Okay. So like fundamentally everyone knows this is a analog signal only because the amplitude is continuous. So all kind of values it can have. Let's just say if this value is 2 volt, let's just say if this value is 2 volt and this value is 5 volt. And let's just say this value is 1 volt. So between 1 volt to 5 volt, it can have all the values, all the possible values. So it can have infinite values. In between, it can have infinite value. So this is an analog signal. So analog signal simply means it has continuous amplitude. Continuous amplitude means it can have all the infinite amount of values. Okay. So this is an analog signal only. So first one, this is an analog signal. Let's come to this signal. What do you think? What kind of signal is that? Digital signal. Look, 90% of the people will say this is a digital signal. But no, if I show you this particular waveform, then you need to ask me, sir, how many values these can have? Let's just say this is 1 volt, this is 2 volt, this is 5 volt, this is 0.5 volt, this is 3 volt, this is 2.5 volt. So again, this waveform is also having a lot of values. This is just sampled in time, nothing else. Okay. The time window is different. Like from 0 to T1, there is a certain value. From T1 to T2, from T1 to 2T1, there is a certain value. To 2T1 to 3T1, there is a certain value. But it doesn't mean that it cannot have infinite amount of values. It can also have any value. Okay. It is not discretized. Okay. Are you getting this point? This waveform can also have any amount of value. 1, 1.1, 1.2 volt. This is just a part of waveform. If I draw more parts, then it can also have any amount of value. So here, amplitude is not fixed, that only these amplitudes are fixed. This is not the case here. Okay. So this is also an analog signal only. We usually call it sampled analog, but you don't need to think sample analog, all kind of things. When we study signal systems, there I will tell you sample analog, what do you mean by sample analog and all kind of things. Okay. Now, what is this signal? Here, I have fixed the amplitude, V1, V2 and V3. So, amplitude are fixed. Only 3 kind of amplitude you can have, V1, V2 and V3. That's it. Okay. There could be 5 kind of amplitude, there could be 10, there could be 20. But the amplitude is fixed. Amplitude is discretized. That only these kind of amplitude you can have, V1, V2 and V3. Only these levels you can have. So, this is a digital signal. So, do you understand the fundamental difference between analog and digital signal? In analog signal, the amplitude is continuous. From 0 to 5, any value you can have. Again, here as well, this is just discretized in time. Okay? This is just discretized in time. This is discrete time and continuous amplitude. Discrete time, continuous amplitude. Here, the amplitude is V1, V2 and V3. 3 kind of amplitude only you can have. Or it could be V4 as well. But the amplitude is fixed. You cannot have any value between V1 and V2. Okay. That's why it is known as digital signal. Same goes here. Amplitude are fixed. V1, V2 and V3. Or V4 can also be there. V5 can also be there. V6 can also be there. It is discretized in time. Okay. It is discretized in time as well. It is discretized in amplitude as well. So it is also digital signal. So on top level, what did you understand? If your amplitude is discretized, if your amplitude is fixed for some values, that means that would be your digital signal, otherwise it would be analog. If your amplitude is continuous, that means that is analog. And if your amplitude is discretized in some fixed amplitudes, that means it would be a digital signal. So that is the fundamental difference between analog and digital signal. So if 4 kind of waveforms are given, I hope you will be able to tell which is analog and which is digital. So you just need to see if continuous amplitude is there, that means the amplitude can have any amount of value, that would be analog, otherwise that would be digital. So basically this is the thing. Continuous amplitude, that means analog signal, and discrete amplitude, that means that is digital signal. That's it. This is the major difference between analog and digital signal. Okay then. Now, what is the advantage of digital over analog? Why would I use a digital system rather than analog system? Okay. So from analog signal, how can I make a digital signal? So basically, this is just a waveform from 0 to 5. I will have all the values from 0 to 5. Now what I will do, I will define the levels. Let's just say what I say, from 0 to 1 volt, all the values, whatever the value are there from 0 to 1 volt, I will define that as level L1. Okay. Let's just say there is my input value is 0.5 volt. So what I will do, I will put that in L1 only. If my input value is 0.75 volt, I will put that in L1 only. If my input value is 0.99 volt, I will put that in L1 only. If my input value is 1.02 volt, I will put that in L2 level. Okay. Similarly, from 1 to 2 volt, I have defined another level. From 2 to 3 volt, I have defined another level. And from 3 to 4 volt, I have defined another level. So in this manner, I have defined the levels. Level L1, level L2, level L3, level L4. So from basically you can have only this value. So this is becoming a digital signal only. You can have this value. This value can be denoted by anything. This can be, let's just say I denote this value as 1 volt. This value as 2 volt. This value as 3 volt. Then 4 volt and 5 volt. So now I can have only 1 volt, only 2 volt, only 3 volt, only 4 volt, and only 5 volt. Need not necessary that I define this value as 1 volt only. I can define this value as 0.5 volt only. I can define this value as 0.5 volt as well. What I mean to say is that from 0 to 1 volt, whatever the value I get, I will denote all the values by 0.5 volt. And need not necessary I define it with voltage. I can define it with bits as well. What do you mean by bits? That we will study. Let's just say level L1 I am defining as 0001 by these bits. Level L2 I am defining as 010, 00011, 000. Let's just say I am defining by 000, and this I am defining by 111. So by any amount of bits also I can define it. It's just that these bits should be different. 001 is different from 010, 011. All these are different. So I can define different levels by different naming. Basically, till now you just need to think I am defining different levels by different naming. Okay. So just a continuous signal, I have made that discretized. So this is my digital signal. Okay. Now let's just say I am transmitting a particular signal over a wire. Okay, over a wire I am transmitting a particular signal. So these bits are not certain. If you did not understand the meaning of these bits, there is no issue. We will understand the meaning of bits. What do you mean by bits? How do we define it? So everything, how do we discretize it? How do we quantize it? Everything we will study in this particular subject only. So you don't need to worry if you are not able to understand this bits thing. Okay, 011, 000. How do I define it? So everything we will study. Okay. No need to worry. So now what I am doing, I am transmitting some particular input value over a wire to this is the transmitter and this is the receiver. Okay. This is the transmitter and this is the receiver. So over a wire, I am transmitting a particular value to a receiver. So let's just say if I do analog transmission. Okay. So I am putting 1.72 volt here. This is a wire or this is a channel, and here there is a receiver. So I transmitted 1.72 volt, but in the channel there was, or in the wire there was some noise present. So because of the noise, I should make it like this. So because of the noise, 0.3 voltage, 0.03 voltage is being added. Because of the noise, 0.03 volt voltage is added, and at the receiver you get 1.75 volt. Now what receiver will see? Receiver will see 1.75 volt. Now the receiver doesn't know how much noise is added and what the transmitter transmitted. The receiver doesn't know what was the amount of noise and what was transmitted. If receiver already knows that 1.72 volt was transmitted, then what is the need of receiver? Basically, what do you mean by receiver? You transmit something and you receive it. You transmit something from here, and at the receiver you use it, right? You are using 1.75 volt. Now you don't know what was transmitted. The transmitted value was 1.72 volt. But the same case is, but if I take the same case for digital transmission, so what was there? 1.72 volt, right? I need to transmit 1.72 volt. And 1.72 volt will be denoted by level L2. 1.72 volt will be denoted by level L2 only, right? So this is our level L2. Now what will happen? Noise will be added. How much noise will be added? Plus 0.3. Now this much noise is added. That means here you will receive 1.75 volt only, right? And 1.75 volt will be denoted by level L2 only. So here L2 was transmitted and L2 is received only. So whatever that was transmitted, the same level is received. So even if there was 0.3 volt noise, there is not much effect of the noise, right? Because you are transmitting L2 only and you are receiving L2. So that's why we say there is better noise performance in digital signals. So if someone is asking what is the biggest advantage of digital over analog, then you need to say it is better in noise performance. Now people will say, sir, this is not a reliable transmission, because you actually sent 1.72 volt and you are receiving 1.75 volt. So here, like, resolution is better. Certainly in analog, resolution is better because you would know 1.72 and 1.75. But here all the values between 1 volt to 2 volt all are defined as L2 only. So no matter whether you send 1.1 or 1.9, it will take it as L2 only. So let's just say I need a system which does not need me between 1 and 2 volt. Let's just say I need a system where like I don't need better resolution. I just need that from 1 to 2 volt, it can be defined by a certain level only. So depending on the requirement of system, you will use analog and digital. But the thing is, if I use digital, it will be better in noise performance. Okay, it will be less affected by the noise because what my system requires, that between 1 volt to 2 volt, I can name it as one level only. 1 से 2 volt के बीच में जो भी है मैं सबको एक ही level दे दूंगा. This is what my system requires. So if I transmit L2, I will receive L2 only. So that's why we call it, this is digital system is better in noise performance. So this is the example that you can give. If you give 1.72 volt, noise is added, you receive 1.75. You give L2, noise is added, you receive L2 only. Okay, because all are defined as a certain level. So this is better in noise performance. Also, there is one more advantage that you can write. Easy to store. How it is easy to store? Digital bits are easy to store. And now in the next part of this video only, you will get to know that we define digital bits by 0 and 1 only. So there are only 2 bits. So they are easier to store. Digital bits are easier to store. But let's just say I need to store 0 to 5 volt. So these are continuous value. I need to store 0 to 5 volt continuous value. There will be infinite values in between. So better if we need to store only 0 and 1, that is a better thing, right? So digital bits are easier to store. So digital data are easier to store. So this is also one of the advantages. So there are major 2 advantages only. Easy to store. How do we store it? We store digital bits in flip-flops. So that we will study in the next part of this chapter only about flip-flops. And how do we store an analog signal? Capacitor. In the capacitor we store, right? This is the switch, this is the 5 volt. If I turn on the switch, then 5 volt will be stored here. So we store analog signal through the capacitor and we store digital bits in flip-flops. Okay, what is the use of a flop? To store digital data, right? So we will study about these things, about the capacitor and everything we have studied in analog electronics. If you haven't studied analog electronics, then you will certainly study it as well. Okay, so yeah, so these are the advantage of digital signal. So basically, till now, what can be asked? Difference between analog and digital signal and what is the advantage? So only 2-minute summary is there. Analog and digital signal, continuous amplitude, analog signal, discrete amplitude, digital signal. Advantage of digital over analog, noise performance. Okay, if 0.03 volt is added, then it is, the receiver wouldn't know 1.72 volt was transmitted. But here, if you add 0.03 noise, then certainly L2 is received and L2 was transmitted only. Okay, so better in noise performance and easy to store. Well and good. Now we will see. Now this thing is there, that how do we define a digital system. So in digital system, there are only two possible states. Okay, majorly two possible state only, high state and low state. So generally we show high state by 1 volt. Sorry, not 1 volt. Generally we show high state by 1, bit 1. And this is bit 0. What do you mean by bit? So 1 and 0 are called bits only. And the number system in which it is defined, that is known as binary number system. Okay. Basically, in our decimal number system, forget about decimal, our normal number system, we define values from 0, 1, 2 till 9, right? So these are the values we can have in our normal number system, 0 to 9. In binary number system, we can have only two values. Basically, we say we have base 10. So if we have base 10, that means we can have values from 0 to 9. Here we have base 2. So we can have values from 0 to 1, 0 and 1. So this is known as binary number system. So by bit 1, we generally show high, and by bit 0, we generally show low. High we can show by plus 5 volt, and low we can show by 0 volt. Or we can show high by plus 5 and low by minus 5. Basically, it will be defined in the problem that what is high, what is low. And if it is not defined, then generally you will take plus 5 and 0. Plus 5 is shown by high and 0 volt is shown by low. Okay. So this is our this is how we define a digital waveform or a digital signal. Okay. So 1 and plus 5, 0 and 0 volt. Could be other ways as well, plus 5, minus 5. So these kind of ways can also be there. So this is how we generally define a digital signal or a digital waveform. Okay, so digital systems such as computers can understand only 1 and 0. So this two-state number system is known as binary number system, and these two bits, these two numbers or these two digits, 0 and 1, are called as bits. Okay, very simple thing. Now let's move on to the next slide, where here we will see a digital waveform. So this is known as a digital waveform. So basically what we are doing, we are going from 0 to 1 and then coming down from 1 to 0 again. And here we are going from 1 to 0 and then coming up from 0 to 1. So these kind of digital waveform you will see. Okay. 0 to 1 you are going, 1 to 0, then from 0 to 1 you are going. So basically this part, 1, 0, 1, 1 to 0, 0 to 1 is this. Okay. And this part, you are going from 0 to 1 and coming 1 to 0. This part, 0 to 1 and 1 to 0 is this. Okay. So these two parts I have drawn. Now there are different terms. So if you are going from 0 to 1, that means this is known as rising edge. Because you are rising from 0 to 1. So this edge is known as rising edge. So these kind of things will be a lot of times used. In the complete digital electronics, you will see me when we study sequential circuits. So there you will see me telling rising edge of the clock, falling edge of the clock. We will understand what is a clock, but these terms you need to know. Rising edge means 0 to 1. And this is known as falling edge. From 1 to 0 it is coming. So this is your falling edge. Okay. 1 to 0 you are going. What do you think? What is that? Falling edge. This is what? Falling edge. Zero to 1 you are going. That means this is rising edge. So rising edge will have arrow upward and falling edge will have arrow downward. Rising edge. Okay. Now this width is known as pulse width. This width is known as pulse width. So pulse width is the amount of time for which your signal is high. Okay. The amount of time for which your signal is high. So pulse width is defined for high amplitude only. It could be plus 5 volt as well. It could be 1 as well. It could be anything. Okay. Can I call this as pulse width? Is this my pulse width? No, absolutely not. This is not the pulse width. Okay. Because pulse width is defined only for high amplitude. So this is low amplitude. This is not pulse width. This was the part of this particular waveform. 1, 0, 1. So this much part was there. So this is not the pulse width. This part is not pulse width. This part can be defined as pulse width. This is your pulse width. So for the amount of time it is high, that amount of time only known as pulse width. So this is your pulse width. Okay. So 3 terms we have understood: rising edge, falling edge, and pulse width. Now what is rise time? Rise time is time taken to go from 0 to 1. Time taken to go from 0 to 1. Here what is the rise time? What do you think? You are going from 0 to 1. How much time you are taking? Here it is 0 and here it is 1. How much time you are taking? 0 second. So ideally rise time is 0 and fall time taken from to come from 1 to 0. Time taken to come from 1 to 0. 0 to 1, 1 to 0. How much time you are taking? How much time you are taking to come from 1 to 0? 0 second only. Here it was 1 and immediately you came down to 0. So ideally rise time is equals to fall time is equals to 0 second. Okay. 5 terms we have seen: rising edge, falling edge, pulse width, rise time, and fall time. I hope you know the meaning of everything. But this is an ideal digital waveform. But generally, you cannot make a digital waveform which is ideal. So generally, this is how your digital waveform will look like. So only this digital waveform I have made here. Okay, only this one, 0 to 1 and 1 to 0. This waveform I have made here. Okay, so practically digital waveform will have a finite rise time and a finite fall time. Okay, so you are rising from 0 to 1, so you are taking some time. This is the time you are taking. Now, how do we define a rise time? So generally, we take 10% to 90%. That means if my high amplitude is shown by 1 volt, it could be shown by 1 volt as well. High is shown by 1 volt and low is shown by 0 volt. Anything can be there. High is shown by 2 volt, low is shown by 0 volt. Let's just say my high is shown by 1 volt only. That means when my amplitude is 0.1 and when my amplitude has reached 0.9 volt. So from 0.1 to 0.9 volt, how much time it is taking? That time is defined as rise time. So TR, that means rise time. Rise time. Okay. So from 10% to 10% of the maximum value and 90% of the maximum value. So this much time window is defined as the rise time. And same for the fall time, 90% to 10%. So this is defined as fall time. Full time. If my amplitude was, let's just say if my high amplitude was 5 volt, if this was 5 volt, if this one was 5 volt, then what would be the 90%? 4.5. And what would be the 10%? 0.5. So the time taken to go from 0.5 to 4.5 would be your rise time. And the time taken to come from 4.5 to 0.5 would be your fall time. Both has to be same. Rise time and fall time has to be same. No. It depends on the system. Let's just say I'm making if you don't know these kind of things, then you can ignore it. Okay. If I'm making a digital waveform from a CMOS inverter, let's just say, okay. So if I keep it low, then first it will charge and then it will discharge. So it will charge and then discharge. It will charge and discharge. So charging and discharging will depend on the W by L ratio of this, right? W by L ratio of this or the mobility of this, because you will replace this with the resistance. If you don't know, you can ignore it for some time. I am telling this for only those guys who know it. So rise time and fall time can be different. So for now, you can just understand that rise time and fall time is different. It depends on the system from where you are making your clock. Okay. If you are making your clock from here, rise time and fall time. If you are making your digital signal from here, so both can have different rise time and fall time. Okay. It depends on these particular blocks. Okay. So it's not necessary that rise time and fall time will be same. And now what will be defined as a pulse width? From where you will take the pulse width? Pulse width was that for the time it was 1. So how do we define pulse width? From here to here or from here to here? No, 50%. Take the 50% of this. So basically, if my high amplitude was plus 5 volts, so the time when it was 2.5 volt. So here also it will be 2.5 volt and here also it will be 2.5 volt. So this much window I will take as pulse width. Okay, so this will be defined as pulse width. 50%. So this is a practical waveform. Ideally, in the simulations, you will never get these kind of waveforms. In the simulation, you will get these kind of waveforms only. 0 to 90%, 90 to 10% is defined as rise time and fall time, and between 50% and 50%, this is defined as pulse width. Okay, so here I will write going from 10% to 90%, 10 to 90%, and what is fall time? Coming down from 90% to 10%. This is your fall time. Okay, so these kind of basic things we are understanding very, very nicely. Okay, let's move to the next part. So what do you mean by periodic digital waveform? So the waveform is periodic. What does that mean? That after a certain time it is being repeated. So you can see after this much of time it is being repeated, right? After time t it is being repeated. So this is known as the time period of this digital waveform. You can see this waveform is being repeated after this much of time. Time t. So this waveform is being repeated after this much time. So this is known as time period. So what is time period? The time window for which or at which the waveform is being repeated. So that is known as time period. So the very basic thing in your elementary classes also you must have studied it. Time t. So this is a periodic digital waveform. Is this a periodic digital waveform? You cannot see any pattern being repeated. Here this was the pattern, here this is the pattern, here this is the pattern. So you cannot see any pattern being repeated. So this is non-periodic digital waveform. Now there is one more famous term, that is duty cycle. So a lot of times it will be used. What do you mean by duty cycle? So the amount of time for which it was high. What was that? That was pulse width. So pulse width divided by time period. Basically this width, the amount of time for which it was high. This was defined as pulse width, right? This would be your pulse width. This would be your pulse width. PW means pulse width. Okay, PW means pulse width. So the amount of time for which it was high divided by the time period. So duty cycle is defined only for periodic waveforms. Okay, for non-periodic waveforms it will not be defined. You cannot say that, sir, pulse width divided by the time period. Which pulse width you will take? This pulse width or this pulse width? Right, so it is not defined for non-periodic waveform. It is defined only for periodic waveforms. So pulse width divided by time period. And what is the frequency? Here I did not write frequency. What is frequency? Frequency of oscillation or frequency 1 by time period. Okay, did I define it? No. So frequency is defined as 1 by time period. Okay, this is also a very basic formula which you might remember, or if you don't remember then now you can remember it. So frequency is 1 by time period. Okay, so let's see this question. Very basic question is there. So 1010, this is a digital waveform. So for the given waveform, you need to find the pulse width. What is the pulse width? This is the pulse width. The amount of time for which this is high. So pulse width is 1 second. What is the time period? The time for which waveform is being repeated. So from 0 to 10, this waveform is being repeated for this much time window, right? Or this much time window. This waveform is being repeated for this much time window. So that is 10 seconds. What is the frequency? 1 by time period, 1 by 10. That is 0.1. What is the unit of frequency? Hertz. Okay. Second inverse you can say over hertz. So this is the frequency. What is the duty cycle? Duty cycle is 1 by pulse width divided by, what is the pulse width? 1 divided by the time period, 1 by 10. Duty cycle is defined in percentage. So into 100%. So that would be 10% duty cycle. So for the complete amount of time, only for 10% of the time it was high. This is what you mean by duty cycle. Only for the 10% of the time it was high. So in 10 seconds, it was high for 1 second. That means 10% of 10. That is 1 only. So only for 10% of the time it was high. So this is what you mean by duty cycle. So pulse width, time period, frequency and duty cycle. So these terms you must have understood. Very basic terms. Rising edge, falling edge and pulse width. Rising edge, falling edge, pulse width, duty cycle, time period, frequency, all these terms you must have understood. Analog digital signal you must have understood. And what did we see? The advantage of digital over analog. So these kind of terms we have understood. Now a very important term will come, that is clock. So what do you mean by clock? So it is an electronic signal which will oscillate between 1 and 0, high signal and low signal. Okay. electronic signal which will oscillate between 1 and 0, and ideally duty cycle is 50%. That means for 50% of the time it was high and 50% of the time it was low. 50% high, 50% low. So this is known as clock. Okay, high, low, high, low, high, low. So this will be the rising of the edge of the clock, right? It is going from low to high, rising edge. This is also 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 rising edge. And then this would be the falling edge, falling edge, falling edge, falling edge, falling edge, falling edge. So rising edge and falling edge will come alternatively. So this is what you mean by clock. Okay. It will oscillate between 1, 0, 1, 0, 1, 0, 1, 0, and ideally with the duty cycle of 50%. So what is the time period here? So this is the cycle which is being repeated. If I again write it. So this is the cycle which is being repeated. This much of cycle. If you see it clearly, how much cycle is being repeated? This much cycle is being repeated. So this is the time period, right? And what will be the frequency? 1 by time period. Okay, this word is between only. Nothing is written after that. So an electronic signal which oscillates between high state and low state at a constant frequency ideally have a duty cycle of 50%. So this is known as clock. Okay, and it will be highly used. All time it will be used in your digital electronics chapter when we start studying sequential circuits.
So now we will see data sequence. Actually, there will be a cut in between the video because some interruption came in between. So now let's study about data sequence. So what is data sequence? Data sequence is the electronic representation of a information. Okay, let's just say there is some information which I want to give to my laptop. So what did I say? A digital system. That means let's just say a computer. So a digital system can understand only 0 and 1 only. So if I need to give some information, let's just say my information is type the name Himanshu, Himanshu. So I have to give that in the terms of 0 and 1 only, in the terms of bits only, because the computer can understand 0 and 1, right? So 0, 1, 0, 1, 1. So let's just say I'm giving some data sequence 0, 1, 0, 1, 1, 1, 0, 1, 1, 0 to my digital system. And now I am saying my data rate is 2 bits per second. What is BPS? Bits per second. Bits per second. So what do you understand by that? 2 bits per second. That means in 1 second, we are understanding the meaning of 2 bits per second. And let me tell you, people will study complete digital electronics, they will study complete communication system, and they do not know the meaning of this. So understand it very carefully. 2 bits per second, that means in 1 second I will get 2 bits. In 1 second I will get 2 bits. So 1 bit I will get in half second, right? 1 bit I will get in half second. So this bit 0 will be there for half second. Then what you will get? You will get 1. This bit 0 will be there for half second. Then what you will get? You will get 1. For how much time? Half second only. Then you will get bit 0 again. For how much time? Half second. Then you will get bit 1. For how much time? Half second. Then again you will get bit 1. For how much time? Half second. Half second. Then again you will get bit 1. For how much time? Half second. Then 0 for how much time? Half second. Then again 1 for half second. Then again 0 for half second. Then again 0 for another half second. So basically, let's just say if this was your 0 second, then this would be your half second. This would be your 1 second. This would be your 3 by 2 second. What this would be? This would be 2 second. This would be 2.5. This would be 3. This would be 3.5. This would be 4. This would be 4.5. And this is 5. So in 5 seconds, how many bits you will have? 10 bits. So let's just count 3, 3, 6, 9 and 10. So in 5 seconds you are having 10 bits. So the meaning of this 2 bits per second, that means in 1 second you are getting 2 bits. That means 1 bit you are getting in half second. So this window is half second. This window is 0.5 sec. This window is also 0.5 second. This window also 0.5 second. So 0.5 sec, 0.5 sec, 0.5 sec, 0.5 sec, 0.5, 0.5, 0.5, 0.5. Okay. So this is the meaning of data rate. So there is a difference between clock and data rate. If I am saying the time period of my clock is 1 second, That means this window is 1 second, not this window is 1 second. Okay, so very basic difference is there, but it is very important. Time period is 1 second, that means this much window is 1 second, not this window is 1 second. So let's solve a problem regarding that, you will understand it more. So the question given is, you need to make a clock and data sequence, given that the clock frequency is 100 megahertz and the data rate is 100 megabits per second. So clock frequency, let's just make the clock first. You need to make a clock. And what they are saying, the frequency is 100 megahertz. 100 megahertz. Megahertz means 10 to the power 8 hertz. So can you make the time period? That would be 1 by f, 10 to the power minus 8 second, or I can write 10 nanosecond, right? Because 10 to the power 8 I can write as 10 into 10 to the power minus 9. So 10 to the power minus 9 would be nano. So 10 nanosecond. So my time period is 10 nanosecond. So if I make this clock, this is how my clock would look like. It will keep on going like this. Right? Again rising edge will come. So this much window will be 10 nanosecond. Say yes or no, right? This much window will be 10 nanosecond. Now what I need to make, take any random data sequence. We need to make a data sequence. Data sequence is not given. Okay, it could be anything. It could be 1 0 1 1 1 or 0 1 1 0 1 1 1 0, anything it could be. So we need to take any random data sequence. So if you don't know the data sequence, then how do we draw it? So usually we draw it like this. This is how we draw it. So in a lot of textbook, you will see some diagrams like this. So if you see any diagram like this, that means certainly it is a data sequence. And it is a random data sequence. Because we don't know what will be our sequence. It could be 1 0 0 1 1 0 0 1. So basically we show both of the waveforms here. So in this particular waveform you can see 1 as well and you can see 0 as well, right? So this is how we show a random data sequence. Look, these terms will not be used right immediately. Now in the next lecture we are going to study about gates, logic gates. We will build a digital system. So we will study about logic gates. So there you will not use these terms data and all. But when we study sequential circuits, there it will be used. So for that I am building up your concept here. Okay. So in a lot of textbook you will see waveforms like this. What does that mean? This is a random data sequence because it can take one value as well. It can take zero value as well. It can take one value. It can take zero value. It can take one value. 1 0 1 0 1 0. So if I say this was my data sequence, so yeah, 1 0 1 1 1 0 1 1. If I say this was my data sequence, 0 1 1 0. If I say this is my data sequence, 1 1 1 0. So for a random data sequence we show both of the waveforms, 1 0 1 0 1 0 1 0. Okay. So it could be anything. So I will write it in a better manner. So any random data sequence could be there, 0 1 0 1 1 0 1 1 1 1 1 1 0, anything can be there. Okay. Now what they are asking, your data rate is 100 megabits per second. Data rate is 100 mega, that means it would be 10 to the power 8 bits per second. So basically in 1 second, how much bits you will get? 10 to the power 8 bits. So 1 bit you will get in 10 to the power minus 8 second. Basically the reciprocal of this, that would be the time period. So that is the time window. That means in 10 to the power minus 8 second you will get 1 bit. So this much time window will be 10 to the power minus 8. 10 to the power minus 8. Or you can say 10 nanosecond. 10 nanosecond. So this window is 10 nanosecond. So are you understanding the difference? In this much of window only this waveform will come. 10 to the power 10 nanosecond. And then this waveform will come. And then this waveform will come. although data rate is defined as 100 megabits per second and clock frequency is defined as 100 megahertz. So those number 100 mega and 100 mega are equal, but it doesn't mean the two data will come here. No, one data will come. So in this much of window, only one data will come. Are you getting this point? A lot of guys get confused. If you say the data rate is 10 to the power 8 bits per second, okay, they will take reciprocal 10 nanoseconds. So in 10 nanoseconds, they will make two data, irrespective of knowing what is the meaning of data. Data bit is 1. So this is bits per second. So in 10 nanosecond, only one bit will come. So this is 1 bit. It could be either 0 or either 1. Either 0 or 1. Okay. So this thing you need to take care. Now, so this is the answer of this question. You need to make a random data sequence. So this I have made, and with the 10 nanosecond. Okay. Now solve this question. This would be the last question of this particular lecture. After that, we will move to our next lecture. Okay. So you need to tell me the data rate. This data line is shown. Write down your answer in your notebook and tell me the data rate in megahertz. So this is your question. So first tell me the time period. What did you write? The time period is 4 microsecond. Is this your answer? Wrong. Why is that so? Although the time period term is not even defined. Okay. For data, time period term is not even defined. Or we can define it as well, like data is coming for this much of time period. We can define it. Okay. So what was the time period? What did you write? Find the data rate in megahertz. Sorry. In megabits per second. It should be written as megabits per second. In megabits per second. Really sorry, not in megahertz, because data rate cannot be in megahertz. It would be in megabits per second. So what is your answer? 4 microsecond. That is wrong, because this is not a clock. This is not a clock. This is not a clock. Not a clock. What is this? This is a data sequence. And what you need to define? Data rate. That means one data is coming in how much microsecond? In 2 microsecond. So 1 bit you are getting in 2 microsecond. So in 1 second, how much bits you will get? In 1 second, how many bits you will get? 1 by 2 micro. Right? That means 0.5 megabits you will get in 1 second. In 1 second, 0.5 megabits you will get. So what is your data rate? Your data rate is 0.5 megabits per second. Basically, reciprocal of 1 by 0.2. So in the examination, sorry, 1 by 2. 1 by 2 micro. So in the examination, if this question comes, so answer would be 0.5 megabits per second. Okay. So if your answer was 1 by 4, if your answer was 1 by 4 micro, that means 0.25 megabits per second, then it would be wrong. Okay. It would be wrong. This is a data sequence. Now my data sequence is 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. My data is looking like a clock, but this I have written, it is a data line. So my data rate is 0.5 megabits per second. This is a very simple point, but a lot of guys get confused in that. Okay. Even when I was a student, I was also confused. So now I hope it is clear to you. What is the difference between clock and data? So this was the most important part of this particular lecture. So this is the clock, okay, and this is a data line. So in 1 second, how many bits you are getting? 1 bit you are getting in how much time? In half second. So here the data rate is 2 bits per second. Then we solved this question. Although both the units looks like the same, clock frequency and data rate. Clock frequency is 100 megahertz, data rate is 100 megabits per second. But there is a difference. In 10 nanosecond, here you will have only 1 bit. In 10 nanosecond, you will have high value and low value both. Okay. So this question we solved. Here it was written, data line is shown and you need to tell that data rate in megabits per second. That means 1 bit is coming for how much second? For 2 microsecond, 1 bit is coming. So data rate would be 1 by 2 microsecond. That means 10 to the power 6 by 2. Or it could be 0.5 megabits per second. So that is your correct data rate. So that's it. Now in the next lecture, what we will do, we will start building a digital system. So what is the fundamental block of a digital system? That is logic gate. So first we will study logic gates, then we will combine all the logic gates. We will move to combination circuits. After that we will move to sequential circuits. In sequential circuits, we will study about flip-flops, counter and all kind of things, registers and everything. So now we are going to build our digital system. So these were kind of prerequisites, you can say, or some basic terms that we need to know before going into digital electronics. So these things we have understood here. Now we will start building our digital system, and that we will build using the logic gates. So we have to study logic gates now. Okay then? Yeah. So thank you very much. Let's meet in the next lecture. Hi everyone. So this lecture onwards, we will start building a digital system. In the last lecture, we studied the basics of digital systems. Now we will build it. So what is the basic building block of a digital system? That is logic gates. So with the help of logic gates, by interconnecting those logic gates, we will build a digital system. So these are the building blocks, and this is complete our digital system. Okay. So what all logic gates are there? So there are three different kind of logic gates: basic gate, universal gates and arithmetic gate. So in the basic gates, AND, OR, NOT and buffer gate will come. In universal, NAND, NOR, and in arithmetic, XOR and XNOR gate will come. Why they are called basic gates, why they are called universal gate, that we will talk about it. Okay, so no need to worry. In the further part of this video only, we will talk about why they are called universal gates, and then there will be arithmetic gates. So in this lecture, we will study about basic gates and universal gates. Before going into the gate part, first we need to study Boolean algebra. Okay, Boolean algebra. Look, there are different kind of things: normal addition and subtraction, multiplication and division, like 2 plus 3 is 5, 2 plus 4 is 6. These things we have studied. 2 minus 4 is minus 2, 2 by 4 is 1 by 2, 2 into 4 is 8. So this is our decimal operations, right? In the number system, there will be a chapter called number system. In there we will study about binary operations. Binary operations. Now a lot of people confuses Boolean algebra with binary operation. Okay, a lot of people confuse Boolean algebra with binary operations. Both are very different thing. Binary operation is a different thing and Boolean algebra is a different thing. So here I will write it down. When we study our number system chapter, there you will study what do you mean by binary operation. Okay, so both are very different thing. So here I am just noting it down that binary operation is not equals to Boolean algebra. Now let's study what is Boolean algebra. So what did I tell you? I told you one thing, that our digital system can understand only 2 bits, 0 and 1. So we will do all the calculation between 0 and 1 only. So now treat it as a normal calculation. 1 plus 0 will be 1 only. Okay, your answer is 1. 0 plus 0 is 0. 0 plus 1 is 1 only. 1 plus 1 will be 2. But we can have only 0 and 1 only, right? Now 2 is near to 1. So answer would be 1. This is how you can remember. 1 plus 1 will be 1 only. In Boolean algebra, 1 plus 1 will be 1. 2 cannot be there. 2 cannot even be there. Why so? Because we have only two numbers, 0 and 1. So 1 plus 1 will be 1 only. Okay. 1 into 0. Anything multiplied with 0 will be 0 only. 0 into 1, 0. 1 into 1, 1. And 0 into 0, 0. Okay. Now tell the answer of this. 1 plus 0, 1. Again 1 plus 0. 1 plus 0, this will be 1. Then 1 plus 0, 1. 1 plus 1, 1. Plus 0, 1. Right? Answer will be 1. Basically, 1 plus anything will always be 1. Because 1 plus, if you put a equals to 0, what will be answer? 1. If you put a equals to 1, your answer will be 1 only. So 1 plus anything will always be 1 only. And 0 into anything will always be 0. Are you getting this point? So I can write down one more point here, that 1 plus anything means any variable a I am taking, that will always be 1. And anything multiplied with 0 will always be 0. Now another thing you will see, one more thing, 0 bar, that means not 0. 0 bar means not 0. That means it has to be 1, because there are only two numbers, 0 and 1. 0 bar means not 0, then what it would be? 1 only. 1 bar, that means not 1, so what it would be? 0 only, right? And if I put 2 bars, let's just say I am doing a bar and then another bar I am putting. What does that mean? Let's just say my a is 0. So 0 bar, that means not 0, that would be 1. Now another bar is there, So value of this is 1, and then another bar is there, that means not 1, so answer would be 0 only. If I put 1 bar and then another bar, so 1 bar will be 0, and 0 bar will be 1. So this same number I am getting, no? So a bar to the bar will be a only, right? A bar to the bar will be a only. So these things you need to take care. Very easy things. These calculations, just only this you need to take care. 1 plus 1 is 1. Now anything plus 1 will be 1 only. Anything into 0 will be 0 only. Not 0, 1. Not 1, 0. And bar again, then it would be the same number. Okay, very easy thing. Now we will start studying about our first gate, that is AND gate. So this is our AND gate. So in AND gate, now let's just say you go to an interview and they ask you what is AND gate. So a lot of people will get confused. What should you answer? So this should be your answer. In AND gate, your output will be logic high when all the inputs are logic high. Okay, that would be your answer. If someone is asking what do you mean by AND gate, then sir, your output will be logic high in AND gate if your all the inputs are logic high. Basically AND gate is Boolean multiplication. So let's just say if this was my input A and this was my input B. So this you don't need to remember. For interview perspective you need to remember, but for calculation purpose what you can do, A into B. So AND gate is simply Boolean multiplication, A into B, and this is the symbol of an AND gate. One line and then this. This is the symbol of your AND gate. So AND gate is Boolean multiplication. So what will be the truth table? What do you mean by truth table? Truth table means it will consist all the possible values of A and B. Okay, there are two variables A and B. Now A can be 0 or A can be 1, and B can be 0 or B can be 1. So here there are two chances, and here also there are two chances. PNC we are using. A can have 0 and 1. Two values it can have. It can also have two values. So basically there will be four combinations. So 0 0 0 1 1 0 1 1. Initially both are 0. Then this is 0, this is 1. Then this is 1, this is 0, and then both are 1. So these are the four chances A and B can have. Okay. Now these four chances A and B can have. And what do you mean by truth table? Truth table means it will consist all the possible combination of all the variables and their respective output. So what will be the respective output? 0 into 0, 0. 1 into 0, 0. 1 into 0, 0. 1 into 1, 1. So this will be the truth table. You can draw it very easily, right? A into B, basically A dot B we should say. So AND gate does a Boolean multiplication. So I hope you already know these kind of things. These are very basic things. Now if the inputs are 3, if 3 inputs are there, then what will be the output? Again A dot B dot C, because it will do the Boolean multiplication. So 0 into 0 into 0, 0. A dot B dot C. Here did I write? Here it is A dot B. What I am doing? Boolean multiplication. So A dot B dot C, 0. 0 into 0 into 1, 0. 0 into 1 is 0. 0 into 0, 0. 0 into 1 is 0. 0 into 1, 0. 0 into 1 is 0. Into 1 is 0. Anything multiplied with 0 will be 0 only. Anything multiplied with 0 is 0. Anything multiplied with 0, 0. Anything multiplied with 0, 0. 1 into 1 is 1. Into 1 is 1 only. So this will be the truth table. Only one you are getting, that is here. Now we will show the switch representation. What does that mean? That if I am saying on, that means it is 1. And if I am saying off, that means it is 0. This is your output. Here is your output. You want your output to be 1. That means you want your bulb to turn on, right? If I am saying I want my output to be on, that means I want my bulb to be turned on. So when the bulb will turn on? When both switches are closed, right? When this is also closed and this is also closed. If both switches are closed, if both switches are on, closing means basically if this is my switch, if this is the scene, that means this is on. Switch is closed, and if I make like this, that means switch is off. That means switch is open. Basically, if I am making this, that means it is shorted. And if I am saying arrow is this side, that means switch is open. It is open circuited. Okay. So if both switches are closed, then there is a closed path and current will flow. And if current flows, that means bulb will turn on. So S1 and S2 both are on, then you will get on only. Now if any of them is off, let's just say my S1 is off. If my S1 is off, that means my switch is open circuited and this is shorted. So no current will flow, right? Because this switch is off. So no current will flow. And if current is not flowing, that means bulb will not turn on. So switch will be off only. Similarly, if S2 is off, let's just say S1 is on, but S2 is off. S1 is on and S2 is off. Then again the current will not flow. If the current doesn't flow, then bulb will not turn on. Again off. And if both switches are off, then again there will be no current flow. The complete circuit will again be open circuited, because circuit is open circuited, there will be no current flow, so again it will be off. So when the bulb is turning on, when both are on, that means both are 1. On is 1, off is 0. So 1 into 1 is equals to 1. So this is the truth table. Are you getting this point? So when two switches are in series, then we can write them S1 into S2. So bulb operation is simply S1 into S2 only, right? Bulb operation is S1 into S2, because if both are on, then only the bulb will be turning on. If both are on, that means both are closed switch. Switch are closed, that means both switches are on, then only bulb will be turning on. So this is the switch operation of AND gate. If I make three switches in series, S1, S2 and S3, and here I am collecting my output. So how you can write down this function? S1 into S2 into S3. Switches in series means Boolean multiplication. If switches are in series, that means Boolean multiplication will be there. That's it. So this thing you can keep in your mind, because if three switches are in series, that means you have to turn on every switch, then only the current will flow. If one of the switch is off, that means the current cannot flow, because if all the switches are on, then only you will have a short circuit path, and if short circuit path is there, that means the current can flow. If there is open circuit, then current cannot flow. Okay, let's move to our next gate, that is OR gate. So in OR gate simply shows Boolean addition. Okay, OR gate simply shows Boolean addition, and this is the logic this is the symbol. Basically one curve like this and another curve like this, and these are the inputs. So this is the logic symbol of OR gate. So OR gate simply shows Boolean addition, and if someone asks you the definition, then what you will say? The output will be logic high when any of the input is high. If you see one of the input to be high, then output will be logic high, and it shows Boolean addition. You will not say it shows binary addition. Nah, binary addition is different thing. Here in the AND gate, you will not say it shows binary multiplication. Nah, it shows Boolean multiplication. This also shows Boolean addition. Okay, so Boolean addition will be there. 0 plus 0, 0. 1 plus 0, 1. 1 plus 0, 1. 1 plus 1, 1. Output will be logic high when any of the input is logic high. Any of those input is logic high. Here 1 is high, 1. 1 is high, 1. Here 2 are 1. Here 2 are high. Still it would be 1, because any of them, one of them should be high. That's it. So this is the truth table of our OR gate. Okay. And if we say 3 input OR gate, so for 3 inputs A, B, C, how many total combination will be there? This can have 2 values 0, 1. This can also have 2 values 0, 1, and this can also have 2 values 0, 1. So 2 into 2 into 2, 8. So total 8 possible combination will be there. If there were 4 variable, so this can also have 2 values, this can also have 2 values 0, 1, this can also have 2 values, this can have also 2 values. So 2 into 2 into 2 into 2, so 2 to the power 4, right? So similarly, if there were n variables, for n inputs, total combination will be 2 to the power n. Very simple thing, right? For n input, total combination will be 2 to the power n, right? So let's write down the output. What will be the output? A plus B plus C. So 0 plus 0 plus 0, 0. 0 plus 0, 0. 0 plus 1, 1. Anything in addition to 1 will be 1 only. A plus 1 is equals to 1. So if you see any 1 there, output will be 1. So here 1 is there, output is 1. 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 1 is there, output is 1. 1 is there, output is 1. Okay. So this is the output of our OR gate. How will be the switch representation? Pause the video and try making it on your own. Think about it. How will the switch comes? Here there is a hint as well. The switch will be coming in parallel, right? Switches will be coming in parallel. S1 and S2 both will be in parallel. Now why both of them will be in parallel? Think about it. If any of them turns on, this is S1, this is S2. Let's just say from here current is coming. If this turns on, then this current can flow from here, right? If this turns on, then current can flow from here. If both turns on, then current can directly flow. If both turns on, then it will be a shorted path only, then still current can flow. But if both are off, then what will happen? If both switches are off, then current cannot flow. It will not have short circuit path. So if both are off, then only bulb will be off. Otherwise, bulb will be on only. Because if any of them turns on, then the current can flow. So parallel combination of switches can be written as addition. Okay. Now if I ask you this question, let me make it more clear. These kind of questions will come later on in this particular lecture only. But if I ask you this question here only, S1, S2 and S3, and here I am collecting my output. So what will be this combination? S1 and S2 both are in series, that means it would be S1 into S2. Then S1 into S2 is parallel to S3, then S1 into S2 plus S3. This will be your output Y, right? Are you getting this point? If both are in series, then S1 into S2. If one is in parallel, then addition, that's it. If both are in parallel, then S1 plus S2. If both are in series, then multiplication. Okay, let's move on to our next gate. Before moving on to our next gate, we need to understand a very important concept of delay. But here we will only see the basic definition of delay. Okay, very basic definition we are going to see. The in-depth concept will come later on. Once we study about the gates, then I will deal the concept of delay as well, but later on. Okay, here I just need to tell you the basic concept of delay, because it will be used in our further analysis. So what do you mean by delay? So generally, let's just say if I say my output is A into B. So if I apply my input to be 1 and my B input is also 1, so output Y I will get without any delay. Let's just say this is my time t equals to 0 and I applied my A input to be 1. This is my input A and this is my input B. So and this is my output Y I am drawing. So just as I applied both of them to be 1, my output will be 1 only. If there is no delay, directly A is 1, B is 1, directly my output will be 1. Now if there is some delay, so I know output has to be 1. Let's just say there is a delay of TD time. There is a delay of 5 nanoseconds. So my output will be 1, but it will take 5 nanoseconds to be 1. So after 5 nanoseconds, I will get my output to be 1. That's it. This is the question only. Okay. This is the problem. From here you will understand the concept of delay. So what they are saying, for t less than 0, A and B both are 0. For t less than 0. For t less than 0, A and B both are 0. A is also 0 and B is also 0. This is your A, this is your B. Now tell me one thing, if both are 0, A and B both are 0, then what will be your output? Because what is your output? Output Y is A into B only, right? Output Y is A into B. So what will be your output? Output will be 0 as well. Now for t greater than 0, A has become 1. A has become 1 and B has also become 1. So what will be your output? Your output will be 1 as well. But the gate will take 5 nanosecond. The delay is 5 nanosecond. So the gate will give different output after 5 nanosecond. So till that time it will carry this output only. But after 5 nanosecond it will give you, one output. So this is the meaning of delay. So generally in all the logic circuits you will have the delay, but ideally we will take delay to be 0. So you will get output 1, Y equals to 1 after 5 nanoseconds. So this is the meaning of delay. We will see a lot of questions on that. We will see a detailed concept of delay, but later on in this, in the next video or in the further videos. So, but later on we will see. Here just I need to tell the basic of delay. That's it. That I have told here. Because when we study NOT gate, it will be used. Now first study what is a NOT gate. So NOT gate is called as inverter as well. We call it inverter. So what is the job of inverter? It will simply invert. So if I have applied x here, then my output will be x bar. Okay. If my input is 0, then my output will be 1. And if my input is 1, my output will be 0. It will simply do the bar. That's it. There can be different symbols. This could be also symbol. They will not make this triangular structure. They will just make this bubble. Here also they will just make this bubble and then triangular structure. So three different kind of symbol can be there. Okay. These are the symbols of NOT gate. Now try making the switch operation on your own. There is only one input. In inverter, there can be only one input. Now try making switch operation on your own. Okay. If I hope you have made the switch operation on your own by pausing the video. Now I will show you the switch operation. So this will be the switch operation. In parallel to the output. This is the output. In parallel to the output, you have made the switch. If the switch is on, then what will happen? Whatever the current that is coming from here, that current will go here. So in the bulb, there will be no current. So bulb will be off only. And if this switch is off means S is 0. So if switch is off, then whatever the current that is coming here, no current will go into switch, the complete current go into bulb. So if switch is off, then the bulb will be on. Okay. So this is the switching operation of NOT gate. Now there is another gate that is called buffer. So buffer is whatever that is at input, it will give the same output. So if this is x, y will be equals to x only. Whatever that is at input, it will give the same output without changing it. Okay. So if x is 0, y will also be 0. If x is 1, y will also be 1. Now you will say, sir, then why to use it? It is doing nothing, then why we are using it? It will be used to introduce some delay. Let's just say I am making a circuitry, I am making a PLL, I am making a DLL. These are analog circuitry which you will study when you go to masters. Okay. So there will be a lot of structure where you require delay. In your chip, you are designing, let's just say, a particular block where you require delay, that this input should come after a delay of 10 nanosecond. So for that you will use a buffer there. You will put a buffer there that it introduce a delay of 10 nanosecond, and after 10 nanosecond that particular input will come and it will do the operation. So that's the thing. You require delay. So what is the use of a buffer? To introduce some delay. Buffer is used to introduce some delay. There is another use of that. There is another use of a buffer. So ideally, when we design a buffer, the input current of the buffer is 0. If you have studied network analysis, there also I told this thing. The input current of a buffer is 0. So let's just say I am interconnecting two circuits. This is one of my circuits, and another circuit I need to add in cascade only. Two circuits I am interconnecting. So in between I will introduce a buffer. Okay. So if input current of the buffer is 0, that means whatever the current that is coming from here, that will flow through the capacitor. And whatever the voltage you get here, let's just say I get 5 volt here. So there's the same 5 voltage will come here, and this capacitor will also charge. So when you introduce a buffer, it will not take any amount of current. So loading effect will be minimum. There will be no loading effect. If I had directly connected it, if let's just say if I had directly connected in this manner, then what will happen? Whatever the current that is coming here, that current will be divided into two paths. So capacitor will not get complete I current. So it can be used to introduce delay and avoid loading effect. Okay. So just for effect I have told this thing, because like people will think that what is the use of it, sir? Then if directly something is coming, then what is the use? So the thing is, the input current of the buffer is 0. Okay. So this is the truth table. Now make the switch on your own. Make the switch on your own. So this is how the switch will be looking like. So this is our switch. If this is on, that means the current will flow. If this is on, the current will flow. So bulb will be on. And if this is off, then there will be no current, because the circuit is open circuited. So if this is off, then there will be no current. Okay. Now the conclusion of switch representation is this. Okay. This is the conclusion. So x, y and z all are in series. That means series means multiplication. X into y into z. If all are in parallel, that means x plus y plus z. If this is parallel to the output, that means bar. And if this is in series with the output, then direct A. Got it? Three things we have seen: x into y into z. If all are in parallel, then addition. If it is in parallel to the output, then directly it is, then bar will come. And if it is in series with the output, then simple variable will come. Okay. Now let's revise it once again, whatever that is there. So the basic gates we studied, then we study about 3 input gates. Here we study about AND gate, then we study about 3 input gate, then we study about OR gate. We saw the truth table as well. Then we saw the concept of delay, that output will be fetched after some particular time. And then we studied about NOT gate, and then we saw the switch representation. Then we studied about buffer. Okay. And if we saw the switch representation of buffer as well, then we saw the conclusion of our switch representation. Okay. Wait a second, someone is calling. Yeah, so till now we have seen these kind of things. Let's solve a problem now. So if both circuits are equivalent, then find the value of x in terms of A, B, C, D, E and F. So try doing it on your own. So what will happen to this? A in parallel to B, A plus B, right? This switch will be A plus B. And then C in parallel to D, that would be C plus D. So this is A plus B and then C plus D. Now both are in series, then what will happen? Both are in series. If both are in series, that means there will be multiplication. So A into B, C into D. Okay, so sorry, C plus D. A into B into C plus D. Now this much of circuitry, this switch is in parallel to this switch. What is this? This is E and F. E and F. E and F. If both E and F are in series, that means what will happen? Multiplication. Both are in series, that means multiplication. So E into F. Now this and this are in parallel. If this and this are in parallel, so what will happen? A into B into C plus D. If both are in parallel, this switch and this switch are in parallel. So if they are in parallel, that means there will be addition. So A plus B into C plus D plus E plus F. Now your output is, now this is your output. This is your output. Now your output is in parallel to the switch. Your output is in parallel to the switch. And here it is in series with the switch. And this is your output. This is your output. This is your output. So here your output Y is equals to X. Y is equals to, now here what will be your output? This is your output. So output is in parallel to this switch. So you will connect F bar here, right? So A plus B into C plus D plus EF bar you will do, right? So Y is equals to X and Y is equals to A plus B, Y is equals to A plus B into C plus D plus EF bar. So basically what will be your answer? This will be your answer. Your X is equals to A plus B into C plus D plus EF bar. Okay. So this is the way of solving these kind of problems. So very easy, very easy problem, very straightforward concept. If they are in parallel, then addition. If they are in series, then multiplication. If they are in parallel to the output, then simply bar. And if they are in series with the output, then simply same thing will come. Okay, that will be buffer. So this is the switch representation of our circuits, of our logic gates. Okay, let's move on to our next concept. Now tell me one thing: if two NOT gate are in cascade, now very important concept is about to come. Okay, the concept of multivibrator will come now. So if two NOT gates are in parallel, sorry, if two NOT gates are in series, not in parallel, two NOT gates are in series, or we can say cascade. Cascade means series only. So if two NOT gates are in cascade, then what will be your output? X. This will be your X bar. Then another bar will come, right? X bar and bar. So what that would be? X only, right? Bar of X and then bar. This we have already seen here. Where we saw? Here. A bar to the bar is A. So here also we saw the same thing now. x bar, then another bar, that would be x. So if there are even number of NOT gate in cascade, then what will be your output? If there are even number of NOT gate in cascade, then y will be equals to x only. Basically, one NOT gate, then another NOT gate, then another NOT gate, and then another NOT gate. These four are there. Here there is x. So this will be x bar. Then another bar will come. This will be x. Then another bar will come. This will be x bar. Then another bar will come. This will be x. So this output will be equals to x only. Right? Understood? Okay. So if even number of NOT gate are in cascade, then y will be equals to x. Here, if three NOT gates are in cascade, then x. Here you will get x bar. Then another bar will come. You will get x. Then another bar will come. What you will get? X bar. So if odd number of gates are in cascade, then y will be equals to x bar. Take the example of odd, means one gate also is odd only. This is one gate only. So if x, it would be x bar, right? So equivalently, I can replace this as a buffer. Are you getting this point? Equivalently, this is a buffer only. Two NOT gates are there. If even number of NOT gates are there, so basically you are getting your output same as input only. So here, how I can replace this one? If three are there, then this will be replaced with a buffer, and buffer in series with an inverter will be an inverter only. So if three are there, that means it can be replaced with a single inverter. Okay. So this is your x and this is your y, which is equals to x bar. This was your x and your y will be equals to x. So can you don't need to remember it. This is a very simple concept. If even numbers are there, then simply the same output you are getting. If odd numbers are there, that means you are getting the complemented output. This is known as complement as well. Okay. One more term is there, that is complement. We call this as complement as well. This is our x bar. So we call it complement of x. Okay. I will write down this thing. Complement of x. Complement of x. Now this is the question. If only one question is there, two inverters are there. If two inverters are there, one is having the delay of 2 nanoseconds, this is having a delay of 3 nanoseconds. So what will be the total delay? If two are there, you can replace this with a buffer, right? You can replace this as buffer. If two are there, you can replace this with as a buffer. What will be the total delay? So let's just say here there is an input x. So x bar you will get after 2 nanoseconds. Then x bar from x you will get after 2 nanoseconds plus 3 nanoseconds. So total delay will be 5 nanoseconds. So this is your answer. That's it. Total delay will be added. If I have applied input x, I will get x bar after 2 nanoseconds, and from x bar to x I will get after 3 nanoseconds. So from here to here, what is the total delay? 2 plus 3, 5 nanoseconds. Very simple thing, very simple concept. Okay. Now let's study the concept of multivibrator. So this is important to study because of the next concept that we are going to study. We will design multivibrators using NOT gate and buffer. We will use NOT gate and buffers to design the multivibrator. So first you need to know what is a multivibrator. So multivibrator is nothing but some electronic circuit which will implement some state output. Okay. Multivibrators implement some state output. Then 1 0 0 1 0 1 1 0. Clocks we have seen, right? Clock. So clock was simply 0 1 0 1 0 1 0 1. In that manner clock was going. So they just implement some state output. Now let's study the type of multivibrators, then you will understand it better. Okay. So let's forget about all the electronics and something. Let's take a live example. Let's just say some guy is sleeping there. Some guy is sleeping. Okay. Now you go to that guy, you slap that guy. He was sleeping, you slapped that guy. So what will happen? He will wake up. Now you just slapped him once. You went there, you slapped him once. He woke up. Then after some time he will sleep again. Then after some time he will wake up again. After some time he will sleep again. Wake up again, sleep again. Wake up again, sleep again. Wake up again, sleep again. Just with one slap, you just gave one trigger. This is known as trigger. You went to that guy, he was sleeping. You just gave him one trigger. You just gave him one slap. Now he is waking up, sleeping, waking up, sleeping, waking up, sleeping. By its own, you are doing nothing. He's just doing all the things on his own. Waking up, sleeping, waking up, sleeping, waking up, sleeping. So there is no stable state. So he is 1, then 0, 1, 0, 1, 0. He is toggling between 1 and 0. There is no stable state. You just gave one slap and now sleeping, waking up, sleeping, waking up. There should be some stable state. No, if he is continuously sleeping, then we can say his stable state is sleeping, and he is continuously woken up, then we can say his stable state is woken up. But now he is toggling, sleeping, waking up, sleeping, waking up, sleeping, waking up. So this is known as oscillator. This is an oscillatory output. Okay, oscillatory output 1 0 1 0 1 0 1 0 by just one trigger. So this is known as astable multivibrator. So this is not stable, not a stable. So there is no stable output, not stable. Although we have seen this in our analog electronics course as well. So if you have already studied then you can skip this part. If you haven't studied, then you can study it. Now there will be monostable multivibrator. So what do you mean by monostable? Let's just say that that guy was waken up only. So he was waken up only. You went to that guy and you slapped him. So what happened? If you slapped him, he went to sleeping. Okay, you slapped him, he went to sleeping. Now after some time he will wake up again, and he will always be waken up only. Are you getting this point? He was waken up only. So this was his stable state. This was the stable state of that guy. Now you went there, you did something. You did the trigger. You applied the trigger. That means you slapped him and you told him to go to sleep. So he went to sleep, but for a very minute time, for only this much of time. Then without even slapping him, he woke up. Are you getting this point? So there is only one stable state, which is this one. This is the stable state. The guy was there in stable state only, but you went there, you had something in you, you triggered him. Then he slept only for some time, then again woken up. Without doing anything. You did not do anything. You went there, you just slapped him once, he slept, then again woken up. So with the effect of your trigger, he lost his stable state, but only for a very minute time. He lost his stable state, but only for a minute time, and then he again woke up. We designed monostable multivibrator using Schmidt trigger in analog electronics. Do you remember that? There only for a minute time this unstable state comes. What was the time window? I also forgot the formula. It was ln beta only, right? And beta was R1 by R2 as far as I remember. Because I am not good at remembering the formula. We can derive it in 1 minute only. So are you understanding the meaning of monostable multivibrator here? Waken up, then you slapped him, he went to sleeping, then again woken up. Okay? Or it could be the case, this is one of the example. What could be the other example? He was sleeping, then you went him, you slapped him, he woke up, but only for a minute time, then again he went to sleeping. So here you have applied some trigger here. So this structure is known as trigger. If this is applied at the rising edge, then it is known as positive trigger, and if it is applied at the negative edge, then it is known as negative trigger, which is of no use. You can just say you just applied some trigger, you gave him some triggering. So here his stable state is 0, here his stable state is 1, and here his stable state is 0. This is his stable state. So this is a monostable multivibrator, stable state. So both cases can be there, right? Now let's see bistable state. So bistable means there will be two stable state. Monostable, one stable state. Bistable means two stable state. So in this thing, what was happening? So guy was sleeping, you slapped him, he woke up. Okay, he was sleeping, you slapped him, he woke up. Now he will be waken up only until you apply some trigger, until you apply another trigger. So I again slapped him, then again he slept. Now he will be sleeping only until you apply another trigger. So if I again slap him, he will again wake up. So to change the state, I need to slap him. Now if here I have slapped him, now he has waken up, so he will be waken up only. He will be every time waken up until you slap him back. So if I slap him back, he will be slept. He will be sleeping. Now if I slap him again, then he will again wake up. Now people will be confused, sir, what is the difference between these two? So in this thing, if I slap him back here again, let's just say I go here and I give him another slap here. So what will happen? He will sleep again, but after some time, without even slapping, he is waking up. Here, look, I slapped him here. So he slept, but without even slapping, he woke up. Without even slapping, he woke up. Here, to wake him up, you need to slap again. To wake him up, he was sleeping. To wake him up, you need to slap him again. So he was waken up only. You slapped him, he slept. Now he will be sleeping only until you slap him back. So you again slapped him back, you again applied a trigger, then he went to state 1. Now 1 state is his stable state until you apply another trigger. So I have applied another trigger, then 0 will be his stable state. Now 0 will be his stable state until you apply another trigger. So I applied another trigger, now 1 is his stable state. Now again I applied another trigger, here 0 is his stable state. So there are two stable states. He can have 1 as stable state as well and 0 as stable state as well. So both are his stable state until you apply some trigger. Now what is the difference between A stable and bistable? In A stable there is no stable state, you just slapped 1. You just slapped him once, then he went 1 0 1 0 1 0 1 0, he is just toggling, sleeping, waking up, sleeping, waking up. So that's why there is no stable state. In monostable there is one stable state, you slapped him, he went down, then again he came back to the same state. What was there? Here it was 1, then he came down, then again came back to the same state. Now in this one, bistable, this was the state, you slapped him, came down. Now he will be down, down, down only. You again slapped him, he will be up. In A stable, he was here, you slapped him, he went down, again went up, again went down, again went up, again went up. I hope it is crystal clear to you the difference between all kind of multivibrators. With the example as well, with these waveforms as well. I hope it is crystal clear now. Okay. Now we will do something. What we will do? Let's just say there is an inverter and I am having output. So initially, I am assuming initially you can assume any input. Okay. Let's just say initially my A was 0. This is my A. Initially my A was 0. So if my A was 0, then after TD time you would get 1, right? After TD time. But this is for t less than 0. I am making this is your t equals to 0. For t less than 0, let's just say at some 100 second and my TD is, and TD I am assuming to be 5 nanosecond. So at 100 second my input A was 0. At 100 second my input A was 0. Then after 5 nanosecond I would have got 1, right? After 5 nanosecond I would have got 1 here and it would be always 1. Are you getting this point? What I mean to say is that for very longer time, at 100 second I applied 0 here. So my output would be 1, right? So till t equals to 0, if my A is 0 then B is 1. My output will be 1 after 5 nanosecond, but that doesn't matter. Here it was 0, then after 5 nanosecond I got 1. So till this time it is 0 only and it is 1 only. So for t less than 0 the steady state has been reached. So at steady state A is 0 and B is 1. Now what I do, at t equals to 0, I remove this input. And I directly connect this output here. What I have done, I have removed this input and I connected this output directly here. So if this is my 1, now this 1 will travel down, see this arrow, 1 will travel down and come here, right? So now my A has become 1, immediately my A has become 1 now, right? A has become 1. Now if A has become 1, sorry, it was 0, no? It was 0. So my A has become 1. At t equals to 0, I have connected this feedback. I have removed the input and connected this feedback. So A has become 1. What will happen? Now this will become 1 to 0. But after how much time? 5 nanosecond. So it will take 5 nanosecond. So till 5 nanosecond, it will be 1 only. Initially B was 1. So it will be 1 only. Initially A was 0, it has become 1 now. So after 5 nanosecond, it will become 1. After 5 nanosecond, since A has become 1, so B will become 0 after 5 nanosecond. After 5 nanosecond, this has become 0. So this is 5 nanosecond. This time window is 5 nanosecond. Okay. So if this has become 0, then 0 will come here. This will become 0. Now A has become 0. So A became 0 after 5 nanosecond. Right? A became 0 after 5 nanosecond. Now from 0 to it will become 1. If A is 0, it will again become 1 after how much time? After again 5 nanosecond. After it will be 0 0 0 only. But after 5 nanosecond, it will again become 1. Now if it has become 1, then 1 will travel down here and then again it will become 1. Immediately it will become 1. So till this time it was 0 only, and just as this has become 1, so A will also become 1. A will also become 1. Okay, and this has also become 1. Are you getting this point or not? Look, I will again explain it. Initially A was very for t very less than 0, A was 0, so B was my 1. Okay, I remove the input and close the switch. Then 0 after td time 0 will become 1. After td is 5 nanosecond. After 5 nanosecond, this B was 1 only. So after 5 nanosecond, from 1 to 0 you will get. After 5 nanosecond. After 5 nanosecond, from 1 to 0 you are getting. Now this 0 will travel down here. So this 1 will become 0. This 1 has become 0. So now from 0 to 1 you will get, but after 5 nanosecond. So again after 5 nanosecond, 0 will be there for 5 nanosecond. Then again after 5 nanosecond, this has become 1. Now 1 will travel down here. So this 0 will become 1. This 0 will become 1. Now from 1 to 0 you will get. From 1 to 0. From 1 to 0 you will get. After again 5 nanosecond. So it will be 1 only. From 1 to 0 you are getting after 5 nanosecond. So easiest way would be, I will get from 0 to 1 after 5 nanosecond. You can write down things like this. From 1 to 0 after 5 nanosecond I will get. So here as well, if this has become 0, so this 0 will immediately go here. Now it will become from 1 to 0. And this 0 I am getting after 5 nanosecond only. So in the gap of 5 nanoseconds, I am getting 1 0 1 0 and 1 0, right? Then again the same cycle will keep on going. Okay, 1 0 1 0 1 0. The same cycle will keep on going. 5 nano 5 nano 5 nano, in that manner it will keep on going. So if someone is asking you what is the frequency of oscillations, this is my output. Okay, if I am saying this is my output, so what is the frequency of oscillation? Frequency of oscillations. If someone is asking you what is the frequency of oscillations at output, so what would be your answer? First tell me the time period. Time period of this waveform. What is the time period? 5 nanosecond plus 5 nanosecond, 10 nanosecond. What is the frequency of oscillation? 1 by t. That would be 1 by 10 nano. Nano is 10 to the power minus 9. So that would be 10 to the power minus 8. It would go 10 to the power 8. So it would be 100 megahertz. So frequency of oscillation is 100 megahertz. That would be your answer. Okay. So these kind of questions come in the examination. They will give an inverter. They will say the delay is 5 nanoseconds. So what is your actual answer? 1 by 2 TD. Say yes or no. This is your answer only. 1 by 2 into TD. 2 into 5 nanosecond. So 1 by 10 nano. This is the answer. 1 by 2 into TD. TD is 5 nano. So 1 by 10 nano. That is the answer. Okay. So delay of the inverter. Reciprocal of the delay of the inverter. That is the frequency of oscillations. Well and good. Let's see more examples. 3 inverters are connected. This has the time, this has the delay of 2 nanoseconds, this has the delay of 3 nanoseconds, this has the delay of 2 nanoseconds. How will you solve this problem? I told you one thing, if 3 inverters are in cascade, then it can be replaced with 1 inverter only. This is a single inverter. So this is a single inverter, right? With time period of how much? Sorry, with the delay of how much? 2 nanosecond plus 3 nanosecond plus 2 nanosecond. 3 plus 2, 5 plus 2, 7 nanosecond. So there is total delay of 7 nanosecond. This is your input, this is your output. Now in the examination, I told you this thing that initially A was 0, then you took the feedback, right? What did I say? There was no feedback. There was no feedback initially. Then from 0 to 1 you got, and then you connected the feedback. But in the examination, they will not tell this thing. So ideally, what is assumed is that there is some noise in the circuit. there is some noise in the circuit, and because of the noise you will get something in your circuit. Because of the noise you might get some 5 volt here. If you get 5 volt here, that means you will get 0 volt here, and now this 0 volt will travel here, 5 volt will be gone, 0 volt will travel here, and then you will get 1 volt here. Now this 1 volt will travel here, and then you will get 0 volt here, then again 0 volt will travel here, and again you will get 1 volt here. So this is assumed that because of noise some input is coming. Here I gave you the example that first I apply some input and then I receive the output, then I connect the feedback, but in the examination this circuit only will come. So you have to assume that because of the noise some input came here and you got some output, then this output traveled back, then again output, traveled back and again output. So in this manner it is traveling back. So 7 nanosecond time it is taking. So for 7 nanosecond time it will be high, and for another 7 nanosecond it will be low, right? For 7 nanosecond it would be high. So how will your output look like? Seven nanosecond it is high, then 7 nanosecond it is low, then 7 nanosecond it is high, then after 7 nanosecond it is low, then again high, then again low, right? So in that manner we will proceed. So this is your 7 nanosecond, and this is your also 7 nanosecond. So what is the total time window? That is 14 nanosecond. Okay, and if someone is asking you the frequency of oscillation, that would be 1 by 14 into 10 to the power 9. Okay, so 1000 by 14 would be the answer. If I do the calculation, 1000 by 14, so 71.42 megahertz. Let's see this question. Let's check, will there be any effect of this one? So there are 3 inverters in the loop. 3 inverters in the loop. Can I replace my circuit? Okay, forget about replacing. So again you have to assume because of the noise some, let's just say some 0 voltage was coming here. Okay, because of the noise some 0 was coming here. So I will make the waveform of A, I will make the waveform of this X, okay, and I will make the waveform of B. I will make 3 waveforms. You have to do it on your own in your rough notebook, otherwise you will not be able to understand. We need to check, will there be any effect of this 2 nanosecond. So let's check that. Okay, so starting with, let's just say because of some noise my A was 0. If my A was 0, then what would be your B? 0, then after 2 nanosecond you would get 1, then 0, then 1, and then again 0, right? So your X would have been, if it is 0, this also would have been 0. And what would have been, sorry, X is this, 0, 1, 0, 1, X would have been 1. X would have been 1 and B would have been 0. Are you getting this point? There is no feedback. This is for t less than 0. There is no feedback. So 0, 1, 0, 1 and 0, right? 0, 1 and 0. Now there is a feedback, right? So this 1 will reach here. So this was 0, this was 1, this was 0, this was 1, this was 0. X I will make somewhere here. Now this 1 will reach here immediately, this one, this is the 1, this 1 will reach here immediately. So A will become 1. In the examination it will not take that much of time because I will tell you a trick, right? So A will become 1, A will immediately become 1. Now after 2 nanoseconds this 1 will become 0 here, right? But after 2 nanoseconds, because of this 1, because this is only 1 only, this is 1 only, after 2 nanoseconds this is 1 only, so B will remain at 0 only, B will remain at 0 only. So after 2 nanoseconds this is at 1 only, this is at 1. कौन कॉल कर रहा है यार अभी? Yeah, so after 2 nanosecond, what I was saying, so after 2 nanosecond this has become 1, sorry, this has immediately become 1. After 2 nanosecond this has become 0, after 5 nanosecond this has become 1, and after 7 nanosecond this has become 0. 3 plus 2 plus 5. So after 7 nanosecond this has become 0. So how much time it took? 7 nanosecond. 7 nanosecond. So this took 7 nanosecond time. And till that time, until it has become 0, this will be 0 only. So till that time this is 0 only. Till that time this is 0 only. Now since this has become 0, so after 2 nanosecond this will become 1. So this has taken 7 nanosecond time, right? This has taken 7 nanosecond time, but it will take more 2 nanosecond. So it will take more 2 nanosecond to become 1, right? So it will become at 9 nanosecond. It will become 1 at 9 nanosecond. So it has become 1 now, but after 9 nanosecond. So shall I tell my answer to be 1 by 18 nano? No, that is wrong, because this is not the steady state. So what happened here? Now from this 0 will become 1 here. This 0 will become 1 here. So it will take time 2 nanosecond. But at that time only, this 0 would have traveled here. So in this 2 nanosecond, when this was becoming 1, this also has become 1. Are you getting this point? So after 7 nanosecond only, this point has become 0. A has become 0. After 7 nanosecond only, A has become 0. And in 2 nanosecond, this has become 1. So now after 3 nanosecond, this will become 0. After 2 nanosecond, this will become 1. And after another 2 nanosecond more, this will become 0. So from here to here we are reaching. From here to here, this much window we are covering. So 3 plus 2 plus 5. So after 7 nanosecond, you will get 0. Are you getting this point or not here? After 7 nanosecond only, you are getting 0 here. Did you understand this point? I will again explain it. Let's came back to the 7 nanosecond part. So here after 7 nanosecond, this was 0. Okay. After 7 nanosecond, this became 0. So if this became 0, so in 2 nanosecond, after 2 nanosecond, this has become 1 here. This has become 1 here. So it took 9 nanosecond. So in this 2 nanosecond, this 0 has traveled down here. This 0 has traveled down here. If this 0 has traveled down here, this has become 0. So in this 2 nanosecond, this window has also been covered. So in 2 nanosecond, this has become 1. Now you need to check at B. So 1 will become 0 after 3 nanosecond. 3 nanosecond. Then 1 will become 0 after 3 nanosecond. Now this 0 will become 1 after 2 more nanosecond. And this 1 will become 0 after 2 more nanosecond. So 3 plus 2 plus 2. So after 7 nanosecond, this will become 0. 7 nanosecond, this will become 0. Now this 1 has reached here already. And in the time when 1 was becoming 0 in 2 nanosecond, this already has become 0. Now it has to clear this much window only. Are you getting this point? So this waveform also we can draw. This waveform we forgot to draw. So from 1 to 0 it became. Then from 0 to 1 it will become after 7 nanosecond only. Because it has to clear this 2 nanosecond plus 3 nanosecond plus 2 nanosecond. So again after 7 nanosecond. 7, 7, 14. So again after next 7 nanosecond, it has become 0. So and again after another 7 nanosecond, it will become 1. Okay. Now 1 is becoming 0. Now this 1 is becoming 0. So this is at 0 only. But for how much time it will remain at 0? So for first 2 nanosecond, this is the window of 2 nanosecond. Okay. So in this 2 nanosecond, this 1 has traveled down here and this 0 has become 1. This 0 has become 1. It will take 0 time. And this 2 nanosecond, this 2 nanosecond window has been cleared, and then this 1 has become 0. So this window has been cleared. Now you need to clear this window only. So after 7 nanosecond only, your 0 will become 1. Basically, this 0 will become 1, this 1 will become 0, and this 0 will become 1 in the time of 7 nanosecond only. 3 plus 2 plus 2, 7 nanosecond. Okay. So again after 7 nanosecond, now let's just say I assume something that I'm saying that if this was 1 nanosecond, so here you must have understood that now this cycle will keep on repeating. Okay, this cycle will keep on repeating, this cycle will keep on going in this manner. So what will be your frequency of oscillation? Your frequency of oscillation will be 1 by 14. Your frequency of oscillation will be 1 by 14 nano, right? And what is the answer of 1 by 14 nano? That would be 71.42 megahertz. You have to understand it on your own only. You make the graphs on your own, then you will understand what is happening in the circuit. Now if I say this, instead of this 2 nanosecond, this delay was 1 nanosecond, what would be your frequency of oscillation? Do it on your own, pause the video. Instead of this 2 nanosecond, if this was 1 nanosecond, what would be the frequency of oscillation? It would be 1 by 12 nano or 1 by 14 nano. If your answer is 1 by 12 nano, then it is absolutely wrong. It would be 1 by 14 nano only, because you are not doing the calculation if you are saying 1 by 12 nano. Do it again. What will happen? Let's check that out. Let's just say this is the condition only. Okay. Now from 0 to 1 it will become 1 to 0 and 0 to 1, and then this is 0 only. So this is the condition. Now what will happen? This one will travel down here, this one will travel down here. So it will take 7 nanosecond time to become 0, 7 nanosecond time to become 0, and it will take 8 nanosecond time. This will just be replaced with 8 nanosecond. So it will take 8 nanosecond time to become 1. Now this has taken 2 nanosecond here, this has taken 1 nanosecond here. So in the meantime you are somewhere here. Now how much window you need to cover? 1 nanosecond plus 3 nanosecond plus 2 nanosecond. This much window you need to cover to come here. Then another 1 nanosecond you need to cover. What did you get to know? That from here to here, it was becoming from 0 to 1 after 1 nanosecond. From here to here you are going, it was taking 1 nanosecond. It was taking 1 nanosecond, right? In 1 nanosecond, this 0 would have traveled down, and this 1 would have become, sorry, this 1 would have traveled down. What would have traveled down? 0, 0. So this 0 would have traveled down, and this 1 would have become 0, right? And this 0 would have traveled somewhere till here. It has to cover 2 nanosecond time. Then you will get 1 here. It has to cover 2 nanosecond time. It has to cover 2 nanosecond time. Then you will get 1 here. But in 1 nanosecond it would have covered somewhere here. Then another 1 nanosecond it needs to cover. Another 1 nanosecond it needs to cover. So this much 1 nanosecond window it needs to cover. Then 3 nanosecond it need to cover. Then 2 nanosecond it need to cover. And then after that 1 more nanosecond it need to cover. Then your output B will change. So output B will change after 1 nanosecond plus 3 nanosecond plus 2 nanosecond plus 1 nanosecond. So 3 plus 2 plus 1 plus 1. So after 7 nanosecond again your output will change. So what is the conclusion we are making here? So whenever, now no matter even if you did not understand anything from this particular lecture, okay, so from this particular part of the video, if you did not understand anything, then also you don't need to worry. You need to remember only one thing: if these kind of questions are coming, you only need to look into the loop. So in the loop, how much delay is there? Twice of that, and then take the reciprocal. That would be your frequency of oscillation. Okay. So I will write down the conclusion here now. और ये नहीं मिटाना था यार. So let's remove this. Let's remove this. Let's remove this as well. Let's remove this as well. Let's remove. Okay. So let's remove these as well. So what is the conclusion? That is the most important point. See the loop. If it has odd number of inverter, then it is astable multivibrator. This is astable multivibrator only, no? The output is toggling 1 0 1 0 1 0 1 0. Output is toggling 1 0 1 0 1 0 1 0. So what is this? This is a stable multivibrator. So this is known as stable multivibrator. Okay. Stable multivibrator. Another name is ring oscillator. There is another name of it that is known as ring oscillator. Okay. So this is very important part you need to remember. Stable multivibrator or ring oscillator. So this is our ring oscillator. So if there are odd number of inverter in the loop, you just need to see the loop. In the loop, if there are odd number of inverter, that means it is stable multivibrator. Stable multivibrator. Calculate the delay of the loop. Calculate the total delay in loop. Total delay in loop. Then frequency of oscillation will be 1 by twice of total delay. That's it. This is your task. If you just remember this thing, you will be able to solve all the problems. Okay. No need to worry about anything. If you just remember this much of thing, I will write down the frequency of oscillations again. So what will be my frequency of oscillation here? 1 by twice of total delay. 2 nanosecond plus 3 nanosecond plus 2 nanosecond. 3 2 plus 5 7 7 nanosecond. So 1 by 14 nanosecond. That means 71.42 megahertz. So in this manner you need to proceed. Okay. Let's solve more examples. This example is there. What did I tell you? Just look into the loop. You can analyze it by drawing the timing diagram like this, but you will get the same answer only. You will get exactly the same answer you will get. So see the loop. So what will be your frequency of oscillation? 1 by twice of total delay. In the loop, what is the total delay? 3 plus 2 plus 2. Again 7 nanosecond only. So no matter here it is 1 nanosecond, 2 nanosecond, doesn't matter. Just see the loop. So 1 by 2 into 7 nano. So answer would be 1 by 14 nano or 71.42 megahertz. Okay. Let's see the next question. No matter how many inverters, whatever that is there, again see the loop. Just look at the loop. In the loop there are odd number of inverter. That means it will act as what? If there are odd number of inverter, it will certainly act as oscillator only. It will certainly act as ring oscillator or stable multivibrator. And what will be the frequency of oscillation? 1 by 2 into the total delay. That is 3 plus 2 plus 2. So 7 nano. So 71.42 megahertz. Let's see the next one. This is the complete circuit. See the complete loop. How many inverters are there? One inverter is there. This is buffer. Right? Only one inverter is there. What is the total delay? 1.5 plus 2. 3.5 plus 2. 3.5 plus 2, 5.5. 5.5 plus 0.5. 6. 6 plus 4, 10 nano. So what will be the frequency of oscillation? 1 by 2 into 10 nano. So that would be 10 to the power 8 by 2. So 100 by 2, 50 megahertz. So this is the answer. Okay. See the loop. These are the buffers. Okay. But they will introduce some delay. But odd number of inverters should be there. Odd number of inverter is there. Then let's just say this is my output. So here what will be the frequency of oscillation? Frequency of oscillation will be 50 megahertz only. Are you getting this point? Okay. So now this stable multivibrator has been covered. Now if I do this thing, this is a buffer. Okay. This is a buffer. And for t less than 0, for t less than 0, here it was 0 only. So what would be the output here? After td time you will get 1. But steady state is there for a very long time. This is 0, A is 0, then B will also be 0 because this is a buffer. Then B will also be 0 because this is a buffer. Now what I do? I connect back a feedback. So if I connect back a feedback, then this is gone. So this 0 will come here. This 0 will come here. If 0 is coming here, then still output will be 0 only. After TD time, you will get 0 output. After TD time, you will get 0 output only. After TD time, you will get 0 output only. It will all be 0 only. It will all be 0. But what I do is that at some time T1, I apply a trigger here. At some time T1, I apply a trigger. At some time T1. This is the trigger I am applying. This is the time T1. At some time T1, I am applying the trigger. So if I am applying the trigger, how will I apply the trigger? I will break the loop. First I will break the loop. And I applied the trigger means I am changing the input. Now I have changed the input to 1. So input has been changed. At t equals to, when I apply the trigger, at t equals to T1, I have changed the input. At t equals to T1, I have changed the input. And I have made the input to be 1. I have made the input to be 1. And then again I close the loop. Then again I close the loop. What I do, at t equals to T1, मेरे को कुछ जमा भाई, मेरे को कुछ तो हुआ मेरे को. तो what I would have done, I will just break the loop and then I will apply 1 here. So if I apply the 1 here, then after TD time you will get 1 here. So this is T1. After T1 plus TD time, this time would be T1 plus TD time. Because this one will be traveling down from 0 to 1 you will be getting after TD time. And this was initially 0. This was initially 0. Because of the trigger, I will write, because of the trigger you are getting 1 here. So after TD time you will get 1. So now it will always be 1, right? Because now what will happen? This 1 will again travel down and then it will be 1 only. Because this is a buffer. 1 will travel here, no inverter is there, again it will be 1. So all the time it will be 1 only. All the time it will be 1 only. All the time it will be 1 only. Now what happened? Again I tried to do something. Again I applied a trigger. So again I applied a trigger. This time I applied this trigger. Some different trigger I applied. Okay. At time T2. So again I applied some trigger. If I apply some trigger and by applying the trigger I made the output to be 0. How would I apply the trigger? I will break the loop. Then I will make this input to be 0. I will make this input to be 0 and then I will again close the loop. So now this is 0. So this 1 will go to 0. This 1 will go to 0. But after how much time? This 0 will travel down here. This 0 will travel down here. But after how much time? After TD time. So from here it will take TD time to come to 0. Then again it will always be 0. Why it will always be 0? Why it will always be 0? Because this 0 will travel down here. So this will become 0. Then again 0 and 0, here it will also be 0. Then again 0 will travel down, again 0. 0, 0, 0, 0. So it will always be 0. So what you are seeing here? Until you are applying some trigger. Here trigger was applied. Here also trigger was applied. Until you are applying some trigger, it is remaining there in same state only. What does that mean? This is what? This is a monostable multivibrator. Monostable multivibrator. So in the loop, if there are odd number of inverters, buffer means, sorry, even number of inverters. Buffer means even number of inverters. Because if even number of inverters are there, then they will make buffer only. So in the loop, if you find even number of inverters, that means it will make a monostable multivibrator. And in the loop, if there are odd number of inverters, there is only one inverter, that means it will make a stable multivibrator. Now if someone asks you what is the frequency of oscillation here, actually there is no oscillations, because in the examination this trigger will not be there. If some trigger is there, then we can think about it, but in the examination this trigger will not be there. So there are no oscillations, because it will remain. Now if I say I don't apply any trigger, so it will always remain at 0 only if I don't apply any trigger, and this will also remain at 0 only. So the steady state value is 0 only. Are you getting this point? The steady state value is always 0. This is the steady state. So at steady state, there are no oscillations. So if someone is asking you what is the frequency of oscillation, then what you will say? 0, because there are no oscillations. So if this question is coming in front of you, in the loop, how many inverters are there? Even number of inverters. Even number of inverters. And if there are even number of inverters, then what you will say? This is a monostable multivibrator. Monostable multivibrator, MM I have written, okay? Monostable multivibrator. Then what is the frequency of oscillation? Frequency of oscillation is 0. That means there are no oscillations. Because in monostable multivibrator, there are no oscillations. There will be a constant steady state value, okay? Unless you apply some trigger. So triggering you cannot keep on doing. Always you cannot keep on doing. Always you cannot keep on clicking the switches. So just as you stop doing the triggering, this will be the steady state. So there will be no frequency of oscillations. So this is the concept of multivibrator using NOT gate and buffers. I hope you must have understood. This is a very important point and a lot of guys are confused. So these kind of examples we have seen, every single example you will be able to solve if that is coming in your examination. Each kind of example, right? Each and every single kind of example you will be able to see, and some good question also you will see in the test series from this particular chapter. We should not say from this particular topic, because this is a very important topic and it is highly asked in the gate examination. Last year also a very easy question came. There was only one inverter and they gave the time, they gave the delay and they just asked the frequency of oscillation. So 2 and TD, not n was 1 only basically. It's at somewhere you will find this formula written 2 and TD, where n is number of inverters. N is number of inverters. So let's just say 2 nanosecond, they will give the same delay, 2 nanoseconds. So what will be the frequency of oscillation? 2 into 2 nanosecond plus 2 nanosecond plus 2 nanosecond. So you can write 3 into 2 nanosecond, right? This is 6 nanosecond only. So that will be the frequency of oscillation. So somewhere they write 2 and TD. But it's not necessary that all the delay will be same. Delay can be different only. So you can just simply count the delay and then make the twice of the delay. That will be the time period, and reciprocal of that, that will be the frequency of oscillations. Okay. So 1 0 1 0, it will be toggling in that manner. Toggle means changing the state. 1 0 1 0 1 0. I am again and again using this term toggling. Toggling means 1 0 1 0, changing the state. Okay. Now we are not studying the De Morgan's theorem here. Okay. We are not going into the depth of De Morgan theorems, but it will be used. It will be used in our further lecture only. In the next lecture also it will be used. So it can be used anywhere in the chapter, but we will again study it. Okay, we will again study it, and we will study it in much depth when we again study it. So till now, for now, you can just remember it. So A into B bar can be replaced with A bar plus B bar. Multiplication of Boolean multiplication of A and B, and then there is a bar. So that can be replaced with A bar plus B bar. Okay. So bar, individual bar you can make, this dot will be replaced with plus. And if there is a plus, then individual bar you can make, but the plus will be replaced with dot. Very easy to remember, right? Now you can write down the same thing for this. Whole bar is there, you need to make individual bar. If you need to make individual bar, then what you will do? A bar dot B bar dot C bar, plus will be replaced with dot. Here whole bar is there, you need to make individual bar, so dot will be replaced with plus. So A bar plus B bar plus C bar, dot will be replaced with plus. Okay. Now some more important points. A into 1, anything multiplied with 1 will be the same value. 0 into 1 is 0, 1 into 1 is 1. So anything multiplied with 1, 0 0 same, 1 1 same. So anything multiplied with 1 will be the same value only. So A into 1 will be A. Anything multiplied with 0 will be 0 only. A into A, A into A, that will be A only. Basically 1 into 1 is 1 and 0 into 0 is 0. So same multiplied will be the same value, same multiplied will be the same value. So these kind of basic thing you need to remember. Now A into A bar, let's just say my A is 1. So what I am doing? A into A bar. So A is 1, what will be my A bar? 0. So 1 into 0 will be 0. And let's just say my A was 0. So A into A bar, A was 0. What will be A bar? That would be 1. So 0 into 1 will be 0 only. So A into A bar will be 0 only. Are you getting this point? Now tell me, by taking the example only, what will be a plus a? You take a equals to 0, so 0 plus 0 will be equals to 0 only. You take a equals to 1, 1 plus 1 will be equals to 1 only. So a plus a will be equals to a only. So if I ask you a into a into a into a lot of times, so a into a is a, then another a into a, again a, then another a into a, again a, so it will be a only, right? Now anything in addition to 0, the same. Anything in addition to 1, I told you a plus 1, anything in addition to 1, 1 plus 0 is equals to 1, and 1 plus 1 is equals to 1 only. So this one is constant here, and this a is changing. So what is the answer you are getting? Always you are getting 1. So a plus 1 is 1 only. Now a plus a bar, a plus a bar. So if a is 1, then what will be a bar? 0. So 1 plus 0 is 1 only. And if a is 0, what will be a bar? 1. So 0 plus 1 is 1 only. So a plus a bar is 1. So these 8 identities can you remember? A into 1 is a into 0 is 0. A plus 1 is 1. A plus 1, anything in addition to 1 is 1. Anything in multiplication to 1 will be the same variable. Anything in multiplication to 0 will be 0. Now a into a will be a only. A plus a will be a only. All any kind of a you need to add. A plus a plus a plus a plus a plus a. It will be a only. A into a into a into a into a will be a only. Now a plus a bar. So if a is 0, a bar will be 1. So 0 plus 1 will be 1. And if a is 1, a bar will be 0. So 1 plus 0 will be 1 only. So a plus a bar will be 1. A into a bar. If a is 1, a bar will be 0. So answer will be 0. And if a is 0, a bar will be 1. So 0 into 1 will be 0. So a into a bar is 0. This also you can remember. A plus a is a plus 0 is a plus 1 is 1, and a plus a bar is 1. So very simple identities, these you can remember. And De Morgan's theorem, what did you understand from De Morgan's theorem? De Morgan's theorem simply says, if whole bar is there, then you can take individual bar but replace dot with plus. Replace plus with dot. Okay, whole bar is there, you can take individual bar, replace plus with dot and dot with plus. So whole bar is there, replace plus with dots, dot with plus. That's it. Okay, so these things you can remember, right? Now let's just take a simple example only. If I need to write down this thing, how will I write down? P plus Q whole bar. So P bar dot Q bar, right? Whole bar is there, so I can replace plus with multiplication, then plus R. So P bar dot Q bar plus R. Okay, so in that manner I can change. Let's move on to our next gate, that is the universal gate, that is known as NAND gate. So should we cover it in next lecture? Because there will be NAND gate, then we will study switching circuit, then there will be NOR gates. Switching circuit will be there, then why they are called universal, then both will be used as universal gate. So let's cover it in next lecture. In next lecture I will need to change the slide in between, so that I will do. So in this lecture, the most important point for the examination, see the loop, find the number of inverters. If odd number of inverters are there, that will be your ring oscillator or astable multivibrator. If even number of inverters are there, that means that will be your monostable multivibrator. So for astable multivibrator, what will be the frequency of oscillation? The frequency of oscillation will be 1 by 2 into total delay. So total delay you need to calculate. So 1 by 2 into total delay. That would be your final answer. Well and good. I hope you must have understood very clearly. Okay, then let's meet in the next lecture and we will study about universal gates. Okay, thank you. Hi everyone. So in the last lecture we were studying about basic gates, right? We studied AND gate, we studied OR gate, and we studied about NOT gate, and we studied about buffer. Now we are going towards the universal gates. So this is the first universal gate, which is NAND gate. So how NAND gate is made of? AND plus NOT. So there will be an AND gate and then there will be a NOT gate. So that is our universal gate. AND gate plus NOT gate. So AND plus NOT, that is known as universal gate. So what will be your Y? Y will be A into B bar, right? First AND operation, A into B, AND operation, and then bar. Okay, so Y will be AB bar. Y will be AB bar. And what did I tell you? De Morgan's theorem. Do you remember? So AB bar can be written as A bar plus B bar, because there is dot in between. So if you want to replace dot with plus, then you can take individual bar. So A bar plus B bar. Now A bar plus B bar, how it can be made? Look, this is A, then I make this bar, because I told you our inverter can be simply replaced with a simple bubble, right? So it's a simple bubble. So here A bar is going and here B bar is going. And what is this? This is OR gate. So what OR gate does? It will simply add. So A bar plus B bar. So both are equivalent only. Instead of OR, I should make this arrow. This is the arrow of equivalence. So both gates are equivalent only. So and NAND gate can also be called as bubbled OR gate. Bubbled OR gate. Bubbled OR gate. Because these are the bubbles there, which is A bar plus B bar. So AB bar can be written as A bar plus B bar as well. What will be the truth table? 0 into 0 is 0, and then you take the bar. First you do the multiplication and then you take the bar. 0 into 0 is 0, 0 bar will be 1. 0 into 1 is 0, 0 bar will be 1. 1 into 0 is 0, 0 bar will be 1. 1 into 1 is 1, 1 bar will be 0. So this is the truth table. Okay. Now in the examination, if someone asks you, or in the interview if someone asks you what is a NAND gate, what you will say? So NAND gate is the gate where output will be logic low if all the logics are high. If all the input logic are high, output will be logic low if all the input logic are high. If any of them is 0, if any of the input logic is 0, then output will be logic 0 only, right? Because let's just say this is my input A, B, C, and my output is going from a NAND gate. So what will be my output? A, B, C bar. If any of them is 0, let's just say this is 0, then A into B into C will be 0 only. 0 bar will be 1. Okay. So my output will be logic low if all the logics are, or if all the input logic are high. Okay. So this is the definition of NAND gate. What will be the switching circuit? Here you can see this is the switching circuit. Y is equals to AB bar. This is the switching circuit. This is the 3 input NAND gate. 3 input NAND gate. You can write down the truth table on your own. Here I am not making the truth table. You can certainly write down the truth table on your own as well. So how it can be implemented? This bubble comes here and this AND gate will be replaced by OR gate. This is how we will remember. Bubble will come here. So 2 bubbles are there and this AND gate will be replaced with OR gate. That's it. Bubble comes here and AND gate is replaced with OR gate. So here what you will get? A, B, C whole bar. So certainly here it is A bar plus B bar plus C bar. So this A into B into C bar can be replaced with A bar plus B bar plus C bar. So same thing you are getting here as well. Okay, so this is another way of representing it. Let's see NOR gate. So OR plus NOT. First there is OR gate, A plus B, and then there is a bar. So how you can replace this? If you take individual bar, then plus will be replaced with dot. So A bar dot B bar. Then what will happen? This bubble comes here, this bubble comes here, and your gate OR gate is replaced with AND gate. So NOR gate is called as bubbled AND gate. Okay, NOR gate is called as bubbled AND gate. So it can be replaced at A bar dot B bar. Okay. Now let's do the let's write down the truth table, that is A plus B whole bar. So 0 plus 0 is 0. 0 bar is 1. 0 plus 1 is 1. 0 plus 1 is 1. 1 bar is 0. 1 plus 0 is 1. 1 bar is 0. 1 plus 1 is 1. 1 bar is 0. So in NOR gate, output will be logic high if all the inputs are logic low. Okay. In NOR gate, output will be logic high if all the inputs are logic low. So in the examination, if they are asking you the definition, then quickly you will write down the truth table, and based on that you will tell the definition. Okay. And this will be the switching circuit. How it will be the switching circuit? Because both are in parallel, so it would be A plus B. And since it is connected parallel to the output, so there will be bar. So this will be your switching circuit, right? For 3 input, certainly this bubble will come here and this OR gate will be replaced with AND gate. So this will be your output. So here how can I write the output? A plus B plus C whole bar, or it can be replaced with A bar dot B bar dot C bar. What about this one? A bar, this is A bar, and since this is AND gate, so A bar dot B bar dot C bar. Okay. Now this is the most important question, and listen it very carefully. Why NAND and NOR gates are called universal gate? So let's read down the first point. With the help of AND gate, OR gate and NOR gates combined, you can design any Boolean function. Let's just say I give you AND gate, OR gate and NOT gate, and then I ask you design a random Boolean function. Let's just say this is the random Boolean function I am giving you. This random Boolean function I am giving you, and I will ask you, can you design this Boolean function using these three gates? You will say yes, I can design any Boolean function using these three gates. So that's why they are called basic gates. Now if I say I am giving you only AND gate, and I ask you to design this thing. So are you able to design this particular expression using only AND gate? So your answer will be no. I need three gates there, AND, or not. Actually you need only two. You need AND gate and NOT gate, or you need OR gate or NOT gate. So if you have these and these with you, basically these two you need. With and OR, with these two gates you will not be able to design this, because from where will you get this bar? So for bar you need NOT gate. Okay, in the further part of this chapter only I will tell you that using only two gates only, and NOT, or and NOT, you can design any Boolean function with the help of only two gates, but you certainly need NOT gate. So what did you understand here? Alone basic gate is not enough to design any Boolean function. If I only give you NOT gate, so NOT gate can only do bar, nothing else. It cannot do addition, it cannot do multiplication. So only one gate is not enough to make any Boolean function. You need these three combined, or at least these two or these two, right? So at least two you need. So alone they are not enough to make any Boolean function. But if I give you only NAND gate, if I give you only NAND gate, and then I ask you, can you design this function? Then your answer will be yes, I can design this function. So only NAND gate is enough to design any Boolean function that is present in this whole universe. Or here I will type, I should not write or, because or is also a gate. So what should I write? In smaller letter I am writing or. Or if I give you only NOR gate and I ask you, can you design this function? Then your answer will be yes. So alone NAND gate is enough to make any Boolean function. Alone NOR gate is enough to make any Boolean function. So that's why they are called universal gate. They are not called universal gate because they are alone not enough. And OR and NOT are not alone enough to make any Boolean function. But NAND gate alone is enough to make any Boolean function. From NAND gate you can make NOR gate as well. From NAND gate you can make AND gate as well. From NAND gate you can make OR gate as well. From NAND gate you can make NOT gate as well. Basically from NAND gate, if you can make these gates, then certainly using only NAND gate you can implement any Boolean function. So are you getting the point? What is the condition? That if you are using basic gates, then you need at least two, and in those two one has to be NOT gate as well. That means you need NOT and OR, NOT and OR, NOT OR. NOT and this is one of the possible combination. NOT OR, this is another combination. So you need at least two. They alone are not enough. But if you are given only NAND gate, then it is alone enough to implement any Boolean function. That's why they are known as universal gates. Okay. So here I will write alone enough to implement any Boolean function. That's why they are called as universal gate. Okay, let's see this. Now from NAND gate we will design AND gate, OR gate and NOT gate. We will design other gates as well, but later on this chapter. Okay. Now using NAND gate, we will design AND or NOT, and then using NOR gate, we will design AND or and NOT. Okay. So let's see this NAND gate as universal gate. So first we will design NOT gate using AND gate. So what do you need? A bar you need. Okay. So what I do, I simply take this one NAND gate only, and both of the input I connect with single A only. So here A will go, here also A will go. What will be your output? A into A and then bar. What is A into A? A into A is A only. We studied it in Boolean Algebra. We studied A into A into A into A will always be A only. So A into A is A only, and then there is a bar. So NAND gate, from NAND gate you got OR gate. By only using one NAND gate you have designed NOT gate. Understood? Now what you need to design? You need to design AND gate. So what AND gate does? A into B. This is our target. Our target is to design this thing. Our target is to design this thing. So if I put A here and B here, what will be my output? AB bar, right? This is my output, AB bar. My output is AB bar. Now what I need to do? I am having AB bar. Now if I take another bar, then what will be my answer? AB. And this is what is required. So for another bar, what I need to do? I need to use an inverter. But I directly cannot use an inverter. I cannot use this. I need to make it using NAND gate only. So I will use this structure. Are you getting this point? I will simply take this structure. This AB bar goes here. This also AB bar goes here. So what will be your output? AB bar dot AB bar, multiplication of both, and then whole bar. So AB bar dot AB bar will be AB bar only, and then there is whole bar. So AB bar and bar will be AB only. Are you getting this point? First A into B, AB bar, and then whole bar will be AB only. So first there is an AND gate, and then there is an inverter. Now you need to make OR gate. What do you need to make? OR gate. We will see this topic again. Here my target is only to show you that they are working as universal gate. I will give you an intuition how you can make any kind of gate using NAND gate. This topic will come, okay, and it will be very interesting. In the next lecture only you will see how to design any Boolean function with using two input NAND gate and NOR gate, and with minimum number of gates. Using minimum number of gates, that also you will see. Now what is our target? Our target is to design y is equals to a plus b. This is what we need to design, right? Y is equal to y is equals to a plus b. So a plus b, but using what we need to use? We need to use NAND gate, right? So what I can do? Look, now you will have the question, sir, how did you think of it? So I know it. That's why I thought of it. But I will give you the intuition. But in the next lecture. Okay. So first what I am doing, I am getting a bar here. What I am doing, I am getting a bar here. Second, what I will do, I will get b bar. This will give you a bar and this will give you b bar. Now what do I know? That this AND gate can be replaced with bubbled OR gate, right? Bubbled OR gate. Here I am having a bar and here I am having b bar. So if a bar goes here, so a bar and then another bar, it will become a only, and b bar then another bar, it will become b only, and then there is OR gate, so plus will come. That will be our output. Did you understand this point? Here what I am going to make is that This is NAND gate only. Say yes or no. This structure is of NAND gate only, right? This is NAND gate only. This is A bar and this is B bar. So Y is equals to A bar bar plus B bar bar. It would be AB. Sorry, A plus B. A plus B. And this is what you wanted. So this is a NAND gate only. Understanding this point? I hope you must have understood. So better we should replace this with this. We should replace this with this structure only. With this structure, okay. So the same structure I will be replacing it, not with this one. So I will remove it. Look, what will be your y if I only replace this with this structure. So A bar dot B bar and then whole bar, right? And then whole bar. Now there is dot in between. If you want to replace this dot with plus, what you will do? You can take individual bar. A bar, then individual bar, plus B bar and then individual bar. So A plus B. That's your answer. So your answer is A plus B. Okay. Now let's see NOR gate as an universal gate. So what you need to do? You need to make an inverter. So same thing I will do. Inverter means NOT gate. So same thing I will do. Y is equals to A plus A plus A bar. So you will get A bar. Now you need to make OR gate. So how will you make OR gate? What is our output? Our target is to get A plus B. This is our target. So from here what I will get? So let's make it. So first I am having A and B with me. So first what I will get? A plus B bar. First I will get A plus B bar. And then I will simply make an inverter. So how will I make an inverter? By using this structure. So A plus B bar goes here, A plus B bar goes here. Both are added and then there is one more bar. So it would be Y is equals to A plus B. Now I need to make AND gate. So what is my target? My target is to make A into B, right? So let's just say how I will design it. Let's see. So first this is my A. If A goes here, what will be my output? A bar. And then B goes here, what will be my output? B bar. A bar, B bar, right? Now I know one thing, that this gate can be replaced with this gate as well, right? This is how also it can be replaced. So here I am having A bar and here I am having B bar. So A bar and then bar, it would be A. B bar and then bar, it would be B. And since this is AND gate, there will be multiplication. So AB, this is what I am getting. So here I am just replacing this structure. A bar, this is your A bar and this is your B bar. Bar of A bar, A. Bar of B bar will be B. A into B will be AB. So better I need to show with the same structure only. So that's how I will show it. So y is equals to a bar plus b bar. Here first we will do the addition and then take whole bar. So let's assume a bar as x plus y bar. B bar I am assuming as y. X plus y bar, what it will be? X bar dot y bar, right? X bar dot y bar. So a bar and then bar dot b bar and then bar. So a bar and bar will be a into b. So y is equals to ab you are getting. Okay. So y is equals to ab. This is the AND gate I am getting. So this is how I am using AND gate as an universal gate. Now we will study about arithmetic gate. Okay. There are a lot of things in those universal gate, but once we study arithmetic gate, after that we will move towards those points. So I am not going to skip anything. Everything that is there, that is necessary for your examination, that will be there. Okay. So first let's study about arithmetic gate, then we will come back to universal gates. So I have to pause the video because I have to change the slides. So I will continue now. So let's see our first arithmetic gate, that is XOR gate. So there are two arithmetic gates, XOR gate and XNOR gate. Okay. So we will see it one by one. We will see all the properties and everything. So XOR gate. So output will be logic high when both inputs are different, and output will be logic low when both inputs are same. So this thing is written for only two inputs. It is written only for two inputs. So generally in the interview you will not say this thing. In the interview you will say this thing. What you will say in the interview, that I will tell you. So in the interview you will not say that output will be logic high when both inputs are different. What you will say in the interview, that I will tell you. But let's just write down the output expression for two input. So that would be a bar b plus a b bar of one and then another one on its own plus a and then the bar of another. It can be replaced with the a into b bar plus b into a bar as well. Basically just I inverted it, nothing else. Just inverted it, nothing else. AB bar, this AB bar comes here and then this is BA bar comes here. AB is equals to BA. AB is equals to BA and A plus B is equals to B plus A. A plus B is equals to B plus A. This you can do. Okay. AB is equals to BA, A plus B is equals to B plus A. This I am writing down here. So anyhow it can be replaced. So let's check the truth table, what we get. So first I am writing A bar. What will be A bar? 1, 1, 0, 0. Bar of A. Bar of A. Bar of A. Bar of B will be 1, 0, 1, 0. Now I am doing A bar into B. A bar into B. So A bar into B. 1 into 0, 0, 1, 0, 0. A into B bar. A into B bar. So 0, 0, 1, 0. A into B bar. Now we need to add them up. I need to add both of them. 0, 1, 1, 0. So what did you understand? This was your AB. Just look at here. AB and this is your output. So A XOR B. 0 XOR 0. 0 XOR 0 is equals to 0. 0 XOR 1. This is the sign of XOR, okay? This can be replaced with A XOR. This is the sign of XOR B. Plus and then there is circle. Plus and circle. Okay. 0 XOR 1 is 1. 1 XOR 0 is 1. And 1 XOR 1 is 0. So when both input are same, your output is 0, and when both input are different, your output is 1. Are you getting this point? When both inputs are same, your output is 0. When both inputs are different, your output is 1. So 0 XOR 0, 0. 1 XOR 1, 0. 0 XOR 1, 1. 1 XOR 0, 0. Getting this point? Okay, so that's why it is known as non-equivalence detector. But this definition is true only for two input XOR gate. This is true only for two input XOR gate. So non-equivalence detector it is known as. Okay. And then there is very interesting thing that 3 input XOR gate does not exist. Generally in the examination you will never see a gate like this, that I am telling y is equals to A XOR B XOR C. So this thing is wrong. Generally only 2 input XOR gate exist. 3 input XOR gate doesn't exist. But in Morris Minor this structure is given. So it might be possible that in some of the gate question paper you can see this structure. But generally this should not come. 3 input XOR gate does not exist. This structure does not exist. Okay. But in Morris Minor, as per Morris Minor, in Morris Minor you will find this particular structure, that A XOR B XOR C, but that is wrong. It should not exist in this manner. Okay. So 3 input XOR gate does not exist, neither 3 input XNOR gate exists. If you want to make 3 input XOR gate, then how you will make it? With the 2 input XOR gate. Okay. So A XOR B, here output will be A XOR B. Now this output is going into another XOR gate. So A XOR B XOR with C. So A XOR B and then XOR with C. So this is how you can make this output. Making this output like this is not possible. In simulation as well, you will never make this structure. You will get A XOR B XOR C by this only. Okay. So 3 input XOR gate does not exist actually. So if someone is asking you what is the definition of XOR gate, then you can tell this. But it is not necessary that the guy who is interviewing you knows this thing, because this is not very famous thing. So if you tell this thing to him, that it is a non-equivalence detector, and when both of the inputs are if both of the inputs are same, then output will be 0, and both of the inputs are different, then output will be 1 or output will be high. If you tell this thing to him, then he might be saying that what if it is a 3 input XOR gate. So there you cannot argue to him. So that's why I generally avoid telling this definition. So how will I tell that? Let's check out this in this particular video only. So let's proceed in this lecture. So first solve these values. 0 XOR 0 is 0. 0 XOR 0 is 0. 0 XOR 0 again is 0. 0 XOR 0, 0. 0 XOR 0, 0. Look, you will assume XOR as plus only. Assume XOR as plus only. But when you see 1 XOR 1, then you just need to think, okay, both are same, I will give 0. 0 as you assume you assume XOR as plus only. 0 XOR 1, 0 plus 1, 1. 0 XOR 0, 0 plus 0, 0. 1 XOR 0, 1 plus 0, 0. 1 XOR 1, 1 XOR 1, 1, 1, same. Then it would be 0 only. Okay. And how do I usually remember it? I will tell you. 1 XOR 0. It is like that, right? And one more I will write, 1 XOR 1. So what I would do, I will pick this one and mix it in this. I will pick this 0 and mixing it in this. 0 को उठाया 1 में डाल दिया, क्या मिलेगा? 1. 1 was there. I will pick this one and put 1 in that only. 1 को उठाया और उल्टा करके उसमें डाल दिया. Like you take it like this. उल्टा करके डाल दिया है. This is 1 and so it would be 0. Right? If I write A XOR A. So I will pick A and reverse it and put it there. Basically reverse it and put it there. This is how I remember it. So it will become 0 only. If it is there A XOR A bar. So I will reverse it and put it there. So A XOR A will become 0, but bar is there. So this bar, since I am reversing it, so this bar will become something like this. So A XOR A bar is 1. This is how I remember it. It makes me remember it. Okay. So A XOR A bar is 1. In the later on this chapter only, I will tell you these things you need to remember. So 1 XOR 1 is 0. So put this one, reverse it and mix it in 1 only. So 1 is mixed with 1, 0. 0 is mixed with 0, 0. 1 is mixed with 0. 0 is going here. Nothing is happening. So it would be 1. 0 is mixed with 1. 1 will be reversed and goes into 0. So it would be 1. Right? But same is mixed, then it would become 0. It's like interference. Constructive interference and destructive interference. So it is like that interference only. 1 is going into. So this is how you can remember it, because there will be a lot of things people will say that how we can remember it. But once you are habitual of these gates, then these will be a cakewalk for you. But this is just a simple way I am asking you to remember. Now 1 XOR 1, 1 XOR 1 will be 0, and then again XOR with 1. So 1 XOR 0, it would be 1. 1 XOR 1 will be 0. 1 XOR 1 will be 0. And then again XOR with 1, that would be 1. Then again XOR with 1. So 1 XOR 1, that would be 0. Are you getting this point? Look, 1 XOR 1 is 0. Then there is an XOR sign. And let's just solve this value. 1 XOR 1. Again it is 0. 0 XOR 0 is 0 only. So no matter how many zeros are there, it will always be 0. But did you notice one thing here? What did you notice? When there are odd number of ones, then answer is 1. And when there are even number of ones, answer is 0. 1 XOR 1 will be what? 0. But if I do 1 XOR 1, XOR 1, XOR 1, XOR 1. So 1 XOR 1 will be 0. And then there is again 1 XOR 1, that would also be 0. And then again XOR 1. So 0 XOR 0 will be 0. 0 XOR 1 will be 1 only. So if there are odd number of ones, then it is known as, so if there are odd number of ones, then answer will be 1. But if there are even number of ones, answer will be 0. That's why your XOR gate is known as odd number of ones detector. So in the examination, in the interview, they are asking you what is the meaning of XOR gate, then you will tell that it is odd number of ones detector. So that would be a good definition, irrespective of the inputs. So XOR gate is a odd number of ones detector. If at the input I am getting odd number of ones, then my output will be high. If at the input I am getting logic high odd number of times, then my output will be high. That's it. This is the correct, and this will be the correct answer. Okay. Now let's see this question. Odd numbers of one detector. 1, 2, 3. 3 times 1 is there. Answer will be 1. Look at this one. 1, 2, 3, 4. 4 times 1 is there. Answer will be 0. And you could have solved it as well. No need to mug it up. Okay. Basically, if I write A XOR B XOR C, so I can replace these values. C XOR A XOR B. Anywhere I can replace those. This can come here. This can come here. So what I would do, I will keep all ones aside. 1 XOR 1 XOR 1, and then all zeros aside. No matter how many zeros are there, they will become 0 only. How many zeros are there, they will be 0 only. So this will be replaced as 0 only. Now 1 XOR 1, it will be 0. XOR 1 XOR 0. So 0 XOR 1 will be 1. That's it. This is the correct answer. You can solve it as well. All the ones you take one side only. They are even. 1 XOR 1 0. XOR with 1 XOR 1 0. 0 XOR 0, all are 0 only. So it would be 0. So this way you will be able to write down the correct answer quickly. Or you can remember it is odd number of ones detector, which I have already written in the next page. So XOR gate is odd number of ones detector. So if let's just say I give you one more example, will you be able to write it down quickly? Look, you might be forgetting this thing, but you will not be forgetting how to solve these kind of problems. I told you, take all ones aside. So 1, 2, 3, 4, 5, 6, 7. 7 ones are there. You know 1 XOR 1 is 0. Then another 1 XOR 1 is 0. Another 1 XOR 1 is 0. So 6 ones will make 6 ones are there. 6 ones will make 0 only. 1 XOR 1, 0. 1 XOR 1, 0. 1 XOR 1, 0. Only this is left. So 0 XOR 0, 0, 0 will be there. XOR 1 and then XOR, more zeros will come. But there is no meaning of that. So basically 1 XOR 0 is left. So answer will be 1. So from here you got to know that there are odd number of ones. So it is odd number of ones detector. Because in the examination you will be forgetting it. If after 5 days I come to you and I ask you what is XOR gate? Odd number of one detector, even number of ones detector, even number of zero detector, or odd number of zeros detector. Okay, then you will think 0 or 1 or odd, even. Like this you will think. But when you take the example, okay, if there are all zeros, then there is always answer will be 0. What I mean to say is, if there are even number of zeros or there are odd number of zero, answer is 0 only. So you cannot say it is odd number of zero detector or even number of zero detector, because for both even input as well and odd input as well, your answer is always 0. So you cannot differentiate. Even if there is odd input or even if there is even input, your answer is 0. So here you cannot differentiate, because always it will be 0. But if there are odd number of ones, then you will think, okay, if there are 3 ones, 1 XOR 1 will make 0, 0 XOR 1 will be 1. Okay, so if there are odd number of ones, my output is 1. If there are even number of ones, 1 XOR 1 is 0, 1 XOR 1 is 0. Okay, 0 XOR 0, it will be 0 only. So if odd number of ones are there, my output was 1. So it is odd numbers of ones detector. So better than mugging it up, you keep it in mind. So I have seen a lot of guys forgetting this thing, odd number of ones detector, because XNOR gate will also come there, right? Now XNOR gate will also come, so there the scenes will be different. So a lot of guys forget it. So if we better keep it in mind, then it will be more clear to us. Now we will see the switching circuit. So for this switching circuit, we will use a different kind of switch that is known as two-way switch. So if my A is connected to B, then I will assume the switch to be on. And if my A is connected to C, then I will assume the switch to be off. It can be other way around as well. Like if A is connected to C, then it would be on. A is connected to B, then it would be off. It will be given in the question. Whatever the question is there in your examination, it will be given that if A is connected to B, then you consider it on. On means 1 and off means 0. So it will be given in the question. Okay. So if S1 is on and S2 is on, that means A is connected to B and this B is connected to A. So what will be the circuit? This is V in, A is connected to B, A is connected to B and B is connected to A. So this path I am getting, this complete path I am getting. So this wire is completely shorted. Are you getting this point? This path I am getting, this path I am getting. So this wire is completely shorted here. And then there is a bulb. So current goes here and it flows from here. The bulb will not turn on. The bulb will not have any current because the complete current is flowing from this short circuit path. So bulb will be off. Let's do the next thing. In the next structure, what they are saying, A is connected to S1 is on and S2 is off. So A is connected to B. A is connected to B. But S2 is off. That means A is connected to C. 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 So do you have any path? This is the input. Do you have any path? The current will come here. It will not go here because this is open circuit. Are you getting this point or not? A is connected to B and B is connected to, sorry, and A is connected to C here. Here it is connected to B and here is connected to C. So the current comes here, it cannot flow here, right? Because there is this open circuit path. This is open circuit path. Here also there is open circuit. So no current will flow here as well. So the current will go into bulb directly. So bulb will turn on. Bulb will turn on. Do it on your own. Do the third one on your own. In the third one, what is happening? A is connected to C. A is connected to C because S1 is off. That means A is connected to C. A is connected to C. And A is connected to B. A is connected to B. S2 is on. S2 is on means S2 is on. That means A is connected to B. A is connected to B. So will any current come here? Because this is open circuit. This is open circuit, so no current will come here. This is also open circuit. No current will flow here. So the current will flow in this manner. So bulb will turn on. Bulb will turn on. And what about the last one? If both are off means A is connected to C. A is connected to C. And here also A is connected to C. So this will be the path. This will be the path. So current can flow here as well. Okay. And the bulb will not turn on. Current can flow here. So bulb will not turn on now. The bulb is not turning on. So it would be O. So here you can see 1 XOR 1 is 0. So this is XOR gate only. If both are on, if both are high, then output is 0. If both are low, then output is 0. 1 is high, 1 is low, 1 is high, 1 is low, then output is 1. So this is the XOR gate. So this is how we make XOR gate. Right? Well and good. So some properties that this I have already told. A XOR B is equals to B XOR A. Just the reverse. A XOR B XOR C would be equals to first A XOR B and then you take the XOR. Then first you take A only, then you take the XOR. Basically, anywhere you can put the bracket. That's it. Okay. Now XOR gate using basic gates. What you need to make? A bar into B plus A into B bar. So what is my target? What I need to make? A bar into B plus B bar into A. So A bar, and then here goes A bar into B. This is my A, this is my B. A bar into B. And what else I need to make? B bar into A. So take invert of that, B bar into A. And this A comes directly. B bar into A. And then both of them are added. So both are added. So A bar into B, B bar into A, and both are added. We will make this structure using NAND gate and NOR gate as well. But later on in the next lecture, using NAND gate, we will make this structure using NAND gate and NOR gate, but in the next lecture. So this is all about our XOR gate. XOR gate using basic gates. So basically A bar comes here, this will be your A bar, this will be your B bar. So A into B bar, this is A into B bar, and this is A bar into B, and both are added. So A B bar plus A bar B. Okay. Now important observations that I have already told. A XOR A. So let's do it. First as it is, bar of the second one plus second bar of the second one plus first as it is. So A into A bar, what that would be? I have told this thing in the last lecture only. A into A bar 0 plus A into A bar 0. That would be equals to 0. So A XOR A. So that you need to remember. A XOR A is equals to 0. I told you, how will you remember? A goes in here. So A goes in here, so 0 is left. A XOR 0. Take XOR as plus only. So A XOR 0 will be 0. Or you can take in this manner. A into bar of 0 will be 1. Plus, or let's write it more. First as it is, bar of the second one. Plus bar of the first one and second as it is. So A into 0 bar will be 1 plus A bar into 0. A bar into 0 will be 0. A bar into 0 will be 0. So that would be equals to A. Basically A XOR 0. 0 goes in, so it would become A only. A XOR 1. So A into bar of 1 plus bar of A into 1 as it is. Bar of 1 is 0. A into 0 plus A bar into 1 will be A bar only. So A into 0 is 0. This would be A bar only. So A XOR 1. So what will happen? This 1 will go here and it will act as bar. Are you getting this point? This was A XOR 1. So 1 goes here and it will become bar. 1 is becoming like this. 1 is rotated 90 degree. 1 was there, it is rotated 90 degree. So it is A bar. So A XOR 1 is A bar. Now A XOR A bar. A XOR A bar. So this goes in, but this bar is left. So that will be rotated 90 degree. So answer will be 1. This is the way I am telling. This is just the way that you can remember. Otherwise you can derive it as well. But in the examination, a lot of variables will be there. So you will not be deriving there. Okay, you need to remember it. So first one as it is, bar of the second one. First one as it is, bar of the second one, plus second one as it is, bar of the first one. So a into a is a, plus a bar into a bar is a bar. So a plus a bar is 1. In the next lecture, in the last lecture only, I told you a plus a bar is 1. So what you have to remember? These are the final answer that you have to remember. A XOR a bar will be 1. Now this is very interesting. If A XOR B is C, then what will be A XOR C? What will be A XOR C? So let's try it out. What you can replace? A XOR. What is C? C is A XOR B, right? C is A XOR B. C is A XOR B. I can open this bracket. A XOR A XOR B. What will be A XOR A? A XOR A. It will be 0. A XOR A. A XOR A is 0. So it would be 0 XOR B. And what will be 0 XOR B? That would be equals to B only. So that's it. This is the answer. 0 XOR B will be 0. So what did you understand from here? If A XOR B is equals to C, then A XOR C is equals to B. This is the first one. Or instead of A, I can replace C as well. C XOR B is equals to A. Okay. Basically, if I had written B XOR A is equals to C, if I had written B XOR A is equals to C, then these two can be replaced. Not these two can also be replaced. Okay. So C XOR B is equals to A, or C XOR A is equals to B. So these properties you will have to remember. Okay. Let's see more interesting thing about XOR gate. More interesting things are there. Let's solve this. Four A's are there in XOR gate. So A XOR A is 0. Then another XOR. A XOR A is another 0. So 0 XOR 0 is 0. So A XOR A XOR A XOR A is 0 only. A XOR A is 0. Then XOR with again A XOR A 0. Then again A XOR A, again XOR 0. That would be 0. Even number of A's are there, answer is 0. A XOR A is 0. And then XOR with A. So A XOR 0 will be A only. Initially A XOR A 0. XOR A XOR A is 0. And then simply A. 0 XOR 0 is 0. And then XOR with A. A XOR 0 is A. So if odd number of A's are there, answer is A. That's why it is known as odd numbers of one subtractor. So A XOR A XOR A, in that manner it will go. If there are even number of A's, answer will be 0. If there are odd number of A, answer will be A. Are you able to understand this point? So this is also you can keep in mind. You don't need to remember these things. You can keep in mind. Okay, even numbers are coming, then A XOR A 0 0 0 0 0 XOR 0 will be 0 only. If odd numbers are coming, then 0 0 0, but one A will be remaining. So that will be the answer. So you can just keep in mind. Nobody mugs it up. I remember these things just by pick the A, mix it 0. Pick 0, mix it. The same value will come. Pick 1, mix it. It will be bar. Pick A bar, mix it. So A and A will be 0, but there is bar, so that would make it 1. More interesting thing will be there. More interesting things will be there. But we will cover that later on. But first, let's see about XNOR gate. So XNOR gate we will see. So what is XNOR gate? XNOR gate is simply XOR gate plus NOT. So this was our XOR gate. And then bar will be there. That's it. XOR gate and then bar. It is denoted as A dot and then circle B. This is how also it is denoted. And what will be its output? That would be A bar, B bar plus AB. Let's see how do we get it. A bar B plus AB bar. And then whole bar is there. Do you remember De Morgan's theorem? X plus Y bar. That would be written as X bar plus Y bar, right? So take bar of this. Sorry. There will be dot. X bar dot Y bar. So take bar of this. And then take bar of this. Now what is this? X into Y bar. So that can be replaced with X bar plus Y bar, right? So a bar, it would be a plus b bar into a bar plus b. Now multiply this. A into a bar is 0. A into b is ab plus a bar into b bar is a bar b bar, and b into b bar is 0. So what you are left with? A bar b bar plus ab. If you are not able to solve it, no need to worry, because we will see a lot of examples of De Morgan's theorem in the next part of this video. No, not of this video, in this chapter only we will see a lot of examples of De Morgan's theorem. So there you will be habitual, but here also you can build the habit. X plus y bar and x bar dot y bar. Then you need to take bar of this. So two variables are there, bar of the first one plus bar of the second one, and then simply the multiplication. A into a bar is 0. A into b, b bar into a bar plus b into b bar will be 0. So a bar b bar plus a b bar. So just the bar we are taking, nothing else. Now what is the what will be a bar here? It would be 1 1 0 0. What will be b bar? That would be 1 0 1 0. What will be a bar into b bar? So 1 0 0 0. What would be ab? 0 0 0 1. And what would be the addition of both of them? 1 0 0 1. Okay, so what you are seeing, this is equivalence detector. If both the inputs are same, then output is 1. If both the inputs are different, output is 0. But generally I do not solve XNOR problem by this thing. How do I usually solve that? I will tell you. So 0 XNOR 0 is 1. 0 XNOR 1 is 0. 1 XNOR 0 is 0. 1 XNOR 1 is 1. Solve this. 1 XNOR 1. 1 XNOR 1 will be 1. 1 XNOR 1 will be 1. And then again XNOR with 1 will be 1 only. Right? 1 XNOR 1 will be 1. Then again XNOR with 1. Then again XNOR with 1. So 1 XNOR 1 will be 1. 1 XNOR 1. Same. Equivalence detector. XNOR with 1 will be 1. So no matter if even number of inputs are there or odd number of inputs are there, it is 1 only always. If there are even number of ones or there are odd number of ones, output is 1 only. So you cannot say it is even number of ones detector or odd number of ones detector. But let's see in the case of 0. So 0 XNOR 0 will be what? 1. Equivalence detector. 0 XNOR 0 will be 1. And 1 XNOR 0 will be 0. So answer is 0. Right? 0 XNOR 0 will be 1. Then again XNOR. 0 XNOR 0 will be 1. 1 XNOR 1 will be 1. So answer is 1. So in case of 0, if there are odd number of zeros, then answer is 0. But if there are even number of zeros, answer is 1. So XNOR gate is known as even number of zeros detector. Okay. So let's write down both of the things. XOR gate was what? Odd number of ones detector. In one number of problem, this can be asked in MCQs. That what is XOR gate, what is XNOR gate. XNOR gate is called as, XNOR gate is called as. Okay. So in XNOR gate, you cannot define by 1. Because why you cannot define by 1? Because in both of the cases, you are getting 1 only. But here, in both of the cases, you are getting different. If odd number of zeros are there, your answer is 0. If even number of zeros are there, your answer is 1. So it is even number of zeros detector. So in MCQ it can be asked, but even if you forget, you can derive it in the examination and then tick the correct answer. Deriving will take 30 seconds. You will see, okay, 0 0 0, and then you will be able to derive it. Okay, let's solve this. 1 2 3. Odd means 0. 1 2. Even means 1. But in the examination I will not be doing this. I will be solving it. 1 XOR 0, what that would be? 0. Sorry, 1 XNOR 0, and 0 XNOR 1 will be 0, and then again 0. 0 XNOR 0 1 1 XNOR 0, 1 XNOR 0 will be 0. That's it. This is my answer. Okay. In the examination, I will not be doing by this method. I will tell you one easiest method. By that, you will not have to solve XNOR calculation any day. Okay. In this lecture only, I will tell you that method. So 1 XNOR 0 will be 0. XNOR with 1 will be again 0. 0 XNOR 0 will be 1. 1 XNOR 1 will be 1 only. So answer is 1. In the examination, I will not be solving by this method. There will be another method that I will tell you. Now very interesting observation will come, and this is the method by that we will be solving in the examination. So first tell me what will be A XOR B. So 0 XOR 0, 0. 0 XOR 0, 0. 0 XOR 1, 1. 0 XOR 1, 1. 1 XOR 1, 1. 1 XOR 0, 1. 1 XOR 0, 1. 1 XOR 1, 0. 1 XOR 1, 0. Right? Now let's do A XOR B. So just the bar of this will come, right? Or we can solve it as well. 0 XOR 0, 1. 0 XOR 0, 1. 0 XOR 1, 0. 0 XOR 1, 0. 1 XOR 0, 0. 1 XOR 0, 0. 1 XOR 1, 1 XOR 1, 1. 1 XOR 1, 1. Let's do A XOR B XOR C. A XOR B XOR C. XOR of both of them. So 0 XOR 0, 0. Right? 0 XOR 0, 0. 1 XOR 1, 0, 1. 1 XOR 0, 1. 1 XOR 1, 0. 0 XOR 1, 1. 1 XOR 1, 0. 0 XOR 0, 0. 1 XOR 0, 1. Let me check if I am doing it correct. 0, 1, 1, 0, 1, 0, 0, 1. Yeah, it is correct. Now what I need to do? A XOR B with this XNOR. Shall I do only the shall I do simply the bar? Shall I simply use not get here? Shall I simply use not get here? No, this is not I need to do, because this is A XNOR B with XNOR C. So A XNOR B with XNOR C. So this I need to do. 1 XNOR 0 will be 0. 1 XNOR 1. 1 XNOR 1 will be 1. 1 XNOR 0 will be 0. Sorry. These two I need to do. 0 XNOR 0 will be 1. 1 XNOR 0 will be 0. 0 XNOR 0 will be 1. 1 XNOR 0 will be 0. 0 XNOR 1 will be 0. 1 XNOR 1 will be 1. What did you see here? What did you see? That A XOR B is bar of A XNOR B, but A XOR B XOR C is equals to A XNOR B XNOR C. So for even number of inputs, both are bar of each other, but for odd number of inputs they are the same. So XNOR you can replace with XOR if there are odd number of inputs. Are you getting this point? So this is the thing I have written. For even number of inputs, XNOR is equals to XOR is equals to XNOR bar. But for odd number of inputs, XNOR and XOR are equal. Okay, so very interesting point. So A XOR B, I can write it as A XNOR B bar. But A XOR B XOR C, I will write it as A XOR B XOR C. Here, I will write it as A XOR, I will write this as A XOR B XOR C XOR D bar. But here I will write both are equal only. One more interesting thing I will tell you, that A XOR B XOR C bar, is that equals to A XOR B XOR C? No, not at all, because both are same. Without bar both are same. Without bar both are same. So it is not equals to this value. How will you make this one? How will you make this? How will you make this? So what I would do, I will get this. Okay, then this I will get, and then one inverter I will connect. So this is my A, this is my B, this is my C. So this will be A XOR B. So here what I will get, what this value will be, A XOR B XOR C. So eventually then this will be my Y. So my Y will be A XOR B XOR C. Or how I can write Y? Think about it. Can I write Y as this? A XOR B and bracket here and XOR C. Say yes or no. Did you understand this point? What I am doing is, this bubble was there, no? This bubble was here, right? This bubble was here. So this bubble can come here. This bubble can come here. If this bubble comes here, that means it is acting as a XOR gate only. And what will be XOR of A XOR B and C? XOR of A XOR B and C. What that would be? A XOR B XOR of C. So A XOR B XOR C and then bar, sorry, would be equals to A XOR B XOR C. Are you getting this point? This is the point where I am getting this value. Okay. At this point I am getting this value, and then there is a bar. Then there is a bar. So here I will get A XOR B XOR C bar. But if I make this as XOR gate, then it would be A XOR B XOR C. So this is also a very interesting thing. Okay. So what did you understand here? For odd number of inputs, both are same, but for even number of inputs, both are bar of each other. So this was very interesting point, very interesting conclusion. So if you need to solve these kind of problems, so what will be the first thing I will be doing? I will check the number of inputs. 1, 2, 3, 4, 5. Okay, 5 inputs are there. I can replace dot with XOR. And I am very much comfortable with XOR. So then I will be solving XOR gate very, very easily. So 1 XOR 0, 1. 1 XOR 0, 1. 1 XOR 1, 0. 0 XOR 0, 0. Answer will be 0. Here again I will count the input. They are 5 only. But let's just come here. Here I will count the input. Okay, there are 4. 1, 2, 3, 4. There are 4 number of inputs. So what I will do? I will replace with XOR only. I will replace it with XOR, but I will remember one thing. Whatever the answer I will get, I will take bar of that. So 1 XOR 1, XOR 1, XOR 1. I know I will get answer 0, but I need to take the bar. So 0 bar will be 1. So this is how I will be solving in the examination. I will replace XOR with XOR, but if even number of inputs are there, I will take the bar. If odd numbers of input are there, I will not change my answer. So this is how I will be solving in the examination. Okay. So this you can do in your examination. Switching circuit, this you can solve on your own. So this is the same kind of switch there, which was connected in parallel. Now it is connected in series. So simply, if it was connected in parallel, like this it was connected, then I was getting this answer. Now if it is connected in series, then I will simply get bar of it. Basically, if one switch is connected in parallel and I am getting answer as A bar, then if it is connected in series, then I will get answer as A bar of bar. So that would be A. So similarly, if it was connected in parallel, I was getting answer as A XOR B. Now if it is connected in series, I will get bar of that. That would be the answer. Okay. So you can do it on your own. If both are on, that means if both are connected to B, then a bulb will turn on. If one is on, one is off. So one connection here, the switch will be open circuited. So it would be off. One is off, then one is connected here, another is connected here. So no complete path is there, again off. If both are off, that means this is connected to C, this is also connected to C. So both are connected to C, that means bulb will turn on. So it would be A XOR B. Okay. Some properties, A XOR B is equals to B XOR A, and A XOR B XOR C, that can be replaced with A XOR and B XOR C. Anywhere you can put the bracket. Okay. XOR gate using basic gate. XOR gate using basic gates. So what I need to implement? I need to implement Y is equals to A bar, B bar plus AB. So this is your A and this is your B. So here you are getting AB. Then this A goes here in terms of bar. This is your A bar. And then B goes here in terms of bar. This is your B bar. So here you are getting A bar, B bar. and there is this OR gate which will just do the addition. So it would be AB plus A bar B bar. Well and good. Okay, very easy. Now A XOR A, I will treat it A XOR A. I will treat it as XOR gate. So A XOR A XOR A is 0, but XOR is there, so answer will be 1. A XOR 0 is 0. Sorry, A XOR 0 is A, but XOR is there, answer will be A bar. A XOR 1 is A bar. A XOR 1 is A bar, but this XOR is there, then bar will come. So A will be the answer. You can solve it on your own as well, that A XOR A. So bar of both of them plus without bar. So A bar plus A. A bar plus A is 1. So you can solve in this manner, but you need to remember. How will you remember? Two inputs are there, that means even number of input are there. So in the mind I will think XOR, but I need to take the bar of that. A XOR 0 is A, then bar of that will be A bar. A XOR 1 is A bar, then bar of that will be A. A XOR A bar is 1, bar of that will be 0. That's it. This is how I need to think in the examination. If A XOR B is C, then what will be your A XOR C? A XOR C will be what? A XOR C can be replaced with A XOR B. That would be A XOR A XOR B. So A XOR A will be 1. And 1 XOR B will be what? B. 1 XOR B will be B. So A XOR C is replaced with B. So here basically A XOR C is equals to B and B XOR C is equals to A. That's it. This is not the answer. This is how we can replace it. Okay. Now let's solve these problems. A XOR A. So in the mind I will think of XOR gate. A XOR A is 0, but I need to take bar, so it will be 1. These inputs are 3 inputs. That means these are odd inputs. So in the mind I will think of XOR gate only, and that will be my answer. A XOR A is 0, 0 XOR A. That would be A only. Here I will get 1 and here I will get A. You can do it on your own. So if number of inputs are odd, then my answer is A. And if number of inputs are even, then my answer is 1. So you don't need to mug it up in the examination. You will be able to do it on your own. Right? Okay. Very easy. Let's move towards next important properties. Very, very important property it is. Very, very important. So let's solve this. A bar XOR with B. So first as it is, bar of the second one plus bar of the first one, A bar bar, and second as it is. So what I am getting? A bar B bar plus AB. That can be replaced with A XOR B, or it can be replaced with A XOR B bar. So if there is bar on 1, then whole bar can be taken. So how this can be done? If there is bar on 1, then whole bar can be taken. Then there is bar on the another one, then another whole bar will be taken. So 2 bar will cancel out each other. So A XOR B only. You can solve it as well. A bar XOR B bar. So first as it is, bar of the second one plus bar of the first one, that would be A only, second as it is. So this is A XOR B only. So if there is bar on 1, the whole bar can be taken. Same goes for this one. You can solve it. You can solve this one. Bar of the first one, and the bar of the second one plus as it is. This is XOR gate. In XOR gate, what do we do? Bar of the first one, and then bar of the second one plus both as it is. A bar B bar plus AB, bar of the first one and then both as it is. So AB bar plus A bar B. So it can be replaced with A XOR B, or I can write A XOR bar. So there was a bar and then whole bar is there. 1 bar will be taken as whole bar. So what will happen to this one? 1 bar is there. So because of this bar, 1 complete bar will come. Because of this bar, another complete bar will come. So it would be. So that's it. So this is a very important property. If bar is there on one variable, then whole bar can be taken. Okay. So you will remember it, right? So let's see what we have. So now we will see example of all these in assignments. More examples can be there, like 3 variables are there, then how we will deal it. So more examples can be there. So let's take one example. So if I write A XOR bar of this, now how you can replace it? So can I assume it as A bar XOR X, where my X is B XOR C. So can I write it as A XOR S? Why I can write it in this manner? Because whole bar I will be taking. Basically I skipped one step. That step is A XOR X whole bar. So that can be replaced as A XOR X. And what is our X? B XOR C. So this can be replaced with this. So these kind of questions will come. So basically you will just have to make it 2 variables. If you are able to make it 2 variables, then you will be able to solve it. Okay, no need to worry about it. These kind of questions are very easy. So NOT gate and buffer using XOR gate. So let's just say if this input is A and this input is 1, what will be your output? Y. That would be A XOR 1, because this is XOR gate. So this answer would be A bar. So what is this? This is acting as NOT gate. This is acting as NOT gate. Very simple thing, very easy. If here I am having A and here I am having 0, so what will be my output? A XOR 0. So that will be A only. So your input was A and output is also A. So what is this? This is acting as buffer, right? If this is A and this is 1, so Y will be A XOR 1. So that will be A only. So what is this? This is also buffer, because A XOR 1 is A only. If this is A and this is 0, so what will be your Y? Y will be A XOR 0. That will be A bar. So what is this? This is NOT gate. Well and good, very easy. Okay. Now we will see this thing in next lecture, because we need now our target is to implement any function using minimum number of NAND and NOR gate. So in the next lecture we will see what are their equivalent representation, because this equivalent representation we have already seen. What is this? This is NOR gate. So NOR is bubbled AND gate. And what is this? This is NAND gate. NAND gate is bubbled NOR gate. If this is bubbled NOR gate, so basically what is this gate? This is AND gate. So AND gate can be replaced with one note and then another note, right? So this can be replaced with this much of gate and then another note will come. So this is how this can be replaced. Okay. Right. So in the next lecture we will see it, and similarly for this one as well. Then we will see the basic definition of SOP and POS, sum of product and product of sum, because that will be used in our analysis. Okay, so yeah, so in this lecture there was a lot of information. So before moving on to the next lecture, or before shutting down your laptop, once revise this lecture again. Okay, revise it very fastly. You will be able to revise, you will be having the notes as well. So revise it and then move to the next lecture. Next lecture will also be very interesting. Hi everyone, so this is going to be a very important video and very conceptual video, and like 90% of the guys are confused in this particular topic. That's why I thought of making a separate video on this particular topic. So in this video we will try implementing a random Boolean functions, some random Boolean functions using minimum number of NAND gate and NOR gate. Minimum number of NAND and NOR gate should be used. Okay, it's not that if 4 gate can implement a particular function, then we will be using 5 gates. Not like that. Minimum number of NAND and NOR gate. Okay, so before that there will be some prerequisites. So can you replace your NAND gate by this gate? Because I told you NAND gate is bubbled OR gate. So this bubble will come up in front, right? This bubble will come in front, and this gate will be replaced with OR gate, right? Similarly, NAND gate is nothing but, what I mean to say is, NAND gate is, this is the NAND gate, and then there is another inverter. This is our NAND gate is, right? Sorry, basically what I was saying, what is our AND gate? NAND gate, then another inverter. So I just replaced this gate and then there is one inverter. So can I replace my AND gate something like this? Do you agree to my point? Can I replace my AND gate something like this? Basically NAND gate and then there is an inverter. So NAND gate, there is an inverter. Similarly with NOR gate, this bubble will come in front and this OR gate will be replaced with AND gate. And similarly, what is this? This is a NOR gate with another bubble. NOR gate with another bubble. So this bubble will come in front and it will be replaced with AND gate, and this another bubble can be replaced here. So this is how I can replace my NOR gate. So these examples I hope these are clear to you. If you are not able to remember this 2 and 4 point, then at least remember 1 and 3. These are very important. Bubble will come upward, bubble will come in front and it will be replaced like this. So these are NAND gate can be replaced with bubbled OR gate and NOR gate can be replaced with bubbled AND gate. Well and good. Okay. Now I will be using these two terms, SOP and POS. So SOP means sum of a product. Sum of a product. So this is a product term, no? A into B. This is a product plus C into D. So this is an example of sum of product. Sum of product. Sum of product, SOP. More example can be there. AB plus BC plus CD. Sum of product. Now we will see product of sum. Product of sum. So first we need to do the sum and then product. These two are the sum terms. Again we will discuss it when we study K-maps, when we study Boolean algebra. At that time we will discuss it again. But here basic prerequisite you need to have product of sum. Product of sum. You are doing the product of sum terms. These are the sum terms, or it can be replaced with A into B plus B into C plus C into D. So product of sum. So this is known as product of sum. So very easy thing. Sum of product. Sum of product. Product of sum. Product means multiplication. Now let's start our topic. So we need to implement random Boolean function using minimum number of NAND gate. First we will study about NAND gate, then we will study about NOR gate. So these are the points which you might not be able to remember, right? You might not be able to remember these points, but when I am talking NAND gate, you should always think about SOP, sum of product. So my target will be to implement the function in sum of product form. Basically in this form, sum of product, sum of product. This will be my target. When I talk about NAND gate, my target will be sum of product. This is what you need to remember. So basically there will be a function. First we will implement that function using basic gates. Using basic gates we will implement that function and then we will convert the basic gate into NAND gate. We will see the examples, it will be more clear to you. But do you remember for implementing NOT gate how many NAND gates were required? For implementing NOT gate, how many NAND gates were required? How did you implement NOT gate using NAND gate? This is how you implemented, right? A and A bar. Only one gate was required. That's it. Right? For AND gate and OR gate, you might not be remembering the answer, but let's derive it. Let's see how we will be able to do it. So if I need to make A bar, how will I make it? Using NAND gate. Using NAND gate, I need to implement all these functions. So how will I make it? This is how I will make it. This is your A, but Y will be A bar. Now what do I need to make? I need to make AB. So implement AB using basic gates. How do I make AB using basic gates? This is how I make AB using basic gates. AB using basic gates. This is A, this is B. Y is equals to AB. But you need to use NAND gate, right? You need to use NAND gate. Now tell me one thing. if I say my input is A and I want my output to be A only, and if I use one inverter here, so to compensate this inverter I need to use another inverter, right? If I am using two inverter, then if I have applied A here also I will get A only. So similarly, I need to use NAND gate. So if you need to use NAND gate, here you need to add an inverter. So if I am adding an inverter here, I will have to use another inverter here. Say yes or no? Because if I am adding an inverter, then another inverter I have to use. So to implement this gate, how many NAND gates are required? This itself is a NAND gate, so 1. And to implement this inverter, how many NAND gates are required? Another 1. So what will be your answer? You need 2 NAND gate to implement this particular function. This we have already seen how we will implement. AB bar, and then simply both will go here, and that would be the answer. AB bar here, and answer Y is AB. So in this manner you can proceed. What is the way we are proceeding? Are you able to understand this point? First I have implemented it using simple basic gates, and then I thought what I need to do. Let's go to this example. A plus B I need to implement. A plus B. Okay. So how can I implement A plus B using basic gates? A plus B. That's it, right? A and B, my output will be A plus B. But what I need to use? I need to use NAND gate. So from here, if I need to make NAND gate, how will I make NAND gate? I have to use one inverter here. If I am using one inverter here, so to compensate that, I have to use another inverter here. I can use one more inverter here. To compensate that I need to use one more inverter here. What is this? This is a NAND gate only. Look here. This is a NAND gate only. That's why I told you need to remember it. NAND gate is bubbled OR gate. Why did I do this thing? Because I need to use NAND gate. So I am introducing a bubble here. So if I am introducing a bubble from my own side, so to compensate that I need to use one more inverter. Because otherwise one inverter I introduce, that I cannot do. If I am introducing one inverter from my side, so to compensate that I need to use another inverter, so that this logic function remains the same. Here A plus B was there, output will also be A plus B. So to compensate that I am using another inverter. So this is an AND gate. So one gate you will require here. To make this inverter, how many gates you will use? To make this inverter, another one gate you will use. And to make this inverter, how many gates you will use? Another one gate you will use. So how many gates are required? 1 plus 1 plus 1. 3 gates are required. So that is your answer. That is 3 gates. And how did we implement that? If you remember it clearly. So first A will be going through an inverter. This is an inverter. So this will be your A bar. Then B will be going through an inverter. That will be your B bar. And then there will be another NAND gate. This is a NAND gate only. So this is how you will implement A plus B. So to implement OR gate you required 3 NAND gate, and to implement AND gate you required 2 AND gate. To implement AND gate using NAND gate you required 2 NAND gate. Okay. Let's go to the next one, that is AB plus C. So how will you implement AB plus C? Using basic gates. Using basic gates you need to implement. So how will I implement? This is my AB, A into B, then C will come. Sorry, plus C is there, no? AB plus C. AB plus C. Right? Now, what is the scene? You need NAND gate, right? You need NAND gate. So you need one inverter here. If I am introducing one inverter here, I have to introduce one more inverter here. Right? If I need to make this as NAND gate, then I have to introduce one inverter here. So if I am introducing one inverter, then another inverter I have to use here. Well and good. So what is this? This is one NAND gate. this is another NAND gate, and to make this one you will need one AND gate. So one NAND gate, sorry. So how many total NAND gate you required? 3 NAND gate. Can you make this structure on your own? Yes. Look, again and again I will not be making, but you will be uncomfortable now, right? So C will come as C bar, this is A, this is B, this is C. So C bar is coming here, and this is AB bar. So here what will come? Y is equals to AB plus C. So this is how you need to proceed in the problem. AB plus CD, which form is that? SOP. SOP form is that sum of product. So no need to worry. If sum of product form is there, no need to worry. Just implement that using basic gates. I I forgot to tell this thing, that sum of product, this is also sum of product. So if sum of product is there, then you don't need to worry. So AB plus CD. So again I will implement AB plus CD. So AB CD. So AB and CD multiplication I need to do, and then I will do the summation. Then I will do the summation. So what will be my answer? AB plus CD. But I need NAND gate. So if I need NAND gate, I have to introduce one bubble here. If I am introducing one bubble here, so another bubble will be introduced here. If I am introducing one bubble here, then another bubble will be introduced here. Say yes or no. Two bubbles I can introduce, right? Two bubbles if I introduce, it will be a simple wire only. It will be a buffer, and you can add a buffer anywhere. So this is one of the NAND gate. This is another NAND gate, and this is another NAND gate. So 3 NAND gates are there. So AB plus CD also I implemented using 3 gates. Try doing the next one on your own. AB plus BC. How many gates will be required? Pause the video and write down your answer. 3 gates, right? Which form is that? Sum of product. Do not change the form. Sum of product, don't change the form. This is also an AND gate, right? This is an AND gate only. Similar, ditto similar structure will be there. Ditto similar. AB, BC. A, B, and both will be same here. This will be your B, this is your C. So sorry. This bubble is not there. This bubble will not be there. What we are doing, we are just implementing AB plus BC. AB plus BC. Okay. So if I introduce a bubble here, another bubble I need to introduce, that will be introduced here. If I need to use bubble here, another bubble I will introduce, that will be introduced here. So AB plus BC. That will be our answer. So 1, 1 and 1. Answer will be 3. AB plus BC. Answer will be 3. Let's take more example. AB plus BC plus CD. Now my target will be to take something common. Here I can see something common will come. Here also I could have seen that something common can come. That if I take B as common, then A plus C would come. Can I do anything about it now? Can I change it? Anyhow can I change it? Any changes can I do? No. No changes I can do. This will be again AB plus BC only. I will try to take common here. So B common I am taking. B into A plus C plus CD. Can I do anything about it? Nothing. Nothing I can do. Right? So again, the same way I need to proceed. AB, A into B, then B into C, and then C into D. Making sure that I have only 2 input gate, not 3 input. I have only 2 input gate. So I will use 2 input gates only. So this is A, this is B, this is B, this is C. So here I am getting AB plus BC. So AB plus BC. this is C and this is D. So this is CD. So here AB plus BC plus CD you are getting, right? So if you introduce a bubble here, then another bubble will come here. If you introduce a bubble here, another bubble will come here. If you introduce a bubble here, then another bubble will come here. Then to make it an AND gate, to make it an NAND gate, you need to introduce one more bubble. So if you are introducing one more bubble, then one more bubble will come. So 1, 2, 3, 4, 5 and 6. So answer is 6. Are you getting this point? Bubble I introduce, then another 2 more bubble I need to introduce. One bubble I introduce here, then another bubble I need to introduce here, right? To make it NAND gate, I need to introduce one bubble here. To make it NAND gate, I need to introduce one bubble here. So to compensate this bubble, I need to use one more bubble. So to make this one, this is a NAND gate. NAND gate, NAND gate, NAND gate, NAND gate. This is an inverter. To make an inverter, how many NAND gates I require? 1. So 1, 2, 3, 4, 5, 6. Answer is 6. Or how you could have done it? That to implement this AB plus BC, how many you require? 3. So let's just say I have implemented this function AB plus BC and I am denoting it as X. So X plus CD I need to implement. So to implement X plus CD, how much you require? Another 3. So for this you required 3 and for this another you required 3. So answer would be 3 plus 3 is equals to 6. In the examination, this is how also I can answer. Let's try doing this problem. Can you take anything common here? Yes, I can take anything common. So B will come common, A plus C. Plus, can you take anything common from here? Yes, I can take D as common. So A plus C. So what will be happening? B plus D into A plus C. Now very interesting thing I will observe here. What is that? If I assume this as X, B plus D as X. So X into A plus C. So what I need to implement? AX plus CX, where X is B plus D. I need to implement AX plus CX. How much this will require? 3. And how much this will require? This is what? This is an OR gate only. This will also require 3. So 3 plus 3, total answer will be 6. Are you getting this point or not? First I will implement B plus D. First I will implement B plus D. How will I implement B plus D? This is how I will implement B plus D. First I will implement B plus D. This is B and this is D. So B plus D will be implemented. And then B plus D, AX plus CX. So this is the X which I was talking about. So this X I will take and my target is to implement AX and CX. So X will go here and A will come. And this X only will come and C will come. This is X, this is A, this is C. So AX plus CX you are having. Then you can simply use a OR gate, or if I use OR gate, then simply inverters I will have to add. So this will be my final answer. This answer would be AB plus BC plus CD plus DA. So that will be the design. Okay. So as a designer, you need to think in this manner that B plus D, I can replace this with the X. So to implement that particular X, look, if I had been doing in this manner, that AB plus BC, this will require me 3. CD plus DA, this will require me 3. So this can be replaced with X and this can be replaced with Y. So X plus will require me another 3. So my answer would be 9. Right? 3, 3 plus 3, 9. But you need to use minimum gates. So for there, I first thought that if there is something common coming, yes, something common is coming. Then I got to know that if I replace this with X, then AX plus CX, this will require me 3. And X will another require me 3. So 3 plus 3, 6 will be my answer. That's it. Okay. So in this manner I will be proceeding. More examples will come. Now examples will be tougher only. Okay, it will not go easy. A B C D, very easy. What is the form? This is product term only. This is a simple product term. There is no plus. It could be product of sum, but there is no plus. So it is a simple product term. This is AB. अरे यार A B C D. A B C D. Then multiplication of this A B C D. So if I use inverter here, then another inverter I will have to use. If I use inverter here, then another inverter I will have to use. So this will require 1. This will require another 1, 2. This will require another 1. This will require 1 more. And how much this will require? 2, right? This will require 2. So this will be, are you getting this point? This is AND gate. This is AND gate. How much AND gate requires? 2. AND gate requires 2 NAND gate. AND gate will require 2 NAND gates. So for this there will be 2. 2, 3, 4, 5, 6. Answer is 6. So in this manner we will be getting answer as 6. Okay, well and good. Let's try implementing this function. So first question, is this the form you want? You want sum of product, right? Is this sum of product or product of sum? This is product of sum. So this is not the form I want. So first thing is this. Second question, can you do anything about it? Can you change it anyhow? Then yes, I can change it. How will you change it? This is x bar plus y bar. Can I write it as xy bar into w plus z? Can I write in this manner? And I am assuming a as xy bar. My a is xy bar. So if I assume this a into w plus z, so that can be replaced with wa plus za. To implement this a, how much will be required? 1. And to implement this, how much will be required? 3. So what will be the answer? 1 plus 3 is equals to 4. So in 4 NAND gate only you will be able to implement it. How? Let's check that out. What I need to implement? What was my first question? I saw that this is not the form I require. Then I thought, can I do something about it? Yes, I can do. What I can do? X bar plus y bar, I can replace this as xy bar. So xy bar, I am assuming it to be a. So wa plus za. wa plus za I can implement in 3. That I know. ab plus cd I can implement in 3. ab plus bc also I can implement in 3. These will be in your brain, right? ab plus c, ab plus cd. That I can implement in 3 only. ab plus c, ab plus cd. These things. ab plus bc. I can implement all these in 3. So that will be in your mind. So here this is also is in my mind that I can implement this in 3, and this I can implement in 1 only. That's it. Now how I will do it? xy bar. So first I needed to implement xy bar. Then xy bar into w. xy bar into w. And xy bar into w, xy bar into z. That's it. This is the answer. xy bar came here. xy bar into w, xy bar into z, and then addition of this. So this will be my function. That would be x bar y bar into W plus Z. So this question came in GATE examination, and you need to think in this manner. More examples we will see what can come in future. Okay, this has already come. What can come in future? Let's see this example. Can you do anything about it? Yes, I can do. What you can do? You can take A bar common, B bar plus C bar. First question would be, this is the form you want. Yes, this is the form I want. This is the form that I want. Why you want this form? Because this is in the SOP form only. But something is coming common, so we will try something can we do, right? Something different can we do, because something is coming in common. Now what I can do? A bar, B bar plus C bar, B bar plus C bar. Can I replace this as BC bar? Right? So it feels like that I have reduced something. So I can easily make BC bar. I can easily make BC bar. Then I need A bar. Then I need A bar. And both combined can go into a simple AND gate. This can happen, right? This is my A, this is my B, this is my C. So here BC bar is coming into A bar, that would be A bar into BC. But you require NAND gate, so here you need to introduce a bubble. So if you are introducing a bubble from your side, then you need to introduce another bubble. So 1, 2, 3 and 4, that's the answer. If I had directly implemented, then what would be the issue? A bar B bar plus A bar C bar. So what I would have done, first I would have implemented A bar differently, B bar differently and C bar differently. It would have taken me 3, and then to make this function another 3. So answer would be 6. That would be wrong. So here intelligently I got to know that something is coming in common and I can reduce my number of gates. So that can happen. Okay. So in bar, if there is bar, then you need to think, you need to ponder there, you need to think something that something different can happen. Now this one is very interesting. What you can do? What you can do about this one? Very interesting. This is, let's just say this is x bar plus y bar. Can I write it as xy bar? Xy bar. So what I can do? AB into BC bar. What is AB into BC? That is ABC bar. So I just need to implement this ABC bar. That's it. AB bar plus BC bar is ABC bar. So when bar is coming, I will think about it. Okay. I will think something that what different can I do? Or this could have come in this manner as well. AB bar can be replaced as A bar plus B bar plus B bar plus C bar. Now you would be thinking, sir, there is no certain formula how you are doing it. There is nothing certain. Like study it from anywhere. No one will tell you that these many things as well, which I have taught, that see the SOP form, see if this is the form you require. If you don't require this form, take common. So there is no certain way. You have to think only here. Okay. You have to think. But I am from my side, I am dealing every possible example which can come in your examination. So this is the way you will be thinking. It could have come in this manner as well. AB, A bar plus B bar plus B bar plus C bar. So it can be replaced as A bar plus B bar plus C bar. And A bar plus B bar plus C bar can be replaced as ABC bar. So in NAND gate, there is multiplication. So I would want multiplication. I would not want plus. My target is to get multiplication. And in one term only I am getting multiplication. Then what's better than that? So AB into C. AB into C. And then bar I need to take. So this is what I want. AB into C. So this is already an AND gate. To make this as an AND gate, I need to use one inverter. So another inverter I will introduce. So 1, 2 and 3. Answer is 1 plus 1 plus 1. That is 3. So in this way you can proceed. More interesting example will come. This one. What you can do about it? You can write it as ABCD bar. AB into CD bar. Right? x bar plus y bar is equals to x into y bar. So a b c d bar. So a b c d and then multiplication and then bar. What you need this to be an a b c d. If I am introducing one inverter here, so another inverter I will introduce. If I am introducing one inverter here, another inverter I will introduce. This is already an AND gate. 1, 2, 3, 4 and 5. So answer is 5. What about this one, a bar bc? Can you do anything about it? No, I cannot do anything about it. So I have to implement it. A bar bc, nothing more I can do about it. This a bar bc will be a bar bc only. So a bar and bc. This is my a, this is bc. So a bar bc, answer will be a bar bc, but I need to use NAND gate. So this inverter will come here, another inverter will come here, this inverter will come here, and then another inverter will come here. 1, 2, 3, 4 and 5. So answer is 5. A bar bc, answer is 5. You cannot do anything about it. 1, 2, and this is the form you want. You want multiplication, right? You want multiplication. You don't want addition. You want multiplication. So if you want multiplication only, this is what you are getting. Can we do anything else? No, I don't think. So 5 you will be requiring minimum. Okay. So this is the answer, that you will be requiring 5. Let's see more interesting example. This is the interesting example, very interesting. And this can come in future. This hasn't come yet, but this can come in future. What you will be doing here? This is the form you want. First question, this is the form you want? No. I want sum of product, not product of sum. This is product of sum. I want sum of product. So what will I do? Let's do multiplication. If I do multiplication, what I will be getting? X bar y bar, x bar z, y w bar plus z y. It is becoming more complex, right? It is becoming more complex. And if I say, like, if I assume this as a, and then I will do w bar plus z, so this will take me 3. And how much a will take you? A is OR gate plus 1 inverter, so this will take you 4. So here your answer is coming 7. Are you getting this point? How did I write 4? X bar plus y. So x bar will take you 1 and x plus y will take you 3. And then if I assume this as a, so a into this will take you 3 plus 4, so 7 is the answer. That is also coming as pretty large. But this is not you want, this is also becoming very complex. So if nothing clicks, then take the double bar. What did I say? If nothing clicks, take double bar. That you need to take. Look, this is not the form I want. If I do this thing, this is becoming more complex. And then the another way I thought, it is taking me 7 possible cases. So if nothing is clicking, I will take double bar. If we take double bar, let's see what happens. Double bar means, like, if I take a double bar, then it will be a only. So that's why I am taking double bar. So this will not change this Boolean expression. If this Boolean expression is a only, then if I am taking double bar, then it is not changing. It is becoming a only. So I will take double bar now. So x bar plus y into w bar plus z, double bar of that. So what this will become? X y bar into, okay, you are not habitual of it. So let's just say if this is a and this is b, so this is ab bar, right? So ab bar can be replaced as a bar plus b bar. So this is what I am going to do now. So x bar plus y whole bar plus w bar plus z whole bar, right? This is how it can be replaced. Now what is this? This is also x bar plus y bar. Then how it will be replaced? X into y bar. This we have already seen, right? And another whole bar is also there, so that whole bar we cannot forget. Another whole bar is also there. First we solved this bar, then another whole bar is also there, so that whole bar also I implemented. Okay, so now this is a plus b whole bar, so that would be a into b bar plus w into z bar, and then another whole bar is there. अरे यार भाई, another whole bar is there. Now if I solve this bar, what I will get? X bar plus y, then w bar plus z. I will get the same expression. So why would I solve this bar? So this is the expression I am getting, right? X into y bar plus w into z bar to the bar. And this is what I want. What did I want? AB plus CD. Just bar is there. This is my A, this is my B, plus this is my C, and this is my D. This is what I wanted. And on the upper side there is a bar. So tell me how much this will take. Forget about the bar, how much this will take. AB plus CD, that will take 3. How much y bar will take? 1. How much z bar will take? 1. How much the whole bar will take? Another 1. Answer will be 6, not 7. The previous one were taking you 7, but here intelligently I thought that this is not the form I want. If nothing is clicking, I will take double bar. If I am taking double bar, then this is the form I am getting, and this is the form I am getting. So here I got to know AB plus CD is taking me 3, y bar is taking me another 1, z bar is taking me another 1, and then whole bar is taking me another 1. Let's make this structure. Very easy it will be. Y bar into x. Y bar into x, w into z bar, then addition and then whole bar. If you need to make this as AND gate, then another bubble will you will introduce here, and this as an AND gate, then another bubble you will introduce here. 1, 2, 3, 4, 5, and 6. So answer is 6. Okay, so that is the answer. So very important thing it was. This was a very good example as well. So this example I am expecting, if they are going to ask any question from this particular topic, then they will give this scenario this time, because they have already given this one. Why did they give this one? Because this is equivalent to XOR gate. This is equivalent to XOR gate. Okay, we will see it in the next lecture or in this lecture only, because time is passing. So this is equivalent to XOR gate, and this is equivalent to XNOR gate. This is equivalent to XNOR gate. So XNOR gate can be implemented using 5 NAND gate only, but this is being implemented using 6 NAND gate. So this is equivalent to XNOR gate. That's why I'm expecting this example can come. Okay, so let's solve the same kind of problems using NOR gate now. So in NOR gate, what is my target? If NOR gate is coming, I will be going towards POS form. So tell me one thing. POS form, then I will implement it using basic gates, and then I will convert basic gates into not NAND gate. I will convert basic gate into NOR gates. So to implement NOT gate, how many NOR gates are required? I just copied the page, that's why these are there. How many number of NOR gates are required? 1. For OR gate 2 are required, for AND gate 3 are required. You can check it out. Here also I will write it down. Okay, I have already written it down. So 2, 3, we will check it out now. So how will I make A bar? How will I make A bar? Only 1 is required. This is how I will make A bar. This is a plus a, y will be equals to a bar. How will I make a plus b? A plus b. A plus b I need to make. So simple, to make a plus b, wait a minute. To make a plus b, this is my a plus b. So this is my a plus b, but another inverter I have to use to make it a NOR gate. Then another inverter I will have to use, because if I am introducing an inverter, I will have to use another inverter to compensate it. So 1 plus 1, answer is 2. 2 is required. You can make it on your own, right? How will you make it? You can skip this part if you have already made it. This is how you can make it on your own. Y is equals to a plus b. Now y is equals to ab. Y is equals to a into b. So what I will do? This is a, this is b. Y is equals to ab. But what you need? You need NOR gate. So for NOR gate, here you need to introduce a bubble and another bubble you need to introduce, because NOR gate is equals to, what is your NOR gate? This bubble will come upward, this bubble will come in front, and this gate will become NOR gate. Okay, so this is a NOR gate. So if I am introducing two bubble from my side, I need to introduce two more bubble. So 1, 2 and 3. So answer will be 1 plus 1 plus 1. Answer will be 3. And you can make it on your own as well. How will you make it? This is how you are going to make it. This is A, this is B. This is A bar, this is B bar. A bar plus B bar ka bar, that would be AB. Okay, so this is how you will be making it. Let's check out other. AB plus C, is this the form you want? Yes, this is sum, this is product of sum. This is sum only, no? A plus B into C plus 0. This is product of sum only. So this is the form I want. Yes, this is the form I want. So AB, AB, A plus, sorry, A plus B I can make like this, and then into C. So how will I make it? This bubble is there. Sorry, I need to introduce one bubble. Why do I need to introduce one bubble? To make it NOR gate. Then another bubble I need to introduce. Then this bubble also I need to introduce, so that it becomes a NOR gate. So another bubble I will have to introduce. One bubble I introduce to make it NOR gate, so another bubble I will have to introduce. Then another bubble I will have to introduce to make it NOR gate, and then another bubble I will have to introduce, because in the compensation of this NOR gate, right? So one NOR gate, another NOR gate, and another NOR gate. So 3 NOR gates are required. Do the same for AB plus B, A plus B into C plus D. So A plus B into C plus D. Right? This would be A plus B into, sorry, into C plus D. So this will be like that. So 1, if I am introducing 1 here, so I will have to introduce one another here. So if I am introducing 1 here, another one I have to introduce here. This is A, B, C, D. 1, 2 and 3. So again answer will be 3. So this format we have seen. AB will take me 1, sorry, AB will take me 3. A plus B into C will take me 3. A plus B into C plus D will take me 3. So this is the form that we have already seen now. Okay. Now let's move to the next one. A plus B into B plus C. It will also take me 3 only. You can implement it on your own. A plus B into B plus C. A plus B into B plus C. So I will introduce, here also introduced, here also introduced, here also introduced. Okay. So what is the answer? 3. What about this one? Let's check. This one will take 6 as far as I think. This will take 6. A plus B, because this is the form I want. This is the form I want, so I will not change it. And nothing common and nothing like that, something is coming. So this is the form I want, so directly I will keep this form only. A plus B into B plus C. And then C plus D there you go. A, B, B, C and C, D. Bubble here, then another bubble here, bubble here, then another bubble here, bubble here, then another bubble here. If you are introducing a bubble here, then you need to introduce bubble here as well, right? So this is 1 gate, 2 gate, 3 gate, 4 gate, 5 gate and 6 gate. So answer is 6 gate. Okay, 6 is required. How you will do it? AB plus BC will take you 3. So I can assume this as X. So X into C plus D. A plus B into C. Then another 3 will take. So this will take 3 and this will also take 3. So answer is 3 plus 3, 6. So this is how also you could have solved it. Right? So this will take me 6. A plus B plus C into D plus C. This is the form you want? Yes, this is the form I want. So I have to solve it. A plus B and then plus C. This will come and then from here D plus E will come. D plus E will come and then both will be multiplied. So A, B, C, D, E. Okay. So one bubble I have to introduce here. So another bubble I have to introduce. One bubble I have to introduce here and another bubble I will have to introduce here. This is a NAND gate. This is an AND gate, sorry. So one bubble I have to introduce here and another bubble I will have to introduce here. 1, 2, 3, 4 and 5. So answer is 5. Okay, 1, 2, 3, 4, 5. So that is the answer. So 5 is the correct answer. Now let's take this example. A plus B plus C plus D. A plus B plus C plus D. Can you do anything about it? Because this is the form I want. Sum I want. What I want? Product of sum. So in the product there is nothing else. This is the sum product. This is the sum term only. Only the sum. Sum is there. Are you getting this point? If I was implementing using NAND gate, then ABCD. This is the form I wanted. I did not do anything with that because this is the product term. So I want product term there. Here I want sum term. So I want sum term that I am having. So again, A plus B, B plus C, and then both will be added. Right? So this will require 2. This will require 2 because this is a NOR gate. So to implement NOR gate, how much you required? 2, right? Here you so to implement NOR gate, Sorry, to implement OR gate you required 2. To implement OR gate you required 2. So here also you will require 2. 2 and 2. Answer will be 6. Or you could have gone with the concept of inverter as well. If I use inverter here, then another inverter will come. So 1 plus 1, 2. Inverter here, another inverter. Again 2. Then inverter here, another inverter here. So 3. Right? So 1 plus 1 plus 1 plus 1 plus 1 plus 1. So answer would have been 6 only. Are you getting my point how I am doing it? Look. This inverter I would have introduced, so another inverter I will have to introduce. This inverter I would have introduced, another inverter I would have to introduce. This inverter I would have introduced, so another inverter I will have to introduce. So 6 would be my correct answer. Now see this one. This is also very, very interesting. First question, this is the form I want? No. Can you do anything about it? Yes. X bar, Y bar plus WZ. This question can also come in the examination. That's why I have put a star mark there. This kind of question can also come. So this is not the form I want. So X plus Y bar plus WZ. Is this the way I can write it? Say yes or no. If I assume X plus Y bar as A, so A plus WZ. Now in the Boolean algebra, I will teach you one thing. What is that? Let's see it here. A plus B into A plus C. If you solve it, what you will get? A into A is A only. A into C is AC. B into A is AB. B into C is BC. From here I can take A as common. So 1 plus C plus B. I need to put the charge on. Wait a second. So A into 1 plus C plus B plus BC. So what you are getting? A plus BC. Right? What you are getting? A plus BC. So A plus BC can be replaced with A plus B into A plus C. This theorem is known as consensus theorem. What is the name? I don't know. Consensus theorem. I guess this is the name only. Because the name is not important. Consensus theorem, this theorem is known as. So A plus BC can be replaced with A plus B into A plus C. Because you solved it, you got A plus BC. Anything in addition to 1 is 1 only. So A plus BC I am getting. So A plus WZ can be replaced with A plus W into A plus Z. Say yes or no. How much you will require, and what is our A? This is the different thing. This is a complete different thing. Complete different thing. So better I should keep in a box. So this is a complete different thing which we will be learning in Boolean algebra. But here only I told you A plus B into A plus C. So A plus AC plus AB plus BC. So A if I take common, so I am getting A plus BC. So reverse way if I am writing A plus BC is equals to A plus B into A plus C. This multiplied with this into this this in addition to this A plus B into A plus C. So A plus W into A plus Z. What is my A here? Where my A is X plus Y bar. Where my A is X plus Y bar. A is X plus Y bar. So A plus W into A plus Z. So A plus W into A plus Z. How much it will require? 3. And X plus Y bar, how much it will require? 1. What would be your answer? 4. That's it. What is this? This is looking like a XNOR gate, right? This is looking like a XNOR gate. So to implement XNOR gate using NOR gate, you will require 4 only. So let's do it. How we will do it? X plus Y bar. What we need to implement? First X plus Y bar will come. Now from X plus Y bar, I have assumed it to be A. So A plus W into A plus Z. How I can implement? Very easily I can implement. A plus W. So one NOR gate. A plus W. And then another NOR gate. A plus Z. And then end of these two. Right? So if I make bubble here, another bubble I will make here, another bubble I will make here, another bubble I will make here, and this bubble can be replaced with simple XOR gate only, XNOR gate, sorry, not sorry, XNOR, no, sorry, NOR gate only. So 1, 2, 3 and 4, answer is 4, answer is 4. Okay, so this is the way we can go. So this was a very good example. Now another good example we will see, this example. First question, can you do anything about it? Sorry, is this the form you want? No. Can you do anything about it? No. If nothing clicks, then take that double bar. And how this is looking? This is looking like a XOR gate. A bar B plus A B bar. So this is looking like a XOR gate. So take double bar. Take double bar. If nothing clicks, I will take double bar. Okay. What I could have thought? I could have thought that if I assume this as A, then what I can do? A plus W bar Z. So A plus W bar into A plus Z. So this will require me 3. This will require me 3. This will require me 1. This will require me 1. And X bar Y, this will require me 4. So my answer would have been 8. W bar will require me 1. This complete will require me 3. And X bar into Y, because XY will require me 3. XY will require me 3. And X bar will require me 1. So 4 plus 4, answer would have been 8. But in the lesser one, I can make it. In less, I can make it. And how I will make it? Let's check that out. Nothing is clicking. I took the double bar. So can you solve this bar? A plus B whole bar it is. So I can write A bar dot B bar and then whole bar. So X plus Y bar into W plus Z bar and then whole bar, right? So this is the form I want, POS form, and then there is a bar. So X plus Y bar, X plus Y bar. W plus Z bar. And then there is a AND gate. And then there is a bubble. Okay. So how I can replace this? This bubble if I am making, another bubble I will have to make. This bubble I am making, another bubble I will have to make. This I implemented using standard gates. X, Y bar, X, Y, then Y bar will come. W here, then Z bar will come. And then addition of all these, let's forget these bubbles. Let's forget these bubbles. So X plus Y bar into W plus Z bar. And then whole bubble is also there. So this I made. Now, if I need to make it, NOR, then I will use a bar. I will use a bar here. So if I use a bubble here, I will have to introduce another bubble here. I will have to introduce another bubble here. So now what is this? This is an XOR gate. Sorry, not XOR gate. This is a NOR gate. That itself is a NOR gate. So 1, then another one here, then one here, then another one here, then one here, and then another one here. So answer is 6. Are you getting this point? This much of structure, only this much of structure. Forget about the bubble. Only this much of structure is one NOR. And to make this bubble, you will need another NOR. Right? You will need another NOR. Better I should have made this bubble somewhere here. Somewhere here. Somewhere like this. To make this structure, I will need another one. 1, 2, 3, 4, 5, 6. So answer is 6. So this way we will be proceeding in these kind of problems. When we study K-maps, we will come back to these kind of problems. Look, these many examples, 15 plus 11, 26 examples, no one will teach you. Okay, I'm not saying that I am the best, nothing like that, but so many examples I have taught here. And if you are comfortable with these many examples, if you have built a good intuition, then if the question is coming, you will be able to solve it. And when we study K-maps, I will tell you another method to solve these kind of problems. Okay, there will be another method when we study K-maps. So two or three examples I will take there as well to implement any Boolean function using minimum number of gates. So that's it. This is the complete concept. Now we will implement XNOR gate and XOR gate using, now we will implement XNOR and XOR gate using NAND gate and NOR gate. But before that, one important thing is there. So you know this thing, right? A XOR B is A bar B plus AB bar. This can be replaced in another way. How it can be replaced? A bar plus B bar into A plus B. If you solve it, what you will get? A bar into A into A, plus A bar into B, plus A bar into B, plus B bar into A, plus B bar into A, plus B bar into B, B bar into B. A bar into A is 0, plus A bar B, plus B bar A, and B bar into B bar is 0. So A bar B plus A B bar. This is the answer. So these two are same only. How will you remember it? So you will remember it that this is SOP form, sum of product form. If I need to write in product of sum form, then I will remember XNOR. So what is the answer of XNOR? This is the answer of XNOR. A bar B bar plus AB. So A bar plus B dot A plus B. This is how I will remember it. Say yes or no. And this is also which form? Sum of product form only. If I need to write in product of sum form, then how will I write? I will remember XOR. So A bar plus B into A plus B bar. That's it. Okay. So is this the way can I remember these two formulas? Say yes or no, right? So let's solve this problem. You need to implement XOR gate using NAND gate. I am implementing XOR gate using NAND gate. So A XOR B is there. A bar B plus A B bar. First question, is this the form you want? Yes, I want this form. This is sum of product form. But bar is there. Can you do anything? Yes, I can do anything. What I can do? I remember another form of it. What is that? That form is A bar plus B bar into A plus B. So I will think about this form as well. If I think about only this form, then what will be my answer? A bar B plus A B bar. How much this will require? 3. How much A bar will require? 1. How much B bar will require? 1. My answer would be 5. Okay, let's hold on to this. My answer here, if I directly go by this method, my answer will be 5. That I need 5 NAND gate to implement XOR gate. But if I go by this method, A bar plus B bar into A plus B. Can I write A bar B bar as A bar plus B bar as AB bar into A plus B? Can I write in this manner? Say yes or no. And if my AB bar is X, if I am taking AB bar as X, then can I write it in this manner? That my X is equals to AB bar. So what it would be? AX plus BX. So this will require me 3 and this will require me 1. So what would be my answer? 3 plus 1 is equals to 4. So in 4 only I am able to implement. Did we see the same kind of example here? Say yes or no. The same kind of example here. XY whole bar into W plus Z. So with respect to that example, gate framed this question. So that's why I am thinking with respect to some another example, they will frame this problem. What is this example? This example is based on XNOR gate. Or they can frame these problems. Problem 10, problem 9. So these problems may come up any day in your examination. This is what I am thinking. Okay, if some question is coming, then these two problems will come. And nowhere in the gate industry you will find these two problems. Okay, this I framed myself only. One problem you will find that is coming from the gate examination only, but those 3 problems that you will not find, because that I framed here only and then I solved that. Okay, and I'm pretty sure my answer is correct there. So this is the way we can implement, right? Okay, so answer is 4. So how we will implement? First we will implement AB bar and then this we will implement. So this we have already seen. So this is A, this is B. AB bar will come here and A will come here and AB bar will go there and B will come here. So this is our XA plus BX. This is our XA plus BX. This is AX plus BX. And this is X. Now tell me one thing. If this gate has delay TD and this gate has delay TD and this also has delay TD. So if I apply A and B here, let's just say I apply A and B at t equals to 0. So after how much time I will get my output? TD plus TD plus TD, because TD and after TD time here there will be some input, and at t equals to 0 only here there will be some input. So this will wait. This input will wait for this, because this input will come after TD time. So after TD time this input will come. So after TD plus TD, after 2 TD you will have something here, and after TD plus TD, after 2 TD you will have something here, and 2 TD plus TD, that will be 3 TD. So after 3 TD time you will get your output. So there are 3 levels, right? Level 1, level 2, level 3. There are total 3 levels. This also I can remove. Level 1, level 2, level 3. So this is known as 3-level assembly. Okay, 3-level assembly. So if I introduce something at t equals to 0, then I am getting that output after 3 TD delay. So my output will be I am getting after 3 TD delay. Okay, so propagation delay of one NAND gate is TD, then total propagation delay would be 3 TPD. Well and good. Now we will make XNOR gate. So there could be 2 ways of making XNOR gate. This is the first one. In first one, what we are doing? We are taking A XOR B, and then simply we are taking the bar. So here we are getting A XOR B, right? This is our A XOR B. This much structure. The same structure I have copied here. A XOR B. And then A XOR B, and then another. What is this? This is an inverter only, right? This is an inverter. This thing is an inverter only. So here what you will get? A XOR B bar. Or you can say A dot B. How many levels are there? Level 1, level 2, level 3, and level 4. So this is what? This is 4-level assembly. This inverter I will remove. This is 4-level assembly. So if propagation delay of each NAND gate is TPD, then what will be the total propagation delay? That would be 4 TPD. Okay, if propagation delay of each NAND gate is TPD, then what will be the total propagation delay? That will be 4 TPD. So now my question is this the best way of implementing this function? So your answer is no. This is not the best way. There could be another way as well. Look, how many NOR gates you required? Sorry, how many NAND gates you required? How many NAND gates you required? 5 NAND gates. 5 NAND gates. Here, how many NAND gates you required? 4 NAND gates. 4 NAND gate. 4 NAND gates. Right? And here you required 5 NAND gates. So the number of gates are 5, that is good. But the propagation delay is 4 TPD. Can I implement it in another way? What that way could be? What is your Y? Y is A XOR B. And that can be written as A bar B bar plus AB. So A bar B bar plus AB. So A bar B bar plus AB, let's just say it is XY plus YZ. XY plus WZ. XY plus WZ. How much this will take? 3. And A bar will take 1. And this will also take 1. B bar will also take 1. Basically, this will take 1. This will take 1. And this combined will take 3. So 3 plus 1 plus 1. So answer is 5. So using 5 gates only I can implement XNOR gate, but in a different manner. So I will check there how much delay I am getting. Using 5 gates only I can implement my XNOR gate. Using 5 NAND gates only. But that would be a different structure. This is a different structure. How did we get this structure? First we implemented XOR gate, then we just simply inverted it. That's it. But there could be another way, a bar b bar plus ab, right? There could be another way. So what that way would be? First we will take a bar, then we will take b bar. So a bar b bar, and then we will do this structure. We will do this structure. Basically, let's make it here. A bar, b bar, and then multiplication, and then ab, a into b, and then what is there? Then there is addition, right? So here if I implement one bubble, another bubble I have to implement, one bubble here, another bubble here, 1, 2, 3, 4 and 5. This is A, B, C, D. So answer is 5. So this is the answer. So in the same way I have implemented this, right? Now tell me, if this has TPD delay and this has TPD delay, all are having TPD delay, then how much will be total delay? 3 TPD, right? Because this is level 3 assembly. If I apply at t equals to 0, if I apply input here, then after TPD time you will get here, after TPD time you will get here. So TPD time after A bar and B bar will come. So after more TPD time, at 2 TPD time you will get something here, and this you will get after TPD time, but this has to wait for this one because this will come after 2 TPD. This is there after 2 TPD, this is there after TPD. So 2 TPD plus TPD will be 3 TPD. So this is level 3 assembly, level 1, level 2, level 3. So this is 3 level assembly. So you made your XNOR gate using NAND gate only, but here your delay was 3 TPD and here your delay was 4 TPD. So which is a better method? This is the better method, no? Here I am getting less delay. But in my design, let's just say I am designing something, and in my design if I need both XNOR gate and XOR gate, if I need both gates, then I will use this structure. Because from here I can get the function of XNOR gate, from here I can get the function of XOR gate, and from here I can get the function of XNOR gate. But if I am designing only XNOR gate, if I need only XNOR gate, then I will use this function. Because in between here you cannot get XNOR gate, right? In between here you cannot get XOR gate, sorry. In this structure, in between only you can get XOR gate. But here at this node, will you get XOR gate? No. You will separately have to make it. So in my design, if my requirement is I need XOR gate and XNOR gate both, then I will go with this structure. Otherwise, if I only need XNOR gate, then I will go with this structure because here there is minimum delay. And also cost is same only. Here also you are requiring 5 NAND gate. Here also you require 5 NAND gate. So cost is same. Here 5 NAND gate is there. This is also taking 5 NAND gate. So cost is same. So based on the requirement you need to see. If you only require NOR gate, then you will go with this particular structure. Okay. Not NOR, XNOR. Yeah. So that's it. Now we will make implementing XNOR gate and XOR gate using NOR gate. So first we will implement XNOR gate. First we are implementing XNOR gate using NOR gate. So A bar, B bar plus AB. Is this the form you want? My question is this the form you want? No, I don't want this form. Because I want sum of product, right? What I want? Product of sum. I am implementing using NOR gate. So I want product of sum. So what I can do about it? A bar, B bar plus AB. What I can do? I can replace this as AB bar plus AB, right? And if I assume AB bar as X, AB bar as X. Sorry, this is not AB bar, this is A plus B bar. So if I assume A plus B bar as X, so it would be X plus A into X plus B. How did I write X plus A into X plus B? By consensus theorem. Here I taught this theorem, no? Here only. X plus AB. So X plus A into X plus B. Right? Here I am writing X plus AB, or I can write P plus QR. P plus QR is equals to P plus Q into P plus R. So this is how I wrote it. Now X plus A into X plus B, that can be made in 3. And this can be made in 1. So what is the total answer? 3 plus 1. That would be 4. So first I will make A plus B bar and then I will make this structure. So A plus B bar, here this is my A, this is my B. If this is having TPD delay, so here I am getting A plus B bar, right? This is my A, this is my B, and then this is the structure which will eventually it will give me A XOR B, okay, or you can say A XOR B bar. So all are having TPD delay, then my answer would be 3 TPD, right? So total delay will be 3 TPD. Now what I will make? Now I will make XOR gate. Sorry, XOR gate. XOR gate I can make. This is the way 1. What is the way? Simply XOR gate. So simply I can make XOR I have already made. So just take the bar. So this is XOR. A XOR B. So I will just take the bar here. So this I will get. So if this is having TPD delay, then total delay would be 4 TPD. Right? Total delay would be 4 TPD. Now the next one. Now I need to make this. Now there could be 2 ways. In the same manner, there could be 2 ways. Here, if each delay is TPD, then total delay will be 4 TPD. And what is this? This is level 4 assembly. Level 1, level 2, level 3, and level 4. So this will be level 4 assembly. Right? Now what could be the way to? First I will see this, and my question will be, is this the way you want? No, this is not the way I want. Right? Because I want product of sum form, product of sum. So for product of sum, I am having this A bar plus B bar into A plus B. So combined this will take 3, right? Combined this will take 3. This will take 1 and this will take 1. So total it will take 3 plus 1 plus 1. So total 5 will be required. So A bar plus B bar into A plus B. So 5 will be required. So A bar, this is your A bar, B bar. So A bar plus B bar, A plus B, and then multiplication. So if you introduce one NOR gate here, sorry, one NOT gate here, then you have to introduce one NOT gate here as well and one NOT gate here as well. So this will take 1, 2, 3, 4 and 5. So answer is 5. So this will be the structure A bar, B bar. So this is level 3 assembly. Level 3 assembly. Okay. So if this is taking TPD delay, then how much delay this will take? Because this is 1 level, 2 level, 3 level. So 3 TPD delay it will take. So based on the requirement, you will see what you need to implement. If you need both the functions, then you will take this this particular structure. But if you need only XOR function, then you will take this particular structure. So that would be your answer. Okay. So TD delay here, 3 TD delay. Sorry, 3 TD delay in this one and 4 TD delay in this one. So based on the requirement, you need to check. Okay. Now this is the question. 2 input XOR gate and XNOR gate are implemented using minimum number of 2 input NOR gate and NAND gate respectively. Find the minimum propagation delay. So 2 input XOR gate is implemented from 2 input NOR gate. 2 input XOR gate is implemented from 2 input NOR gate and XNOR is implemented from NAND gate. So how many it will be required? How many will be required? 5 gates. Here also you will require 5 gates. What will be the minimum propagation delay? Minimum propagation delay, for that you need level 3 assembly. You need level 3 assembly. So answer will be 3 TPD, not 4 TPD, right? Answer will be 3 TPD. 4 TPD would be wrong. This answer would be wrong. Why this would be wrong? Because this is the minimum delay. If we need minimum delay, then I will go with this structure, not with this structure. When I will go with this structure, if I need both the operation, XNOR and XOR. But if I need only one operation, then I will go with this structure. Okay. Now let's implement NOR gate and NAND gate using like NOR gate using NAND gate and NAND gate using NOR gate. Very simple, right? What I need to implement? A plus B bar. This I need to implement. A plus B bar. NOR gate using NAND gate. Right? if I need to implement, let's do it again. First I will take a plus b and then I will take bar. So if I introduce a bubble here, then another bubble I will have to introduce here. If I introduce bubble here, then another bubble I will have to introduce here. So this is one of the NAND gate, 1, 2, 3 and 4. So what is your answer? Answer is 4. So you will require 4. How will you implement it? Very easily you can implement. This is your A bar, this is your B bar, and then it will go here. Sorry, this is not bar, this is A and B only. This will go here and then another bar will come. So that's it. This is the way you can implement. And what about this one? What do you need? A into B and then another bar. So you have to introduce a inverter here, you have to introduce an inverter here. So another inverter you have to introduce, another inverter you have to introduce here. So 1, 2, 3, 4. So answer will be 4. How will you introduce? How will you make it? These should be simple by now. Okay, you should be comfortable with these kind of problems at least. This is your A, this will be your P. I am simply making an inverter only. Then another NOT gate will come. That's it. Okay, so y is equals to AB bar. Now let's make a table and let's write down the minimum number of gates required. And how will you remember it? That also I will tell. So to implement NOT gate, NAND and NOR both are required, only one only. Now NAND is near to AND, right? NAND AND. So it will require 2. And NOR is near to OR. So this will require 2. NAND is far to OR. This will require 3 and this will require 3. Can you remember it this way? NAND is near to AND. So it will require 2. NOR is near to OR. It will require 2. Rest of them will require 3. NAND, from NAND to NOR, very far away. NAND to OR is requiring 3. So this will require 1 more, 4. NOR to NOR. NOR to NOR, 1 only. NOR to NOR, 1 only, because NOR is itself NOR, right? NAND to NAND, 1 only. Now NOR to AND is 3. So this will require 4. Now, how you will remember this XOR and XNOR? So what you will remember? NOR to XNOR you will remember, because only you need to introduce one word, that is X. So NOR to XNOR will take 4. So from NOR to XOR will take 5. And here it will be opposite. This will take 4, this will take 5. Did you understand what did I tell you? You will remember only one thing, that if let's just say in the examination question is coming, how many NAND gates are required to implement XNOR gate? This question is coming. Now you are blank. So what you will do? Okay, I know from NOR to XNOR only one extra word is there. So from NOR to XNOR it requires 4. So from NAND to XNOR it would require 5. That's it. Opposite are there, no? Opposite are there. So from NOR to XNOR you will remember. This will require 4. So that will require 5. From NOR to XNOR it requires 4. So from NOR to XOR it will require 5. And from NAND to XOR it will require 4. Opposite are there. 4, 5 are opposite. So this is the table which you need to remember. Okay. These tables, this is the table which you need to remember. Well and good. So in that manner, this part is completed. Now next what we will see, we will see something. We will see about Boolean algebra. So next we will see Boolean algebra, or yeah, now we need to see concept of delay. That is very important. So next we will see concept of delay. So we will draw the timing diagram based on concept of delay. Also we will see Venn diagrams as well. So logic gates are not completed, but this was a very important lecture and I hope you must have understood a lot of new things here. So this lecture is completed. Next we will see concept of delay and logic gate and Venn diagrams. Okay, so let's meet you in the next lecture.
Hi everyone, so in this video we are going to study the concept of delay only, but before that we will see a very interesting concept of universal gate. So what is a universal gate? I told you. So that universal particular gate is enough to implement any Boolean expression. So I told you NAND gate is a universal gate. Then from the NAND gate we implemented NOT gate, AND gate, OR gate, NOR gate, NAND gate itself, then XOR gate, XNOR gate, and any kind of Boolean expression, right? So NAND gate was alone enough to implement any Boolean function. Similarly, NOR gate was also alone enough to implement any Boolean expression. So this is what we mean by universal gate. Now the question is, are there only two universal gate? So fundamentally your answer should be, generally there are only two universal gates. So what you will say if this question is asked to you, are there only two universal gates? So you will say generally there are only two universal gate, which are NAND gate and NOR gate. But if any logic circuit can give you AND or one of these and or one of these and or and note. Look, what you need? AND plus note. So note should be written in capital. AND plus note or plus note. So if any logic circuit can give you AND or and note both together, then the circuit can be used as universal gate with the condition that 1 and 0 are present. Basically, high voltage and low voltage should be present. You might not be able to understand this. Let's understand with an example. So here what I have written, NAND gate alone is enough to implement any Boolean function. NOR gate is also alone enough to implement any Boolean function. AND plus note, that is also alone enough to implement any Boolean expression. OR plus note, if two gates are given, then also they are enough to implement any Boolean expression. AND plus OR plus note, they are also enough to implement any Boolean expression. Now this gate is given, that is A bar B. This gate is given to me, A bar B. Now my question is whether it is a universal gate or not. Universal gate or not. I have a gate which can implement this function A bar B. That means what is the gate? This is the gate. This is the gate, right? Can it implement any Boolean expression? That we need to know. Okay. Now what will be my target? If from this gate, if I can get OR gate, AND gate and NOT gate, if I can get these three, that means I can implement any Boolean expression. Say yes or no. My target will be to get these three. That's it. Or what could be my target? That I can make NAND gate from here or NOR gate from here. If I am able to make NAND gate or NOR gate from here, then my task is done. So here I will try to make NAND gate from here, or all the gates I will try to make. So first let's try to make NOT gate. From here let's first try to make NOT gate. How will I make NOT gate? What I will do, I will pick the same. This is your A, and here I will keep 1. So what will be the output? Y. That would be, if this is A, this will be A bar. So A bar into 1. So Y will be A bar. That's it. This is the output. What is this? This is a NOT gate. Now let's try next. What I should try? I should try making AND gate. Let's try making AND gate. So what AND gate will do? AND gate will do AB, right? So first I will use this inverter. I will put A here and get 1 here. So from here what I will get? A bar into 1, that would be A bar. Then here I will go A bar, and here I will put B. So what I am getting? Here I will get A into B, y is equals to A into B. So what I have got? AND gate I have got. NOT gate I have got. What else I should try? OR gate. So for OR gate what you need? OR gate. For OR gate you need A plus B. Or I can say I can take double bar here. What if I take double bar? I can say I need A bar dot B bar. This is what I need. I can say that, right? So what I will do? First I will take the bar. Of B. So here I am getting, this is B bar into 1 would be B bar. So here I am getting B bar. And then here I will take A. So A bar into B bar. What I will get here? A bar into B bar. And then another inverter I will have. Here I will have another inverter. So what I am getting? So this is my output. A bar, B bar, and here I will put 1. So my output will be A bar, B bar, and that would be A plus B. So I have got OR gate, I have got AND gate, I have got NOT gate. If I need to make NAND, I can easily make NAND. How will I make NAND? I will pick this one and simply I will add an inverter. That's it. This y is equals to AB is already there, and then after that I just need to add an inverter. And how will I add an inverter? This is a simple inverter is there. So if I am able to make a NAND gate, then from NAND gate I can implement anything. Any single thing I can implement from the NAND gate. So that's it. This I am having. This I will put as 1. This will be my AB bar. Well and good. Very easy. So if I am able to implement NAND gate, then it can implement anything. Can implement any Boolean expression. Implement any Boolean expression. So that's it. In that manner you will be able to proceed. Okay, from NOR gate also you can make. How will you make NOR gate? OR gate is already there. Just add an inverter. OR gate is already there. A plus B is already there. Just add one more inverter there. That's it. That is your target. Or here also you are getting, no? This is your NOR gate. Yeah, this is the NOR gate. This much portion is NOR gate. This is your NOR gate. NOR. Because it is B bar into A bar. B bar into A bar will be A plus B whole bar. This is your NOR gate. So they can implement any Boolean expression. So my target was only to implement one of the universal gate. If you are able to implement one of the universal gate, then you can implement any Boolean expression. So what did I tell you? AND gate plus NOT gate If both of the operation you can get, then they are more than enough to implement any Boolean expression. Or if you are having OR gate plus NOT gate, then they are more than enough to implement any Boolean expression. Same goes with this one, A bar plus B, A bar plus B, A bar plus B. So this is up to you. This is up to you. You can implement anything. What I will do, I will implement only NOR function. NOR should I implement? Okay, I can implement NOR. So what I will do, first I will make an inverter. Yeah. Okay. So my target is to implement NOR now. So first I will make an inverter. This is the logic gate I am having. This is A, this is B. Instead of B, I will put 0. So A bar plus 0 will be A bar only. So this I am getting as A bar. So A bar goes here. And then inverter comes. So it will be A. And this will be B. So from here I am getting A plus B. So this I will get as A plus B. Here it would be A plus B bar. A plus B bar. And then I will put 0 here. A plus B. I need A plus B bar. So A plus B bar here it will be. And then there to go. So here I am getting A plus B bar. Basically this was an inverter. This is the response of an inverter. So in one logic circuit only you can see 3 logic circuits there. And this, what is this? This is A plus B. This is A plus B. So this is a OR gate. And finally you can see NOR gate. So if you are having NOR gate, that means you can implement any Boolean expression. So this is also a universal gate. So these are the examples. So if you think that you need 3 gates, then you are thinking wrong. You need only 2 gates. Because in your chip, in your IC, there will be plus 5 available. There will be ground available. So you will always have 0 and 1 with you. If you are having 0 and 1 with you, you can implement any kind of Boolean expression. Okay, so this was a very, very important point. Very, very conceptual point. Okay. Now let's see any question. Which of these are universal gate? So this is NOR gate. First one is NOR. Certainly universal. What about this one? This is also universal only. What is the final function? A bar plus B bar. So that would be AB bar. AB bar universal. What about this one? What is this? A bar dot B bar. That is equals to A plus B whole bar. This is NOR only. What about this one? What do you think? Is this your universal gate? Let's try. A bar plus B bar and then whole bar. So what that would be? AB bar bar. So that would be equals to AB. So here in the final expression you are not getting NOT response. You are not getting NOT response. NOT is not there. Inverter is not there. So this is not. Okay, just by looking at the bubble you cannot say it will be a universal gate. You need to see the final expression. In the final expression you are not getting a bar there. So that is not the final answer. That is not a universal gate. So this is not a universal gate. What about this one? A bar dot B bar. So it is A plus B bar. So this is also a universal gate. What about this one? A bar dot B bar bar. So that would be A plus B. So this is also not a universal gate because here you are not getting the response of bar. Okay, so this is also not a universal gate. So this was the concept of our universal gate. So this question came in 2022. In GATE 2022, this question came. So what they are saying, why is A plus B bar? So using instance of a D gate, basically this D gate is represented as A plus B bar. So which of the following option is correct? NAND gate can be implemented, OR gate can be implemented, logic gate can be implemented, and AND gate can be implemented. So 1, 2, 3, 4. And this is what I did in the examination. because gate 2022 was my attempt. Okay, but here I did not even check cannot is written. So these two options will not be there. Everything can be implemented, right? NAND can be implemented, NOR can be implemented, AND can be implemented, OR can be implemented, NOT can be implemented, XOR can be implemented, XNOR can be implemented, everything can be implemented. So I knew this thing that everything can be implemented, but what did I see? NAND, OR, NOR, AND. Tick down or fall. It costed me 2 marks. Okay, so don't do these kind of mistake. Cannot is written here. It really happened with me in the examination. I clicked on over 4. So A plus B bar, this is a universal gate, so everything can be implemented. Okay, so yeah, that was the concept.
So now let's see the concept of delay, very important concept. So you have to draw the timing diagram of different digital circuits involving the elements which are having non-zero delay. So here inverter is there which is having 5 nanosecond delay, and your XOR gate is there which is having 15 nanosecond delay. For t less than 0, A was 1 and B was 0, and for t greater than 0, A is 0 and B is 0. So basically A is going from 1 to 0 and B is remaining at 0 only. So how will C look like? That you need to draw. Okay, so how you need to solve these kind of problems without doing any error? If you want error free answer, then this is the method you need to solve. So after every gate you will define a variable. So A is there. After this NOT gate I will define a variable, let's just say X. After this XOR gate I will define a variable, that is Y. Y is equal to C only, but that we can see later on. So I am defining a variable from my side, right? So what is X? X is equal to A bar. So first I will draw the timing diagram of A, and then I will draw the timing diagram of X, and X is simply A bar. So timing diagram of A I have already drawn 1 to 0. So what will be the timing diagram of X? But this timing diagram is without delay. First I will not think of any delay. I don't know there is 5 nanosecond delay. I will directly draw X is equal to A bar. So without any delay, without introducing any delay, I know this is how your X bar will look like. This is how your A bar will look like from 0 to 1. Now I will check the delay. What I will check? I will check that X I will get after 5 nanoseconds. So there is a delay of 5 nanoseconds. So X after 5 nanosecond delay. So this waveform I will shift by 5 nanoseconds. So this waveform will be shifted by 5 nanoseconds. This waveform is shifted by 5 nanoseconds. This waveform is shifted by 5 nanoseconds. Now what is my second target? My second target is Y. What is Y? Y is X XOR B. I am not thinking about the delay. My target is only to make the waveform. So X XOR B. Now which X I will take? The delayed one. Here I will take the delayed one because new waveform I have got. No, this new waveform I have got. So delayed one I will be taking. This XOR with B. So this XOR with B. 0. This is 0. Here also it is 0, and then it is becoming 1. So till 5 nanosecond it will give me 0 only. So 0 XOR 0, 0 XOR 0, 0, 0, 0, 0. And then 0 XOR 1 will be 1. This is my Y. And this window is 5 nanosecond. This is my Y without delay. And Y with delay, what is the delay? Delay is 15 nanosecond. And Y with delay, that is 15 nanosecond, that is equal to C only. So here I will introduce a delay of 15 nanosecond. So 5 nanosecond plus 15 nanosecond. So this will go to 20 nanosecond. So this is how your C will look like. This is how C will look like. That's it. So this is the way you need to answer the problems. This is 20 nanosecond. So from 0 to 20 second, your Y will be 0, and then it would be 1. So these kind of questions can come in your examination. They can ask till what time C will remain at 0. So 20 nanosecond, and then it will be 1. Steady state value of C will be 1. So these kind of questions can come up in your examination. We will solve more examples. Let's solve this one now. Two gates are there. First one is NAND, and then there is XOR gate. 10 nanosecond delay, 20 nanosecond delay. All the inputs are changing from 1 to 0. All the inputs are changing from 1 to 0, 1 to 0, 1 to 0. ABC, ABC, ABC. After every gate, I will define a variable X, and here it is y only. So better we should define PQ, P and Q. So first I will make the waveform of P. What will be the waveform of P? P is equals to AB bar, A into B bar, A into B bar. Okay, so 1 to 0 they are going. So initially 1 into 1 is 1, 1 bar is 0. So initially P is 0. Initially P is 0. P is 0. And then 0 into 0 will be 1. 0 into 0 will be 1. So better like I have to make it a bit congested because there will be 4 waveforms, right? So 0 to 1 we will go. This is without delay. But I have to introduce a delay of 10 nanosecond. So P with the delay of 10 nanosecond. So 10 nanosecond will be delayed. It will be delayed by 10 nanosecond. So it will be delayed by 10 nanosecond. This is delayed by 10 nanosecond. So this window is 10 nanosecond. This window is 10 nanosecond. So this is 10 nanosecond, right? Now, what is my Q? Q is P delayed. P delayed I am saying XOR with C. So P delayed XOR with C. This is what I need to do. So what will be my Q? Q without delay. Q without delay. So this XOR with C. So 1 XOR 0 is 1 only. 1 XOR 0 is 0 XOR 0 is 0 only. 0 XOR 0 is 0 XOR 0 is 0 only. And 1 XOR 0 is 1. This is 10 nanosecond, right? Now I have to introduce the delay. So this 20 nanosecond delay I have introduced. So this is the best possible method of solving these kind of problems. If you show your intelligence there, then there is high chance that you will mess it up. So do not show the intelligence, go by the method. You will be able to solve it quickly in the examination. You will not run out of the time. Okay. So 20 nanosecond delay I will have to introduce. So 0 will go to 20 and 10 will go to 30. So 20 nanosecond delay I am introducing. So this is your 20 nanosecond and this is your 30 nanosecond. So this is the waveform of Y. So these kind of questions they can ask that for what window you will have 0 output. In Y, for what window you will have 0 output? 20 nanosecond to 30 nanosecond. That would be the answer. What is the steady state value of Y? That is 1. So these kind of questions can come. Okay, let's solve more examples. This is a big example. A is changing from 0 to 1 and B is changing from 0 to 1 but at t equals to 2.5 nanosecond. B is changing from 0 to 1 at t equals to 2.5 nanosecond. Draw the timing diagram and find the time window for t greater than 0 for which output is 0, or find the time as well. This can also be written. So here I will show how I will be solving in the examination, because in the examination you are not going to draw the diagrams like this. So in the examination how I will be solving. So A is changing from 0 to 1. First I will draw the waveform of A. Roughly only I will draw. A is changing from 0 to 1 at t equals to 0 and B is changing from 0 to 1 at t equals to 2.5 nanosecond. So this is how I will be solving in the examination. Okay. Now I need to draw the timing diagram. So again X, okay, Y is there already. So P, Q, R, there is no delay here. There is no delay. Okay. Still S, T. So P is A only, because P is equals to A only, no? A into A is equals to A. So P is equals to A, but with 5 nanosecond delay. So P is equals to A with 5 nanosecond delay. P is equals to A with 5 nanosecond delay. So this 5 nanosecond delay I can directly show. This is my P. Now here I comes. Q is A bar with 3 nanosecond delay. Q is A bar. So this is your Q. Q is A bar. So 1 to 0 it will go, but with 3 nanosecond delay. 1 to 0 it will go. 1 to 0 it will go, but with 3 nanosecond delay. So this is changing at t equals to 0. So this will change at t equals to 3 nanosecond. Are you getting this point? This will be 1 to 0, but with 3 nanosecond delay. Now what I need to do? XOR of these two. So XOR of these two. P XOR Q. So first I will do the XOR. So this is 1, this is 0. So 1 I will get. 1 I will get. Then 0 XOR 0, 0 I will get. And then 1 XOR 0 I will get 1 only. Right? And this window is 3 nanosecond. This window is 5 nanosecond. But this is without delay. So with delay I will make here P XOR Q with delay. With delay, how much delay is there? 4 nanosecond delay is there. So I will shift the complete waveform with 4 nanosecond. So from, if I am shifting from 4 nanoseconds, so 4 plus 3, this will go to 7 nanosecond, and this will go to 5 plus 4, this will go to 9 nanosecond. This will go to 9 nanosecond. Okay, 1 0 1 it is going. Now this is my R. R I have got. From R to S, this is simply inverted. R to S is simply inverted without any delay, because this is having 0 nanosecond delay. So S waveform I will draw simply inverted. This is 7 nanosecond, 9 nanosecond, 0 to 1, 1 to 0. This is my S. So S and B is coming. What was my B? B is starting from 2.5 nano. B is starting from 2.5 nano, and it is going like this. So I need to XOR these two. XOR of these two. So S XOR B, that would be 0 XOR 0, 0. 0 XOR 1 will be 1. 0 XOR 0 will be 1. So 2.5 nano to 7 nano. Then 1 XOR 1 will be 0. So 7 nano to 9 nano it will be 0. Then 0 XOR 1 will be 1. Will be 1. So this we are starting from t equals to 0. From t equals to 0 nanosecond we are starting. Okay. Now what we need to do? We need to introduce a delay of 10 nanosecond. We need to introduce a delay of 10 nanosecond. So if we need to introduce a delay of 10 nanosecond, so basically all will be increased by 10 nanoseconds. So this will be the final waveform. This is my output Y. This is my final output Y. So this is how I will be drawing in the examination. Each waveform I will take, but I will keep in mind that initially I need to make the simple waveform, but I will introduce the delay. I will not forget introducing the delay. Let's check it out from the beginning what we did here. A waveform, B waveform we had. A waveform, B waveform we had. First one is simply A with 5 nanosecond delay. Simply A with 5 nanosecond delay. Then we had Q, which is 3 nanosecond delayed and inverted. Then we had XOR of these two. XOR of these two. So 1 0 1 0 0 1 0 1. So that we got without delay. Right? Then we introduce a delay of 4 nanosecond. So 4 plus 3 7 and 5 plus 4 9 nanosecond. Then S is simply inverted. It is inverted without any delay. Then B is coming here. That is this kind of waveform. Then we need to take the XOR and then delay by 10 nanoseconds. So first we took the XOR and then delayed it by 10 nanoseconds. Now for how much time it is 0? Find the time for which it is 0. It is 0 for 0 to 12.5 nanosecond and 17 nanosecond to 19 nanosecond, which implies 12.5 nano plus 2 nano, that is equals to 14.5 nanosecond. So for this much of time it is equals to 0. That's it. So this is the concept of timing diagram. This is how you draw the timing diagram. So in gate examination, if these kind of questions come, you will be able to draw the timing diagram and then tell the final answer. Okay, so no other problem is there. Now this is a short lecture only. This lecture will be of 30 minutes only. So here we studied the interesting concept of a universal gate, and then we saw how to draw the timing diagram. In the next lecture onwards, we will study about Boolean algebra. So there only we will study about Venn diagram. So in the next lecture, we will cover the Boolean algebra completely. We will see examples as well, and we will cover the theory part as well. Okay, so let's meet you in the next lecture. Hi everyone. So now we will start studying about Boolean algebra. Okay, so Boolean addition, Boolean multiplication, these kind of things we have already seen in logic gates. So what is Boolean addition? 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is not 2, it is 1 only. Okay, because we have only two binary digits, these are 0 and 1, so we cannot go above 1. So 1 plus 1 will be 1. Multiplication, 0 into 0 0, 1 into 0 0, 0 into 1 0, and 1 into 1 is 1. Now let's see this question, very easy question. We need to determine the value of a, b, c, d such that first one, a into b bar into c into d bar is equals to 1. So you need this equals to 1. Then if you need this equals to 1, then you know that if we need 1, that means all the values should be 1. All these values should be 1. So a has to be 1. And what b has to be? B has to be 0, because 0 bar will be 1. So b has to be 0. C has to be 1. C has to be 1. And d has to be 0, so that d bar will become 1. So if we need 1 in the output, in AND operation, this is the AND operation, dot 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 dot. In AND operation, if we need 1 output, that means all has to be 1. So is a is equals to 1, b is equals to 0, c is equals to 1, and d is equals to 0. Similarly, if you need 0 output, then you need all of them to be 0, because if any of them is 1, then output will be 1. So a has to be 0. And what b has to be? B has to be 1. B has to be 1. C has to be 1, and D has to be 0, right? A has to be 0, B has to be 1, so that it becomes 0, C has to be 1, so that it becomes 0, and D has to be 0. Okay, very easy problem. Some laws are there for Boolean algebra. You don't need to remember the names. There is very rare chance that they will ask you the names, but you need to remember these simple expressions, that a plus b is equals to b plus a b is equals to ba, a XOR b is equals to b XOR a XOR b is equals to b XOR a. Very simple thing. So this is known as commutative law, that you can interchange the variable a b b a. Associative law, a plus b plus c, then you can put bracket anywhere. This is known as associative law. A into bc, then you can do ab and then you can do c. Similarly here as well, first you are doing the XOR of ab and then c, or you can do the XOR of bc and then you can do the XOR with a. Both things are same only. Same goes with XOR as well. Okay. Distributive law, a into b plus c, so that would be ab plus ac. A into b plus c would be ab plus ac. Does this follow in this XOR gate? Does this follow in this XOR gate? Yes, it follows. AB XOR AC. Now the interesting thing will come. A XOR b plus c. So can I write it as a XOR b plus a XOR c? No, this is wrong. Okay, this does not follow. So many times I have seen student doing this thing. This does not follow. A XOR b plus c. So a XOR b plus a XOR c. Nothing like that. You have to solve it separately only. You have to solve it separately. Okay, so this doesn't happen. So this you need to remember. This was the most important part. All other things you already remember as per my estimation. Okay. And let's see more rules of Boolean algebra. A plus 0 is a. Anything in addition to 1 is 1. A into 0 will be 0. A into 1 will be a. No matter how many times you add a, it will always be a. A plus a is a. A plus a plus a plus plus a, it will be a. A into a will be a. A into a into a into a, that will also be a. A plus a bar will be 1, because if you put a equals to 1 and a bar will be 0, so 0 plus 1 will be 1. And if you put a equals to 0, a bar will be 1, so 1 plus 0 will be 1. So a plus a bar will always be 1. And what is a into a bar? A into a bar is 0, right? A into a bar is 0. So if a is 1, a bar will be 0. A is 0, A bar will be 1. So 1 into 0 is 0, 0 into 1 is 0. So A into A bar is 0. Now A bar bar, bar of A and then another bar and bar will get cancelled. So it would be A. What this would be? A plus AB. So what you can do? You can take A as common, then 1 plus B. What will be 1 plus B? It will be 1 only. So A into 1 and that would be equals to A only. Okay. A plus AB. A you took common, 1 plus B. Anything in addition to 1 will be 1 only. So answer would be A. Okay. Let's see this one. A plus B into A plus C. Do you remember the answer? A plus BC. If you don't remember, let's solve it. A into A will be A, plus A into C will be AC, plus B into A will be AB, plus B into C will be BC is equals to A. Then common will be 1 plus C plus B plus BC. Anything in addition to 1 will be 1 only. So A plus BC. So from here we will remember the other way around as well. That if A plus BC is given, then I will be able to write A plus B into A plus C. Other way around also I need to write. Now A plus A bar C. So how will I write? Can I assume this A bar as B? So what will be my answer? A plus B. B is A bar into A plus C. A plus A bar into A plus C. What is A plus A bar? A plus A bar is 1. A plus A bar is 1. So 1 into A plus C. That would be A plus C only. So this is the answer, A plus C. Let's try solving this one. So what did I do here? I assumed A bar to be B. So A plus B into A plus C. So A plus A bar into A plus C. A plus A bar is 1. So A plus C we are getting. Let's solve this one. This also you can remember. Very interesting result will come. So let's solve it. So this, if this is A, I can assume this as B. So first as it is bar of the second one. First as it is bar of the second one. Plus second as it is bar of the first one. Right? So A into A plus C bar. Can I solve the bar of this? A bar into C, A bar into C bar. So that would be, I can say X into Y bar. So that would be X bar plus Y bar. So bar of A bar. So that would be A plus C bar. So that would be A plus C bar. So basically bar of A, that would be A only. Bar of C would be C bar. Plus A bar into A bar C, that would be A bar C. So A into A would be AC plus A into C would be AC bar plus A bar C. So A common I will take, 1 plus C bar will be there plus A bar C. Anything in addition to 1 will be 1 only. So A plus A bar C. Now A plus A bar C can be replaced with A plus C. A plus A bar C can be replaced with A plus C. A plus A bar C can be replaced with A plus C. So this you can directly remember. Okay. I will again write it here. This you can directly remember. X plus X bar Y can be replaced with X plus Y. Directly remember it. You won't need to do X plus X bar into X plus X bar into X plus Y, because X plus X bar will be 1 only. So X plus X bar into Y will be replaced with X plus Y only. So this you can remember. So what is the answer we are getting? A XOR A bar C. What is the answer we are getting? We are getting the answer same as this thing, A plus C. So better I can write in terms of X only. So X plus X bar Y is X plus Y only. So X XOR X bar Y is also X plus Y. So these two are equal things. Both are equal. Can you remember this thing? Yes, you will be able to remember it. Okay. Let's solve this one. X XOR Y XOR XY. So X XOR Y XOR XY, what I can do? I can take Y as common. I am taking Y as common. So here I will be left with 1 XOR Y. Sorry, 1 XOR X. 1 XOR X. Do you agree to my point? I took y as common. So 1 XOR x. So what that would be equals to x XOR, this is y. 1 XOR x will be x bar. So what I can write, x XOR y. So what that would be equals to x plus y. So in the conclusion, what you can remember, this you might not be able to remember. I also don't remember it because I can derive it very easily. Y will come 1 plus x bar, so y into x bar. So x plus y will be my answer. X plus y will be my answer. Once you are habitual of this, you will be able to write down the answer very quickly. Okay, once you are habitual. So let's check out what all you have studied. This thing we have studied, this we have studied, very important. This is also very important, right? This is very important. And these things we have studied only. Okay, so these three are very important relations. This is also very important actually. Here only I will write a plus b into a plus c, that is equals to a plus bc. This is also very important, a plus bc. Okay, so these four you need to remember. Let's solve these one. A plus b into a bar plus b. So you can open the bracket and then solve it, or how you can solve it, can I write it as b plus a into a bar plus b. Basically forget about it, something is same, b plus a, and then other thing is different, a bar plus b, or I can write b plus a bar. So what did we studied? A plus b into a plus c, that is a plus bc. So I can write it as b plus a into a bar, right? B plus a into a bar, and a into a bar will be 0 only. So that would be equals to b. Answer will be equals to b. What about this one? Can I write it in this manner? A plus b plus c into a plus b plus d. So let's just say if this is x, so this will also be x. So equation is becoming x plus c into x plus d. What that would be? X plus cd. So what will be the answer? A plus b plus cd. X plus c into x plus d. So x plus cd. So a plus b plus cd, right? What about this one? What I can write? ba plus a bar. This x I will remove. Let it be here in this manner only. A bar plus a bar bar b. What I have studied? X plus x bar y is equals to x plus y. Here only I studied x plus x bar y is equals to x plus y. So similarly, a bar plus a bar bar is equals to b. Sorry, a bar plus a bar bar b. What that would be equals to? X plus x bar y. So that would be equals to a bar plus b. You just show the bar here, that means this value will not come. So a bar plus b is the answer. Okay. You show the bar here, that means this value will not come. So it would be b bar plus a bar. And b bar plus a bar can be written as a b bar. So this can be replaced with a b bar as well. You show the bar here, so this value will not come. You show the bar here, that means this value will not come. Understood? What about this one? What this will be replaced with? PQ plus RS. Bar of this one. So PQ will come, but this PQ bar will not come. A plus A bar B is equals to A plus B. So this bar will not come. So PQ plus RS will be the answer. So in this manner, you will be able to write down the answer. For now, it may seem that, sir, how we will be able to remember all those things. But here I have marked what you need to remember. These only properties you need to remember. And once you have enough practice, you will be able to see these kind of things. In the examination, you will be able to see, okay, this will happen, this will happen. And even if you are not able to see, when we study K-maps, it will be more easier for you. In K-maps, it will be very easy. So no need to worry, you will be able to reduce it. Let's try this one. So what I can do in this one? First I can take b as common, b as common. So a plus a bar I am getting here. Then I can take b bar as common. So a plus a bar I am getting here. What is a plus a bar? A plus a bar is 1 plus b bar. A plus a bar is 1. So what I am left with? B plus b bar. And what is b plus b bar? That is 1. Very simple. Now this is a theorem which is known as consensus theorem. So we will see it. So in this theorem what you will do? You will find the bar of something. What will be the target? My target is to find the bar of something. I have a bar available. Bar of a is available. Now with a, which numbers, which variable are in multiplication? B and C. With a I have B and C. So I will find if I have multiplication of B and C available. Do I have BC available? Yes, BC is available. That means this BC is redundant. So BC will not come. So that is your final answer. A bar C plus AB. Did you understand what I am doing? My target will be to find the bar of a single variable. So bar of A is available, that is A bar. With A you have B, with A bar you have C. So BC is available, yes, BC is available. That means that is redundant. So that will not come. So AB plus BC plus C bar A can be reduced to A bar C plus AB. How it is reduced? Let's check that out. Let's see the proof. Let's see the proof. So AB plus C A bar plus BC is there, right? So can I write A plus A bar here? Because A plus A bar is 1. If BC is written, that means BC into 1 is written. And what is 1? 1 is A plus A bar, right? So AB plus CA bar plus ABC, BC into A, ABC plus A bar BC. So AB plus ABC. So AB into 1 plus C plus this is CA bar, this is A bar BC. So here I can take A bar C as common, 1 plus B. So 1 plus C will be 1 only. So what I am getting? AB plus A bar C. So this is the proof. So our target will be to find the bar and see what all are there in the multiplication and find that term. Let's solve more examples. Find the bar. Bar of A bar is available. In the multiplication, B bar and C bar is there. B bar C bar is available? Yes. That means this term is reluctant. This term is redundant. So A bar B bar plus C bar A. That's it. Find the bar. Bar of C is available? Yes. In multiplication, B and A is there. AB is available? Yes. That means this is redundant. So AC plus C bar B. In any order you can write. CA, AC, any order you can write. C bar B, BC, you can in any order you can write. Now find the bar. This is bar. But here 2 bars are available. One more is available. 2 bars are available. So not applicable. The theorem is not applicable. Not applicable. Theorem is not applicable here. Okay. So you have to solve by simple method only. Because 2 bars are available. Here I can see A bar is available and this is also available. So theorem is not applicable, and by simple method as well, what we can solve here? Nothing much we can do, or we can do anything. If I take B bar common, then it would be C bar plus A bar, C bar plus A bar, that is CA bar. Yeah, we can do something. So let's take this example here. A bar B bar plus B bar C bar plus CA, right? So if I take B bar common here, so it would be A bar plus C bar plus CA. Can I write this B bar plus A bar plus C bar as CA bar plus CA? This is CA bar only, because what will be your CA bar? CA bar will be C bar plus A bar. CA bar will be C bar plus A bar. So what is this becoming? X plus X bar Y. So that would be X plus Y. So this is becoming B bar plus AC. B bar plus AC. So this is how you can reduce it. Okay. B bar iso, A bar plus C bar iso. So A bar plus C bar I can replace it as AC bar. So which is bar of this. So X plus X bar Y. X plus X bar Y. So that is X plus Y. So CA plus B bar. So that is the answer. So this is how you can replace it. Okay. Let's check out here. B bar is available. Okay. And AC is available. If AC is available, then this term is redundant. So AB bar plus BC. Now the same thing can happen in product of sum as well. This was sum of product. Sum of product. This can happen in product of sum as well. So A plus B, B plus C, C plus A. Again you need to find the bar. This is the bar, A bar. In addition there is C, in addition there is B. B plus C is available? Yes, that is redundant. Okay, this term is redundant now. So if that is redundant, so my answer would be A plus B into A bar plus C. So let's do the proof here. So A plus B into A bar plus C into B plus C plus. In addition, what is there? 0 or 1? 0, right? In addition, if there is 1, that will be replaced with 1 only. So in addition, there is 0. So if there is 0, so 0 I can replace with A bar. 0 I can replace with A bar. Say yes or no, right? Now what I can do? Now A plus B and C. Okay. So basically this is my X plus A bar, right? So can I replace this as X plus A into X plus A bar? So basically this is A plus B, this is A bar plus C, this is B plus C plus A, this is B plus C plus A bar. So A plus B into A plus B plus C, this is A bar plus C and A bar C plus B, right? Now this is, let's just say this is X. So what I am saying, X into X plus Y. So what that would be equals to? X into X plus Y. That would be equals to X plus XY. So you take X as common, 1 plus Y. So it will be equals to X only. So this term X into X plus Y can be replaced with A plus B only. And this term X into X plus Y can be replaced with A bar plus C only. So this is the answer. So this is the proof. Okay. Proof also, if you remember, that is good. But at least you need to remember how you will be able to solve in the examination. Let's check more examples now. Find the bar. Find the bar. In addition, A is there, C is there. A plus C is available. That means this is redundant. So A plus B bar into B plus C. Find the bar. C is there, C bar is there. A plus B is available. Yes. So that means this is redundant. So B plus C, C bar plus A. Find the bar. B bar is available. In addition, A bar plus C bar is available. That means this is redundant. Okay. So A bar plus B bar plus into B plus C bar. Find the bar again. C bar is available. A bar plus B bar. Yes, this is available. So that is redundant. So B bar plus C bar into C plus A bar. What about this one? Yeah, this is interesting one. Bar of what is available? Only one bar is available. A bar is there. C is there. But B bar is there. So bar of only one is available. In multiplication there is A bar, in multiplication there is C. So A bar into C is also available. So that is redundant. Are you getting this point? Find the bar. B bar is there. In B, A bar is there. Here in B bar, C is there. So A bar C is available here. So that is redundant. So what is your answer? A bar B plus B bar C. Now you might be worried that, sir, in examination how it will click to me. So there, when we study K-maps, I will tell you one method. K-map is that method only. So in the examination, if it doesn't click directly, you can use K-maps. So after that, you will be comfortable in this. But here we are using our brain, so using the brain is important. And if you are preparing for placements, then the interviewer can ask you this question intuitively as well. Like, don't use K-maps. Without using K-map, tell me how it will be reduced. Okay, so this is how it will be reduced. So let's try this one. C bar is there, B bar is there, A is there. So basically bar of this one is available. And then AC bar is also available. So this is redundant. So B bar, C bar plus AB. Did you understand this whole concept or not? So you need to see the variables. B bar is available. Okay, bar is available. C bar is available. A and A is available. So AC bar is redundant. So that is one. Okay, so this is the whole concept. Now more examples are there. Simplify whatever that we have studied. Based on that, you need to simplify all those things. So A B bar C plus A bar B. Let's see what we can take common. So C we can take common, or anything else we can take common. A bar C we can take common here from here. So let's take this as it is. Now from here I can take A bar C as common. A bar C as common I am taking. So if I take A bar C as common, so B plus B bar will be left. B plus B bar is 1, right? So A B bar C plus A bar C. A B bar C plus A bar C. So C is there. A bar plus A B bar. So C is there. A bar plus A B bar. So that would be equals to C. A bar plus A B bar. What that would be equals to? X plus X bar Y. A bar A. That is the bar only. So X plus Y. So it will be equals to A bar plus B bar. So your final answer could be, that is equals to C A B bar, because A bar B bar can be replaced with C A B bar. So this is how it can be reduced. Let's try this one. This is very easy. What is coming in common? A bar B. So A bar B will come in common. 1 plus some C bar will come, plus D will come, plus C bar D E bar will come. So 1 plus anything will come. That will be 1 only. So that is equals to A bar B. That's it. Okay. What about this one? Find the bar. A bar is there. And then BC is there. A bar is there and BC is there. So multiplication of BC is available. Yes. But with that DEF is also available. But that does not matter. Your target is to find BC only. So if BC is available, you can reduce it. Still this term will become redundant. Let's prove it. Okay. Let's prove it. Why should we only assume? Let's prove it. AB plus A bar C. And even in the examination, you can confirm by proving. Okay. B, C, D, E, F. In multiplication, there is 1. So 1 I can replace with A plus A bar. That is AB plus A bar C plus A, B, C, D, E, F plus A bar, B, C, D, E, F. So here I will take AB as common. So this will become 1 plus C, D, E, F. Right? This I am taking. 1 plus C, D, E, F plus A bar C. So it would be 1 plus B, D, E, F. So 1 plus C, D, E, F will be 1 only. 1 plus B, D, E, F will be 1 only. So what you are left with? AB plus A bar C. So B and C, multiplication of B and C is available here. So this term will be redundant. So directly you could have written AB plus A bar C, or in the examination you can confirm as well. If you have the doubt, you can confirm. Here find the bar C and C bar. Now find the multiplication AB into BD. Is that available? AB into BD. What that would be? ABD. AB into BD will be ABD, which is available. So this is redundant term. So that would be equals to ABC plus BC bar D. In first go, you might not be able to solve these kind of problems because they are conceptual. But in the examination, that's the max they will go. Okay. So all kind of problems we will deal in the class notes itself. In the test series also you will not have some problems. So ABC plus BCD bar. So C bar is there. So ABD multiplication is available. Yes, it is available. So that term is redundant. So this is the answer. Okay. Let's move to our next theorem, that is De Morgan's theorem, which we have already studied. De Morgan's theorem. So what is AB bar? AB bar. So dot can be replaced with addition, but individual bar will be there. This plus can be replaced with dot, individual bar will be there. This dot can be replaced with addition with individual bar. Plus can be replaced with dot with individual bar. This also individual bar. This also individual bar, but dot will be there. Okay. So this is the way of De Morgan's theorem. Okay. टेढ़ा लिखा जा रहा है यार शायद, अब तो लिखा ही गया. Okay, but yeah, I think handwriting is fine. So simplify all these things. So dot will be replaced, here also there is dot. Dot will be replaced with addition but individual bar. So A bar of A bar, that would be A, plus bar of B, that would be B bar, plus bar of C bar, that would be C. What about this one? This will be replaced with A plus B bar. Dot is there, so it will be replaced with addition C plus D bar. Now A plus B bar, that will be replaced with A bar dot B bar plus C bar dot D bar. What about this one? A plus B plus C bar plus D bar. Dot is replaced with plus and individual bar we are taking. So bar of A bar is A, bar of B bar is B, bar of C is C bar, and bar of D is D bar. What about this one? This would be A bar dot B dot C bar dot D plus A bar plus B bar plus C bar plus D. Right? Understood? So A bar plus A bar B C D bar plus A bar plus B bar plus C bar plus D plus C bar plus D. So from here A bar I can take common. So if I take A bar common, then 1 plus B C D bar is coming, plus B bar plus C bar plus D. Right? So 1 plus anything will be 1 only. So A bar plus B bar plus C bar plus D. This is the final answer. Or how it can be replaced? It can be replaced as A B C D bar whole bar. This is also how it can be replaced. So A B C D bar whole bar. So this term completely becomes irrelevant. Right? Yeah. This term is completely irrelevant. This one. This is completely redundant, because finally we are getting A bar plus B bar plus C bar plus D bar, which is equals to this one only. So this is how it can be replaced. What about the next one? So solve next one. A bar B bar C plus individual bar will be there. A bar B bar C plus A bar B bar C bar D. Right? So that would be equals to A bar, basically A bar B bar C plus A bar B bar C will be equals to A bar B bar C only, right? A bar B bar C only. So A bar B bar, then C will come common, so C plus C bar D. So A bar B bar C plus C bar D would be C plus D. C plus C bar D. C plus C bar D. What that would be equals to? C plus D. X plus Y bar Z. Sorry, X plus X bar Z. Sorry. X plus X bar Z. That is equals to X plus Z. So C plus C bar D would be equals to C plus D. So this is equals to A bar B bar C plus A bar B bar D. Right? Now what about this one? Can anything happen here? If I take C as common, so, or if I find bar, C is there, B bar, A bar, क्या तो कर सकते हैं, कुछ तो कर ही सकते हैं. If ABC was there, no, if ABC was there, then it would have been reduced to into ABC bar, C into AB bar. How can this be replaced? Yeah, so A bar C we can take common. Actually, I am pretty tired, that's why I am not able to think now. So A bar C here I can take common. A bar C I can take common. So B plus B bar will be left. B plus B bar will be 1 only. So A bar C I took common. So I can take. So now this would be A B bar C plus A bar C. So I can take C as common. So C as common. So A bar plus A B bar. A bar plus A B bar. So this can be C into A bar plus B bar. And A bar plus B bar will be A B bar. A bar plus B bar will be A B bar. Okay. A bar plus B bar is A B bar. So this is the way we can proceed. Okay. Are you understanding this point? A bar plus A B bar. What that would be? A bar plus B bar. A bar plus A B bar. X plus X bar Z. That would be X plus Z. So same thing we are doing here. X plus X bar Z is equals to X plus Z. So A bar plus B bar, and A bar plus B bar can be replaced with A B bar. Okay. Now let's see the Venn diagrams. Venn diagrams we are going to see. So A and B, two variables are there. What this will be replaced with? Tell me. Here there is A but not B. So AB bar. If I say A and not B, in set theory we would have replaced it by this value, right? A minus B. A but not B. A but not B. So in Boolean algebra there is no minus. There is only two operations, which is plus and dot. So instead of minus we will put bar. Okay. So A is there but not B. What you will call this one? B is there but not A. Part B is there but not A. What you will call this one? Both A and B are there. Common part of A and B. So this is what? AND gate. What you will call this one? That both A is also not there and B is also not there. Or you can say A plus B completely is not there. So what this will be? What this will be? What do you think? What is this? This will be A plus B. Everything that is in A, everything that is in B. That would be A plus B. So can you tell me what will be your A plus B? That will be A plus B will be A but not B. Right? A bar plus B plus AB. That would be your A plus B. Do you agree to this point? If I take A B bar B plus A bar B bar, that would be A plus B, not A plus B bar. B bar C. If I take C common here, if I am taking C common here, then here I will get A B bar plus A bar B plus A bar B bar. A B bar plus A bar B plus A bar B bar. Okay, that's the thing. So this is your A plus B, right? This is your A plus B. A plus B is A B bar plus A bar B plus AB. This much. This is A plus B. And what this will be? This will be 1. Everything is there. Every single thing is there. This will be 1. What is this? This is a b bar plus a bar b plus ab plus this outside one. What is this outside one? Neither a neither b. So this will be 1. Why this will be 1? Because what this can be replaced with? This is a plus b. And what this can be replaced with? This is a plus b bar. A plus b bar. So x plus x bar will be what? 1. So this complete will be 1. Complete whole will be 1. Right? We will again come to Venn diagram when it requires. In the next lecture only, I guess, we will again come to Venn diagram. Okay, Venn diagram is a very interesting thing in Boolean algebra. Are you able to understand? So, will you be able to remember this thing? That this much is equals to 1. A b bar plus a bar b plus ab plus a bar b bar will be equals to 1. So, I will be highly using it. In the whole chapter of digital electronics, I will be using it again and again. A b bar plus a bar b plus ab plus a bar b bar. Everything is coming. A not b, b not a, both a b and both not a not b. Everything is coming. That means that is equals to 1. Okay. So this is the Venn diagram. For 3 variables, tell me what this would be. A is there, but b is not there, b is not there and c is not there. So a, b bar, c bar. What this would be? B is there, but c and a both are not there. So c bar, a bar. What this would be? C is there, but a part is not there. Only this part, only this green one. So this I am talking about. Okay. Here also I was talking about this part only, and here also I am talking about this part only. So C is there, but not A and not B. What about this one? A, B, C all are there. A is also there, B is also there, C is also there. What about this one? And what about the outer one? This outer one. A is not there, B is not there, and C is not there. What about this one? What about this? That A is there, B is there, but C is not there. What about this? A is there, C is there, but B is not there. What about this? A is there, sorry, A is not there, B and C are there. Now what about this one? What about this one? That A and B both are there. So how you will get this AB? How you will get this AB? This AB will be equals to this much part. A is there, B is there and C bar is there, plus this much of part, which is A is there, B is there, C is there. So if you solve it, what you are getting? AB, C plus C bar. That is AB only. So sometimes for 2 variable and 3 variable, K-map is a very useful thing. Okay. If in your mind K-map is fit, then you can solve these problems easily. Sometimes it is useful for 2 variables and 3 variables. For 4 variables, we should not use K-maps that much. No, okay. Did I say K-maps? I was talking about Venn diagrams. Okay. Venn diagrams are very useful for 2 variables and 3 variables. Right. Next, what is the topic? Okay. The question is there. What this shaded area represent? What do you think? What is the answer? This complete shaded area is A. This complete one is A. Right? A plus. What about this one? What is this? B is there, C is there, but not A bar. So this is A plus A bar BC, or it can be replaced with A plus BC, because this is X plus X bar Y, X plus X bar Y. So X plus Y, A plus BC, and this is logically true as well, that A is there and BC part is also there, which is common into B and C, which is common for B and C. This part is common for B and C. So A plus BC, this area represents A plus BC. Okay. Now this is very interesting concept as well. Distinct logical expression. So first let's see what is distinct logical expression. What do you mean by distinct logical expression? So one logical expression is A and another logical expression is A plus AB. Are they distinct? Are they same or are they distinct? They are the same only, because a plus ab can be replaced with a into 1 plus b, and 1 plus b is 1 only, so it can be replaced with 1. So both are same, both same. But a and ab and a plus b, all these three are different. These three, all three different. All three different. EIFFERENT. Now why a and a plus ab are same? Why they are same? Because they have the same truth table. Let's check the truth table of a. The truth table of a will be 0 0 1 1 only. Simply a will be copied. What will be the truth table of a plus ab? So what is a? 0. ab will be 0. So 0. A plus ab. A is 0, ab will be 0. So 0. A is 1, ab will be 0. So answer will be 1, because 1 plus 0 will be 1. A is 1, 1 plus ab is 1. 1 plus 1 will be 1. So both have the same truth table. Same truth table. So if you are having same truth table, that means you are same only. Same truth table, that means you are same. So that is the meaning of distinct expression, distinct logical expression. So they are distinct logical expression. So what is the quality of distinct logical expression? That they will have distinct logical expression. What is the quality of distinct logical expression? That they will have different truth tables. They will have different truth tables. They will not have the same truth table. Okay. So that is the quality of distinct logical expression. So this will be used in our next concept. So what is our next concept? You need to tell total number of logical expression with the given variables. Okay. So if they are asking total number of logical expression, that means they are asking distinct logical expression only, because a plus ab, that is same. So distinct logical expression only they are asking. So suppose you are given one variable, then how many distinct logical expression you can make from one variable? From one variable you can make a as well. You can make a bar, you can make 0, and you can make 1. So these 4 you can make. Say yes or no. So what is your answer? 4. So from one variable I can make 4 distinct logical expression. A bar, 0 and 1 will always be available. 0 and 1. Basically directly if I connect my output to ground, this is my output. If I directly connect it to ground, this will be 1, this will be 0. If I directly connect it to my positive supply, my output will be 1. If I directly connect my output to inverter, then my output will be a bar. And if I just connect it with the buffer, then my output will be simply a. Right? Now from two variable, how many distinct logical expression you can make from two variables? So here I cannot write down all, but I will tell you how I can find how many distinct variable I can have. So if two variables are there, so how many total possible combinations are there of variable a and b? That means a can have value 0, b can have value 0, a can have value 0, b can have value 1, a can have value 1, b can have value 0, and both can have value 1. How do you find it? This can take two values, 0 and 1, and this can take two values, 0 and 1. So answer will be 2 into 2, 4. So 4 possible expressions are there. Okay. Now with respect to each combination, there are two possible output. Basically, with respect to this particular combination, there can be two outputs which are 0 or 1. Basically, this can have two outputs which is 0 or 1. With respect to this as well, there are two possible outputs which is 0 or 1. For this as well, there is two possible outputs 0 or 1. For this as well, there is two possible outputs 0 or 1. Are you understanding this point? Basically, what I mean to say, that for 0 0, my output is 0. For all these, my output is 0. Next case could be, for this only my output is 1, for rest all my output is 0. Next case could be, for this my output is 1, for this my output is 1, for rest all this is 0. Next case could be, for this my output is 1, for this my output is 0, for this is 1, for this is 0. Next case could be 1, 0, 0, 1. Next case could be 1, 1, 1 0. Next case could be 1 0 1 1. The next case could be 1 1 1 1. Now more cases can be there, 0 0 0 1. In that manner, again a lot of cases can be there, 1 1 0 1, right? Distinct I need to make 1 1 0 1. So in that manner 16 will be there, because this can have two value, this can have two value, this can have two value, this can have two value. So 2 into 2 into 2, 2 into 2 into 2 into 2. So 2 to the power 4. And from where this 4 came? That was 2 to the power 2 to the power 2. So total 16 possible variables are there. 16 possible variables. Basically, this will give you an output equals to 0. What this will give you an output? This will give you an output equals to AB bar. What this will give you as an output? This will give you an output as AB bar plus, sorry. This will give you A bar dot B bar. Really sorry. How I am writing this output, you will get to know. Later on you will get to know. So for this output will be A bar dot B bar. For this output will be A bar B bar plus A bar B. So simply output will be A bar only. So for this output will be A bar. So in that manner you can have different outputs. So total 16 possible outputs are there. That means total 16 Boolean expression you can get. Distinct logical expression or Boolean expression you can get. Total 16. Now with 3 variables, how many total? With 2 variables, 16 possible distinct logical expression you are getting. With 3 variables, what will be the condition? With 3 variables you can have these 8 outputs, right? Why 8 outputs? Because this can give 0 1 value, this can give 0 1 value, and this can give 0 1 value. So 2 into 2 into 2. So total possible outputs are 8. 0 0 1 1 0 0 1 1 0 1 0 1 0 1 0 1. So total 8 possible outputs are there. Now this can have 2 values. With respect to this possible combination, output can have 2 values, 0 or 1, 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 0 or 1. So what is my answer? 2 into 2 into 2 into 2, 8 times. Into 2 into 2 into 2 into 2 into 2. So my answer is 2 to the power 8. How did I get to this answer? 2 to the power 2 to the power 3. So for n variables, 2 to the power 2 to the power n distinct की स्पेलिंग क्या होती है भाई? Distinct, logical or Boolean expression will be there. So for n variable, 2 to the power n distinct logical or Boolean expression will be there. Understood? Right? 2 to the power 8. That is the answer. So this kind of question can be asked. Like you are given 4 variables. So with 4 variables, how many distinct logical expression can be there? So 2 to the power 16. With 4 variables, what will be the answer? 2 to the power 16. Okay. Now this term will be used, literal. What is the meaning of literal? So in a Boolean expression, those like how many variables are there, this is known as literal. So 1 2 3 4 5 6. So literal count here is 6. 1 2 3 4 5 6 7 8. Literal count here is 8. If they are asking how many variables are there, so your answer will be 1 2 3 4 5 6. 6 variables are there, but literals are 8. A and A bar both are different. Now B is connected with A bar and here B is connected with A. So this is also different. So literals are 8. Okay, but variable is 1 2. A bar is the another thing. So variable is A only here. So 1 2 3 4 5, 6. So variables are 6. So this is the difference between literal and variable. Okay. So how many variables are, how many literals are there? So literal count is 6. So this is the meaning of literal. Each variable in logical expression. Okay. 1, 2, 3, 4, 5, 6, 7, 8. Just for effect I am telling it. Okay. So now there is a term called dual. This term will be used, dual. What is the use of it? That we will see. So, but let's first understand how to take dual of any expression. How do you take dual? So for taking dual, only two things you need to do. Plus will be replaced with dot and 0 will be replaced with 1. Nothing else. Plus will be replaced with dot and 0 will be replaced with 1. So if and you do not need to complement the literals. Do not complement the literals. Okay. Don't complement the literals. Complement we don't need to do. So if I am taking dual of this, so what did I tell you? 0 will be replaced with 1. Dual of this, 1 will be replaced with 0. Dual of this, plus will be replaced with dot. Dual of this, dot will be replaced with plus. Dual of this, so plus will be replaced with dot, and there is dot, no, so this will be replaced with plus, and then there is dot, this will be replaced with plus. Then for the whole thing is being added, right? This whole thing is being added. So this whole thing is being added. So this plus will be replaced with dot, and in between there is dot, so that will be replaced with plus. Right? Are you getting this point? So this is the dual. Did you understand this point? Plus is there, that will be replaced with dot. Then dot is there, that will be replaced with plus. Then plus is there, sorry, dot is there, that is replaced with plus. Now this whole thing is being added with CD. Whole thing is being added with CD. So now whole thing will be multiplied with C plus D. Right? Now take the dual of this one. If you take the dual of this one, so A plus B into B plus C, plus is replaced with dot, into C plus A. Now let's try to solve it. So what we will get? AB plus AC plus B plus BC into A plus C. So from here I can take B as common. If I take B as common, then A plus 1 plus C I will get plus AC, then A plus C. So if 1 plus A plus C will be B only. So B plus AC into A plus C. So AB plus BC plus AC plus AC I am getting. So what that would be equals to? AB plus BC plus CA. So F dual is AB plus BC plus CA. So F dual is equals to F. Here F dual is same. I took the dual, I got to know that F dual is equals to F. So these kind of functions are called as self-dual function. Self-dual function. So this is a very important function. It will be used in our combinational circuits as well. When we study combinational circuit, there also it will be used. So if you take the dual and the same function is coming, that is known as self-dual function. Okay. So this AB plus BC plus CA is a self-dual function. Right. Now, if F dual is equals to F, then it is known as self-dual function. And if you take dual and then again you take the dual, then the function F only you will get. Basically, if F is equals to A plus B, if I take dual of it, what I will get? A into B. Then again I take the dual, what I will get? A plus B. So dual and dual, I will get the same function only. So F dual and then again dual, that will be same function only. Now, where dual is used? So for taking complement. So how will you take complement? Complement. For using complement. Now if there is a very large expression, so for taking complement for that particular large expression will be very difficult. Let's just say I ask you to take complement of A plus B. So what will be the complement of A plus B? That will be this. So taking complement of this is very easy, a bar dot b bar. But if there is very large expression, it will be very difficult. So what is the other method we came from? So first take the dual of a plus b. What that would be? A into b. Then take the individual bar. That's it. So first take the dual and then complement each literal individually. So if I ask you, take the complement of this function. So how will you take the complement of this function? So first I will take the dual. A plus will be replaced with dot into b bar plus c. Then whole will be this complete. This complete will be added with d. Right? Dot is replaced with addition. Everything is going fine. Now this whole value, this is not required because this is added, no, so this is not required. Since this is added, this is only added, so this is not required now. Now this whole will be multiplied with e bar and now it will be added with f, and now this whole will be multiplied with g bar. Now what you need to do, you need to take individual bar. So take the bar of this one, remove the bar from here, take the bar of this one, take the bar of this one, remove the bar from here, take the bar of this one, remove the bar from here. So this will be the complement of this function. The complement of this function is this one. That's it. So this is how you take the complement of this. What will be the complement of this? So what thing I know? This is a self dual function. This is what? This is a self dual function. Self dual function. So f dual is equals to f. So what will be the complement of f? So dual of this will be this value only. Dual of this. Dual of f will be ab plus bc plus ca only. This is the dual. And for taking complement, what we need to do? Take individual bar. So this is the answer. And that will be equals to a plus b, b plus c, c plus a. That will be the dual, and then take individual bar. So this will be equals to this as well. So that's how you can take the complement. Are you able to understand this concept? This was very easy. How to take the dual? Plus is replaced with dot and dot is replaced with plus. That's it. And 0 is replaced with 1, 1 is replaced with 0. So these things you need to do. And you do not need to complement the literals. But when we are taking the complement, so first take the dual and then put the individual complement. So first I took the dual and then I took the individual complement, individual complement, individual complement, individual complement. So this is the complement of this particular function. So here this was self-dual function. So if this is self-dual function, that means the dual of this will be ab plus bc plus ca only. And if I need to take individual complement, then I can take individual complement. So I will get complement of f. This will be the complement of f. Okay, and this will be equals to this as well. So that's it. This is the concept of dual. Now one more fact is there, that if there are n variables, then 2 to the power n will be total possible Boolean function, and out of these 2 to the power n minus 1 are self dual. Okay, so basically let's just say there are 3 variables. So in 3 variables, 2 to the power 3, that means 2 to the power 8, or we can say 256 will be total possible Boolean function. Total possible Boolean function. And out of these 2 to the power 2, that is 2 to the power 4, that is 16 are self dual. After this 16 are self dual. So this fact you can remember. Okay, so from 3 variable you can make 16 self dual function from 3 variables. One of the example is this ab plus bc plus ca. What could be the other example? A plus b into b plus c into c plus a. That is also self dual, right? A plus b into b plus c into c plus a. That will also be self dual. So yeah, that is the thing. Okay then, so that's it about this lecture. So we are done with this lecture, and in the next lecture let's see what we need to cover. In the next lecture we will see some assignment, because this is the end of this particular our first chapter. So in the next lecture we will see some assignment. Okay, so let's move on to our next lecture. Hi everyone, so in this video we are going to see our assignment 1. Okay, so first assignment we are going to see, so I will show you the questions first. So this is the first one, this is second and third question, fourth, fifth, sixth, seventh. You can pause the video and solve on your own. 8th, 9th, 10th, 11th, 12th, 13th, 14th, 15th, 16th, 17, 18, 19, 20, 21, 22. This is a very good question. And 23. Okay. So these 23 questions are there. We will solve one by one. First one. Which of the statement is true? Y is given as A XOR B XOR C XOR D XOR E XOR F. So Y can be used as odd number of ones detector or even number of ones detector. Y is equals to A XOR B XOR C XOR D XOR E XOR F. So what is this? This is XOR expression, right? This is XOR operation. Why this is XOR operation? Number of inputs are even. Number of inputs are even. If the number of inputs are odd, then it could have been XNOR operation as well, because I told you for odd inputs, let's just say A XOR B XOR C, that would be equals to A XNOR B XNOR C. But number of inputs are even, and XOR operation is known as odd numbers of ones detector, right? Odd number of ones detector. So this option would be correct. Odd number of ones detector. If it would have been something like this, A XOR B XOR C XOR D XOR E, if this would have been the case, then both A and B would have been correct, because this could be odd number of ones detector as well, and this can be equal to this as well. So both are same. If both are same, then this is XOR operation. XOR operation is known as odd numbers of ones detector, and XNOR operation is known as even number of zero detector. How would you remember? Okay, XOR operation. If I have odd number of ones, that means 1 XOR 1 will be 0, 0 XOR 1 will be 1. So that I can call as odd number of ones detector. And then XNOR will be even numbers of zero detector. So if this was the case, then both options would have been correct. But here 6 inputs are there, so this option is wrong. Okay. Let's see other options. The number of possible input combination for y equals to 1 is 32. So we need y equals to 1. We need y equals to 1. So if you need y equals to 1, then what can be the case? There is only one 1. Only 1. If there is only one 1, then your y will be 1. Only 1 and rest all are 0. Basically 1 XOR 0 XOR 0 XOR 0 XOR 0 XOR 0. So only 1 is there, then output will be 1. If there are only 3 ones, if there are only 3 ones, 1 XOR 1 and then rest all are 0, then output will also be 1. And if there are only 5 ones, because you need odd number of ones, what you need odd number of ones, so only 5 ones, right? So out of these 6 you need 1 6C1. Basically what can be the case? If A is 1 and B is 0, B is equals to C is equals to D is equals to E is equals to F is 0, then A is 0, basically B is 1 and then rest all are 0. This could be the other case. Then C is 1, rest all are 0. D is 1, rest all are 0. So that could be 6C1. Out of these 6 variables, one of the variables should be 1. Or 6C3, that 3 variables, 6C3, 3 variables should be 1. That means A is equals to B is equals to C is equals to 1 and rest all are 0. Or A is equals to B is equals to D is equals to 1, rest all are 0. Or A is equals to B is equals to E is equals to 1, rest all are 0. Or A is equals to B is equals to f is equals to 1, rest all are 0, or b is equals to c is equals to d is equals to 1, rest all are 0. So these kind of condition can be there. More condition can be there. b is equals to c is equals to e is equals to 1, rest all are 0. b is equals to c is equals to f is equals to 1, rest all are 0. So these kind of condition. So 6 is C3. Out of these 6, we need to choose 3 variables which are 1. So 6C3, right? Plus 6C5. So out of these 6 variables, I can choose 5 variables which are 1 plus 6C5. So that would be the correct answer. So what is the value of 6C1? That is 6 only. What is the value of 6C3? So 6 into 5 into 4 divided by 6. So that is 20. Basic concept of PNC it is. So 6C3 is 20. Plus 6C5 will also be 6. So what is the answer? 32. So for y equals to 1, to get y equals to 1, there are total 32 combinations. So this option is correct. Now what are the total combination of A, B, C, D, E, F? Total combination. Total combination of A, B, C, D, E, F. Basically A can have two values 0 or 1, B can have two values 0 or 1, C can have two values 0 or 1, this also can have two values, this also can have two values, and this also can have two values. So all can have two values, right? 0, 1, 0, 1, 0, 1. So what all are the total combination? So total combination are total combination. So total combination is 64. Out of these 64, 32 times you are getting 1. So you are getting 0 another 32 times, right? So this option is also correct. So the number of possible input combination for y equals to 0 is 32. For y is equals to 1, you are getting 32 times. Then y is equals to 0, you will get 32 times only, because total combination will be 64. If there were two variables a and b, so how many total combination were there? 4 total combination was there. If there were 3 variables, then how many total combination were there? 3 variables, there were 8, right? 2 into 2. If there are 6 variables, then answer would be 2 to the power 6. That means 64. So total combination would be 64. So out of these 64, 32 times you are getting 1. So rest 32 times you will be getting 0. So this option is also correct. So this was a very good question. These kind of questions can come in your MSQ. So you use your brain correctly and these kind of problems will be solved. Okay, let's move towards the next one. A XOR B, this function is given. How many NAND gates are required to implement the function? So in these kind of problems, first task is to reduce it. So let's solve this. Y is equals to, what is A XOR B? That would be A B bar plus A bar B plus B C bar plus B bar C plus C A bar plus A C bar, right? Okay then. So if I take B bar as common, then A plus C I am getting here. Then if I take B as common, then A plus C bar I am getting common. B common, A plus C bar. Sorry. If I take B common, then A bar plus C bar. And B bar I took common, so I am getting A plus C. B I am taking common, A bar plus C bar. And from here, what I can take common? I cannot take anything common, so let's not take this as common. Something different will happen for sure. So XOR operation is there, no? This should not be XOR operation here, because in XOR operation we are not getting anything. Actually, this will be XNOR operation. Okay, the question is wrong. This should be XNOR operation. XNOR operation should be there. I'm really sorry for this mistake. This should be XNOR operation. Okay, otherwise we are not getting anything. So this should be XNOR operation. So if we are doing the XNOR operation, then what we will get? So A bar B bar plus AB plus B bar C bar plus BC plus C bar A bar plus CA. So can I write it? AB plus BC plus CA plus A bar B bar plus B bar C bar plus C bar A bar. Do you remember one thing? That AB plus BC plus CA is self dual, right? Is a self dual function. This is self dual function. Then if I write this as y, what is this? This is y bar. What was the complement of AB plus BC plus CA? Just go to the last lecture. Just see the 2 slides back. 2 slides back you will see what is the complement of AB plus BC plus CA. That is this only. So y plus y bar is 1. So your answer is 1 only. So how many NAND gates required? 0 NAND gate. You need 1. Direct 1. A constant value. Supply. 1 is VDD. The supply. So you need 0 NAND gates required. So there is 0 NAND gate required. Okay, so there was an error in the problem. Here it should be XOR operation. So in XOR operation, we got to know that AB plus BC plus CA, A bar B bar plus B bar C bar plus C bar A bar. So this is Y, then this is Y bar. So Y plus Y bar is 1. Let's solve the next one. What will happen to this one? These two are in parallel. So B plus C and D plus E are in series. Sorry, D plus E is also in parallel. So D and E is also in parallel. So D plus E. Then both will come in series. So multiplication. Then this much of switch and switch F, these are in parallel. So plus F. And then which one will come in series? This one will come in series. So this one will come in series. So multiplication A. So this we have already seen, switching circuit. B plus C into D plus E plus F into A. So that is the answer. Okay. Let's see this one. AB plus AB bar C plus A. So AB plus AB bar C. What this can be replaced with? AB plus C. Say yes or no? X plus X bar Y. That would be X plus Y. So this can be replaced with AB plus C. So now what you need to find? AB plus C plus A. So A common will come, 1 plus B plus C. So answer is A plus C. So this is the answer. Okay, very easy. AB plus AB bar C. So AB plus C, A will come in common. A will come in common. So 1 plus B will be remaining. Here, from here you will get 1. From here you will get B. So 1 plus B. So A plus C is the answer. Let's solve this one. Reduce the following expression. So A bar plus B into A bar plus C. This can be replaced with A bar plus BC. Say yes or no? A bar plus BC bar, sorry. A bar plus BC bar. Did you understand this? A bar plus B. X plus Y into X plus Z is equals to X plus YZ. So this is what we are doing here. A bar plus B plus A bar into A bar plus C. So A bar plus BC bar plus A bar B bar plus A bar C bar. See the bar of B is present, and then in the multiplication there is C bar, here it is A bar. So A bar C bar is present, yes. So this term is redundant. So this term will be gone. So what we are left with? A bar plus BC bar plus A bar B bar. Now here A bar is coming in common. So A bar into 1 plus B bar. From here I will get B bar plus BC bar. So what I am getting? A bar plus BC bar. So A bar plus BC bar. That's the correct answer. A bar plus BC bar. Okay. So A bar plus BC bar plus A bar B bar is also, let's just say if this was also an option, then it would not be correct. Okay, because we need to write down the reduced expression. So reduced expression is this, A bar plus BC bar. That is the correct answer. Okay. Let's move to the next one. Reduced expression will have how many literals? How many literals will be there in the reduced expression? So first we need to reduce it. So y is equals to A into B plus C bar. Now you need to take bar. How will you take it? Simply by taking the dual. So if I take the dual of A plus B, it would be A plus B. Then individual bar I can take. Individual bar I will be taking. And here I will get, then plus will be replaced with dot, A bar plus C. Right? So A, B plus C bar. This will be replaced with A bar plus B bar C. Say yes or no? Right? A bar plus B bar C, because X plus Y into X plus Z, X plus YZ. So A bar plus B bar C. Are you getting this point? I just took the I need to take the complement. So how will I take the complement? By the concept of dual. So I will be taking the dual a plus b into a plus c bar. But I need to take individual bar. So a bar plus b bar, a bar into c. So a bar plus b bar c. So if I solve it here, a into b plus c bar into a bar, a into b plus c bar into a bar, right? Because c bar into c will be 0 only. C bar into c will be 0 only. Now a into b will be ab, a plus a bar will be 0. So this will be the final answer. So how many literals we are having? 2. So answer is 2. Okay, reduce the expression. C bar into c is 0. So this time I did not write. Now a into b is ab plus a into a bar is 0. So ab we are getting. So literals are 2, 1 and 2. This is 1, this is 2. 1 and 2, 2 literals are there. Reduce expression, reduce this one. So what we will get here? First reduce this one. So you need to take the complement. So how will you take the complement? You can go with the concept of a dual. So what will be the dual? A b bar c. Then individual bar we need to take. So a bar b c bar plus a into b into c bar plus a bar b c plus a b c. A bar b c, a b c bar, a bar b c bar. Okay. So what is coming in common? BC bar is coming common here. BC bar is coming common here. So it would be a plus a bar plus here what is coming? BC is coming common here. So it would be a plus a bar here again. So BC bar and a plus a bar is 1, a plus a bar is 1. BC bar plus BC. So B is coming common here and C plus C bar will be 1. So answer will be B. Very easy, very straightforward. Answer will be B. Let's solve this one. Which of the following gate is redundant? Which of the following gate is redundant? What do you mean by that? So first we will find out the output expression and then we will get to know that which gate is not useful here. So let's see it. Okay, let's see the problem. So what you will get here? A bar. What you will get here? B. What you will get here? A bar B. And what you will get here? Here you will get A bar. And what you are getting here? B bar C D. Here you are getting B bar C D. So what will be your final output F? That would be A bar plus A bar B plus B bar C D. So A bar plus A bar B. Can I replace this as A bar and I take A bar I am taking common. So 1 plus B will be replaced with 1 only. So A bar plus B bar C D. So in the final output this is coming and this is coming, but this is not coming. That means this gate is not useful at all. There was no use of this gate because A bar B has been gone. A bar B has been replaced with A bar only. So gate 2 is redundant gate. So in these kind of problems you need to see what is being reduced. This is being reduced. So this gate is not useful. So gate 2 is redundant. Okay. So this is the answer. Let's solve this question. PQ, RS bar, PQ, 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 PQ. What you are seeing here? PQ is coming in common. PQ is coming in common. So let's take PQ as common. So RS bar plus RST plus R bar S plus R bar S bar plus R bar ST plus RS plus R bar S bar T. Now look at these terms. RS bar, R bar S, R bar S bar plus RS. Do you remember something? PQ, what did I tell you? RS bar plus R bar S plus RS plus R bar S bar. What that would be? Rest of the terms are RST, R bar ST, RS. Do you remember the Venn diagram? What this was? A B bar. This was A bar B. This was A B. And what this was? A bar B bar. So all combined was what? I told you to remember this expression. A bar B plus A B bar plus AB plus A bar B bar, that is equals to 1. So what this will be equals to? This will be equals to 1. 1 plus anything. 1 plus anything will be 1 only. 1 plus anything will be 1 only. So this can be reduced to PQ only. That's it. This is the answer. 1 plus anything is 1. So this will be reduced to PQ. So this will be used again and again. That A bar B plus A B bar plus AB plus A bar B bar is 1. Okay. Now there are 100 XOR gates. So X plus 1 XOR, this will be X bar. X bar plus 1. Oh, wait a minute. Okay. This is X bar plus X. X bar plus X will be 1. Then 1 plus X, again X bar. Then again X bar plus 1. X bar plus X, sorry. Basically, what is happening? X XOR 1 is X bar. X bar XOR X will be 1. 1 XOR X will be X bar. X bar XOR X will again be 1. So after every even XOR gate you are getting 1. So after 100 what you will get? 1 only. So this is the answer. Are you getting this point? X XOR 1 is X bar. X bar XOR X is 1. 1 XOR X is X bar. X bar XOR X will be 1. Again it will keep on going. So after every even gate you are getting 1. So this is also even. So after this even gate also you will get 1 only. So that is the answer. Okay. Let's see this question. This is also very interesting one. A bulb in staircase has 2 switches. One switch being at the ground floor, another switch being at the first floor. So this is the scene that staircase is there. Okay. So once this is switch 1 and this is switch 2 and bulb is somewhere in between. This is your bulb. Now what they are saying, the bulb can be turned on or turned off by the bulb can be turned on and also can be turned off by and of the switches irrespective, and will not come by one of the switches, by and will not come by one of the switches irrespective of the state of the another switch. The bulb can be turned on or turned off by one of the switches irrespective of the state of the another switch. The logic switching of the bulb resembles as which gate? AND gate, OR gate, NOR gate or XOR gate. So if you are not able to solve this particular problem, then no issue, we will solve it now. So let's understand the meaning of this. So let's just say you are standing here. Now you are going up. So this is the case 1 where I am going up. So if I am going up and I am writing down the condition of switch S1 and S2. S1 and S2 and the respective output that I need. So if I am going up, what I will do? I will turn on the switch S1 because I need light, because I need to go up. So I need to turn on the bulb, right? I need to turn on the bulb. So I will click. Initially what is the scene? S1 is off, S2 is off, both are off. Then bulb is also off. Now I am going up. So I will click on S1. That means I will turn on switch S1. So if I turn on switch S1, S2 is off only. Still bulb should turn on, right? Initially S1 and S2 were off. Now I need to, S1 S2 were off, bulb is also off. Now I need to go up. If I need to go up, then what I will do? I need to turn on the switch. Here there is a switch. I will turn it on. If I turn it on, that means bulb should lit. Bulb should give me light. So bulb should give me light. S2 is off only. Now I am walking here. I walk and I walk here. Now I have reached here. So now I don't need light. So I need to turn off this bulb. So what is the condition of S1 now? Condition of S1 is this, because it has been turned on. When you were going up, you turned it on. So switch S1 is already on. Now what I will do? I will click switch S2. I will click switch S2. That means I am actually turning it on. But what I want as my output, that my bulb should turn off. So this is what I want my output. Are you getting this point or not? Initially, I was on the ground floor. This is the ground floor and this is the first floor. I want to go up. In the staircase, there is in between there is a bulb. This is S1, this is S2. Okay. If I want to go, initially S1, S2 both are off, so bulb is also off. Now if I want to go up, that means I need to turn on the S1 switch. If I turn on the S1 switch, S2 is already off. So bulb should lit. So bulb is lit and it is giving me 1 as output. That means bulb is lit now. So 1 is on. Basically I am taking 1 as on and 0 as off. This is what I am taking. So bulb is lit now. Now I am going up. So S1 has already been on. Now I have reached here. Now I have reached here. Now if I have reached here, I do not need the light. I do not need the bulb. So I will turn it off. That means this is already on. This one is already there. Now I will click on this again. I will click on 1 again. So 1 and 1 should give me 0. That means bulb should be off now because I have reached here. Now there could be other case as well. Let's just say I am coming down. The other case could be if you are coming down. So from the up side I am coming down now. So I am coming down now. So this is S2, this is S1. Bulb is somewhere here. So again I will make the truth table. So if I am coming down, so this condition is not related with this one. Independently I am taking it. Okay, independently. So independently I am taking it. So initially both switches are off. This condition is not related to this one. Independently I am taking it. Independently, that the guy need to come down. So initially both switches are off. Initially both switches are off. That means bulb is also off. Now I need to come down. That means I need to turn on this bulb. I need to turn on this bulb. So I will click on S1. Now I am coming down. Now I am coming down. Okay. So I am coming down now. So I will click on S1. So I need my output to be 1. I need the bulb to turn on and S2 is already off. Now I have reached here. I have reached here. So I do not need bulb now because I have reached to the downstairs. I have reached on the ground floor. I do not need bulb to be on. So now I will click on S1. I will click on S1 and I want my bulb to be off. I want my bulb to be off. So no matter what was there on S2, when I have reached here, I want my bulb to be off. So I will just simply click on S1. I will just click on S1 and my bulb will be off. So these two truth table I am getting. 0, 0 is giving me 0. 1, 0 is giving me 1. 0, 1 is giving me 1 and 1, 1 is giving me 0. So based on that, what did I get? The complete truth table. What I am getting? In the complete truth table, what I am getting? 0, 0 is giving me 0. 0, 1 is giving me 1. 1, 0 is giving me 1. And 1, 1 is giving me 0. So which gate is that? XOR gate. Which gate is that? XOR gate. So there is another name of XOR gate. So XOR gate is known as switching gate as well. Okay. Or what we call it? Non-equivalence detector. This we have already seen, right? Non-equivalence detector. No, not switching it, sorry. Staircase switch. This is known as staircase switch. Sorry. XOR gate is known as staircase switch. Because in staircase we got to know that in staircase we use XOR gate. So it is known as staircase switch. Staircase switch. Non-equivalence detector. What was the other name? Odd number of ones detector. Odd number of ones detector. So these are the names of XOR gate. Okay. So you can remember this. So did you understand this question? This was a very good question. Going up and going down, two different conditions we took. You can, first I went up and then I came down. You can take the condition that first you come down, then you go up. Both independently we took, and we got to know that this is the truth table we are getting. So based on that, we got to know that it is a XOR gate. Shall I explain it again? Quickly, I will explain it. S1 both were off. Okay, so my bulb was off. I need to turn on the bulb now. So S1 I turned on. So bulb should turn on. So 1 0 should give me 1. Now I have reached S2. So I do not need bulb to be turned on. So I will click on 1. So 1 1 should give me 0. So that's it. Now I am coming down. So coming down, both bulbs are off only. If both bulbs are off only, so y should be 0. If I am coming down, that means I need the bulb to be turned on. So I will click on S1. So I will click S1, then S1 will be, if I click, sorry, I will click S2. So if I click on S2, then bulb should lit. So if bulb lits, then I am coming down, and then if I have reached to the downstairs, then I will click on S1 again to turn off the bulb. So this is the truth table I am getting. Okay, so this is the XOR gate. Okay, let's move towards the next question. What is the output? Very easy question. AB bar we are getting here. This is AB bar, and what this would be? This is B, and what is this? C. Here what you will get? AB bar into B. So what is your output? Y is AB bar. AB bar can be sold as A bar plus B bar into B, and then into C, and then whole bar. Okay, this is AB bar into B into C and then whole bar. So what I am getting here? A bar B C whole bar, right? So this is one of the option. Since this is MSQ, so A plus B bar plus C bar. This is also one of the option. Just I sold the bar. Okay, so A bar plus B bar plus C bar. So this is also one of the option. Very easy problem, very straightforward. What about this one? So you can solve it by any method, but what I will tell you. Look, what this would be? A XOR B bar and then another bar. So this bar and this bar will get cancelled, no? A XOR B bar and then another bar. A XOR B bar and then another bar. So what this would be? A XOR B. And what about this? This will also be A XOR B. Right? Now if I say A XOR B is Y, so what I will get here? Y XOR Y bar and then another bar. So what I will get? Y XOR Y only. And what is the value of Y XOR Y? 0. So what will be your output? Output will be 0 only. Basically the scene here is A XOR B XOR A XOR B bar and then whole bar. So one bar can be taken as whole bar only. So answer would be A XOR B XOR A XOR B. A XOR B XOR A XOR B is 0. So this is the correct answer. Okay, very easy problem. Which input combination will make Y equals to 1? So you can do it on your own. Y equals to 1 you need. So at least C has to be 1. Because if C is 0, then whole expression will be 0. So C has to be 1. Now, if this needs to be 1, so both A and B cannot be same. If both A and B are same, then it is gone. So this is gone, this is gone. This could be one of the chance. So 1 0 is 1. What would be 0 x nor 1? That would be 0. So this is also 1. Right? What about this one? 0 XOR 1 will be 1. 1 x nor 1 will be 1 only into 1. So 1 into 1 into 1. So this is the correct answer. Okay. Very easy problem. Very straightforward. So answer is D. This question. So I told you in feedback they will not mention anything. The shown NAND gate has a finite non-zero delay TD. The circuit will act as what? I told you one thing, they will not give you anything, like they will not give you any input. So you have to assume that because of some noise, let's just say here 0 input came. If 0 input came, then 1 into 0 is 0. So 1 into 0 is 0. 0 bar will be 1. So this 1 will travel here again. So this 0 will go to 1. Then 1 into 1 will be 1. And 1 bar will be 0. So this will go to 0. Now this 0 will travel here again. So 0 will come. 1 into 0 is 0. 0 bar is 1. So this will again become 1. So 1 will again go here. So what is this? This is being a stable multivibrator only. Right? This is a inverter. This is acting as an inverter only. 1, this is fixed. Let's just say this input is A. So A into 1, that is A bar only, no? So this is acting as an inverter. So one simple inverter is there. Basically, one simple inverter is there. 0, 1, 0. Basically, one simple inverter is there and output is fed back to the input. So this circuit is acting as a stable multivibrator. Okay, this is acting as a stable multivibrator, and they will not say that first I break the loop and I apply the input, then I again make the loop. Nothing like that. They will not give that. You have to assume that there will be some input. You could have assumed 1 as well. So here you will have 0, then 0 would come, again 1 would come, 1 again 0 would come, then again 1 would come. So it will keep on going. So this is a stable multivibrator. Okay, so answer is A. Let's move to the next one. B bar C plus AB plus, let's see this, what this is equals to. B bar C plus AB plus AC bar. So can we apply consensus theorem? 2 bar are there, no? C bar is there, CC bar, 2 bar is there. 2 bar are there, so we cannot apply consensus theorem here. Because CC bar is also present and BB bar is also present. So we cannot apply consensus theorem here. So what we can do? So B bar C plus, I can take A as common. So this would be B plus C bar. Say yes or no. So it would be B bar C plus A. Can I write this as B bar C bar? B bar C bar, right? B bar C bar. That would be B plus C bar. So basically, if this is X plus A X bar, what that would be? X plus A. X plus X bar A. So X plus A. What is X? B bar C plus A. B bar C plus A. Or this can be written as basically B bar C plus A, or you can say A plus B bar C. So this can be written as A plus B bar into A plus C. So A plus B bar into A plus C. This is the correct answer. So this was a very good question. You need to think here. B plus C bar, then I can write this as B bar C bar. So that would be X plus X bar A. So this could come X plus A. So A is A only, X is B bar C. So A plus B bar into A plus C. So answer is B option. Okay. So these kind of things you need to think. Let's solve this question. So first I will tell you how you can do it wrong. So A XOR A bar plus B. So if you are solving in this manner, A XOR A bar plus A XOR B. So what this would become? 1. Right? A XOR A bar would become 1. 1 plus A XOR B. 1 in addition to anything will be 1 only. So this is wrong. I told you one thing. This cannot happen. I told you this. A XOR B plus C is not equals to A XOR B plus A XOR C. I told you this thing, right? If you remember it. So this is wrong. So how we will solve it? By simple method we need to solve it. So A XOR A bar plus B. So that would be A as it is, bar of the second one. What that would be? AB bar. Bar of this. Bar of A bar plus B. What will be the bar of this? AB bar. Plus second as it is, bar of the first one. So AB bar plus A bar plus A bar B. Right? A bar plus A bar B. So from here we are getting A bar only. So A bar plus AB bar. So that would be equals to A bar plus B bar. And that would be equals to AB bar. Okay. So answer is C. Answer is C. Okay. So this A bar plus A bar B, A bar I took common. So this is reduced to A bar only. So A bar plus AB bar. So that would be A bar plus B bar. And that can be written as AB whole bar. So answer is C. Now see the next question. Assuming that variables and their complements are available. Variable and their complements are available. Then the minimum number of 2 input NOR gate needed to implement 2 input XOR gate. 2 input XOR gate. and 2 input NOR gate required. So what is the expression of XOR gate? A bar B plus AB bar, but you require NOR gate. So for NOR gate you don't need that. What you need? For NOR gate you need product of some form, product of a sum. So A bar plus B bar into A plus B. Now what they are saying, variables and their complements are available. That means A, B, A bar, B bar, all these are available. If all these are available, then how much it will require? So this is simply like C plus D into A plus B. So how much this requires? 3. So answer is 3. A plus B into C plus D, we have seen it, right? A plus B into C plus D. How will you implement using XOR gate? So how will you implement this using NOR gate? So how much did we required? 3. Do you remember this? We required only 3. So answer will be 3 here. A plus B into C plus D. If you clearly remember, A plus B, C plus D, and then it goes here. Then I put 1 bar here, 1 bar here, 1 bar here, 1 bar here. So this is 1, 2, and 3. So answer would be 3. Okay. So by this as well you can do in examination that you will require 3 only. So answer is 3. Let's see this question. What possible combination of A, B, C to turn on the LED? So to turn on the LED you need high output here. You need high output here, right? Because this N side, this is a simple diode. Do you know the working of diode? Basically I will tell you. If this is high and this is low, then this LED will turn on. And if high low, I should have written, not positive negative. And if this is low and this is high, then it would be off. Both are high, then also it would be off. Then also it would be off. And if both are low, then also it would be off. So only condition to turn it on is we need 1 here. Our target is to get 1 here. That's it. So how we will get 1? To get 1 here, let's check. A is equals to 0, B is equals to 0. So this will be 0. If A is 0, B is 0. So this will be 0. If this is 0, then certainly this is 1. So this will work. If A is 1, B is to turn on the LED, right? Yeah, okay. If A is 1 and B is 0, then this will be 0. And if this is 0, this is certainly 1. So this will also work. If A is 1 and B is 1, then this will be 1. And if B is 1 and C is 0, so this will be also 1. So 1, 1, 0. This will be 0 now. Now this will not work. And this should be MSQ. And if A is 1 and B is 1 and C is also 1, so this will be 1, 1, 1, 1 would also be here 0. So this will also not work. Okay, let's check back again. Let's check back again. So A is 0, B is 0, so this will be 0. If this is 0, then certainly this will be 1. So there is no doubt LED will turn on, right? If B is 0, then certainly this is 0. So there is no doubt. A is 1, B is 1, so this will be 1. 1, 0, this will also be 1. 1, 1 is 1, this will be 0. So not turn on. A is 1, B is 1, C is 1. So 1, 1, 1, this would be 0. It will not turn on. Okay. So only 2 options are correct, A and B. Easy question, very straightforward. Let's see this question. If A XOR B is equals to C, then B XOR C is equals to what? So what we need to find? B bar XOR C. That can be replaced with B bar XOR C whole bar. And if A XOR B is equals to C, then I told you one thing, that B XOR C will be equals to A. So B XOR C will be equals to A. So that will be equals to A bar. Very easy, right? Now what this will be equals to? A bar XOR B. A bar XOR B. So this bar can be taken as whole bar, right? 1 bar can be taken as whole bar, and then another bar is there, XOR C bar. So this can be replaced as A XOR B, C bar. So this bar is there, so this can be taken as whole bar. So this can be taken as y XOR C bar, y XNOR C bar. So that can be replaced as y XOR C. So y XOR C can be replaced as A XOR B XOR C, and then there is whole bar. Then there is this whole bar. So if there is this whole bar, this is very interesting. Now, is this correct option? No, this is not correct option, because I told you for three variables A XOR B XOR C is equals to A XNOR B XNOR C. So this is not correct. Okay. So now what we can do? So this is the final answer we are having. Basically, another bar was there, right? Another bar was there. This another bar was there. So this bar is coming here. Are you getting this point? Basically, this bar and bar was gone. So A XOR B I am left with. XNOR C, and then there was bar. So another bar I took. So A XOR B I am taking as Y. So Y XNOR C bar. That would be Y XNOR C bar. So basically, this is Y XNOR C only. Y XNOR C only. This can be replaced with Y XNOR C as well, or I can replace it with Y XOR C bar. Y XOR C bar. So so basically A XOR B XOR C bar is there. Now I can take bar on any of the variable, right? On any of the variable, I can take bar something like this, because that can be whole bar as well, right? Are you agreeing to my point? I can take bar on any of the variable. Or what I could have done, I could have taken bar like this as well, A XOR B. So I am taking bar on this only, XOR C, because whole bar will be there. Basically, if A XOR B this is there, then I can take A XOR B whole bar. So if whole bar is there, then I can take bar on one variable as well. So this is what I am doing. Now what this will be replaced with? A XNOR B XOR C. So this is the correct answer. Okay. Are you getting this point? So this way we need to solve. We need to match the option. Other possible answer would have been also there. What all possible answer are there? This could also be one of the answer. Or this could also be one of the answer. So other possible answers are there. This is also correct. This is also correct. This is also correct. So these kind of questions can come in MSQ. So smartly you need to solve. Are you getting this point? How I am solving it? Just take the bar and then you need to match the option that where I should take the other bar. So if whole bar is there, then you can take the bar on one variable. If bar is there on the one variable, then you can take the whole bar. Okay, so option C is correct. Now let's see this question. Very conceptual problem. Very conceptual problem. So and you need to have basic idea of RC circuit. Okay, I am assuming you have studied network analysis, basic idea of RC circuit. So here only I will ask you, if this is R, this is C, and 5 volt is there, then what will happen? This capacitor will charge, right? And let's just say my capacitor has been charged to 5 volt. My capacitor has been charged to 5 volt, and now this node is grounded. This is your R, this is your C. So what will happen? The capacitor will discharge. So this much of transient you need to know. That's it. 5 volt is there, 5 volt will charge the capacitor. If 5 volt R is there, then there is no battery, so 5 volt will be discharging. This much of transient you need to know. That's it. Okay, let's solve this problem now. What they are saying, the inverters are driven off a supply of 2 volt. So we studied about inverter in last videos. In second last video, I guess, we studied about inverter. How will we actually make these inverters? From the CMOS. From the MOS we will make these inverters. Basically, we will connect our MOS in this manner. So this is how we will make the inverter. When we study logic family, I will tell you how do you make AND gate, OR gate, NOR gate, NOT gate, all kind of gates we will make with the help of these IC, not IC, with the help of semiconductors or with the help of MOSFETs or with the help of BJTs. With the help of these devices, we will make all the inverters. So to run these devices, we need a supply. This supply we need. So this supply is 2 volt. So this is running at 2 volt, and another supply they did not mention. Basically 2 volt, and then there would be ground. There could be negative supply as well. If this is VDD, there could be minus VDD as well. So other supply will also be there. One is VDD, other supply could be ground or anything. So if they haven't mentioned, I will assume the other supply is ground. Now what they are saying, and their threshold are at mid supply. Threshold are at mid supply. Let's just say this is V in and this is V naught. Threshold are at mid supply. That means threshold is 1 volt. Mid supply means 2 by 2. That means 1 volt. So what do you mean by that? This is an inverter. If your V in is greater than 1 volt, if your V in is here, if your V in is greater than 1 volt, then it will give output to 0 volt. Then it will give output to 0 volt. Why 0 volt? If V in is greater than 1, output will be 0, because for higher value, inverter will give lower output. Basically, what does it mean? That if your V in is greater than 1 volt, then your inverter will assume it to be high value. And if your V in is less than 1 volt, if your V in is less than 1 volt, if your V in is less than 1 volt, then your inverter will assume it to be low value. So it will give you high output. And what is your high output? High output is 2 volt. High output is 2 volt. So this is the threshold. This is the threshold. This is threshold. So threshold of inverter is 1 volt. If your input is greater than 1 volt, that means it will assume it to be high value and it will give your output to be 0 volt. And if your input is less than 1 volt, then your inverter will assume it to be a low value and will give output as 2 volt. Are you getting this point or not? So if my V in is greater than 1 volt, my output will be 0 volt. And if my V in is less than 1 volt, then my output will be 2 volt. So that's the thing. Now what is happening in this circuit? You are applying the input at t equals to 0. At t equals to 0, you are applying the input. But for t less than 0, there was no input, right? So let's make the circuit for t less than 0. I will just copy this circuit. I will copy the circuit as it is. And I will tell you how it will look like for t less than 0. So for t less than 0, what was happening? This input was not there, right? This input was not there. This was shorted. This input was not there. This capacitor was having 0 voltage. This capacitor was having 0 voltage because capacitor was uncharged. So capacitor was having 0 voltage. So if capacitor was having 0 voltage, so 0 voltage was here. So if V in is less than 1 volt, that means here what you will get 2 volt. Now because of this 2 volt, this would have been charged. This capacitor would have been charged, and capacitor would have been charged to 2 volt. And if V in is greater than 2 volt, that means output would have been at 0 volt. So this is the scene for t less than 0. Are you getting this point or not? For t less than 0, this capacitor is having 0 voltage. Since this capacitor was having 0 voltage, so this inverter, at the input of the inverter, you are having 0 voltage. So this will give as output at 2 volt. If this is giving output at 2 volt, that means this will charge to 2 volt. And if here you are having 2 volt, that means this inverter will give output as 0 volt. So this was happening at for t less than 0. Now for t greater than 0, what will be the scene? For t greater than 0, what you have done? You have applied some input now for t greater than 0. You have applied some input and this has been charged. This is already charged to 2 volt. This was charged to 0 volt only. Now what they are asking? At what point of time V0 goes to VDD? VDD means, here I should have mentioned, VDD means 2 volt. VDD is equals to 2 volt. So at what point of time V0 T goes to 2 volt? So you need this output to go to 2 volt. Tell me when it will go to 2 volt. At what point it will go to 2 volt? Let's just say this potential I am calling as Vx. When Vx goes down to 1 volt, when Vx goes down to 1 volt, at that time your VDD will go to 2 volt. Say yes or no. Basically, when Vx goes down to 1 volt, or you can say 0.9999999 volt, at that time V0 goes to 2 volt, right? Because I told you if V goes below 1 volt, V0 goes to 2 volt. So this is our target. Our target is to find when this will discharge to 2 volt. That's it. Now for it to discharge, for this capacitor to discharge, what is the voltage you require here? You require voltage here to be 0 volt. For this capacitor to discharge, you require here voltage to be 0 volt, right? And when you will get 0 volt here? When this is charged above 1 volt. Say yes or no. So you want this cap to charge to 1 volt. You want this cap to charge to 1 volt, and if it is charged to 1 volt, then it will go to 0. 1 means basically 1.000000001. If it is charged to this much of potential, then it will go to 0, and if it is goes to 0, then it will start discharging. Say yes or no. So this is the scene. So first we will charge this capacitor. This capacitor will charge. So what is the charging equation? Do you remember? Do you know that? So charging equation is 4 into 1 minus e to the power t by 2, and tau is RC. RC is 1 second. So now we want it to charge to 1 volt. So how much time it will take? ln 4 by 3. ln 4 by 3 second. So at ln 4 by 3 second, this will be charged to 1 volt. ln 4 by 3 second, this will be charged to 1 volt. And if this is charged to 1 volt, that means this will go to 0. Now this will start discharging. So what is the discharging equation? That is 2 into e to the power minus t by tau. Tau is 1. And we want it to discharge to 1 volt. Right? We want it to discharge to 0.99 volt or 1 volt. So how much time it will take? This time is t1, this time is t2. So how much time it will take? ln 2 time. So what is the total time? So at ln 4 by 3 plus ln 2, after this much of time, this would have been discharged to 1 volt, and this would have gone to VDD. So this time is 4 by 3, ln 4 by 3 plus ln 2. So 4 by 3 plus into 2. So that would be ln 8 by 3. So this is our answer, ln 8 by 3. So at ln 8 by 3 time, this would have gone to 2 volt. Are you able to understand this point or not? I will again explain it. Okay, very good question. Capacitor is initially having, here it is having 0 voltage, so this will be at 2 volt. This is at 2 volt, so capacitor would have been charged to 2 volt. If this is 2 volt, V0 would have been 0, right? Now at t, for t greater than 0, you have applied an input. What input you have applied? 4 volt. Okay, so 4 volt you have applied. Now this capacitor can charge now, right? But what we want our output to go to 2 volt. That means we want this to decrease to 0.99 volt. Basically we want this potential, Vx potential, to decrease. When it will decrease? When you are having 0 volt here. When you will have 0 volt here? When this is charged to 1 volt. So our first target is to charge this to 1 volt. So how this will charge to 1 volt? So 4 into 1 minus e to the power minus t by tau. So in ln 4 by 3 second, it will be charged to 1 volt. Okay. Now if it is charged to 1 volt, that means it is going towards 0 now. So this has gone to 0. Now this will discharge. So this will discharge to 1 volt. How this will discharge to 1 volt? 2 into e to the power minus t by tau. So to 1 volt it will discharge. So how much time it will take? ln 2 second it will take. So in ln 4 by 3 second, this is charged to 1 volt, and then in next ln 2 second, this has been discharged to 1 volt. So if this has been discharged to 1 volt or less than 1 volt, then Vout will go to 2 volt. So this is what we wanted. So ln 4 by 3 plus ln 2, answer would be ln 8 by 3 seconds. So this was a very good question. Okay, I hope you must have understood it. Now let's see this question. Which of the statement is true? What do you think? What kind of circuit is that? Astable multivibrator, monostable multivibrator. What kind of circuit is that? This is an MSQ. So what will happen? Initially, capacitor is having 0 voltage. Initially, this is having 0 voltage. So this 0 voltage will come here. If 0 voltage is there, then this will be 5 volt. So if 5 volt is there, then this capacitor will charge. So capacitor will first charge. Okay. Then if capacitor is first charging, capacitor will first charge. So let's just say, like, I don't know the supply, I am assuming supply to be 5 volt. So capacitor is charged and capacitor will charge to 5 volt. Now what will happen? This 5 volt will come here. This 5 volt will come here, and inverter is there, so this will go to 0. Now this is charged to 5 volt. Now this 5 volt will discharge. This 5 volt will discharge now. This 5 volt will discharge. So this has discharged. Now what will happen? Since this has discharged, so this will go to 0 volt. So this 0 volt will again come here. Since again there is an inverter, so 0 volt will be converted to 5 volt. Now again this capacitor will charge. So again this capacitor will charge. Then again discharge. Then again charge. So in this manner it will keep on going. Right? So this is what? This is a astable multivibrator. Just simply charging, discharging. There is no stable state. Plus, minus, plus, minus, plus, minus, plus, minus, it is going. There is no stable state. So this is astable multivibrator. So this circuit, monostable it is not. the bistable it is not. This circuit produces a periodic square wave if RC value is very low. So this also I should have mentioned. Basically, if RC value is very low, then there will be fast charging and fast discharging. What I mean to say, if RC value is very low, then this waveform will go something like this. Very fast charging will be there, and then very fast discharging will be there. So very fast charging will be there, very fast discharging will be there. So it is kind of a square waveform only. So it will produce a periodic square waveform if RC value is very low. So charging, discharging will be there. Okay. So first it will go to 0, then 5, then again 0, then this will go to 5, 0 and 5. So the capacitor will charge in the same manner, 5 volt, then this 5 volt will come here, then it will be 0, then this capacitor will be discharged. So this 0 will come here, this will go to 5 volt, 5 volt is here, the capacitor will charge, then 5 volt will go here, then this will be 0, so the capacitor will discharge to 0. So 0 to 5, 5 to 0, 0 to 5, 5 to 0. In that manner you will have a square wave, and this is a astable multivibrator because going up, coming down, going up, coming down. In that manner we are going. Okay, then I hope you must have understood. Okay, so yeah, that's it. That's the end of the assignment. I hope you must have enjoyed the level of the problems. So we are solving good amount of problems and good level of problems as well. Let's meet you in the next lecture. Hi everyone. So in this video we are going to study about representation of Boolean function. So you need to watch this video with full amount of patience. In the end everything will be connected. Here we will study the small dots, we will study the small topics, and in the end everything will be connected and you will feel very good. So you need to study the video with the patience. Okay. So let's start with the basics of number system. Here we are not going to cover the number system. Number system is a separate chapter that we are going to study after this particular chapter. So now we just need to study the basics of number system. So which is the basic number system we use in mathematics? That is decimal number system, right? Decimal number system we use. What do you mean by decimal number system? Decimal means 10. So there will be base 10. What do you mean by base 10? That there can be 10 numbers. So in decimal number system there are 10 numbers which are 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. So these 10 numbers are there, 0 to 9, and using these numbers only, using these digits only we frame any other number. Let's just say 729 is there. So this has been framed with 7, 2 and 9. So there are total 10 digits. That's why it is known as decimal number system. Now 729. What is the place value of 7 here? Place value. Tell me the place value of 9. Place value of 9 is 10 to the power 0. Say yes or no. What is the place value of 2? Place value of 2 is 10 to the power 1. And what is the place value of 7? The place value of 7 is 10 to the power 2. So which has the maximum place value? This has the place value of 100. That means this is known as most significant digit, I should say, not bit. Okay, most significant digit. So MSD I can write and LSD I can write here. MSD and LSD. Okay, this is Mahendra Singh Dhoni and this is some drug. So this is, and what is this? This is least significant bit. LSD, least significant digit, not bit. Generally we use the term MSB and LSB because this has the place value of 10 to the power 0. So this is least significant bit and digit, not bit. Okay. Similarly, what our digital system understand? Binary, right? Our digital system can understand only 2 bits. So this is known as binary number system where there are only 2 bits. Where there is the base 2. Base 2 means there can be only 2 digits, that is 0 and 1, and these 2 digits are known as bits. So we can frame any other number using 0 and 1 only. So look at this number. This number is framed with 0 and 1 only. Now tell me what is the place value of this 0? That is 2 to the power 0. Here it was base 10. So it has 10 to the power 0, place value of 10 to the power 0, it has place value of 10 to the power 1, and it has the place value of 10 to the power 2. But here the base is 2. So 0 has the place value of 2 to the power 0, 1 has the place value of 2 to the power 1, and another one has the place value of 2 to the power 2. 2 to the power 0, 2 to the power 1 and 2 to the power 2. So which one will be most significant bit? This would be known as your MSB, most significant bit, and this is known as LSB, least significant bit. Okay, MSB, LSB, most significant bit, least significant bit. So this has the place value of 4, this has the place value of 1, this has the place value of 0. Let's take more example. 110 already there, so let's take 101. 101, 101. So 1 into 2 to the power 2 plus 0 into 2 to the power 0 plus 1, sorry, 0 into 2 to the power 1 plus 0 into 2 to the power 1 plus 1 into 2 to the power 0. So I can write this as 4 plus 0 plus 1. So 1 plus 0 plus 4. So that would be 5. What about this one? 1 into 2 to the power 2, 1 into 2 to the power 1 plus 1 into 2 to the power 0. So this can be written as 1 plus 2 plus 4, 7. What about this one? This has the place value of 1. 2 to the power 0 is 1. This has the place value of 2. This has the place value of 4. And this has the place value of 8. 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3. So 1 into 2 to the power 3 plus 1 into 2 to the power 2 plus 0 into 2 to the power 1 plus 1 into 2 to the power 0. So that is 8 plus 4 plus 0 plus 1, and that is equals to 13. What about this one? 1, 2, 4, 8, 16 and 32. So this number would be 32 plus 16 plus 8 plus 4 into 0 would be 0 only, 2 into 0 would be 0 only, plus 1. So this number can be written as 24 plus 1, that would be 25. 32 plus 25, that would be 57. So this number can be written as 57. So basically it goes in this manner. This initial bit has the place value of 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, and this bit will have the place value of 2 to the power n minus 1. Now let's talk about two variables. Two variables, and here by D I mean decimal. Okay, by D I means decimal. And if I am talking about two variables, then I am considering this as MSB and this as LSB. This is what I am considering. B2, B1 I have written, that means B2 is my LSB, B2 is my MSB and B1 is my LSB. Here also I have considered this as to be my MSB and this as to be my LSB. Right? This is the least significant bit and this is the most significant bit. So 0, 0, 0, 0. What is that? 0 into 2 to the power 0 plus 0 into 2 to the power 1. So that would be equals to 0. So in decimal it would be 0 only. 0, 1. This is your most significant bit. So 0 into 2 to the power 1 plus 1 into 2 to the power 0. So that would be 1 only. Or directly you can write, here you will write 1, here you will write 2. So this would be 1. 1, 0. Here you will write 1, here you will write 2. 2 into 1 would be 2 only. Or you can say 1 into 2 to the power 1 plus 0 into 2 to the power 0. So that would be 2. So this represents 2. And what 1, 1 will represent? What 1, 1 will represent? This is 1 and this would be 2. So 1 plus 2. Or you should write 2 plus 1. 2 plus 1, that would be 3. So this would represent 3 in decimal. Let's go to 3 bits. What this would represent? 1. What this would represent? Basically this is 1, this has base, this has the place value of 2 and this has the place value of 4, 2 to the power 2, that is equals to 4. So this would represent 1, 1 into 1, 1. This would represent 2, this would represent 2 plus 1, 3. This would represent 4, this would represent 4 plus 1, 5. This would represent 4 plus 2, 6, and this would represent 4 plus 2 plus 1, 7. Let's go here. This would represent 0, 1 because it has the place value of 1, 2, 4 and 8. So this would represent 2, this would represent 3, this would represent 4. In the same manner we can proceed. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 and 15. So in that manner. So if we had 4 variables, so using 4 bits, 4 variables means using 4 bit we could get a decimal number from 0 to 15. So if there are n variables, so in decimal how much can you get? Just a simple question or just a simple fact I am asking, because it will be used later on when we study ADC and DACs. So if there are n variables, so in decimal I will be getting 2 to the power n minus 1. This is the maximum number that I can get. If I have 4 bits, then the maximum number I am getting, that is 15. If I have 3 bits, then the maximum number I am getting, that is 7. If I have 2 bits, then the maximum number I am getting, that is 3. So this is the maximum decimal number. Maximum decimal possible. Right? Now, I will be using these two terms again and again. First one is product term, second one is sum term. What do you mean by product term? Product term means it is the product of literals. A into B, A bar into B, A into B bar, A B C, A B bar C. Okay, it could be A B C D as well. Or A B bar, C bar, D, anything it would be. Just the product. And what do you mean by sum term? Sum term means sum of the literals. So this is the sum, A plus B, A bar B, or it could be A plus B plus C bar D, or it could be anything. So this is known as sum term. So these two terms I will be using again and again, product term and sum term. So you should know the meaning of product term and sum term. Okay, just for the introduction I have written here. Let's study about Minterm and Maxterm now. This is the most important part of this particular chapter. What do you mean by Minterm and what do you mean by Maxterm? So here I will tell these points and nothing will click to you. What is a Minterm? Minterm is a logical AND operation. Simply, one simple definition is Minterm is a logical AND operation including all the variables, where variables can be itself or in complemented form. And output of Minterm function is 1. For now you just can see this, okay? You just can see these points. Later on you will understand what we are doing actually, okay? Just connect the small dots and you will understand everything in the end of the particular topic, okay? So output of Minterm is 1 and Minterm is denoted by small m, and 1 is the normal form and 0 is the complemented form in Minterms. You are not understanding any point, I know that, but still you can just remember these points. Now let's go to this particular table. So A and B, these two variables can have these many bits, 0 0 0 1 1 0 or 1 1, and this is the decimal. This is the decimal form of that. Now in Minterm, what did I tell? 0 is the complemented form and 0 is the complemented form and 1 is the normal form. 0 is the complemented form and 1 is the normal form, okay? And what did I say? It is logical AND operation. So 0 is the complemented form. So Minterm for this would be A bar B bar, because 0 is the complemented form. Minterm for this would be A is 0, so A bar, and B is 1, so B, and in between there is multiplication. Minterm for this would be A into B bar, and Minterm for this would be A into B. This can be represented in this manner. Since this is a decimal 0, so it can be represented as small m 0. This can be represented as small m1, this as small l2, and this can be represented as small m3. What we are doing, why we are doing so, you are not understanding, but we will understand that. This point is not coming, that the output of Minterm is 1. You did not understand this point. We used this point, we used this point, we have used these 3 points. It is logical OR operation, sorry, it is logical AND operation. Minterm is logical AND operation. 0 is the normal, 1 is the normal form and 0 is the complemented form, and Minterm is represented by small m. Can you write down the Minterm for this particular expression? When D is 0, that means 0 0 0. So Minterm would be A bar B bar C bar. Here Minterm would be A bar B bar C. Here it would be A bar B C bar. Here it would be A bar B C. Here it would be A B bar C bar. Here it would be A B bar C. This would be A B C bar, and this would be A B C. Right? A bar B C bar, A bar B bar C. What could be the expression of this? Represented by small m and decimal number is 0. This could be represented by M1. This could be represented by M2, M3, M4. You are not understanding why we are doing so, but you will understand slowly. Okay, no need to worry. Now there is a question, that is this expression for minterm you need to find. So first thing what you will see, whether it is in the product form or not. We need to see the product terms. So it is in the product form, right? It is in the product form. So what is the given expression? That is W bar X Y Z bar. Now here they did not mention which is your MSB and which is your LSB. So you will consider this as MSB and this as LSB. If nothing is mentioned, then the function will be mentioned like this. So this you need to consider as MSB and this you need to consider as LSB. So if W bar is there, that means it would have been 0. If X directly is coming, that means it would have been 1. Y directly is coming, that means it would have been 1. And Z bar is there, that means it would have been 0. So what will be the place value? This will have the place value of 2. This will have the place value of 4. This will have the place value of 1, 2, 4, 8. So 4 plus 2, that is equals to 6. So your minterm would be M6. This is your minterm. Your minterm would be M6. This is your minterm. So if there are n variables, so how many minterms would be there? If there were 2 variables, there were 4 minterms. If there were 3 variables, there were 8 minterms. You can see these are 8, total 8 minterms. Total 8 minterms. You will understand completely why we are doing so, but in few minutes only. Okay, total 4 minterms. So if there are n variables, that means how many minterms would be there? 2 to the power n minterms, right? 2 to the power n minterms. Now let's see a question and you will understand why we were doing so. So truth table for a digital system is given as follows. Okay, you need to find the output y. Now tell me one thing. A is 0 and B is 0. If I need to write it in terms of minterms, then how I will write? A bar, B bar. If I need to write it in terms of V0. Don't look at the output, only see A and B. This would be A bar, B bar. What this would be? A bar, B. What this would be? A, B bar. And what this would be? A, B. Right? So how you can write the output Y? That would be written as the minterm, that is A bar, B bar. Into everything will be in multiplication. A bar, B bar, output is 1 into 1 plus A bar, B, output is 0 plus A, B bar, output is 1 plus A, B, output is 0. So multiply, anything multiplied with 0 will be 0, anything multiplied with 0 will be 0, anything multiplied with 1 will be the same, anything multiplied with 1 will be the same. So this is how you can write your output. This would be your output. And here you can take B bar as common. So A bar plus A. So A bar plus A will be A only. So here you can see your output is B bar. And complement of B only you are getting as output. You see what will be B bar? 0 will be 1, 1 will be 0, 0 will be 1 and 1 will be 0. So you can see this is how we can write our output. So when I said that output of minterm is 1, that means when we are talking about minterms only you need to look at 1 only. So A bar, B bar plus A, B bar, that's it, this is my output. Do you remember the truth table for AND gate? This was the truth table for AND gate, right? 0, 0, 1, 1, 0, 1, 0, 1, 0, 0, 0, 1. You need to look at only here. So what will be the minterm for this? That would be A into B. So what will be your output? A into B into 1. That's it. This is your output. Are you getting this point? Do you remember the truth table of XOR gate? XOR gate. It was 0, 1, 1, 0, right? You need to look at only one. So what is the minterm for this? A bar B. And what is the minterm for this? A B bar. So this was your, what was this? This was the output of XOR gate. Do you remember that? Right? You do remember that, right? So this was your XOR gate. So in that manner we can write down the output. So this is one way of writing. Okay. What could be the other way? Here what you can see. What is A bar B bar? What is A bar B bar? That is M0. What is this? This is M0, no? This is M0. This is M1. This is M2. This is M3. If only A B bar is given, you can tell what it will be. M what? What it would be? Because B bar, that means 0 and A means 1. So it would be 0 and 1. This has the place value of 1. This has the place value of 2. So it would be 2 only. So it would be M2. So directly A B bar is mentioned. That means you can write it would be M2. So similarly, what you can see? Your output is M0 plus this was your M1. M1 multiplied with 0 will be 0 only. M2 multiplied with 1 will be M2 only, plus M3 multiplied with 0 will be 0 only. So your output is M0 plus M2. So it is summation M of 1 and 2. In that manner also output can be written. Okay. So in this manner or in this manner output can be written. So summation M1 2. In that manner also output can be written. So it shows that it has the, for minterm 1 and 2 output is high. Sorry, 0 and 2. So really sorry, it is 0 and 2. Basically for decimal number 0 and 2, this was your decimal number 0. If I write this decimal, this was 0, this was 1, this was 2 and this was 3. So for decimal number 0 and 2, output is high. Okay, I hope you are understanding the meaning. Let's see more examples. Slowly you will understand more. Okay, let's see this example. How will you write down the output? I am writing the output in terms of minterms. So 1 1 1 here I will see. Okay, so what that would be? What would be your output Y? So for this one minterm would be A bar, B bar, C bar. For this what would be the minterm? A bar, B, C. For this what would be the minterm? A, B bar, C bar. And for this what would be the minterm? A, B, C. Right? Is there anything wrong? A bar, B bar, C bar, A bar, B, C, A bar, B, C, A, B bar, C bar and A, B, C. So how will I write my output? A bar, B bar, C bar into 1. So 1 I don't need to write. A bar, B, C plus A, B bar, C bar plus A, B, C. You can reduce it. You can reduce this expression, but this is not our target now. Our target is to just to write down this expression so that we have written. Right? This is our Y. Or how I can write my Y? Y can be written as summation of M 0. What is this? 3. Or directly if it is written A bar B C. So 0 1 1. So that would be 1 and 2. 3. A B bar C bar 1 0 0 1 2 4. That would be 4. And A B C that means 1 1 1. A B C 1 1 1. So that would be 7. 0 3 4 7. 0 3 4 7. Or directly I have written the number here 0 3 4 7. So in that manner you can see this is how we can write down our output. Let's see more example. Now here there is a term that I mentioned, concept of don't care. Let's see wherever you get output 1. Here, here and here and here. Let's write down the decimal number. This has 1, this has 2, this has 0, this has 1, this has 2, this has 3. This we don't know, there is some x coming. So let's drop that. What is this? This is 4 2 6 and this is 7. Now the number is 10x. What does that mean? That means that no matter whatever the value is there, no matter whether it is 0 or 1, irrespective of this particular value, your output will be 1 only. Your system will not change. Your digital system will not change irrespective of this particular bit. So if at A and B, which one will be your MSB? Since it is not mentioned, I will consider this as MSB and this as LSB. if your A is 1 and B is 0, then do not think about C. Even if it is 0 or even if it is 1, it will always give you output as 1. So irrespective of the value of C, your output will be 1. So what I can write from here, what I can conclude from here, that 1 0 1 or 1 0 0 will give me output 1, and 1 0 1 will also give me output 1, right? This is our value of ABC. This is our value of ABC, and this is our output Y. So 1 0, if 0 bit is there, 1 1 0 1, that means our output will be 1. So irrespective of the value of this C, our output will always be 1. So how I can write my output now? So Y would be equals to A bar B bar C bar plus, what about this? This would be A bar B C, right? A bar B C. Look, this is A bar B bar C bar, A bar B bar C bar. This is A bar B C. What about this one? A B C bar plus A B C bar. What about this one? This is A B bar C bar, and this is A B bar C, right? So plus A B bar C bar plus A B bar C. Here you can directly see, what you can see, like that this term can be reduced to A bar B C plus C bar. And what is C plus C bar? C plus C bar is 1. So this term can be reduced to AB bar. So irrespective of the value of C, you are getting AB bar only here. So Y can be further reduced to A bar B bar C plus A bar B C plus ABC plus AB bar. But if I want to write in terms of minterms, सब टेढ़ा लिखा हुआ क्यों आ रहा है? Let's write it down in better way. Y is equals to A bar B bar C bar plus A bar B C plus A B C bar plus A B bar. Okay. Now if I want to write it in terms of minterms, so what that would be? M0 plus M3 plus 1 2 4 6, 1 2 4 6, right? M6 plus, what about this one? In this I am having A B bar, but I know there will be C as well and there will be C bar as well. So what was this? 1 0 1, that means 1 plus 4 5, M5, and what was this? 1 0 0, that means it would have been M4. So basically summation M 0 3 4 5 6, this is your output. So in terms of minterms you will write down in this manner. So in minterms all the values, all the values of ABC for which output can be 1, that would be written. Okay. So 0 3 4 5 6. Write down the truth table for the given below expression. For the given below, write down the expression for the truth table that is given below. So what will be the expression? Here output is 1. So Y would be equals to A bar B bar C bar into 1 plus, let's look at another one, that is A bar B C into 1. Let's look at another one, that would be A B C. Here our output is D bar and D. So what does that mean? If your input is A B bar C bar, then output is D. That's it. A B bar C bar, then output is D. And if your input is A B bar C, if your input is A B bar C, then your output is D bar. This is what it means. That's it. So this is the correct output. Now can you write down the minterm? Yes, I can write down the minterm as well. But minterms will have the variable A B C D. Y is the function of A B C D. Are you getting this point? Can you write down the minterms? If I ask you A B bar C bar, will you say it is 0? A, B bar, C bar, 0, 0, 0. So is that M0? This is wrong. Will you say this is 0, 1, 1? So is that what would be M1? M3. This is M0. This is wrong. This is M3. This is also wrong. Why it is wrong? Because there is D as well, where A is MSB, A is MSB, and D is LSB. Why so? Because our function is ABCD. Here all three variables are there, and if it is mentioned in this manner, then I have to consider this as MSB and this as LSB. So what you can see here, 0, 0, 0, but D is working as a don't care here. So no matter whatever the value of D is there, output will always be 1. So D is working as a don't care. So here it is written A bar, B bar, C bar. So you can consider this as written as D plus D bar, because 1 can be replaced at D plus D bar. So it would be A bar, B bar, C bar into D plus A bar, B bar, C bar into D bar. So basically there is D as well, there is D bar as well. So how I will write it? 0, 0, 0, and then I will make cross. That means 0, 0, 0, it can have value 0 as well, and it can have value 1 as well. So M0 is there, M1 is there. So this represent M0 plus M1. Now it is correct. Okay. And what does this represent? So here this is 0, 1, 1. So it can have 0 value, it can have 1 value as well. So this represent M3, right? 1, 1, 2, 4. Sorry. 1, 2, 4, 6. So this represent M6. Really sorry. 1, 2, 4, 6. Yeah. This represent M6 and this represent M7. So this is M6 plus M7. What about this one? 1, 1, 1, 0, 1, 1, 1, 1. So what does this represent? 1, 2, 4, 8. So 40, sorry, 14. So this represent M14 plus 1, 1, 1, 1. It would be M15. What does this represent? This is simply 1, 0, 0, 1. Right? So 1, 2, 4, 8. So this is M9. And what about this one? 1, 0, 1, 0. So 1, 2, 4, 8. So this is M10. So this is how we can write down all the minterms. Okay. So do consider what is your output. Your output is function of ABCD. Okay. Your output is the function of ABCD. That means D will act as MSB. Sorry, D will act as LSB. And D is acting as LSB and A will act as MSB. So if you cannot see D here, that means it is there, but it in the form of D plus D bar. Are you getting this point? Okay. Find the minterms. Okay, the same question is there now. That's exactly the same question I have mentioned, I guess. A bar BC, A B C. Some difference is there. A B bar C bar D, A B bar C D bar plus A B C. The same question is there. What will be the minterms? M0, M1, M6, M7, M0 plus M1 plus M6 plus M7 plus M9 plus M10, M9 plus M10 plus ABC is having M14 plus M15, M14 plus M15. So these will be the minterms, or I can write it in this manner. That is 0, 1, 6, 7, 9, 10, 14 and 15. Now if someone gives me this question that these minterms are there, now make the truth table. So how will I make the truth table? Making this table will be very difficult for me. So how will I make the truth table? A, B, C, D, and I will write down all the combination. 2 to the power 4, 16 combination I will write down. 0, 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 1. 16 combination I will write down, and with respect to their output. 0, 0, 0, 0, 1. 0, 0, 0, 0, 1, that would be 1. Then 6, that would be 1. Then 7 would be 1. In that manner I will make the truth table. Okay. So yeah, that's it. Okay, so this is about minterms. We will see more points about minterms, but later on. Now let's study about maxterms now. So it is logical OR operation. Maxterm is logical OR operation. OR operation will be there. Okay, where each variable can be itself or in the complemented form. Output will be 0. Output of minterm is 0. 0 is the normal form here and 1 is the complemented form. It is logical OR operation. Just look at this word, logical OR operation. It is logical OR operation. Output of the function is 0, represented by capital M. 0 is the normal form and 1 is the complemented form. These points you need to remember. And what was these points for maxterm? And output is 1, represented by small m. 1 is the normal form and 0 is the complemented form. Right? So let's write down the maxterms. Okay, we are going to write down the maxterm. 0 is the normal form. That means it could be written as A. It is logical OR operation plus B. What about this? A, 0 is the normal form plus B is the complemented form because B is 1. This would be A bar plus B and this would be A bar plus B bar. Now the expression, how will I denote it? This would be M0, this would be M1, this would be M2, this would be M3, right? What about this one? Maxterm, what would be maxterm? A plus B plus C. What would be maxterm here? A plus B plus C bar. We will see it, everything will be clear why we are doing so, what we are doing. This would be A plus B bar plus C. This would be A plus B bar plus C bar. This would be A. This would be A bar plus B plus C. This would be A bar plus B plus C bar. This would be A bar plus B bar plus C. And this would be A bar plus B bar plus C bar. Have I written it right? I hope there is no mistake, no mistake, no mistake, no mistake, and no mistake. And what would be the expression? M0, M1, M2, M3, this would be M4, this would be M5, this would be M6, and this would be M7. If directly this was given and they are asked me the expression of maxterm, then how will I write? Some term is there. What I will see first? Sum. Okay, some term is there. That means A will be 0, B will be 1, and C will be 0. Whatever the doubts that are coming to you, keep that to you. Everything will be clear in the end of the lecture. Believe me, everything will be clear because some people will have the doubt, sir, A plus B bar plus C is written. What if I assume this as A B bar C bar, A B bar C, A B C bar, and A B C? From A you can get these things as well, right? So I can represent this in terms of minterms. I can write A plus B bar plus C in this manner. A bar B bar C bar plus A B bar C plus A B C bar plus A B C, because A will come common. And what is the addition of this? B bar C plus B C bar plus B C, that is 1. So now I am writing in terms of multiplication. So that thing will come. You can write in terms of maxterm as well. So that will come, but we will see it later on. Okay. So no need to worry about that. We will see it later on. So these kind of doubts can come, which I will address. So 0, 1, 0, that means 1, 2. So that is M2. So in that manner, we will be able to write directly. Okay. So let's see a question regarding that. This is given W bar X, Y, Z. W bar, that means it must have been 1. Basically, there is plus. There is plus here. So if there is plus, that means it would be talking about maxterms. So if there is plus, I would take bar as 1 and normal form as 0. So 1, 0, 0, 1. And you will be habitual of this. No need to worry. That's how we will remember it. You will be habitual. This is 1, 2, 4, 8. So this is 9. 1 plus 8 is 9. So the maxterm is M9. So this is the answer. Okay, and for n variable there will be 2 to the power n max terms, right? There will be 2 to the power n max terms, right? 8 max terms are there, 4 max terms are there, right? Truth table is given, you need to write down the output. If now I need to write down the output, I can write down the output in any manner, but let's just see in terms of max term. So if I am thinking of max term, this is the same truth table where you have written the output, same truth table you have written the output for this, but now I will write in terms of max terms. Okay, let's write it in terms of Minterm first. So you are habitual, Minterm, I am writing the output in terms of Minterms. Okay, so y would be equals to a bar b bar plus a bar b. So this is the output you are getting. Sorry, y bar a bar b bar plus a b bar, a bar b bar, a bar b bar plus a b bar. This was in terms of Minterms. So here we were getting b bar as output. Let's write it down in terms of max terms. So max terms, that means you need to look at 0, or let's forget about that. How will I write in terms of max term? A plus b. How will I write this one? A plus b bar. How will I write this one? A bar plus b. And how I will write this one? A bar plus b bar. So how I can write my output now? I will be writing my output as a plus b plus, what is the output? 1 into a plus b bar, what is the output? Plus 0 into a bar plus b, what is the output? 1 plus 1 plus a bar plus b bar, what is the output? 0 plus 0. Anything in addition to 1 will be 1 only. 1 into anything in addition to 0, that would be a plus b bar, that would be the same value. Anything in addition to 1 will be 1 only, and anything in addition to 0 will be the same, a bar plus b bar. So what is the output I am getting? A plus b bar into a bar plus b bar. So what did I understand here? Here I only need to look at 0. Here I only need to look at 0. Now if you solve this particular equation, what you will get? And one more thing, let's solve this particular equation first. So what you will get? A into a bar will be 0, a into b bar will be a b bar, plus b bar into a bar plus b bar into b bar will be b bar. Now what you can take common? You can take b bar as common. So b bar into 1 plus a bar plus a, so that would be equals to b bar only. So you are getting your final answer as b bar. So here also you are getting b bar, and here also you are getting b bar only. Are you getting this point? Do you remember the truth table of XOR gate? 0 0 0 1 1 0 1 1. What is your output? 0 1 1 0. There I told you I can write down XOR gate in terms like this as well. Do you remember? I told you that a bar a b bar plus a b bar, sorry, a bar b. This can be written in this manner as well. Output of XOR gate can be written in this manner as well. How did I tell that? Look at here. Look at here. I need to look at 0 only, but I will write in terms of addition. So a plus b, 0 is the normal form, into a bar plus b bar. So that's it. This is the output I wrote. So this is how I wrote it. Okay. Let's look at the truth table of OR gate. Okay. Let's look at the truth table of OR gate. OR gate. So in OR gate, 0 plus 0 will be 0. 1. 0, this is 1 actually. 1 plus 0 is 1, and 1 plus 1 is 0. Sorry, 1 plus 1 is 1. This is the truth table of OR gate. So in OR gate, you look at only 0. So y is equals to what? 0 is the normal form, a plus b. That's it. You could have written the output y as this as well. If I look at only 1, I don't look at 0. If I look at only 1, that means I am thinking in terms of min terms. So if I am thinking in terms of min terms, then how I will write my output? a bar b plus a b bar plus a b. This is how I will write my output, right? Now, if you solve this a b bar plus a b, that means you can take common. If I take a common, then what will I get? B bar plus b, and what will be b bar plus b? That would be 1. So a into 1 will be a. So this term can be reduced to a only. So y is equals to a plus a bar b. And what is a plus a bar b? Do you remember this formula? That would be a plus b. A plus a bar b will be a plus b only. So y is equals to a plus b. So you can write in this term only, but if you reduce it, it will become a plus b. So we will write simpler form. Here number of ones are more, but number of zeros are less. So we thought of writing in terms of 0. But here both are equal, so we can write in any terms. So here we thought of writing in terms of 0 because in terms of Maxterm, because number of zeros were less. Why would I write this complex expression? I would write this expression only, no? A plus b, that's it. So this is how we proceed. Okay. So that's why Minterm and Maxterm are important. If any truth table is given or you make any truth table, after that you can write down the output. If this table is given, how will you write down the output? Yeah, and there is another way of representing that. What could be the another way? Look here. Y is equals to what? Multiplication of, what was this? This was your M1, right? And what was this? This was your M3. So this is M1 into M3, or it can be written as, this is the sign of multiplication, pi, M13. So when we are writing the minterms, so we write summation 0 2, right? This was your M0 and this was your M2. So we write summation 0 2, but here we are writing pi M12. So this is a sign of product M12, and here we are writing summation 0 2. Sorry, this is M13, sorry, not M12. This is M13 and this was summation M02, right? Let's see this question. What will be the decimal value? 0, 1, 2. Wait a second. Let's read the question again. Repeat the same question for the truth table given, with C being MSB. C is the MSB here and A being LSB. So this is your least significant bit and this is your most significant bit. So 0 0 0 will make it 0. 1 0 0, it is 1 0 0 actually. Are you getting this point? Because C is the most significant bit, and then B, then A. So this is the most significant bit. So 1 0 0, 1 2 4. So this would be 4. What about 0 1 0? So C is 0 0 1 0. So this would be 2. What about 1 1 0? 1 1 0. So 1 2 4. This would be 6. What about 0 0 1? Right? 0 0 1. So this would be 1. What about 1 0 1? 1 0 1. 1 4. This would be 5. 0 1 1. 1 2. That would be 3. And 1 1 1. That would be 7. Now we are writing in terms of minterms only. We can write in terms of Maxterm as well, but let's write in terms of minterms. So here we need to take care. So if I directly write my output, what would be my output? Product of M into, so 4 2 5 3, 4 2 5 3, or you can write down 2 3 4 5, or how I would have written, what was this? Y is equals to A plus B plus C bar, right? Now people will say, sir, we need to write C bar plus A plus B because C is the MSB. So A plus B plus C bar or C plus C bar plus A plus B, both are same thing only, no? So we can write in any manner, A plus B plus C bar. Then this would be A plus B bar plus C. This would be A bar plus B plus C bar. And this would be A bar plus B bar plus C. So this is how I will write my output. Wait a second, why I wrote plus here? This would be multiplication. So I am looking at only 0 output, and this is how I am writing it. Let's see this question. Here don't care is coming. Don't care is coming. So can try writing down the output on your own. Then I will tell you how to write down the correct output. Okay. So we need to see at 0, 1, 2, and these 3 zeros are only there. So y is equals to a plus b plus c bar, and a plus b bar plus c. Now what about this? A bar plus b plus, irrespective of anything, your output will be 0 only, irrespective of anything. So what should I write here? A bar plus b only, don't care about c. A bar plus b, that's it. Don't care about c. Even if c 1 0 1 and 1 0 0, in both cases you will get output as 0 only. So let's write down in better way. So this would be a bar plus b plus c bar into a bar plus b plus c, right? So in both cases output will be 0. So here I need to look at a bar plus b plus c bar into a bar plus b plus c. Let's see this term. So isn't it x plus c bar into x plus c? So how you can reduce x plus c bar into x plus c? X plus y into x plus z. What that would be? X plus yz, right? So x plus c bar into x plus c would be x plus cc bar. And what is the value of cc bar? Cc bar is equals to 0 only. So x plus 0. So answer would be x only. So this term will be reduced to a bar plus b only, right? X plus c bar into x plus c. So that would be x plus cc bar, and cc bar is 0. So it will be reduced to x only. So this term will be reduced to a bar plus b only. So a plus b plus c bar into a plus b bar plus c into a bar plus b. This will be reduced to 0, right? So don't care about c, right? Let's see the next question. Here d bar is coming. So again I need to look at 0, 0 and 0, right? 0, 0 and 0, and then these d are also there. So y will be equals to a plus b plus c bar into a plus b bar plus c into a bar plus b plus c. This I am writing a bar plus b plus c, output is d, so plus d, and then a bar plus b plus c bar plus d bar, and here a bar plus b bar plus c. So this is how I can write my output, right? Are you getting this point? If I had looked at one only, so 1 1 1 and then these two I had to write. So there will also be 5 terms, here also there are 5 terms. So this is how I can write my output. Can you write down the max terms now? Try writing the max terms on your own. A plus b plus c bar is there. That means plus 0 is also there. And 0 can be written as a plus b plus c bar plus dd bar. Say yes or no. Now if I assume this as x, so x plus dd bar, x plus yz, how I can write? X plus y into x plus z. Say yes or no. So similarly x plus d into x plus d bar. So what is x? X is a plus b plus c bar plus d, and a plus b plus c bar plus d bar. So here in a plus b plus c bar, what you can see? A plus b bar plus c bar plus d into a plus b bar plus c bar plus d bar. So both d bar and d both are there. Okay. So if I write this as, basically if someone goes, he may think that a plus b plus c bar, but the thing is the function is of 4 variables. This is your MSB and this is your LSB. So if someone thinks this is how I should write, that means 0 0 1, right, 0 0 1, and that would be M1. So if I write this as M1, that would be absolutely wrong. And if I write this as 1, sorry, this is in terms of addition, right, this is in terms of sum. So for sum 0 1 0, so if I write this as M2, if I write this as M2, that would also be absolutely wrong. So what would be the correct way? Let's see it on the next page. Let's see it on the next page, because the same question I would have put, not the same question this time, not the same question, the question is different. So here only I will write down the maxterms. So A plus B plus C bar, so 0 0 1 0, so 1 2, that would be M2. 0 0, sorry, yeah, 1 2, that would be M2. So in the last question here, did I do any mistake? D and D bar, okay, no issue. Yeah, so this would be M2 and this would be M3, right, because this D can take D and D bar, 0 and 1. So this has the place value of 2, this has the place value of 1. So this would be M2 into M3. Why into? Because I told you this is A plus B plus C bar plus D into A plus B plus C bar into plus D bar. So this is how we can write it. This I proved just a few minutes back. I proved it. I just write D into D bar here, then I told X plus Y Z can be written as X plus Y into X plus Z. So a few minutes back only I proved it. So how did I prove it? You can write it in your, somewhere you can write here, okay, somewhere. If you are having the hard copy of the notes, you might be studying from the hard copy of the notes, so somewhere you can write at some place that whatever that I have proved. So these proofs you can write. Like eventually you will not remember the proof, or you can remember the proof as well. That is a good thing. But how everything is coming, that is my target. You need to know how everything is coming. So A plus B bar plus C, so that would be 0 1 0. So another 0 can be there or another 1 can be there. So 1 2 4, so that would be M4 and this would be M5. So into M4 into M5. What about this one? This is 0, sorry, 1 0 0 0. So 1 2 4 8, this is M8, and then 1 0 1 1. So 1 2 4 8, this is M11. What about this? A bar B 1 1 0 1 1 0. This can take value 0, this can take value 1. So 1 2 4 8. So this is M12 and 1 2 4 8, and this is M13. So multiplication M, what you are getting? 2 3 4 5 8 11 12 13. So 2 3 4 5 8 11 12 13. So this is what you are getting, right? Now let's write down the maxterm for this particular expression. So how will you write down? A plus B plus C, A plus B plus C, that means 0 0 0. First thing what you will see, addition is there, addition is there, okay. So this is product of sum, product of sum. Can I write this as product of sum? So if product of sum is there, product of sum terms, this we have already seen, these two terms we have already seen, SOP and POS. So product of sum is there, in between there is multiplication and these are the addition terms. So product of sum terms. So if product of sum terms is there, that means you need to think of max terms. And here, not here, here what was given? Sum of product. These were the product terms, these are the product terms, product terms. So sum of product is there. If sum of product is there, that means you need to think in terms of min terms. Okay, it would be easier. You need to think in terms of min terms. It would be easier. Okay. So 0 0 0. This would be here D and D bar both will come. So this can take 0 value as well, and this can take 1 value as well. What about this one? This would be 1 0 0. So this can take 0 value as well, and this can take 1 value as well. And what about this one? This is 1 0 0 1. 1 0 0 1. So this is coming twice, right? So 1 I can eradicate. 1 0 0 1 is coming twice. So this would be M0, this would be M1, this would be M4, sorry, 1 2 4 8, this would be M8, and this would be M9. So what would be your expression? That would be 0 1 8 9. So this is how your y can be written. Y can be written in this manner. Okay, that is SOP 0 1 8 9. Now do you notice one thing here? Let's take this example. This was the minterms 0 2, this was the maxterm, that is 1 3. Let's take the same example. I guess the same table was there. This is the minterm, sorry, this is the maxterm 2 3 4 5, right? 2 3 4 5. I hope the same table was there. 2 3 4 5. No, this is, yeah. So this is 0 3 4 7. So the same table is there. For this same table, the minterms is coming 0 3 4 7. Let me write it down here. Minterms is coming 0 3 4 7. So this is 2 3 4 5. 2 3. Okay, the question is different. Okay, the problem is different because C is MSB. So what did I mean to say is that if your minterms is, let's just say 0 1 2, 0 1 5, then your maxterm would be 2 3 4 6 7. That would be your maxterm if it is a 3 variable function. Okay, if let's write it down a question. So from problem you will be able to remember it. F A B C is given as 0 2 4. Write in terms of maxterms. So basically we know there are 3 variables. There are 3 variables. If there are 3 variables, then maximum decimal number. What is your maximum decimal number? If there are 3 variables, then maximum decimal number will be 7. So if I want to write in terms of maxterm, then this M would be 1 3 5 6 7. Now no one will say, sir, why did not you write 8 9 10 11 12 13 14? Because for 3 terms the maximum decimal number could be 7 only. And what if the question is mentioned something like this, that your function a b c d is given as M 0 2 3 5 7. That's it. This is how it is mentioned, and write in terms of minterms. Write in minterms. So how many variables are there? 4 variables. So maximum decimal would be what? Maximum decimal would be 15, right? So in terms of minterms it would be 1 4 6. Is that so? That's it. Is this the answer? No, it can go up to 15. So 8 9 10 11 12 13 14 and 15. So are you thinking both are complement? Both are complement of each other. Can I say minterms and maxterms are complement of each other? No, not at all. Minterms and maxterm will give you the same expression. I told you this thing, minterm and maxterm will give you the same expression. Here, this we solved in terms of minterms. What was the expression we got? B bar. When we solved in terms of maxterms, what is the expression we got? B bar. So minterm and maxterm will give you the same expression. If someone is saying that minterm and maxterm are complement of each other, then this statement is absolutely wrong. Okay, there is no meaning of this particular statement that minterms and maxterm are complement of each other. Not at all. Okay, they are not complement of each other. So just a way that if minterms is given, I can write down the maxterms. If maxterms are given, then I can write down the minterms. Let's see what we are going to study next. So we are going to study the standard. We are going to study about SOP and POS form only. But next we will see what do you mean by standard SOP form, standard POS form. Then we will see some examples and more some questions we will see, and then we will see minterms through logic gate. So we will revisit the logic gate again, and then we will solve some problems. So this we are going to see in the next lecture. So I hope this lecture is being cleared in the end of the video. So I told you in the end of the video every dot will be connected. So I hope the dots are connected now. Why we are writing down the expression, how we are writing down the expression, and how we will write down the expression if we have a truth table. What is minterm, what is maxterm? In minterms we will look at output 1, but in maxterm we will look at output 0. 0 is the normal form and 1 is the complemented form in case of maxterm, and in case of minterm 1 is the normal form and 0 is the complemented form, right? So this is the conclusion of the chapter which I have already given. So this was the most important point. OR operation, it is 0 m 0 normal form and 1 complemented form, and you need to think of POS. If you are thinking in terms of product of sum is there, that means you need to think in terms of maxterms, and if sum of product is there, that means you need to think in terms of minterms. So this is how we will proceed in our lecture. We will see a lot of example, we will use it again and again, and you will be habitual of all these things. In this lecture you might be thinking that, sir, we are not getting habitual of all these things, like how we will remember all these things. So you will remember all these things once you study the complete chapter. Okay then. So yeah, that's it. Let's meet you in the next lecture. Hi everyone. So continuing our previous lecture, in this video we are going to study about SOP and POS, sum of product and product of sum. So you already know the meaning of sum of product, you already know the meaning of product of sum. So there is a new term, that is standard SOP form, standard POS form, or you can say canonical SOP form, canonical POS form. So what do you mean by that? That in standard SOP and standard POS, all the variables should be present. All the variables should be present. So we will see that. First let's see some example of SOP form. So what are the examples of SOP? Let's just say this is one of the example of SOP, right? One of the example of SOP. Sum of product, or you can say, right? Let's write down the example of product of sum terms and together, product of sum. So A plus B plus C into D plus E. Tell me what about this? This is SOP form or POS form? A plus B plus C. So you cannot define whether it is SOP form or POS form, because no one in the examination is going to ask you whether it is written in SOP form or POS form. These kind of questions will not be asked. But what one can say that, sir, A into 1 is written, plus B into 1 is written, into 1 is written, plus C into 1 is written. So it is sum of product. It is sum of product. Some guys can say it is sum of product, and some guy can say that, sir, A plus B plus C into 1 is written. So it is product of sum. So we cannot actually tell whether it is in SOP form or POS form, right? So let's write down in this manner: A bar plus B bar plus C plus D bar plus E. Okay. So these are the example of SOP and POS form. This is not an important part, just for solving the problems it will be used. And what do you mean by standard or SOP form or standard POS form? That all the variables should be present in the product term and sum term. Let's see some example. This is given. So which of them is standard SOP and standard POS? What do you think? The function is of variable A, B and C. What did I say? All the variables should be present in each term. So here also C should be present and here A should also be present. So not standard. And this is product of sum, so not standard product of sum. Are you getting this point? This is not standard product of sum, because all the variables should be present in each product slash sum term. So in each term, all the variables will be present. Here in this term, all the variables are there, all the variables are there, all the variables are there. That means this is standard POS. Standard POS. What about this one? In this term, C variable is not there. In this term, A variable is not there. So not standard. What is this? This is SOP or POS? Not standard SOP. Because sum of product. What about this one? Each variable ABC, each variable, each variable. So yeah, this is standard SOP. Okay, standard SOP. Right? Now some kind of questions can come, which is this kind of question. So in this question only everything will be cleared. So we will see this question in very in-depth manner. Given function are for the given function you need to write down the minterms, maxterms, and you need to write down the standard SOP and POS form. So all these things you need to do: minterm, maxterm, SOP and POS form. Can you write it down on your own? Because I have already taught you this concept in the last video. So this is a function of ABC, which is given as A plus B bar C. Let's write down sum of product. Sum of product. How will you write it down? I told you one thing, that this A is having the BC variable as well. How it is having? It is having BC variable as that. What is this form? This form is SOP form, sum of product, right? Sum of product. This is SOP form. And if sum of product is there, A plus B bar C is there, sum of product is there, then I can think in terms of minterms. So if I am thinking minterms, so what about this A? A will be 1. I am thinking minterms. A will be 1 because 1 is normal form, 0 is complemented form. So 1 is normal form. Now this 1 can have 0 0 value as well. This 1 can have 0 1 as well. This 1 can have 1 0 as well, and this 1 can have 1 1 as well. Basically this 1 is constant, this A is constant. Now for BC can take any value. B bar C bar, basically it is A B bar C bar plus A B bar C plus A B C bar plus A B C. Because if you take common A, it would be B bar C bar plus B bar C plus BC bar plus BC. And what is the value of this function? I have already told you to remember, that is 1 only. So this is equals to A only. So A has all these components. You need to write in standard SOP form. That means you need to include all the variables. And what about this B bar C? What about this B bar C? So B bar C, that means B is 0 and C is 1. So A can have 0 value and A can have 1 value as well. So 0 0 1 1 0 1. So these are the minterms. These are the minterms. 101 is being repeated twice, so 101 can be eradicated. So these are the minterms. Now what will be the standard SOP form? I am writing standard SOP form. First let's write standard SOP. So in function of ABC, what will be the standard SOP? It was A plus B bar C. So A, with A you will have B bar C bar plus B bar C, BC bar plus BC, and then you had B bar C. So A B bar C plus A bar B bar C, because B bar C can have A value as well, A bar value as well. Now something is being repeated twice, A B bar C. This term is being repeated twice, so you can write it down in one time only. So A B bar C bar plus A B bar C plus A B C bar plus A B C plus A bar B bar C bar. So these are the minterms. So what is this? This is 100. This is SOP form. If SOP form is there, then I need to think in terms of minterms. So this is 100. What is this? 101. What is this? 110. 111. And this is 001. Right? 100, 101, 110, 111, 001. So minterms are, this is 4, this is 5, 1 2 4, this is 6, this is 7, and this is 1. So minterm So are 1, 4, 5, 6, 7. That's it. Now if these are the minterms, then what will be the maxterms? 0, 2, 3, 4, 5, 6, 7 all are there only. So 0, 2, 3, 0, 2, 3, these are the maxterms. And these are the minterms. If these are the maxterm, that means 0 means 0, 0, 0, 2 means 0, 1, 0, and 3 means 0, 1, 1. If these are the minterms, if these are the maxterm, then what will be the POS form with respect to this? POS form A plus B plus C. With respect to this, A plus B bar plus C, and with respect to this, it would be A plus B bar plus C bar. So what would be your standard SOP? Standard POS. Now your standard POS. Since I know the maxterms, then I can write down the standard POS in this manner. Function of A, B, C, that would be A plus B plus C, A plus B bar C, B bar plus C, and A plus B bar plus C bar. That's it. This is my standard POS. Okay, this is the answer. This is the answer. This is one of the answer, and this is one of the answer. So these are 4 are answer. But there is method 2 as well for writing standard POS. Standard POS method 2. Standard POS method 2. Let's just say I don't want to write them in terms. I don't want to write them in terms without even writing them in terms, because first I wrote here min terms, then I got max terms, and then I got this expression. But without even this expression, how I would have done it? Function of ABC is given. That is A plus B bar C. Can I write it in this manner? X plus YZ is equals to X plus Y into X plus Z. I have converted this into POS form, product of sum form. A plus B bar into A plus C. Now tell me what this term is having. This term is having C component as well. This term is having C bar component as well, right? And what about this? This term is having B component as well, and this term is having B bar component as well. Which term is being repeated twice? This term is being repeated twice. This term is being repeated twice. So you can write it down in one term only. So A plus B bar plus C, A plus B bar plus C bar, A plus B plus C. So that will be your standard POS form. So this could also be one of the method of solving. Okay, let's check our answer. A plus B plus C, A plus B bar plus C bar, A plus B bar C. So same answer is there. Answer is also matching. So this was the method 2. So in this method, without even writing the minterms, I got the expression, and from here I can write down the maxterms. Now if this expression is there, I can write down the maxterms. So that would be 0, 1, 0. This would be 0, 1, 1, and this would be 0, 0, 0. So that is, oh sorry, capital M. Did I write small m here? No, capital M is there. So this is 0, 2, 3. So in this manner I can write down. Okay, so these kind of questions are asked, like they will give this expression and they will ask you the maxterms. So what many people will do, first they will find out the minterms and then they will go to maxterms. But here we can proceed in this manner as well. Without even writing down the minterms, we can write down the maxterms. Okay, let's see question B. Question B. F, A, B, C. Okay, AB plus A bar C. Now in the examination, let's just say this question comes and they are asking you standard POS form. Standard POS form they are asking. But you know one thing, this is SOP form, right? This is SOP form. And I can easily write down all the minterms. I can easily write down all the minterms, right? If I need to write down standard SOP form, then I can easily write down all the minterms. If this question comes in my examination, because I know this component will have C as well, this component will have C bar as well, this component will have B as well, this component will have B bar as well, right? Easily I have written. So this would be 1 1 1, this would be 1 1 0, this would be 0 1 1, this would be 0 0 1. So this is 7, this is 6, this is 3, this is 1. So minterms are 1 3 6 7 and maxterms are, what would be the maxterm? Maxterm would be 0 2 4 5. So in the examination I will see this expression. Even if I need to write down the maxterm, first I will write down the minterms, because I know it would be very easy for me. If I solve this question with this method, that would be very lengthy, because how I would have to solve, that I will tell you. Okay, I will tell you how I would have to solve. In method 2 I will tell you, but here we have got this expression. From here I can write down my standard POS form as well, because I have the maxterms. So standard POS. But if I go by method 2, that would be very lengthy, that I will tell you how that would be lengthy. So what are the maxterms? 0 2 4 5, 0 2 4 5. This is what your function ABC is equals to. 0 means 0 0 0, 2 means 0 1 0, 4 means 1 0 0, and 5 means 1 0 1. So function of ABC would be what? A plus B plus C, A plus B bar plus C, A bar plus B plus C, A bar plus B plus C bar. That's it. Now what could be the method 2? Method 2. So directly if I want to write FABC, if I want to write directly, then AB plus A bar C, AB plus A bar C. So I need to consider this as X plus YZ, X plus YZ. This is how I need to consider. Okay, so X plus Y into X plus Z. So AB plus A bar into AB plus C, X plus Y into X plus Z. Now what about this? AB plus A, AB plus A bar. So this is X, this is Y, this is Z. So X plus Y into X plus Z. So A plus A bar, A plus A bar into A bar plus B, X plus YZ. So X plus Y into X plus Z. What about this one? C plus A into C plus B. A plus A bar will be 1 only. So A bar plus B, this is A plus C, and this is B plus C. Now if I write here function of A, B, C. So in this function, A bar plus B, C will also come, C bar will also come. So A bar plus B plus C, A bar plus B plus C bar. What about this one? Here B will also come and B bar will also come. What about this one? Here A will also come and A bar will also come, right? So which is being repeated twice? This is being repeated twice. What else? This is being repeated twice. Anything else? No. So let's start with A plus B plus C. Then let's write A plus B bar plus C. And then let's write A bar plus B plus C, A bar plus B plus C. And then write A bar plus B plus C bar. That's it. And if you match the expression, this is the same only. So that could be the other way. But faster way would be this, because I know this is SOP form and easily I will be able to write it down, right? Let's see the question C. Let's see C. C means last one, the third one, that is given as function of ABC, that is A plus B plus C. So these kind of questions generally come in your examination. Okay, You cannot ignore it. So generally these questions are asked that you need to write down standard SOP. What about this? This is SOP or POS? You can say this is standard POS because there is only one term and in one term all the variables are present. There is only one sum term and all the variables are present. So this is standard POS already. Standard POS already. What will be the min terms now? Sorry, what will be the max term? 0, 0, 1. This would be M1. That would be your max term. This is your max term. That's it. What will be the min terms? This is the max term. Okay. What will be the min terms? Min terms will be 0, 2, 3, 4, 5, 6, 7. These will be the min terms. Min terms. And from here I can write down my expression. Basically 0, 0, 0, 0. What about 2? 0, 1, 0. What about 3? 0, 1, 1. 4 is 1, 0, 0. 5 is 1, 0, 1. 6 is 1, 1, 0. And 7 is 1, 1, 1. So function of A, B, C is equals to A bar, B bar, C bar plus A bar, B, C bar plus A bar, B, C plus A, B bar, C bar plus A, B bar, C plus A, B, C bar plus A, B, C. That's it. So these 7 terms are there, 3, 3, 6. This is your standard SOP. What could be the method 2 for standard SOP? Method 2 for standard SOP. F A B C is given, right? A plus B plus C bar. Now this A will have all the component of BC, right? All the component of BC. So initially B bar C bar, B bar C, B C bar plus BC. This B will have all the component of A and all the component of A and C. So A, B, A bar C bar, A bar C, A C bar, AC. And this will have all the component of A and B. So A bar B bar C plus A B bar C plus A bar B C, sorry, C bar is there, this is C bar, plus A B C bar. So a lot of terms are being repeated twice. So this would be a tougher method. So A B bar C, A B bar C plus, sorry, A B bar C bar, this would be A B bar C, 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 not there. So A B bar C. What about this one? A B C bar, A B C bar, that's it, twice, A B C bar. What about this one? A B C, A B C also twice, A B C and A B C, A B C. What about this one? A bar B C bar, A bar B C bar, A bar B C bar, A bar B C bar. What about A bar B C, A bar B C, A bar B C, not there, A bar B C. What about A B C bar, A B C bar, A B C bar, A B C bar is already there, A B C bar is already there. And what about this final one? This is A bar B bar C. So you can see this is 1 0 1, that means this is 4, this is 1, this was 1 0 0, that means this was 4, this was 5, 1 1 0 means 6, 1 1 1 means 7, this was 0 1 0, this was 2, this was 3 and this was 0, right? So apart from 1 everything is there, 0 2 3 4 5 6 7, so everything is there. apart from 1, 4, 5, 6, 7. So that's it. This is how we can write, but this is a longer method. I would have gone with this method. So first I will see whether it is a POS form or SOP form. So in that manner I will proceed. So it was a standard POS form, so directly I would have wrote down them in terms very easily. Okay, so yeah, that's it about this particular point. Let's solve some problems. What is the function in POS form? What is this function? So what is the function given? A plus b bar c, right? So in POS form you need to check. Okay, the same example I have taken into a plus c. So this POS form I have written. So a bar plus b plus c, a plus b bar plus c bar, a plus b bar plus c. This is being repeated twice, so I will not write it down. So next would be a plus b plus c. So that's it. These three terms are there. So this would be POS form. We need to think. POS means max terms. So this would be 0, 1, 0. This would be 0, 1, 1, and this would be 0, 0, 0. So this is your 0, this is your 0, this is your 3, and this is your 2. So 0, 2, 3. So sometimes what may happen is that we can quickly click on this, but this is wrong, because this is product of sum. Product terms are there, no? So whenever there is max term is written, how do we write? I told you this pi sign is of product sign, so there will be product. Sorry, not this one, this one, m0, m2, m3, m0, 2, 3. So this will be the product form, not the sum term. There will be product terms. Okay, sorry, there are some terms which are in the product form, product of sum. So product will be there. Whenever capital M is written, product will be there. Well and good. And in last lecture I forgot to tell one thing, I guess. Yeah, product of all max terms. Product of all max terms, what that would be? 0. Why is that so? Product of all max term would be 0. I will explain it. And sum of all min terms will be 1. Why is that so? Because let's just say this truth table is given and all are 1 here. All are 1 here. All are 1. Then what is your y? Y is equals to 1. Y is 1. If all are 1, that means y is equals to 1. And what all are the min terms? A bar, b bar. This is min term m0 plus m1. Basically a bar b plus a b bar plus ab. All these min terms will come. m2 plus m3. So if we add all of them, what we will get? 1 only, because y is equals to 1. If all y are 1, that means y is always 1. So y is equals to 1. And when we write in terms of min term, that would be m0 plus m1 plus m2 plus m3. That is coming equals to 1 only. Or I directly know this expression is equals to 1. So sum of all min terms is equals to 1. Similarly, the product of all max term is equals to, wait a second, product of all max term is equals to, where is product of max term? Product of all max term is equals to 0. Let's just say this truth table is given and this is also 0 and this is also 0. So y is equals to 0 only, right? And what it will be in terms of max term? m0 into m1 into m2 into m3. Basically you are going to write y is equals to this, right? 0, 1, 2, 3. This is your y, because you need to take care of zeros. So here there is 0, here there is 0. So 0 is there at m0, m1, m2, m3. Why did you write down this as pi m13? Because at 1 and 3 there were 0. But if there are all 0, then you will write down in this manner. And what is the meaning of this? The meaning of this is m0 into m1 into m2 into m3, and y is equals to 0 only. So y is equals to 0 only. So this is the product of all the max term. So product of all max term is 0. So this you always need to remember. Okay? Or you don't need to remember, you will eventually remember it only, because product of all min terms, product of all max term would be 0 and sum of all min terms will be 1. So that we can understand as well and remember as well. So this thing I just remember that I forgot to explain. So these are all the points which we are covering, nothing we are leaving. So now let's see the next question. A 3 variable table has a high output for the given input. So 0 1 0 0 1 1 1 1 0. It has high output. Output is 1 here. What will be the Boolean expression? So output is 1. If I am looking at 1, that means I need to think in terms of minterms and SOP. Minterms and SOP. So high output 1 if I am thinking. So what will be my Y? That would be A bar B C bar into 1 plus A bar B C into 1 plus A bar, sorry, plus A B C bar. A bar B C, A bar B C bar. Yeah, that's it. So A bar B I can take common. From here I can take A bar B common. This is A bar B plus A B C bar. Right? Now I can take B as common. So it would be A bar plus A C bar. Right? If I am taking B as common, it would be A bar plus A C bar. And this can be reduced to A bar plus C bar. So B A bar plus C bar. So reduced expression is basically A bar B plus A bar C. So this is the final expression. A bar B plus A bar C. That's it. Okay. This is the final expression. A bar B plus A bar C. So in that manner we can proceed. Now we need to see these kind of problems. Minterms through logic gate. That F1 is mentioned 2, 3, 4 and F2 is mentioned pi M1257. What will be our output? Basically F1 is 2, 3, 4. That means it is 2, 0, 1, 0. 3 means 0, 1, 1 and 4 means 1, 0, 0. So it is A bar B C bar plus A bar B C plus A B bar C bar. Now F2 will be some other function, right? F2 will be some other function. Here both are being multiplied. So what will be the output and what will be the minterms of the output? This is what we need to find. Minterms or maxterms. So how we will find that? These kind of questions we will solve. So how we will solve that? So whenever these kind of questions will come in front of you, you need to think of Venn diagrams. Okay, you need to think of Venn diagrams. What this will represent? A into B. If I say A into B, that means this is which operation? AND operation. So in AND operation we need to take the common area. That's it. What this will represent? This is your A B bar. And what is this? This is A bar B. B is there but not A. A is there but not B. I have already told Venn diagram. So what will be the complete expression? A B bar plus A bar B. So what is this? This is your XOR gate. This is your XOR gate. What about this one? Complete A is there, complete B is there. So it is A plus B only. A plus B only. So what is this? This is OR gate. So if I talk about XOR gate, then I need to think whatever that is there in A and B, just the common part will not come. If I need to think of OR gate, that means whatever there in A and B, everything will come. What about this? What is this? This outer expression is A bar B bar and this inner expression is AB. So what will be the function? A bar B bar plus AB. What does this represent? XNOR gate. Basically XNOR is the complement of XOR. You can directly see that whatever that is shaded here, that is not shaded here. So if I am thinking of XNOR, that means I will not think of XNOR, I will first think of XOR, then I will simply take the complement. Okay, I will simply take the complement later on. What this will represent? A plus B bar, right? A plus B whole bar. So this is NOR gate. NOR gate. So if I need to think of NOR gate, then first I will think of OR gate and then I will take the complement. What about this one? What does this represent? This is AB whole bar, because this area is AB. Apart from AB, everything is there. So AB whole bar. This is not A bar dot B bar. Okay, A bar B bar is different. A bar B bar is A plus B whole bar. So which is this one? A bar B bar, that means whatever that is there not in A and not in B, so that means this area only, so that would be A bar B bar. What about this shaded area? That is AB whole bar, because whatever that is there in both AB, apart from that everything is there. So this is your which gate? This is your NAND gate. NAND gate. Now let's solve the given problem. So if these kind of questions are there, so first task I will do is I will convert everything in minterms. So this is 2, 3, 4. This also I will convert in minterms. So that would be 0, 3, 4, 6. So first task is to convert in minterms. Now the first function is f1 dot f2. f1 dot f2. Venn diagram is there in my mind. f1 dot f2. A dot b. AB. That means whatever that is there in A as well, whatever that is there in B as well. So I need to take common. So what is the common of these two? 2, 3, 4 and 0, 3, 4. Common is 3, 4. So minterms would be 3 and 4. That's it. This is your answer. So by Venn diagram I will be solving it. In my mind Venn diagram will be running. Let's see the next one. Let's see the next one. F1 plus F2. So whatever that is there in F1 plus F2. Complete part. F1 plus F2. But one minterm we will write one time only. So 0, 2, 3, 4, 6. 0, 2, 3, 4, 6. Inverter means simply complement. Okay. Inverter means simply complement. So complement of this, that would be, here I will write down, complement of this would be complement of F1. So apart from 2, 3, 4 everything will come. So 0 will come, 1 will come, 5 will come, 6 will come and 7 will come, right? If they are asking minterms, I can write down this minterms. If they are asking maxterms, then what will be the maxterm? For this one, what will be the maxterm? 0, 1, 2, 5, 6, 7. So maxterm you can write here also 1, 5, 7. Here what would be? 2, 3, 4. That's it. 2, 3, 4. What about this one? First what I will do? This is your NAND gate. So first I will do AND. So from AND operation I will get this thing. From AND operation I will get 3, 4. Because I need to take the common part. And then I need to take the complement. So what will be the complement? Apart from 3, 4 everything will be there. So 0, 1, 2, 5, 6, 7. First I need to do OR, then I need to take complement. So 1, 5, 7. What is this? This is your XOR gate. XOR gate. So how will I remember it? XOR gate. A bar B. A bar B, that means this area, plus A B bar, that means this area, right? So all of them, but common part will not come. What all are common? 3 and 4. 3 and 4. So 3 and 4 will not come. Rest everything will come. So 0 is there, 0 is there, 6 is there, 2 is there. So 0, 2, 6. These are the minterms. And here first XOR gate and then simply take the complement. So what will be the complement? Complement will be 1, 2 is there, 3, 4, 5 and 7. This is the complete answer. This is how we need to solve these kind of problems. So all the gates are there and in that manner we will be proceeding. Let's solve one more problem. First solve it on your own, then you can see the solution. So what is the first task? I told you to convert it into minterms. 0, 1, 4, 6, 7. 0, 1, 2, 4, 5. And this is the same only, but let's write down again 1, 3, 6. What is the first gate? AND gate. AND gate means A into B. A into B. So only the common one I need to take. F1 dot F2. Common of these two. 0, 1, 0, 1, 4, 4, 6, 7, 2, 5. Different. So here you will have 0, 1, 4. This is your F3, that is 136. F3 is 136. What we need to do? We need to add all. F1 plus F2. We need to add it all. Add it all. That would be 0, 1, 3, 4, 6. and here it will be coming, that would be 136. What about this? This is XOR gate. In XOR gate, A bar B plus A B bar, whatever that is there, complete, but not the common part. What is the common part? That is 136. Everything is there. 136. 136 is there. 136, and here also 136 is there. So that means apart from 136, everything will be coming 0, 4. So this will be your min terms, and max term also you can write. Let's check it again. 0, 1, 4, 6. So common part should come. Common of these two, that would be 0, 1, 4, 0, 1, 4. And here both should be added. So 0, 1, 3, 4, 6. Here 136 is there. So apart from common part, everything will be coming. So 136, 136 is common. 136. Apart from common part, 0 and 4 is there. So 0, 4 is coming. Okay. So if I need to write down the expression, how I can write down? This is 3 variable function because maximum number is 7. So A bar, B bar, C bar plus 4. 4 is 1, 0, 0. A bar, B bar, C. So A bar I can take common. So my final answer is this. That's it. B bar, C bar. So this is my final answer. Y output is B bar, C bar. So basically, if you write down F1, F1 you can write down by this expression. Then F2 you can write down by this expression, and F3 you can write down by this expression. And then you keep on solving and you get this output, that would be B bar, C bar. Okay. So that's it about this chapter. Is there anything else? No. So now we have done the minimization technique. Okay. Now we have done the expressing the Boolean algebra, or expressing the Boolean expression. So this is how we express the Boolean expressions. Now we are going to see a very interesting minimization technique that is known as K-maps. So now we are going to study about K-maps. So in the next lecture we will study about K-maps, and I hope you are enjoying the lecture series. If you are enjoying the lecture series, you can let me know how we are proceeding in this particular chapter. Okay then, thank you very much. Hi everyone. So in this video we are going to study about Carnot maps, or it is known as K-maps as well. So what is a Carnot map? Carnot map is, or K-map is, a graphical method to minimize the Boolean expression. We previously have minimized the Boolean expression in previous lectures. How did we minimize? Let's just say A bar plus AB is written. So that would be A bar plus B. So using some certain methods, we minimize the Boolean expression. Now we are going to do this thing with the help of some graphical methods. Okay, so that graphical method is known as K-maps. So in this lecture as well, you need to have the patience. Like previous 2 lectures, I told you one thing, we will connect the small dots and in the end everything will be clear. So again here as well you need to have the patience. In the end everything will be clear and we will solve a lot of problems, so it will be more clear after that. So have the patience with you, then only you will be able to understand this particular lecture. Okay, so this is a graphical method to minimize Boolean expression, and for n variables you will have to make 2 to the power n cells. This is known as cell. Here there are 4 cells. This is one of the cell. This is known as cell. Okay, so for n variable you need to make 2 to the power n cells. So for 2 variables, how many cells will be there? 4 cells, right? Now let's just say there is a function AB. There is a function AB where A is MSB and B is LSB. So A can have the value 0, 1, right? A can have the bits 0, 1, and B can also have the bits 0, 1. Now this cell will represent 0, 0. This cell will represent 0, 0, and 0, 0 means in decimal 0. Now what this cell will represent? 0, 1, where A is MSB and B is LSB. A is MSB and B is LSB. So 1, 0. What do you mean by 1, 0? This would be, sorry, it would be 0, 1, really sorry. A is 0 and B is 1. So it would be 0, 1. So that means in decimal it would be 1 only. What this cell will represent? A is 1 and B is 0. So 1, 0. So in decimal it would be 2, and this cell will represent 1, 1. So in decimal it would be 3. So basically this is 0, this is 1, this is 2, this is 3. Considering this is 0, this is 1, this is 0, this is 1. So in that manner we need to proceed. Okay, and here I have written SOP. What do you mean by SOP? If I am saying that 0, and in SOP 0 will be denoted as A bar, because SOP means you need to think in terms of minterms, and in minterms this will be denoted as A bar and this will be denoted as A, because these are the values of A. and these are the values of B. So this will be denoted as B bar and this will be denoted as B. Again here as well, 0, 1, 0, 1, right? So 0, 0 will be 0, in decimal it would be 1, in decimal it would be 2, in decimal it would be 3. But this will be denoted as A and this will be denoted as A bar. This will be denoted as B and this will be denoted as B bar. Are you able to understand this point? Say yes or no. Very good. Let's solve this question. Very easy question is given. FAB is given, minterms 1, 2. Fill in the K-map cell. This is not the question on K-maps. We will be slowly moving towards our particular problem. This is just a building block of a particular problem. Okay, this is not the complete question, but a building block. So you know this is 0, this is 1, this is 0, this is 1. This will represent 0, this will represent 1, this will represent 2, this will represent 3. Till now, I did not do any SOP or POS. This is a general form. 0, 1, 0, 1, 0, 1, 2, 3. No SOP, no POS. Now, this is given that FAB is minterms 1, 2. What is the output of minterm? Output of minterm is 1. That means at 1 and 2, your output will be 1. 1 and 2, your output will be 1. And what will be the maxterm for this? That would be 0, 3. That means at 0 and 3, your output will be 0. Your output will be 0. So this is how you will fill in the K-maps. Right? Now for SOP and POS, what will represent what? A will represent A bar. Sorry, this will be A bar and this will be A. For SOP, this will be A bar, this will be A. This will be B bar, this will be B. And for POS, this will be A, this will be A bar. This will be B, this will be B bar. Right? 0, 1, 2, 3, 1, 1, 0, 0. In this particular question, I did not do any SOP or POS because they did not ask. I just know one thing, that this will be 0, this will be 1, this will be 0, this will be 1. For 1 and 2, my output will be 1. And for 0, 3, my output will be 0. That's it. This is how I filled in the K-map. Right? Let's see for 3 variables now. So for 3 variables, how many cells will be there? 8 cells. Now I have given that there is a function FABC where I have assumed A to be MSB and B to be LSB. So in this manner we are going from MSB to LSB. So A can have value 0 and B can have value 1. Sorry, A can have value 0 and 1. What about BC? These are the values of A, 0, 1. What about BC? BC can have value 0, 0, 0, 1. Now what is our habit? We write in this manner 0, 0, 0, 1, 1, 0 and 1, 1. But here we will write 0, 0, 0, 1, 1, 1 and 1, 0. Why we are doing so? Because we need only 1 bit difference. If we are proceeding between the cells 0, 0, 0, 1. If I had written 0, 1, 2, 1, 0, that means this bit has also changed and this bit has also changed. So there is 2 bit distance. That means 2 bits has changed. But I need to change only 1 bit. From 0 to 1 I am going. That means I am changing only this bit is not changed. So from here to here only this bit is changed. So wait a second. So I need to change only 1 bit. So in that manner I will be writing. Okay. Here if I need to write, A can have 0, 1, BC can have 0, 0, 0, 1. What will I write? 1, 1, not 1, 0. And here 1, 0. Right? So A to BC. A to BC we are going because A is MSB. Now if A is MSB, so what this will represent? 0, 0, 0. 0, 0, 0 means this will be 0. ABC, what this will represent? 0, 0, 1. So what this will represent? 1. ABC, 0, 1, 1. What this will represent? 3. And 0, 1, 0. What this will represent? 2. So 0, 1, 2, 3. You remember this order. 0, 1, 2, 3. Now here 1, 0, 0. 1, 0, 0. That means it would be 4. 1, 0, 1. This would be 5. 1, 1, 1. 1, 1, 1 means this would be 7. And 1, 1, 0. That means this would be 6. So 0, 1, 2, 3, 4, 5, 6, 7. So that you need to remember. What about this one? So AB can have 0, 0, 0, 1, 1, 1, 1, 0. Okay. And here C can have 0, 1. So A is the MSB and C is the LSB. So this would be 0, 0, 0. So this is 0. This would be 0, 1, 0. 0, 1, 0. That means this would be 2. This would be 0, 1, 1. Sorry. it would be 110, 110. So 2 4, this would be 6, right? 1 2 4, this would be 6, and 100, 1 2 4, this would be 4, right? 0 2 6 4. You don't need to remember this, only you need to remember this one, because this will be used. If somewhere you need to use this one, then you can derive it, right? 100, that means this would be 4, sorry, it would be 001, really sorry, it would be 001, because A is MSB, so 001, so it would be 1 only. 011, this would be 3, 111, this would be 7, and 101, this would be 5. So in that manner you can represent the number, but you need to make sure that if I am going from here to here, there is only 1 bit distance, okay? If I am using K-map, then only 1 bit distance has to be there. No matter what is the numbering is there, I don't care about that, but only 1 bit distance has to be there. This is the first condition of our K-map. If in question 1 bit distance is not there, then we have to rearrange it, okay? Anyhow we need to rearrange it. Now A is MSB and B is LSB, so this would be 000, so this would be 1, this would be 100, 100, that means this would be 4, right? 100. What about this one? This is 001, that means this would be 1. 011, 011, that would be 3. 010, this would be 2. 010, 2. 011, 011 would be 3. Yeah. So in that manner we are going. Now what this would be? 101, 5. 111, 7, and this would be 6. So in that manner we can write down the number. You have to remember this one, okay? This is very important. 0 1 2 3 4 5 6 7. So in the examination hall you will not be writing these numbers that 0 1. You will just remember it. 0 1 2 3 4 5 6 7. You don't need to remember these ones because it will be tough to remember, right? Fill the K-map cell. This is given, or you can write in this minterms as well. So what will be the minterms? Maxterms are given. Minterms would be 0 1 4 6, right? So general way, this can have A is equals to 0, this can have 1, 0 1 0 0 0 1 1 1 1 0, right? This is 0, this is 1, where A is MSB. I am considering A is MSB. So A to BC, in that manner I am writing. So A is MSB and B is LSB, because nothing is given, then this first one I will consider MSB and last I will consider as LSB. So 0 1 2 3 4 5 6 7, right? Now you need to fill in the K-maps. So how will I fill? What is the output of minterms? That is 1. So 1 you will get at 0 1 4 6, 0 1 4 6, that's it. So here you will get 1, and otherwise 2 3 2 3 5 7 you will get 0. So here you are getting 0. Now if I need to write in terms of SOP, so what I will write here? A bar. So yes or no? And what I will write here? A. Because this is not going to change. 0 1 is not going to change. Here I did not think of any SOP or POS. Directly I have written 0 1 0 0 0 1 1 1 1 0. So this is A bar, this is A. What about this one? B bar, C bar, B bar, C, BC, BC bar. Would you be able to remember this? B bar, C bar, B bar, C, BC, BC bar. I will remember the number 0 1 2 3 4 5 6 7. I only need to write once only here because I am considering SOP, and SOP means I need to think of minterms. So I will only show once. So 0 1 4 and 6, that's it. Wait a second again. Now let's talk about POS. So in POS there is a slight error from my side. If this is A, I am going from A to BC only. So this is 0, this is 1. 0 will be denoted by A and 1 will be denoted by A bar. Here I should write B plus C. Now 0 0 means B plus C. 0 1 means B plus C bar. 0 1 1 means, sorry, 1 1 means B bar plus C bar, and 1 0 means B bar plus C. So this is how I will denote in POS. So 0 0 0 will be 0, 0 0 1 would be 1, this would be 2, this would be 3, this would be 4, this would be 5, this would be 6, and this would be 7. Right? Now what I need to denote, 2 3 5 7. 2 3 5 7. That's it. So this is how I will denote in POS. Let's go for 4 variables. Okay. So A is MSB and D is LSB. So do it on your own. Pause the video and do it on your own. Okay. You can write down the numbers on your own. See what will happen. Yeah. So let's start writing. AB can have 0 0 0 1 1 0 1 1. CD will have 0 0 0 1 1 0 1 1. Right? 0 0 0 0 0. A is MSB and D is LSB. So this would be 0 0 0 1. So this would be 1. What about the next one? This would be, wait a second, wait. 0 0 0 1 1 1 1 0. 0 0 0 1 1 1 1 0. Blunder it was. So it would be 0 0 1 1. So this would be 3. What about this one? 0 0 1 0. This would be 2. Similarly, if you write down these numbers, 0 1 0 0, what that would be? 0 1 0 0. 4. This would be 5. This would be 6. This would be 7. Where you will get 8? 1 0 0 0. Here you will get 8. Here you will get 9. Here you will get 10. Here you will get 11. Here you will get 12, 13, 14, and 15. In that manner we need to go. Okay. So I will erase this up. So generally we go up. Here we will write MSB and then we will write LSB. So this is the important part. 0 0 0 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15. So this you need to remember. We can derive for this one. I don't actually remember myself. 0 0 0 1 1 1 1 0. Only one bit distance has to be there. 0 0 0 1 1 1 1 0. So this is 0 0 0 0 only. So this would be 0. This is 0 1 0 0. What do you mean by 0 1 0 0? This is 4. This is 1 1 0 0. 1 2 4 8. 1 2 4 8. So 1 1 0 0, that would be 12. 1 0 0 0, that would be 8. Right? This would be 8. 0 0 0 1 0 0 0 1. So that would be 1. 0 0 1 1. So that would be 3. So this would be 2. Because 0 0 1 0. So that would be 2. Similarly, this would be 5. 0 1 0 1 5. This would be 6. This would be 7. This would be 8. This would be 9. This would be 10. This would be 12. 11. Sorry. 12, 13, 14, and 15. So in that manner, it will be given names. So here we did not see any SOP or POS. Just for both SOP and POS, in that manner it will be represented. Right? Fill the K-maps. Okay, fill the K-map cell. 0, 1, 2, 3, 4, 5, 6, 7. Most important point will come 8, 9, 10, 11, 12, 13, 14, 15. Okay. Now this is given. So can I write down the minterms? Can I write down the minterms? So what will be the minterms? 0, sorry, minterms I am writing. Why I am writing minterms? Because this is SOP. So 1, 1, 0, 1. Here what I will get? 1, 0, 1, 0. 1, 0, 1, 1. Because here D is also there, D bar is also there. This would be 1, 1, 1, 1. And this would be 0, 1, 1, 1. So 1, 2, 4, 8. So 13, 1, 2, 4, 8, 10, 1, 2, 4, 8. 1, 2, 4, 8. So it would be 11. This would be 15. 1, 2, 4, 8. 11, 10, 13, 15 and 7. So 7, 10, 11, 13, 15. These are the minterms. So these are our minterms. I hope you have seen the previous lecture, so it would be very easy for you to write down the minterms if you have seen the previous lecture. So if I am writing in SOP, then I will show the minterms. So how I can show the minterms? 7, 10, 10, 11, 10, 11, 13, 15. So that's it. This is how I can show SOP. And what this will be represented? This was 0, 0. So A bar, B bar, A bar, B, AB, AB bar. 0, 0, C bar, D bar, 0, 1, C bar, D, 1, 1, CD, CD bar, 0, 1 will be CD bar. Sorry, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. So C, CD bar. This was your SOP. And if I need to write down in POS, then here I should write A plus B into C plus A and here C plus D. So this 0, 0 means A plus B, 0, 1 means A plus B bar, 1, 1 means A bar plus B bar, and this would mean A bar plus B. Same goes here, C plus D, C plus D bar, C bar plus D bar, C bar plus D. Right? This number will not change. 0, 1, 2, 3. No matter whether it is SOP or POS, this number will not change because this is with respect to the decimal number. 8, 9, 10, 11, 12, 13, 14, 15. But you need to write down the max terms. So max terms will be a lot. That would be 0, 0, 0, 0. Apart from 7, everything is 0. Apart from 7, everything is 0. 12, 13, 14, 15 is 1. These are 0. And these are 0. Okay. So this is how I can show. Fill the key maps. You need to fill the key maps. Okay. So I need to copy. Tell me, you count here there are more ones or more 0? There are less ones, no? There are less ones. 1, 2, 3, 4, 5 and 6. 6 ones are there and 10 zeros are there. So I will try to write down the least numbers, right? I will try to write down the least number. And if I am looking at 1, that means I will be looking at SOP. If I am looking at 1, 1 means max term means SOP. So I will be writing down in this table. So what is this decimal number? 0, 0, 1, 0. So let's just write down the minterms. So this is 1, 2, 4, 8. So minterms for this would be 2. For this it would be 5. For this it would be 6. For this it would be 9. For this it would be 11. For this it would be 13. Right? So 2, 5, 6, 9, 11, 13. 2, 5, 6, 2, 5, 6, 9, 11 and 13. So this is how I can write it down. Right? Well and good. Now let's see this question. In this problem, what they are asking? The same question, but here tell me which bit is lesser, 0 bit or 1 bit. 0 bit is lesser. 1, 2, 3, 4, 5, 6, 7. 7 times there are 0 and 9 times there are 1. So I will be going with POS. So I will not going with this. These numbers will not change. This would be A plus B. This would be C plus D. So A plus B bar 0 0 0 1 1 1 1 0 0 0 0 1 1 1 1 0. Why we are doing so? What is the motive behind this? Everything will be cleared, but you need to have the patience. Then only this video is helpful for you. If you don't have the patience, then we cannot do anything, right? So what will be your max terms? Max terms will be 1 2 4 8. So this would be 1. This would be 3. This would be 4. This would be 7. This would be 1 here 1 0 1 1. So 10, right? This would be 12. This would be 14. 1 3 4 7 10 12 14. So at 1 you will have 0, at 3 you will have 0, at 4 you will have 0, at 7 you will have 0, at 10 you will have 0, at 12 you will have 0, at 14 you will have 0. So this is how I will represent in POS form. Okay. Now we have understood how to represent in 3 variable, 4 variable and 2 variables, how to represent. Now what is our next task? Next task is to minimize. So how we will minimize? So there are certain rules. So certain rules there are which needs to be followed for minimization. So first one is club the adjacent cell. You need to club, you need to make pair or quad or a single element, but from the adjacent cell only. What do you mean by adjacent cell? For this particular cell, adjacent cells are this one and this one, and for this particular cell, adjacent cells are this one. Basically for this one, these were the adjacent cell. For this one, this is the adjacent cell and this is another adjacent cell. Now for this one, this is the adjacent cell, and for this was the adjacent cell, and this is one of the adjacent cell. Are you getting the point? This is adjacent to this one, this is adjacent to this one, this is adjacent to this and this is adjacent to this and this is adjacent to this and this. Similarly here, these two are adjacent, these two are adjacent, these two are adjacent, these two are also adjacent, these two are adjacent, these two are adjacent already, these two and these two, these two, these two and these two. One more very interesting thing, K-map is like a closed loop. Okay, K-map is like a closed loop. So this cell and this cell, they are also adjacent. Okay, this cell and this cell, they are also adjacent. Don't feel like it a paper, it is like a closed loop. If it is a closed loop, that means if you close it up, then these cells and these cells will be adjacent to each other. Are you getting this point? What about this one? Think it as a closed loop from these side as well, from up and down side as well. So these adjacent cells we can directly tell these are adjacent, right? These are very straightforward, these are adjacent cells. This we can directly tell, right? all these are adjacent. I will just make all the arrows because I don't want people to get confused. These are adjacent cells. But what else adjacent cell will be there? Think it as a closed loop. That means this cell will be adjacent to this one. This cell will be adjacent to this one. This cell will be adjacent to this one. And this cell will be adjacent to this one. Think it as a closed loop. So from here also it is closed. So this cell is adjacent to this one as well. Okay. And this cell is adjacent to this one as well. This cell is adjacent to this one as well. This cell is adjacent to this one as well. Are you getting this point? So this particular cell is adjacent to this particular cell is adjacent to this one, this one, this one, and this one. This particular cell, let's just say this is A, this is B, this is C, and this is D. So A is adjacent to this, C, and B. A is adjacent to B, C, this one, and this one. Are you getting this point? A is adjacent to B, C, those two dots. B is adjacent to A, D. Are you getting this point? Are you understanding this? Or I need to explain it more? Look, I can have a paper. In that manner, I might be able to explain it. If you are not able to understand, if you are able to understand, then it is fine. So it is like this closed structure, and from upper side as well it is closed. So A will be adjacent to B, right? And from like in this manner also it is closed. So this A will be adjacent to C as well. Are you getting this point? In this manner it is closed, and from upper side also it is closed. So this A will be adjacent to B, and A will also be adjacent to C, because in this manner it will be closed. So these two will be adjacent, and these two will also be adjacent. Same goes for B. B will be adjacent to A, B will be adjacent to D as well. Same goes for D. D is adjacent to B, C, and other two elements, basically these two elements. B as well, B is adjacent to A, D, and other two elements. These elements we can directly see, right? So this is how they are adjacent. So everything, it is like a closed structure. Getting this point? What about this one? Let's just say this is E and this is F. So E will be adjacent to this point, this point, this point, and F. E will be adjacent to this point, this point, this point, and F. Right? Now, don't club diagonal elements. Basically, in this manner, this is your diagonal, right? This is your diagonal. So in this manner, you cannot club that sir, I have clubbed this thing. I have clubbed these two elements. This clubbing is not valid. We have to club in this, like this. So this is acceptable. Or you can club like this as well. This is also acceptable. Or how you can club? Quad also you can make, or you can club all those elements together. This is also acceptable. This is also acceptable, right? But let's just say I do like this, that sir, I am clubbing these elements. So this is like 4 elements only. Basically these are 4 elements. So this is acceptable as well. One more thing will be acceptable. What is that? These 4 elements, 1, 1, 1, 1 here. These 4 elements, because this is like a closed loop, no? So these 4 elements will be also clubbed together, right? These 4 elements can also be clubbed together. 1, 2, 3, 4. This will also make a quad, right? These 2 elements and these 2 elements can also be clubbed together. Closed loop. These 2 and these 2, right? This one and this one can also be clubbed together. So we will see that. Okay. So and there is a note between 2 adjacent cell in K-maps, there will be a difference of 1 bit only between 2 adjacent cell. Let's just say, let's talk about this cell. What this cell would be? If this is 1, this was 0, 0, this 0, 1. So this cell is 1, 0, 1. And what about this one? This was 1, 1. And this cell is 1, 1, 1. So how much difference is there? 1, 1 is same. only 1 bit difference is there. So between two adjacent cells, there will always be difference of 1 bit only. Okay, in any two adjacent cell, if you go from here to here, there will be difference of 1 bit only. So that you can remember. Okay, or I will just write it down in this manner. So these are the points. It might seem typical to you, but it is a very easy chapter. We will slowly proceed in the chapter and you will be able to understand everything. No need to worry. Clubbing can be done in the order of 1, 2, 4, 8 or 2 to the power n cells only. That means you can take a single element, let's just say this clubbing, wait a second. Let us say this clubbing I am doing. So this is acceptable. Okay. This is also acceptable. 1, 2, this is also acceptable. But this is not acceptable. 6. This is not acceptable. 6, 1. Not acceptable. Here you say that, sir, here 1, 1, 1, 1 are there, so I can club all of them together. No, this is wrong. So only 1, 2, 4, 8, these elements can be there. Basically, this clubbing will be acceptable. This is acceptable because 4 elements are there, right? Another one more clubbing is there which is acceptable. 1, 2, 3, and 4. Now, this clubbing will not be acceptable. 3 elements are there. 3 elements are there, right? 1, 1, 1. 3 elements are there. This is not acceptable. So if you are doing the clubbing, you need to make sure that it has the element in 2 to the power n fashion. Okay. Make the best possible pairs, avoid redundant pairs. Number of pairs should be minimum as possible. Okay. So let's understand the meaning of this line. Make the best possible pair. So can I make any pair of 4 elements here? 4 ones. Can I make any pair of 4 ones? No. I cannot make this pair that, sir, this and I will go like, sir, this is my pair. Sir, this is my pair. Now, this is not a valid pair. I told you the pair can be 4 altogether or 2 or 2. So pair the adjacent cells only. So this pairing is acceptable. This pairing is also acceptable. Now, this element has been paired, this element has been paired, this element has been paired, this element has been paired. Now, what if I make another pair? 1, 1. Is there any use of this pair? No, this is redundant pair. Redundant pair. Okay. Redundant pair. So there is no use of this pair. This is a redundant pair. Why this is a redundant pair? Because all elements have been already clubbed. This element has been 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 clubbed. Now in this club, again you are clubbing 1 and 1. So this is a redundant pair. So you don't need to club these pairs. So what they are saying, make the best possible pair and avoid the redundant pair, also making sure that number of pairs should be minimum. So here we are making 3 pairs, but only 2 pairs would be more than enough, right? Let's go to this problem. I can make the pair of 2 and 4. Can I make the pair of 4 here? Yes. There you go. So this is one of the pair. All these elements are clubbed. This is clubbed, this is clubbed, this is clubbed, this is clubbed. Now I need to club this one as well. So will I make this pair only? That a pair of only one element. Pair of only one element. Pair of only one element. Will I do that? No, because I told you I need to make best possible pair. That means I will try to take 4 ones. Can I take 4 ones? I need to include this one and I need to take 4 ones. Can I take that? No. I can take only 2 at a time. I can take only 2 at a time. Okay. Are you getting this point? Now, if someone says that, sir, one more pair is there, this one. This is redundant. Redundant pair. This is redundant. Someone will say, sir, this pair is also there. What is the meaning of that? Because these elements are already paired. If these elements are already paired, why would you think of these pairs? So this is also redundant. So these are redundant pairs. Let's talk about this one. So first thing what I will do, I will see the pair of 4. So there you go, I saw the pair of 4. Okay, now let's see. I need to pair this one, this one, this one. So how will I pair it? There is only one chance. I can pair it with two guys, right? I need to pair this one as well. There is only one chance that it can be paired with this one only. I need to pair with this one as well. There is only one chance. And I need to pair this one as well. There is only one chance. What are you getting? That all these ones which were there in quad, this is known as quad, right? This is known as quad. So all these ones which were there in quad has been paired with another one. So this quad is a redundant pair, redundant quad, redundant quad. Why this is a redundant quad? Because this one has no other chance to go. This one has no other chance to go. This one has no other chance to go. So this one will go with this one only. This one will go with this one only. This one will go with this one only. And this one will also go with this one bit only. So these ones have no other chance. So they have to be paired in that manner only. But in the beginning, the quad that I took, that is needless. Why that is needless? Because all the ones have been already paired. So if I am making 5 pair, I do not want that. I can make only 4 pairs and all the ones are paired. Our target is to pair all the ones, that too in the minimum number of pairs. So number of pairs should be minimum. So if I am making 5 pairs, what is the need of this particular quad? So that is a redundant quad. I will not take this quad in action. Okay, we will solve more problems. It will be clear, more clear. Let's try clubbing here. So I will try to look at 4 numbers. Like I will try to make a quad of 4. Quad will be of 4 only. So I will try to club 4 cells together. Can I club 4 cells together here? Can you see it? Yes, I told you one thing. This and this. These 4 can be clubbed together. These all 4 can be clubbed together because this is like a closed structure. So all these ones will come at a single point. So these 4 can be clubbed together. There is one more quad possible. Can you see that? There is one more quad possible. Which is that quad? This is the quad. The 2 elements from here and these 2 elements are adjacent to these 2 elements. So there is one more quad that is possible. Okay. So basically this element, 2 quads I have made. Now you cannot say that, sir, this one has already been clubbed, but this one was not clubbed. This one was not clubbed. This one was not clubbed. So for that we have made another quad. Okay. And what about this one? That I will make this pair. Why I will make this pair? Because this one has no other chance to go. So this one can be paired in this manner only. This one has no other chance to go. So this has to come here only. This one has other chance to go. And it can go here. But why would I make it? Why would I make this pair? Because I know this thing that this one has already been clubbed. And if I club it with this one, then this one will be empty. So first I will club this particular one. And if I have clubbed this one, then I don't need to club this one now. This pair will be redundant pair. So I will not do that. This pair will be completely redundant. So this is a redundant pair. So I will avoid this. This is a redundant pair. Redundant pair. Try doing this on your own. How will you club? Can you club 4 elements here? No, you cannot. Anywhere you cannot club 4 elements. Basically here also these 2 and these 2 could be clubbed, but there are no ones. So we cannot club 4 elements, right? We cannot club 4 elements. So we will club 2 elements. This is the direct I can see. This is also direct I can see. 1 1. Will this go alone? Will this go alone? No. Why this will not go alone? Because it has one more chance, that is this one. This one can go with this particular one, right? These 2 can go together. So a pair of 2. So you need to take care, it is a closed structure, so in that manner we need to proceed. Okay. Effectively use don't care. So what do you mean by don't care? It can take any value 0 or 1. It depends on me. The output, this don't care is in output now, right? Because we are plotting the output 0 0 1 1. So these ones we are plotting here, and then there is. So basically, no matter, let's just say there was three bit input 0 1 0. So if your input is 0 1 0, then your output, you don't need to care about the output. You can take output to be 1 as well, you can take output to be 0 as well. If your input is 0 1 0, this is what don't care means in the output. Don't care in the input means even if your input is 0 or 1, your output will be same. And here, no matter whatever the input is there, you don't need to care about output. You can take it equals to 1 as well, or you can take it equals to 0 as well. Now tell me one thing. If I assume this as 0, then what will be my pairing? If I assume this as 0, this will be my pairing 1 and 2. But if I assume this as 1, so what will be my pairing? There you go. So I will use it effectively. I will use it effectively, that I will assume this don't care as 1, so that I can make a quad, and that's it. This is the only one quad I have to make, and all the elements are clubbed. Now what about this? If I assume this as 1, if I assume this don't care as 1, then which club we will have to make? This club and this club, right? But if I assume this as 0, if I assume this as 0, that means 1 is not there, I need to club only ones together, so only one club I will have to make. So only one club is there. Look, don't care it can take 0 and 1. I need to do the clubbing. I will do the club of 1 1 1 1. I will do the club of 0 0 0 0. That we are not seeing as of now, but we can do the clubbing of 0 as well. But here as of now we are seeing the clubbing of ones. So if I need to club the ones, then why would I put this don't care as 1? Because if I put this don't care as 1, then I will have to make 2 clubs. If I put this don't care as 0, that means I don't need to club this. What do I mean by that? If I have written 1 1 here, that means here there are zeros, right? Here there are zeros, here there are zeros, here there are zeros. If I have written 1 1 here, so if I put this one as 0 as well, then I don't need to club anything. I will just club these two variables. Okay, that's it. Write down the Boolean expression. Okay, after that you will write down the Boolean expression. How you will write that? Let's conclude everything and solve a problem. So after that, now we will solve a lot of problems. 1 2 3 4, a lot of problems are there. Once you solve these problems, things will be more clear to you. Okay, let's show the minterms now. Minterms is there 0 and 3. I know that, I remember the number 0 1 2 3. If I need to show the minterms, so here there was 0, here there was 1, so a bar A, b bar B. Minterms are 0 and 3, so 1 will come here, 1 will come here, right? 1 will come here, 1 will come here. What is the best possible pair? Can I make this pair? No, they are diagonal. They are diagonal. I cannot make this pair, right? So only single element pair is there. Only single element pair is there. Now, I cannot say this is a pair, only single element is there. So only clubbing is there for single element. Single element clubbing is there. Now for this particular block, what will be your y? Y will be, for this particular block, what is the value of this particular variable? That is a bar. And what is the value of this particular variable? That is b bar. Plus, because we are writing in terms of minterms, in this block, what is the value of this particular variable? That is a. And what is the value of this particular variable? That is b. So y is equal to a bar plus b bar. There was no reduction. Let's just say if there is reduction here, so a bar a, b bar b. This is 0 1 2 3, right? So in 0 I will write 1, here I will write 1, and here I will write 1. What are the possible clubs? One pair is there, another pair is there. These two pairs are possible. Now for this particular pair, what are the values of b and b bar? So value of b is changing. So if value of B is changing, we don't need to care about that. Which value is constant? A bar is constant. So A bar plus, for this one value of A is changing but B bar is constant for this particular pair. For this particular pair, B bar is constant in both of the cells. B bar is constant but A value is changing. So I don't need to care about A. So it will be A bar plus B bar, or you can say AB bar. So isn't it the min terms of a NAND gate? This is a NAND gate only, right? This is a simple NAND gate only. If I had to write down directly, then I would have written in this manner: A bar B bar plus 1 is there, that means 0 1, A bar B plus A B bar. This is how I would have written. Then I can reduce it. So this will be reduced to A bar only. So A bar plus A B bar. So A bar plus A B bar would be A bar plus B bar, and that would be A B whole bar. But by making this diagram only, we have reduced it very easily. So this is the use of our K-maps. We will solve more problems. We will keep on solving the problems and it will be clear to you. Let's go about this problem. So we need to, here max terms are there. Max terms are there. So this would be A, this would be A bar, 0 1. This would be B, this would be B bar. And this I remember 0 1 2 3, irrespective of min terms or max term, this number will be there. Since this was 0, this was 1, this was 0, this was 1, this was B, this was A, this was B bar, this was A bar. So 1 and 2. Any pairing possible? This pairing is possible? No, this pairing is not possible. So single element has to be there. So for this particular element, A bar plus B, I will write in POS form, A bar plus B into, for this particular element, B bar plus A. B bar plus A. This is XNOR gate only, right? This was also XNOR gate, this was also XNOR gate. Basically 0 3 was there, so in pi I would have written 1 2. So I get to know that the same expression I am getting. Sorry, here I have written 1, really sorry. It would be written as 0, because output of max term is 0. So it would be written as 0. So A, for this particular block, B bar plus A, and for this particular block, A bar plus B. So if I am writing in terms of max term means POS form. So in POS form I will be writing. Let's do this thing. 0 1 2, 0 1 2 3. I remember this would be A, this would be A bar, this would be B, this would be B bar. So 0 0 and 0. This pairing and this pairing. These two pairing are possible. So what will be my output? So in this particular way, in this particular pair, only A is constant. In this particular pair, only A is constant. So this is pairing is done. Now bracket multiplied by, because POS is there, you are not going to add now A plus something. No. You are going to multiply. POS form I am writing, product of sum. So one term is there. Now you are looking at the other pair. This is the other pair where B is constant. So Y is equals to AB. That's it. Y is equals to AB. So this is what we are getting. So first I wrote down A for this particular pair. Then I wrote down B. So Y is equals to AB. Are you understanding the point slowly? Did you understand this point? I did not write A plus B. Here what did I do? For this particular block, for this particular cell, or for this particular, I can say block only. So for this particular block, I have A plus B bar, that I wrote. Then bracket, dot bracket. For this particular block, I need to see. Here also for this particular pair, I am writing A. Then dot, for this particular pair, I am writing B. So Y is equals to AB. Let's solve this problem. Now don't care is 1. So this will be 0, 1, 2, 3. 0 and 3 are 1. And this don't care is 1. Okay. This would be A bar, because I am writing in terms of min terms. This would be A, this would be B bar, this would be B, because 0 1 0 1, right? What do you think, what I assume in terms of what will I do of this don't care? What do you think? Will I put it 0 or will I put it 1? I will put it 1 only, because if I put it 0, then these will be my pair. The pairs will be of one element, right? But if I put it 1, then this will be the clubbing. and this will be the clubbing. So what will be my y? Y will be, in this one only a bar is there and in this one only b is there. So y is equals to a bar b. Y is equals to a bar b, and in case of don't care, I have assumed it to be 1 only. So y is equals to a bar b. Here b is constant, a is changing, in this pair a is changing. For this particular element a is a bar, and for this particular element it is a, but b is constant. So a bar, sorry, here I did the mistake. Okay, these kind of mistake you can also do. A bar plus b will come. Sum of product, I am writing sum of product. So a bar plus b. Did you understand this point? It is sum of product. Sum of product. So first term I wrote, then I need to write sum, then second term I will wrote the sum of product. Okay, so these kind of error you should not do. A bar plus b. What about this one? 0, 1, 2, 3. So at 0 place you will get 0, here you will get 0, and don't care is 1. This would be a, this would be a bar, this would be b, this would be b bar. Make sure it is product of sum. This was sum of a product. This was one of the product term, this was one of the product term, and then we did the sum. This is product of sum. What do you think? 0, 2. What do you think? What I will assume? If I assume this as 0, then I will have to make these two pairs, 1 and these two. But if I assume this as 1, then only this pair will work. That's it. So this pair is working, and here only b is constant, so y is equals to b. So your answer is y is equals to b. That's it. Y is equals to b. Okay. Let's go with the 3 variables now. You can solve these examples again on your own. Okay. Let's go to 3 variables. We will solve more problems, no need to worry. So I remember 0, 1, 2, 3, 4, 5, 6, 7. Right? So 2, 3, 5. 2, 3, 5. So this pair is possible. How this one can be paired? No other pair is possible, right? No other pair is possible. Only one can go alone, because one can be paired with this one, one can be paired with this one can be paired with this one, but nowhere there is anything. One cannot be paired with this one, that is diagonal. So one has to go alone. So this will go alone. So this would be a bar a, because 0, 1. This would be b bar c, sorry, b bar c bar, b bar c, bc, bc bar. I actually remember it, 0, 0, 0, 1, 1, 1, 1, 0. You will also have the habit. Now, how will I write down the output? Make sure it is sum of products. So first I will write down the product term, and then I will do the sum, then I will write down the another product term. So first I will look at this pair. In this pair, c is changing, c is c bar, but b is constant, so b will come. And a is also constant because a is a bar only. For this particular pair, a is always a bar and b is also same. So b into a bar plus, for this particular pair, a b bar c, a b bar c. Right? Any other reduction is possible? No other reduction is possible, because after K-maps, least reducted form you will get. Okay, like this is the last reduction you can make. After that you cannot make any reduction. Let's see this one again. 0, 1. We will not write down the numbers now. 0, 1, 2, 3. We have to fill it on our own. Let's try it. This would be 1, 0, 1, 2, 3, 2, 3, 4, 5, 6, 7. Say yes or no, right? So which we dropped? 1 and 5. 0, 1, 2, 3, 4, 5. Yeah, right. Can I make a pair of 4 here? Yes. Can I make another pair of 4? Yes, I can. How I can? There you go. Another pair of 4 is also possible. Now, this I have to write a bar a, b bar c bar, p bar c, BC, BC bar. For this particular quad, A is also changing because here A is A bar and here A is A. So A is also changing. Here C is also changing, C bar. But in this particular quad, B is constant. So B will be there as it is. Remember, it is sum of product. So product term you have written plus you will do. Now let's look at this one. BC bar, B bar, C bar. So B changing here. B changing. B is becoming B bar, but C bar is constant. C bar. What about A? A is changing because A is there in both A and A bar. A is changing. Basically, for this particular quad, here this is A, and for these elements this is A bar. So A is also changing and C is also changing. Sorry, B is also changing, but C bar is constant. C bar is here, C bar is here. So B plus C bar. This is how I can write it. Okay, so this is my reduced expression. Make sure you do not write B C bar. Okay, that would be wrong. This would be sum of product. Sum of product. Okay, let's see more examples. This would be A, this would be BC, right? So 0, 1, 2, 3, 4, 5, 6, 7. This would be A, this would be A bar, 0, 1. And here I have done the mistake, it should be written as B plus C. What this would be? B plus C, this would be B plus C bar, B bar plus C bar plus B bar plus C. So 1 is 0, 2 is 0, 5 is 0 and 6 is 0. 4, is there any pair of 4 numbers? Is there any pair of 4 numbers or 4 cells? No, not possible. Only these two are possible. That's it. There you go. So what will be Y? Make sure it is product of sum. So first I will write down the sum term. So in this particular pair, A is changing but B bar plus C is constant. B bar plus C is constant. Now in this particular pair, A is changing but B plus C bar is constant. That's it. Okay. Let's solve this one. Without even writing, I will solve now. These things I have to write. This is A, this is A bar. This is B plus C was there. So B plus C, B plus C bar, B bar plus C bar, B bar plus C. So 0, 1, 2, sorry, 0 I need to write. 0, 1, 2, 3, 4, 5, 6, 7. Right? 5 element I have shown. 0, 1, 2, 3, 4, 5, 6, 7. Yeah. Directly I can see a pair of 4 here. What I am writing? POS I am writing. So Y will be. What is changing? C is changing but B bar is constant. So B bar. A is also changing. A bar. So A is here and here it is A bar. So A is also changing. C is also changing. But B bar is constant. Product of sum. Product of sum. So next I will put product here. What could be my other pair? My other pair would be this. This 0 can go with this one. I cannot make a pair of 3. I can make only a pair of 2. Now you cannot say that, sir, this 0 can go with this one as well. No. They are diagonal. They are diagonal. But they are adjacent. They are adjacent. Okay. In 4, when there is 4, these are not diagonal there. All these 4 are adjacent because this will frame a closed loop. So all these 4 are adjacent there in 4. Okay. So a closed loop it will frame. So all these 4 are adjacent. But here they are diagonal. So product of sum is there. That means I will put a dot here. And here B changing but C is constant and A is constant. So B bar into C plus A. That's the reduced expression I can get. B bar into C plus A. In this particular quad, B bar was constant. A was changing and C was changing. In this particular pair, C is a constant but B is changing and A is also constant. A is also constant, so C plus A. In that manner we are proceeding. Let's see this one, where don't care are 3, 7. A bar A, B bar C bar, B bar C, B C, B C bar. So 0, 1, 2, 3, 4, 5, 6, 7. 0, 1, 2, 3, 4, 5, 6, 7. Well and good. Which we dropped? 1, 2 we dropped, 4 we dropped. Okay. What do you think? What you will do of don't cares? Can I make a quad using that don't care? If I pick don't care as 1, there you go, I am having a quad. Can this one be clubbed with this one? No, this one cannot be clubbed with this one. So this one has to go here, and this one can go here. That's it. These are the pairs I can make, right? So let's write down y. How I am writing? Sum of product. Sum of product. So in this particular quad, A is changing, C is constant, B is also changing. So C, sum of product plus, in this particular pair, B is constant and A is constant. So AB plus, in this particular pair, B bar is constant because C is changing and A bar is constant. So A bar plus B bar. That's it. This is the reduced expression. Okay. Because if I use don't care as 0, then I will not get a quad. I will still have to make 3 pairs. Because these 1, 1, these two 1, 1 will go together. If I don't assume don't care as 1, so certainly I should assume don't care as 1 only. So quad I am getting, then this I am getting, and this I am getting. So this is the reduced expression. Let's see for the next question. A, B plus C. This would be A here, and this would be A bar. B plus C, B plus C bar, B bar plus C bar, B bar plus C. 0, 1, 2, 3. 0, 1, 0, 1, 2, 3. 4, 4, 5, 6, 7. Right? What do you think? What you will do? I will assume this don't care as 0 because I can make a quad. Why would I assume this don't care as 0? If I assume this don't care as 0, I will have to make another pair which is of no use. So I will don't assume this don't care as 0. I will assume this don't care as 1 only. And now another pair I will have to make. That's it. Because this don't care can be 1 as well. If this is 1, then I don't need to club it. I am clubbing zeros only. So this club and this club. 2 clubs I have made. That's it. And what I am writing? POS I am writing. So y would be equals to what? Here A is changing and C is also changing. Only B bar. Product of sum. So product sign will be there. Product of sum. What about this one? Here C bar is constant and A is constant. A plus C bar. That's it. This is the answer. Okay. So in this manner we can proceed in our calculation. Let's solve some problems for 4 variables. These problems we will solve. More problems are there. Later on we can solve more problems in the next lecture. So let's do it for 4 variables, at least a few examples so that you have a clear idea. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So minterms are there. So 0, 1, 3, 4, 5, 6, 7, 13 and 15. Let's first make the clubs. Club of 4 is possible. Club of 4 is possible here as well. And another club of 4 is possible here as well. So 3 clubs of 4 I have made. Let's show it. Let me show it again. 1, Then club of 4 only I am going to make. 2 and then 3. Any of them is redundant? No, because this one has chance to go here, here and here only. Look, this one is engaged in 2 blocks. This one is also engaged in 2 blocks. This one is also engaged in 2 blocks. But this one is engaged only in 1 block only. Are you getting this point? All these ones are engaged in 2 blocks, but that particular one is not engaged in any other block than 1. So there is no redundant pair. Okay. Here I can write A bar B bar, A bar B, A B, A B bar, C bar D bar, C bar D, C D, C D bar. Okay, so this was, here I can put star mark that this was not paired with anyone. Here also these two were also paired in only 1 block. These two were also paired in 1 block. So no block was redundant here. No clubbing was redundant. All the clubs were fine. And what I am writing, SOP, sum of product. So in the first club, B is not changing, right? And here D is not changing. In the second club, again D is not changing. This is the second club I am talking about. Again D is not changing and A bar is not changing. D into A bar. Plus in the third club, C bar is not changing. C bar is not changing and here A bar is not changing. That is the answer. That is A bar C bar plus A bar into D plus PT. So literal count is 6. Okay, so this is the finalized expression. Try doing this on your own. We will see it in next lecture. Okay, we will continue it in the next lecture. Try doing these questions on your own, which I am showing you. Okay, try doing these questions. Draw K-maps. Don't try these questions. I will tell you how to solve these kind of problems. But at least K-maps problem you can revise, because for now it may seem a bit typical to you. But once you have the habit, because in combination circuit also you will be using it, so you will develop the habit slowly. Okay, so in the next lecture we will see these kind of concepts. Then 5 variable K-map also we will see, and then we will solve a few more problems, a few more concepts we will see, and in the next lecture I think we will be able to finish K-maps. Okay, so let's meet you in the next lecture. Hi everyone, so let's continue our previous lecture only. So we were solving the problems of K-maps. We have understood the basic concept. Now we are solving the problems. So let's solve this one. So 1, right? Then 5 where it will come, 5 here. 6, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So this is our K-map. Very famous example, we have already seen it. If I make this quad will be redundant. Why so? Because this one element can go here, this one element can go here, this one element can go here, and this one element can go here. If I had already made this quad, then it would have been redundant, because each of its element has been already clubbed with another one, right? Each of the element has been clubbed with another one, so this is simply redundant. There is no use of it. And here I will write down the words, that is A bar B bar, A bar B, A B, A B, A B bar. Here C bar D bar, C bar D, C D, C D bar. I am focusing on minterms, that means I will write SOP, sum of product. What I will write, sum of product. So how I will write sum of product? So first let's see this one. So here C bar D is constant, C bar D is completely constant, and A bar is constant. So A bar C bar D plus. Are you getting this? In this club, in this pair, C bar D is constant and A bar is constant. So A bar C bar D. What about this pair? In this pair, A bar B is constant. A bar B is constant, because A bar B is constant here. And what else is constant? C is constant, right? Plus in this pair, CD is constant. Along with that, A is constant. So A C D plus. What about this pair? Here AB is constant and C bar is constant. So AB C bar, right? AB C bar. So that's it. This is our SOP form. So this is how we need to solve. Let's solve more examples. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Did I write it right? And what I am focusing on? Maxterm. Maxterm means I will be focusing on zeros. Zeros means I will be focusing on POS. This would be A plus B and this would be C plus D. So first I will start with A plus B, then A plus B bar, then A bar plus B bar, then A bar plus B. This would be C plus D, C plus D bar, C bar plus D bar, C bar plus D. Okay. Let's check it again. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yeah. So let's start making the pairs. So what do I see? First I will see the pair of 4. Can I see the pair of 4? Yes. These 4 are, this is the pair of 4. This is the toughest pair to see, but we have built the practice. So this is the pair of 4 we can see. Now I need to pair this one, this 0, this 0, this 0 and this 0. Can I make any other pair of 4? No. So this 0 can go here, this 0 can go here, this 0 can go here and this 0 can go here. Do you see one thing here? What is that? The pair that you made 0, 0, 0, 0, that is again redundant because each 0 is being paired. Each 0. In this pair, which zeros are coming? This one, this has been already paired. This 0 is coming, this has been already paired. This 0 is coming, this has been already paired. And this 0 is coming, this has already been paired. So this group is completely redundant, which we will not take. Why we are not taking? Because this is a redundant group. Each 0 has been already clubbed, right? So how I will write the form? So in this one, A plus C plus D. C plus D is constant, A is constant. So A plus C plus D. In this pair, C bar is constant, A plus B is constant. A plus B plus C bar. In this pair, C bar plus D is constant and A bar is constant. So A bar plus C bar plus D bar. And in this pair, C is constant, A bar plus B is constant. A bar plus B plus C. So this is the POS form, minimized POS form. If you had taken this pair as well, then another term would have come that is of no use, right? So these kind of things you need to take care. Let's see this example. 0, 1, 2, 3. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, very random example it is. I have taken very random example actually, right? So don't think we are getting anything good from here, just very random. So 4 club I cannot see. Can I see 4 club? No. So this I have to club, and this I can club. Now this 0 I can club with this one as well and this downward as well. I can club with anything. Okay, this 0 I can club with that other 0 as well, right? This 0. This 0 but this 0 I can club downward as well. So one pair we need to choose. One pair. Okay, it's not that you will choose both of the pairs. One pair you need to choose. This 0 and this 0, because this has only this chance, this has only this chance. This pair will be there. This pair will be there. This pair has to be there. This 0 has 2 chances. This 0 has 2 chances. So there will be 2 outputs of y. There can be 2 outputs of y because this other 0 has 2 chances, right? This has this chance as well. So there can be 2 different expression of y. So from K map we can get 2 expression as well. Okay, here we are getting. But in both of the expression, the number of literal count will be same. What is the literal count here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12. Now we will write two expressions, both will have the same literal count, right? So this is a plus b bar, this is a bar plus b bar, this is a bar plus b, c plus d, c plus d bar, c bar plus d bar, c bar plus d. Let's see this pair first. So a is constant plus c plus d bar. In this pair, a plus b is constant, a plus b is constant, and d bar is constant, a plus b plus d bar. Now let's talk about this particular pair. In this particular pair, a bar plus b bar is constant, a bar plus b bar is constant, plus c bar is constant, c bar is constant. Let's talk about this pair. This pair, in this pair, a bar plus b is constant, a bar plus b is constant, plus c is constant. Okay. And what about this pair? There are two pairs. So let's take this pink one. If we take the pink one, so in pink one, c plus d is constant, c plus d is constant. Or let's take the green one first. So here a bar plus b bar is constant, plus d is there. This is the same. Okay, let's check back again. A plus a is constant here, c plus d bar. For this one, a plus b plus d bar. For this one, a bar plus b bar plus c bar. For this one, a bar plus b plus c. And for this one, a bar plus b bar plus d. Okay. Or what could be the expression? Or the expression could be, first 4 term will go as it is. First 4 terms will go as it is. But in the last term, we will go with the pink one. So in the pink one, a bar is constant and c plus d is constant. A bar plus c plus d. Okay. So note, using K-map, you can get two different reduced Boolean expression with the same literal count. With the same literal count. So in MSQ, these kind of questions can come, that both options you need to click. Which one is the reduced expression? So both are reduced expression only. Both options you need to click. Okay, so these kind of questions can come in MSQ. Right? Let's see more problems. Don't care is 3, 8, 10. So let's start. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 8, 9, 10, 11, 12, 13, 14, 15. Okay. Now let's see. Let's check back again. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. We should always recheck, because if we mess it up, if we mess this one up, then whole question is wrong. So this should be filled with good amount of patience, right? Can I, using the don't care, can I make any pair of 4? I don't think I can make any pair of 4. So which are the best pair I can see? As per me, these will be the best pairs. 1, 2, and 3. That's it. Why should we consider any don't care as 1? So 3 pairs has to be there, because I don't think I can make any pair of 4. If I cannot make any pair of 4, that means I have to make a pair of 2. And if I have to make the pair of 2 and with the 6 element, then certainly 3 pair has to be there. So if 3 pairs are there, then why would we consider these don't care as anything? So let's not consider don't care. Okay, so 1, 1, 1, these 3 pairs are there. All don't cares are 0 here. Okay, So this is your A bar, B bar, A bar, B, A, B, A, B bar, C bar, D bar, C bar, D, C, D, C, D bar. So 3 pairs are there. And what is this? This is sum of product. So here B is constant, C bar, D bar is constant. B, C bar, D bar, B, C bar, D bar, plus here A bar, B, A bar, B plus D, and here A, B, C, A, B, C. Okay, this is Y. What about this one? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So this is the scene. Okay. Can I make a pair of 4? Yes, I can make 2 pairs of 4. What I can do here, I can go like this and this. That's it. Or I have one more chance. What is that? I have one more chance, that is, with the help of don't care, I make this block. Basically, I would take this 4 block and these two zeros will be paired with these two don't care. So again there are two blocks only, one quad and another quad. Or I could have taken one quad and then this quad. This is what I would have done, one quad and another quad, all zeros are captured. Or I could have done one quad and then this quad, one quad and then this quad. So there, here also there are two possibilities, because there are these don't cares. So if don't care, I can take as 0, 0. So this quad and this quad also I could have taken. So in both of the cases, two quads are coming. So both are reduced expression only. Both are reduced expression. So first write down the first one, that is, in this quad C is constant and this quad A is constant. And this is already written there. Okay. So in this quad A is constant, and in this quad C is constant. So A plus C into, in this quad A plus B is constant. This could be one of the answer, or Y is equals to A plus C, and in another quad here C bar is constant and B is constant. B plus C bar, right? B is constant and C bar is constant. So B plus C bar. This could be other answer. So both answers are correct. Okay, both are reduced expression, both are having the same literal count. So two possibilities are there. So you will be having the options, right? So you will check all the options. From options you can check the clubbing, right? You can check the clubbing with the help of options. So you will check which all possibilities are there in the examination. We will solve these kind of problems so that you don't get confused. Okay. So these possibilities were there. Now let's see this question. You are given an n variable logical expression. In K map, you have done grouping of 2 to the power k cells. What will be the literal count of that particular group? N is greater than k and k is a whole number. So what I can take? I can take n is equals to 3 and k is equals to 1. Because if I take n is equals to 2, and k is equals to 1, then 2 minus 1 will be 1. This option will also be 1 and this option will also be 1. So both two options will match. So that I don't want. So intelligently I am taking n equals to 3 and k is equals to 1. That means 3 variable is there, and I am doing the grouping of 2 cells grouping. So basically this is the scene. There are 3 variables and grouping of 2 cells I am doing. This is the grouping I am doing. So let's just say this is A, B, C. So this is B bar, C bar, B, C bar. So basically, what will be the literal count of that group? What will be the literal count? Y will be what? If I am doing this grouping, so Y will be what? B, C bar. So what is the literal count? Lateral count is 2, right? So in which option you will get 2? 3 minus 1, that is equals to 3 minus 1, or you can say n minus k. So that is the correct answer. Okay, are you getting this point? Basically, in n variable, if you do the grouping of 0, then least count would be n minus 0. In n variable, if you do the grouping of 1, then it would be n minus 1. In n variable, if you do the grouping of 2 to the power 2, it would be n minus 2. And in n variable, if you do the grouping of 2 to the power k, it would be n minus k. The least count would be n minus k. This is cell grouping, and this is the variable. N variable are there, cell grouping is of 1, 2, 4. In that manner, if we are going, so least count would be n minus 1, n minus k. So this you don't need to remember, we just took an example and then we solved it, right? So in any kind of variable, these kind of questions can come. I hope you have understood the problem. Let's understand it again. 3 variables were there. I assume that 2 cell grouping is there. So 2 cell grouping is there. So what will be the literal count? That would be BC bar. So literal count is 2, 1 and 2. So that is n minus k. Okay. K map for ABCD is given. Draw the K map for F bar. Let's just say, what is my F? F ABCD is summation M 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. What will be F bar? F bar will be what? Just whatever that is not there, that will come here. So 0, 2, 4, 5, 6, 9, 11, 12 and 14, right? 0, 2, 4, 5, 6, 9, 11, 12, 14. So similarly, wherever you here, if I am not marking anything, that means here there is 0, right? Here all are 0. So wherever there were 0, there would be 1, and wherever there were 1, there would be 0. So 1, 0, 0, 1, 1, 1, 0, 1, 1, 0, 0, 1, 0, 1, 1, 0. So basically, you can see 0, 0, 0, 0, 0, 0, 0. Rest all are 1. So you don't need to do this thing. Just take the inverted of each individual cell. Just I am taking the end of each individual cell, each respective cell. Okay, this is the respective cell of this one. So here I am taking the note of that. So this is what we need to do. Just take the note of each respective cell, right? Let's see the next question. Map the logical expression. Did I miss anything? No. Map the logical expression in K maps and find the reduced logical expression. Okay, so this is our question. So A bar plus BC, this is the first one, that is A bar plus BC, A bar plus BC. So this is A bar, this is A, this would be A bar plus BC. What is this? This is SOP. So in SOP only I will denote. So B bar C bar, B bar C, BC, BC bar. Now let's see it. A bar plus BC. So here only A bar is constant. In how do you think only A bar will be constant? That means this has to be 1, this has to be 1, this has to be 1, this has to be 1. So mark all the cells where you can see A bar. So A bar I can see in all these cells. So this is how I marked it. Then I need BC. So mark all the cells where you can see BC. BC I can see in these two cells. So what will be the possible grouping? This grouping and this grouping. So this is already reduced. That means this will be reduced Boolean expression. Already it is reduced. Okay, we cannot do further reducing. Let's see the second one. In second one, what they are asking? A bar plus AC. So this will be your A bar, this would be your A. B bar C bar, B bar C, BC, BC bar. A bar, wherever you see A bar, mark all that as 1. Wherever you see AC, mark all that 1. A is here, okay, and C is here. A is in this complete one and C is here and here. So what is the common part? These two are the common part. Are you getting this point? A is in the complete one and C are here. A bar plus AC. A bar plus AC. A bar is here and C is AC. That means A is completely here and C is only here. So what is the perfect grouping? This group, and they have done this grouping, but that is not the perfect one. The perfect grouping is this, because we can make a quad here. So what will be your reduced expression? Although I can see it would be A bar plus C only, but let's solve it from the key map. So in this particular quad, what is constant? Only A bar. And in this particular quad, what is constant? Only C, because A is changing and B is also changing. So A bar plus C. So this is the reduced Boolean expression. Okay, let's solve the next one. B bar C bar, B bar C, BC, BC bar. So I hope you are understanding how we are doing it. AC plus BC. Now this would be more interesting. AC plus BC. Okay. So wherever you can see A, here. Wherever you can see C, here. A here and C here. That means what is the common part? These are the common part. C I can see here and A I can see here. BC. Wherever you can see BC, this is the BC. That's it. So 1 and 1. What is the reduced expression? This would be there and this would be there. So if I choose this particular pair, so here A into C would come, and if I choose this particular pair, then B into C would come. So this is already reduced Boolean expression. We cannot reduce this Boolean expression further. So this is already reduced. Let's see the next one. That is A plus C into B plus C. So this is given in terms of product of sum. This is what? Product of sum. So what I will write here? A bar, B plus C bar, B bar plus C bar, B bar plus C, right? A plus C. So A you can see here and C you can see here. So what are the common part? These are the common part. B plus C you can see here. So what is the best possible pair? This one, and the other one would be this one, right? So again, this is also reduced Boolean expression, but this is how we can denote it. Yeah, so this is already reduced Boolean expression. Let's try it in with the 4 variable ABC plus CD plus ABD. 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 So this is your AB, this is your CD. So A bar, B bar. This is what? This is SOP only. A bar, B, AB and AB bar. C bar, D bar, C bar, D, CD and CD bar. AB, wherever you can see AB, here. How you can see C? C is here and C is here. So ABC will be written here. Plus CD. CD is complete this row. CD, CD and CD. ABD. AB you can see here and D you can see here. There you go. Okay. So this is also already reduced expression. Why is that so? Because this is the possible one. Then you cannot make a pair of 3. You can make only a pair of 2. Then again you need to make a pair of 2. And there are no redundant group. If you are thinking there is a redundant group, then you are thinking something wrong. There is no redundant group, right? So this is your reduced Boolean expression. This one is going into 3. This one is going into 3. But this one is alone. This one is alone. And these ones are alone. So there is no redundant group. So this is already reduced Boolean expression. You cannot reduce this one further. And what is this FD? That means this is don't care. Okay. This FD is don't care. So this I can copy because I will not be able to remember all this. So this was my don't care. Let's see if I can reduce it. This is AB, this is CD. So A bar, B bar, A bar, B, AB, AB bar, C bar, D bar, C bar, D, CD plus CD bar. This is not in perfect form, so I will make it perfect. So A bar, B bar, C plus A bar, B bar, C bar plus AB, C, D plus A, B bar, D bar plus C, sorry, B bar, C, D bar, B bar, C, D bar. Let me check it again. A bar, B bar, C bar, A, B, C, D, A, B bar, D bar, B bar, C, D bar. Okay. What about this one? A bar, B, C bar, D, A bar, B, C, D bar plus A, C, D. Okay, let's start now. A bar, B bar into C. A bar, B bar, A bar, B bar is here, and where I can see C, C I can see here only. C bar, D bar, C bar, D, C, D, C, D bar. Okay. A bar, B bar is here, and C I can see here. So this is done. A bar, B bar, C. A bar, B bar, C bar. A bar, B bar, C bar. C bar I can see here. Right? A, B, C, D. A, B, C, D. A, B, C, D. A, B bar, D bar. A, B bar, D bar. A, B bar, D bar. Right? A, B bar I can see here. D bar, D bar I can see here. B bar, C, D bar. So B bar, B bar I can see in this one. First let's check C, D bar. C, D bar is this one, and B bar, B bar I can see here. Are you getting this point? This is C bar, C, D bar. This is C, D bar. This is all C, D bar. And I need to check B bar. So B bar I can see here, B bar I can see here. So these two ones only come. So that has already been come, right? These ones have already been written. These ones are repeated twice. Are you getting this point? B bar, C, D bar. C, D bar is there, and B bar is there in these two. So these two are there. Okay. Now let's see. Don't care. A bar, B, A bar, B, C bar, D. A bar, B, C bar, D. A bar, B, C, D bar. A bar, B, C, D bar. A, C, D. A, C, D. There you go. Okay. A, C, D. So now you need to reduce it. Wait a second. What did I do just? Okay. This is A, C, D, no? A, C, D. Here you can see A, and here you can see C, D. But this is already 1. So this will be only don't care. Because we know this is already 1. Why did I write it 1 here? I should not write 1 here. So let's make the pairs. So this is the one pair that I can make. If I assume this as 1, then this will be a good pair, right? If I don't assume this one, then what will happen? This can go here, right? But what about this one? This one will be alone. So to make that, let's do this thing. So there are only 3 pairs. So what will be a reduced expression? A bar, B bar plus, for this one, A bar, B bar, because only A bar, B bar is constant. What about this one? A, C, D plus, what about this one? Here D bar is constant. So A, B bar, D bar. A, B bar, D bar. Okay, so this is the reduced Boolean expression. Reduced Boolean expression. So this is how if any function is given, you can represent in that manner, and then you can find the reduced Boolean expression. So there were so many of terms, but we reduced it to these many variables only. Why it is important to reduce these variables? Because we have to implement that on a chip, and if we use the least hardware, then the cost will be minimum. That's why we are reducing it. This is the target. Why we are reducing it? So that our cost is minimum, right? K maps for two logical expression F1, F2 is given. perform the following operation: f1 dot f2, f1 plus f2, f1 XOR f2, f1 XNOR f2. So these operations you need to perform. So how will you perform it? So if I write A, this is 0, 1, 2, 3, 4, 5, 6. So f1 is Minterm M1, 5, 6. 0, 1, 2, 3, 4, 5, 6, 7. Yeah. And f2 is Minterm M 0, 1, 2, 3, 4, 5, 6, 7. So 0, 1, 4, 6. 0, 1, 4, 6. So this is f1 and f2. Now I can perform the following operation very easily. f1 dot f2. That means only the common one will come. Venn diagram is in my mind. A into B. So only common will come. So 1 and 6. f1 plus f2. f1 plus f2. I will tell you another method. f1 plus f2 means everything will come. f1 plus f2. So 0, 1, 4, 5, 6. f1 XOR f2. So everything will come but not the common one. So 1, 6 will not come. 1, 6 will not come. So 0, 4, 5. And f1 XNOR f2. That would be 1, 2, 3, 6, 7. Apart from that, everything will come. Apart from here, everything will come. So this is the first way of solving it. This is the method 1, which we have covered here. But what if the K-map is very large? So what you will do? You will write down these things. This was very very easy K-map. That's why I could have solved it. But now let's just assume if it was very large, then how you would have done it. Okay, this is already there. Yeah. So what is my answer? What is my answer of f1 dot f2? What answer I am getting? That is 1 and 6. 1 and 6. 0, 1, 2, 3, 4, 5 and 6. This is the answer I am getting. So basically here there are 1, so rest all are 0 only, right? Rest all are 0 only. If I copy f1 and f2, what do you see here? If these are 1s, that means these all are 0. If I perform f1 dot f2, if I perform f1 dot f2, that means 0 into 1 will be 0. 1 into 1 will be, see the cell to cell operation. Cell to cell operation. 0 into 1 will be 0. 1 into 1 will be 1. 0 into 0 will be 0. 0 into 0 will be 0. 1 into 0 will be 0. 1 into 0 will be 0. 0 into 0 will be 0. 1 into 1 is 0. So cell to cell operation is being performed. So I will write, I should not write adjacent, cell to cell operation, or what I can say, yeah, cell to cell operation only I can say. Cell to cell operation is performed. Okay, so in all the questions you just need to perform cell to cell operation. So if I need to draw for f1 XOR f2, so what I will do? 0 XOR 1, 1, 1 XOR 1, 0, 0 XOR 0, 0, 0 XOR 0, 0, 0 XOR 1, 1, 1 XOR 0, 1, 0 XOR 0, 0, 1 XOR 1, 0, right? So this is how I can frame the operation. So if I am doing f1 XOR f2, then simply 0 XOR 1, 1, 1 XOR 1, 0, 0 XOR 0, 0, 0 XOR 0, 0, 0 XOR 1, 1, 1 XOR 0, 1, 0 XOR 0, 0, 1 XOR 0, 0. So what we are getting? Summation m as, this was your A, B, C. Summation m as 0, 1, 2, 3, 4. Sorry. This would be 4, 5. 0, 4, 5. Were we getting the same answer? 045. Yes, we were getting the same answer. So this is how you need to perform. Okay. So cell to cell operation is there. Cell to cell operation is performed. So this is very, very important line. Cell to cell operation is performed. That would be the correct answer. Okay. So always you need to perform cell to cell operation. Let's see 5 variable K map now. Okay. Very important concept. 5 variable K map. So for 5 variable we need to make 32 cells, right? So if I make 32 cells on one grid only, that would be very typical. So 16 I have made here, 16 I have made here. For the 16 ones, I have assumed A to be 0, and for another 16 one, I have assumed A to be 1. So for all these grids, A is 0. What BC value can take? 0, 0, 0, 1, 1, 1, 1, 0. What DE can take? 0, 0, 0, 1, 1, 1, 1, 0. Now tell me, what will be the value of this cell? The value of this cell will be A is already 0, where A is MSB, and E is LSB. So what will be the value of this cell? A is already 0 here. So 0 and rest all are 0 only. 0, 0, 0, 0. So this would be 0. Right? What will be the value of this cell? A is 0 and rest all are BC is 0 and D is 1. So this would be 1. What about this one? 0, BC is 0, D is 1, 1. So this would be 3. This would be 2. In that manner we will go. This would be 4 because A is 0, BC is 0, 1 and D is 0, 0. Right? So what that would be? 1, 2, 4. So that would be 4. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Oh, sorry. Blunder I am doing here. Sorry. What is the blunder? 8 will come here, no? 8, 9, 10, 11. Why 8 will come here? Because A is already 0 and this is 1, 0, 0, 0. So this is 8 only. 8, 9, 10, 11. 8, 9, 10, 11. 12, 13, 14, 15. Now what about this one? Again this will take 0, 0, 0, 1, 1, 1, 1, 0. 0, 0, 0, 1, 1, 1, 1, 0. What will be the number of this one? A is already 1 and B, C, D, E all are 0. So 1, 2, 4, 8, 16. So this would be 16. So this number would be 16. A is already 1. BC is 0. D is 0. E is 1. So 16 plus 1, 17. This would be 18. This would be 19. 20, 21, 22, 23. What about this number? What will be this number? 1, 1, 0, 0, 0. So 1, 2, 4, 8, 16. This would be 24. So this number would be 24, 25, 26, 27, 28, 29, 30, 31. So in that manner we will go. Right? Okay then. Now can you tell me which all cells are adjacent? Just a question. It will not be used in our analysis. It will not be used. But I am asking you, 9 is adjacent to which all cells? Can you tell me that? 9 is adjacent to 13. 9 is adjacent to 8. 9 is adjacent to 11 as well. 9 is adjacent to 1 as well. That you know. 13, 8, 11 and 1. But 9 is adjacent to some other cell as well. Can you tell me which cell? 25. Why is that so? Let's check that out. This is your 9, right? How I can write 9? 0. From here only I am writing. A is 0, BC is 1, 0 and D is 0, 1. So this is 9. What about 25? 25. A is 1, BC is 1, 0 and D is 0, 1. So your 9 is 0, 1, 0, 1 and your 25 is 1, 1, 0, 0, 1. How many difference bit is there? Only one bit is different. These 4 bits are same. Only one bit is different. So in adjacent cell, there is difference of only one bit. So these two cells are adjacent cell. So corresponding cells are adjacent to each other. Okay, corresponding cells are adjacent to each other. That means this cell is adjacent to this one. These are certainly adjacent. 9, 9, 1, 8, 11. 9 is adjacent to 8, 9 is adjacent to 11, 9 is adjacent to 1. But these cells are also adjacent. Let's just say 15 will be adjacent to 31. Right? 3 will be adjacent to 19. So these cells will also be adjacent. If I say this pair, so this pair will be adjacent to this pair, right? These two pairs will also be adjacent. Or what I can see that this particular pair will be adjacent to this particular pair. So these two pairs will also be adjacent, right? So although diagram is being a bit hazy, but you are understanding the concept. Although it will not be used, I will tell you a simple method how to solve the problems. But what if in one liner they are asking this question that 13 is the cell number 13 is adjacent to what? So 12, 9, 15, 5, but 29 as well. Okay, so this you need to take care. Let's solve the problem. Summation m is given, 3, 4, these values are given, and you need to write down the Boolean expression. So reduced Boolean expression you need to write down. So this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. Let's make the best possible pairs. So is this the best possible pair? No. If you see smartly, there you go. This is the pair we are getting. Four here and 4 here. Are you getting this point? The same kind of pair we are getting here as well. This pair we are getting here. This is the pair we are getting here, this one, right? And in the other one, this is the pair we are getting. Right? This pair. Okay, let's write down the numbers. So B bar, C bar, B bar, C, BC, BC bar, B bar, E bar, B bar, E, DE, DE bar, B bar, C bar, B bar, C, BC, BC bar, D bar, E bar, D bar, E, DE, DE bar. Let's solve for this one. Okay, here A is 0, that means A can be replaced with A bar, because this is what we are talking about, SOP, Maxterm SOP, sorry, Minterm, not sorry, Maxterm, Minterm. So for Minterm, if A is 0, that means A will be replaced with A bar, and if A is 1, it will be replaced with A. So let's look at A bar only. So if A bar is there, then which pairs we are getting? Here what is constant? C is constant, and in this one E bar is constant. So C E bar plus, in this one which is constant? D is constant, and here C bar is constant. So C bar D E. Let's check back again. A bar, for A bar, C E bar is constant. C, here C is constant and E bar is constant, C E bar. So from here we are getting A bar C E bar plus, for A bar C bar, in this one D is constant and C bar is constant. So C bar D E bar. Let's check for this A. So for A we are getting, wait a second, call is, yeah. So for A what is coming? C is constant and E bar is constant. So C E bar plus, Here d bar e is constant and c bar is constant. So c bar d bar e, c bar d bar e. So here what you are getting, a c e bar plus c bar d bar e. So what is your final output y? Addition of all this. So a bar c e bar plus a bar c bar d e. Here a is also there, plus a c e bar plus a c bar d bar e, right? Can you reduce it more? No, like yeah, we can certainly reduce it. This term we can certainly reduce more, right? Because here a will come in common. Sorry, c bar will come in common. So a plus a bar. From here also we can reduce it. That I will tell you. But I was thinking about this term. Can I reduce it more? C bar, no, d c bar e if comes common. No, there is no other chance. Yeah. So a bar c bar de plus a c bar de. So basically total y is coming from here. Total y is coming as c e bar plus a bar c bar de plus a c bar de. A c bar d bar e. A bar. Yeah. So now it is fine. A bar c bar d e. Yeah. Okay. So this is the final expression. Now from here, what did you get to know? That a and here c bar was coming common and a plus a bar would be 1. So that you did not write here. How would you understand this in the K map only? So what did I tell you? These cell and this cell is adjacent, right? So this pair, this is actually not a quad. This is a octet. Look, these are adjacent to each other, no? This is not a quad, this is a octet. This one is adjacent to this one. 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 So this is a complete octet where a is also changing. Here a is 0 and here a is 1. So here a is also changing. So a will not come in the final answer. So directly I could have written c e. Here c is constant and e bar is constant. So directly I would have written c e bar. So in that manner I could have done it. Okay. Are you getting this point? This is a octet, not quad. 4, 4, and these 4 are adjacent to each other. So that's why I could have directly written C E bar. But this is the method I usually go with. I will just write down A bar and then solve all this. Then I will write down A and then solve all this. But in this question, I could have directly seen that the same octave, the same quad I am getting on both of the side. That means that will make octave. And if that is making octet, that means A is also changing. So A bar or A will not come in answer. So only CE bar would come in final answer. So this I could have done. Now solve this problem. You need to draw the K map. So try doing it on your own. I will have to pause the video because I have some work to do, and then I will come back and solve this particular problem. Okay. So did you attempt this question? So what we need to do? We need to plot. So let's do B bar C bar, B bar C, BC, BC bar, D bar E bar, D bar E, DE, DE bar. Here B bar C bar, B bar C, BC, BC bar, D bar E bar, D bar E, DE, DE bar. Okay. I need to plot. First one is this would be our A bar and this would be our A. So first one is A bar, B bar, D bar. So only in A bar we need to see, and B bar, D bar, B bar and D bar. So B bar is here, D bar is here, and this is there in A bar only. Now BCE, BCE, BC is here and E is here, BC is here and E is here. Wait a minute. Some A bar is here and B bar, D bar is here. B bar is there and D bar is there. Okay, yeah. BCE. So in now this BCE is there in A bar as well, and this BC is there in A as well, right? Because if you take BCE common, then a bar plus a would be 1. So this BC is there in a bar and a both. So BC, this is BC and E, right? So similarly here as well. CDE bar, CDE bar, C is there in this one, and DE bar. This is your DE bar, DE bar. This is your DE bar, and this is your C. So similarly here as well, DE bar, and here there is C, right? A B D bar. A, that means only here, and B D bar. This is your B, and this is your D bar. So B D bar, right? So this is the way I can proceed. So can I find the reduced expression of this? So this quad I am getting, this quad I am getting here. Here I can get another quad, and this pair I can get here. This same pair I can get here as well, right? But the same quad I cannot get on this side. I can get this here. So here there is 3 pairs, here there is 3 pairs. So in that manner I can do my pairing and write down my final answer. Okay, so only one pair is common there, only this one pair is common, rest all nothing is common. So let's try writing down the final answer. So let's see. So what we will get for a bar, y would be a bar, here b bar is there, and here d bar is there, b bar d bar, plus this is only here as well, a bar is the element of 4, this is a pair of 2, and if I had made this pair, look, there is very interesting thing in this problem, very interesting thing. What is that? Let's remove everything and let's make the pair again. Okay, so one quad I can see and one quad I can see. 4 element, both are different. 2 element, total element will be 4, right? Now I need to pair these two and I need to pair these two. If I make this one, basically I need to pair these two and I need to pair this one, right? I need to pair this one. So if I make, because here I can see 4 elements, so if I make this one, then I am getting a pair of 4, then another pair of 2 I have to make. Did you understand this point? Till this point everything is fine. 4, 1 common, so this is a pair of 4, this is a pair of 4, this is a pair of 4. Total 3 pairs I have made till now. 1, 2, and these two are adjacent to each other. So total 3 pairs till now I have made. Now I need to pair this one and I need to pair these two ones. So what I can do, if I make this quad, then another pair I have made plus 1, and then if I make this pair, then another one, another clubbing I have done. So total clubbing is 5. Do you agree to this point? Total clubbing would have been 5. 1, 2, 3, 4 and 5. Agreeing? Now if I have been a bit smarter, then what I could have done? Here I would have done this pairing. Now the same pairing I can do here. If I do the same pairing, so previously I had done 1 pair, 2 pair and 3 pair. Now I just need to make, this is 1 pair only because these two are adjacent to each other. So 3 plus 1, only 4 pair will be there. So in 5 variable K map, if I was making 4 variable if I was clubbing these 4s in one go, then I was making 5 pairs. But if I am clubbing these two and these two, then only 4 pairs are there. Everything is quad only. This is a quad, this is a quad, this is also a quad, and this is also a quad. So 4 quads I have made. So this was very interesting thing, and this will be the reduced expression only because 4 pairs are there and 4 we will be getting. If I had made 5 pairs, then I will be getting 5 terms, and that will not be our reduced expression. We need to reduce it further, but 4 pairs are possible. So that way we can proceed. So you just need to know this thing, that these correspondings are adjacent to each other, so we can pair them up. So we can make a quad and only one pair would be there, otherwise I had to make 2 pairs. So that was very interesting thing in this problem, and this would be the reduced pair. So that is the final answer only, right? Let's go to the next question. This you can plot, but this I have written wrong here. Why so? Because this is a Maxterm. Maxterm means I will think in terms of POS. So here I have to write B plus C, here I have to write D plus C. And what this will be denoted as? This will be denoted as A, this will be denoted as A bar. This is B plus C, B plus C bar, B bar plus C bar, B bar plus C, D plus E, D plus E bar, D bar plus E bar, D bar plus E bar plus D bar plus E. So D plus E, D plus E bar, D bar plus E bar, D bar plus E, B plus C, B plus C bar, B bar plus C bar, B bar plus C. This is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, sorry. This error I do a lot of time. 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Sorry, 20, 20, 21, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 28, 29, 30, 31. Let's check back again. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. There you go. Okay. So here I will do the clubbing. So first I can see a quad here. These two and these two. Another quad I can see. These two and these two. Right? What else I can see? Another quad I can see. What is that? This. And this. Now I can club these two together. Basically, this will be clubbed with this. Although only one element is clubbed. No. What I can do is that sorry. This can go like this. 2 and 2, 4. 4 element, 4 element, 4 element, and then this is also 4 element. Now what else I can do? This will be a 2 element, right? This has to be 2 element only, because there is no other option left. This has to go in this manner only. 2 element, and this has the option of being paired with this particular element. Right? So a lot of pairs are there. Let's try writing the final answer. So this chord and this chord is there. So here C bar is there plus D plus E bar. D plus E bar. A will not come. Why it will not come? A and A bar will not come. Why? Because it is there in A as well, it is there in A bar as well. So this pair and this pair is gone into these two. These two I am taking. So here what is constant? E bar is B bar C is constant. B bar plus C is constant, and then E bar is constant plus E bar is constant. Okay. In this one, B bar plus C plus D bar, right? Plus D bar. Because these are common to both of them. This is also common to both of them. This pair. So this pair is gone. This pair is gone. This pair is also gone. This pair is also gone. Now talking about this pair. That is also common. A is also common. What about this one? B here. C is constant and D bar plus E bar. C plus D bar plus E bar. Right. So this pair and this pair is gone. Which one is left? This is left. So this is there only in A bar. So A bar plus what is constant here? B plus C bar. What else is constant here? Plus D bar. And what about this one? This is also common in both. So here B plus C bar is already constant and D bar plus E is also constant. Right? So can I reduce it more? No. I guess this is the final answer. This is my reduced expression. That's it. But these kind of questions will take a lot of time, and there is 99.95% chance that this will not be coming in your examination. But this was a very good question where we had to see all the possible possibilities. Quad is coming here, quad is coming here, quad is coming here, this quad, and then this pair and this pair. So there were 2 pairs and 4 quads. 4 quads and 2 pairs. So this kind of question can come that after clubbing, what you are getting? 4 quad, 2 pair, 4 pair, 2 quad, 1 single element, 2 pair, 3 quad. These kind of questions can come. So this was a good question. So that is the correct answer. Let's move towards the next one. So now we will see now 5 variable K-maps is completed. So this is the maximum limit that can come. Although only one question has, or 1 or 2 question have come from 5 variable K-map. Okay, and you will be able to solve it with the concept that I have given. That is more than enough. So with that concept, you will be able to solve any problem of 5 variable K-map. Let's see the K-maps of XOR gate and XNOR gate, because there will be some kind of symmetry. Can you make the K-map for this one? A bar B. This is your XOR gate only, no? So A bar B plus A B bar 0 1. So in XOR gate, it will always start from 0 and 1, and alternatively you need to write 0 1 0 1. And in XNOR gate, it will start from 1 0 1 0. Alternatively, you need to write 1 0 1 0. That's it. How will you remember if it is starting from 0? It would be XOR or XNOR. So you know one thing, that 0 XOR 0 will be 0 only. 0 XOR 0 XOR 0 any time will be 0. And first term, this term is always 0 0 0 0 0 0 0 only. So XOR gate will start from 0 onwards. Are you getting this point? This particular cell will always be in 2 variable, it will be 0 0. In 3 variable, it will be 0 0 0. And in 4 variable, it will be 0 0 0 0. In 5 variable, it will be 0 0 0 0 0. So always it is starting from 0 only. And if 0 XOR 0 you do any time, it will always give you 0. So XOR gate will start from 0 and alternatively you need to write 1 0 1 0. Okay. What this will represent? Starting from 0, alternatively 0 1 0 1 0 1 0 1 is written. That means this will represent A XOR B XOR C. But wait a minute. For 3 variables, XOR gate and XNOR gate are same. So this will represent this as well. What this will represent? It is starting from 1. So can I write down this thing? It will represent this. No, that is wrong, because both are same. So it will represent bar of this. Bar of this. I need to. Basically, if this is A XOR B XOR C, then these are the complemented form. This is simply the complemented form, no? So this is also simply a complemented form. This is also simply a complemented form only. 0 is replaced with 1, 1 is replaced with 0, 1 is replaced with 0, and 0 is replaced with 1. So this is also A XOR B bar, and A XOR B bar can be written as A XNOR B, but A XOR B XOR C bar cannot be written as, this is not equal, right? Both are the same thing. So this can be written as A XOR B XOR C bar. And if you remember one of our assignment, then I told you it can be written in this manner as well. It can be written in this manner as well. It can be written in a lot other manner as well, that B can come here, A XOR C. Basically, what I am doing, let's check. I will again tell it. So I am doing A, this is written as A XOR B XOR plus C. So can I assume it as X XOR Y, where X is A, Y is B XOR C, and whole bar is there. I told you one property, if a whole bar is there, you can take bar on one of the functions, right? Can I write it in this manner? Yes, you can write it in this manner. So this is X bar XOR Y. Can I write it as X bar Y XOR? And can I write this as X bar X XNOR Y? Yes. What is your X? A XNOR with B XOR C. Whatever the thing that you have done with, so from here you are getting this one. Whatever the thing that you have done with A, do the same with C, you will get this expression. Do the same with B, you will get this expression. Are you getting this point? So basically, this can travel anywhere. If there is bar on the whole one, then one of them can be replaced with dot, and this dot can travel anywhere. So this is the way you can remember it. Okay. What all other possible cases are there? I could have written as C XOR A, or I could have written C B XOR A, or I would have written, because this is the other answer, so I would have written C XOR A, C XNOR A XOR B. So A B C can be interchanged, and this bar, and this plus and dot can move around. Okay, so they are moving around. So in that manner we can do. You can prove it as well. I have given the proof. Whole bar can be taken on one bar. Let's just say I prove this statement. So how I can prove this one? So can I write it in this manner? Bar is coming on 1 and then this. Now what is A plus B whole bar? That is this, right? And here is this one. So you can prove anything. Now here these two are inverted only. B is coming here, A is coming here. So both things are same only. Here also C and B are inverted. Basically anything can move around. You can prove this one. How will you prove this one? A XOR. Can I write it in this manner? Yes, you can write it in this manner. It would be A XOR. What is this? And now these two can move. C XOR B XOR with A. This you are getting. So on top level, how will you remember it? That one of them will be replaced with dot and one will be plus only, and then they can move around. That's it. This is how we will remember it. What about this? What this will represent? What this will represent? Starting from 0 and alternatively 1 0 are written. So this will be your A XOR B XOR C XOR D. What this will represent? Starting from 1, alternatively 0 are written. So this will be bar of, basically bar of this. And what is the bar of this? Since these are the 4 variables, that means even number of variables. So for even number of variables, this would be the condition, right? Let's see the next one. So K-map is shown. What this represents? Tell me. For A, this is your A bar and this is your A. So for A bar you are getting B XOR C XOR D XOR E, and for A also you are getting the same thing, B XOR C XOR D XOR E. So can I write it down in this manner? For A bar I am getting B XOR C XOR D XOR E, and for A I am getting B XOR C XOR D XOR E. So A I will take yeah, so this is what I am getting. Okay, so I cannot take A as common. So what that would be? A bar, this I can write X bar into Y plus X into Y. This is the scene, right? So I can take this B XOR C XOR D XOR E common, that is being taken common, and here we are having A plus A bar, and A plus A bar will be 1. So what you are getting? B XOR C XOR D XOR E. So that would be the correct answer, right? Let's see the next one. If A is 1, A is 0. So if A is 1, what you are getting? If A is 1, what you are getting? This is B XOR C XOR D XOR E bar, right? Plus, if A is 0, that means A bar. So if A is 0, what you are getting? B XOR C XOR D XOR E. So this is X Y bar plus X bar Y. So that would be X XOR Y. So what is your X? X is A and Y is this. So what we are getting? A XOR B XOR C XOR D XOR E, right? X is A and Y is this one. So X Y bar plus X bar Y. So A XOR B XOR C XOR D XOR E. So this is what we are getting, and this is same as this one. Say yes or no? Both are same thing only, no? Because these are 5 variables. D XOR E. So 5 variables will be the same. So this is the same as this. Okay, so that is the answer we are getting. Okay, let's check this question. The same K-map is given, huh? The same K-map is given, but yeah, these 0 and 1s are replaced. So for A bar you are getting B XOR C XOR D XOR E bar, plus for A you are getting B XOR C XOR D XOR E. So this is X bar Y bar plus XY, that would be X dot Y. So that would be A dot B plus C plus D plus E. So this option is correct. What other option could be correct? Can I write this as A XOR B XOR C XOR D XOR E bar? How did I write it? Think about it and then only watch the solution. How did I write it? If I assume X, A as X, XOR, this is your complete Y, sorry, XNOR. So that can be written as this thing. So A is X, XOR B XOR C XOR D XOR E. Now what I can do? If this bar is there, then one of them will be replaced with dot, and then that can move anywhere. Now this dot can move anywhere. So from here this option is correct, right? Along with that, what other thing can happen? That all the plus will be replaced with dot and one of them will be plus. This can also happen, that all of them will be replaced with dot and only one of them will be plus, and then this plus will keep on moving. So this plus is moving here, this plus is moving here. So all of them will be replaced with dot. How I am doing so, you can prove it on your own, right? What I am doing, A XOR B, and then whole bar I am taking on this one, B XOR C XOR D XOR E. So what is the bar of this? That is B XOR C XOR D XOR E. So all these plus are replaced with dot and one of them is plus. Other thing can also happen, all these are plus and this is dot. So in 3, 5, 7, 9, in odd number of variables, what you can do? Shall I write it? So all 4 options are correct. So from here, very interesting conclusion is there. First thing, for 2 variables, bar of this will be equals to A bar XOR B, right? Or it could be replaced as this. For 3 variables, these two are equal to each other, right? Bar of this, if I take bar of this, that means any of them can be replaced with dot and can move around. One is dot, one is plus, and it can move around. Between B and C is there, A and B is there, between A and C also it could be there. B can come in starting, then between A and C it could be there. So basically it can move around. For 4 variables, A XOR B XOR C XOR D bar will be equals to what? A XOR B XOR C XOR D. Anything else we can do here? Yeah, we can do more things here. What things we can do? That this is replaced with the bar and this is taken as one thing only, right? This is what I am doing. Now this can be replaced as right. This can also happen. Are you getting this point? Now can this bar keep on moving? Yes, this bar can also keep on moving. This is A bar. What else I can do here? That I do A plus B whole bar and then C plus D is there as it is. So this could be a C XOR D, sorry. So A XOR B and in between there is C and then XOR D. So this dot can keep on moving here as well, right? And certainly bar of this is equals to A XOR, because B XOR C XOR D is equals to B XNOR C XNOR D. So this can be replaced with this and these two can be alternative. Basically this and this are equal only, no? So this is what we are doing. This can also happen, right? Because A plus B bar if I take and then, so it would be X bar XOR Y. So that can be replaced as X XNOR Y. So this I have replaced. So these things can happen. So in MSQ these kind of questions can come up. So this is what I was trying to do here. Now can I replace 2 with the dot? No, that would be tough. 2 with dot we cannot replace. Basically what I was trying to do, A XOR B XOR C bar XOR with D. But bar of this will be what? Bar of this will be A XOR, bar of this will be one of this, A XOR B XOR C XOR D. This we have already got. So in this one, what did we get to know? That only one of the plus will be replaced with dot. These conclusion I am making here only. Okay, here only I am making these conclusions. Just we are playing with this bar thing, with XOR XOR thing. So only you don't need to remember these conclusion. Okay, just I am telling if some questions are, if some question is coming in MSQ, because there are MSQ as well. So you need to check all 4 options. We don't want you to do that particular question wrong. So if a whole bar is there, one can be replaced with a dot, right? If whole bar is there, only one can be replaced with dot and rest all will be the same. It cannot happen that 2 dots are there and 2 dots cannot be there, right? 2 dots cannot be there, because if 2 dots are there, then 2 bar will come. Yeah, that cannot happen. So 1 and 2, in that manner we can do. And for 3, for 5, that would be equal only. And if you take the bar, then what will happen? That we have already proved that all of them can be replaced with the dot, but one will be at least plus, right? These can be replaced with the plus only, but one of them can be dot, or this dot can keep on moving, basically A XOR B XOR C XOR D XOR E, and then this plus can also keep on moving, A XOR B XOR C XOR D XOR E, and these variables can also keep on moving. So these kind of things can happen. Are you understanding why this is happening? Actually, the thing is, if 3 dots are there, that means I can make 3 bars. And if I'm basically, if 3 dots are there and I need to convert it into plus, that means I need to take 3 bar, 1, 2 and 3. And if 3 bars are there, that means it will be replaced with 2 bars will cancel each other and single bar will be there. So this is only we are getting. Here also I replaced 1 dot. So basically I can take 1 bar. To convert this dot into plus, I can take 1 more bar. So if I convert this dot into plus, I will have to put 1 bar there. So the same thing I am getting. If I need to convert this dot into plus, that means I need to take 1 bar. If I need to convert this dot into plus, I need to take 1 more bar. If I need to convert this dot into plus, I need to take 1 more bar. So if I am taking 3 bar, that means 2 bars are cancelled and 1 bar is left. So this is the final conclusion. This is very interesting conclusion that we have come through. To convert a dot into plus, you just need to take a bar. That's it. To convert this dot into plus, I just need to take a bar. So what I will be getting? This expression only. To convert this dot into plus, I need to take 1 bar, 2 bar and 3 bar, because there are 3 dots. So this is an interesting conclusion, right? So from options we can check in this manner that there are 3 dots. That means I need to take 3 bar to convert these dot into plus. So if I am taking 3 bar, then 2 bar are getting cancelled and 1 bar is there. So eventually I am getting this expression only, or this expression. Basically I can write this as this expression. So eventually I am getting this expression only, right? So similar thing goes here. There are three dots, so 3 bar will be there. To convert that into plus, there is 1 dot, so 1 bar will be there. So to convert that into plus, so same expression we are getting. There is 1 dot, so 1 bar. So this is the interesting conclusion, very interesting conclusion. What did you understand? So one more thing I will write. Let's write down a question only. Question: y is equals to A XOR B XOR C XOR D XOR E XOR F XOR G 3 3 6 7 will be equivalent to option A XOR B XOR C XOR D XOR E XOR F XOR G whole bar. B, A XOR B, XOR C, XOR D, XOR E, XOR F. XOR G. C, C option, what I can write? A XOR B, C, T, E, F and G. And D option I am writing A XOR B, XOR C, XOR D, XOR E, XOR F and XOR G. All these are XOR only. So which of these options are correct? What do you think? Which is your correct answer? 1, 2 and 3. Why is that so? Because there are 3 bars. If you need to convert these 3 bar into one dot is converted to plus, this dot is connected to plus, this dot is connected to plus. So if I convert all these to plus, that means 3 dots I converted to plus. So 3 bars I will have to take. 1 bar, 2 bar and 3 bar. So if I am taking 3 bar, then these 2 bars are getting cancelled. So finally I am getting A XOR B, XOR C, XOR D, XOR E, XOR F, XOR G bar. So this is matching with option 1, right? If I go with the option B, so in option B 1, 2, 3, 4, 5, 5 dots are there. If I need to convert these dots into plus, so I will need to take 5 bars. I will need to take 5 bars. So 1, 2, 3, 4 and 5. I am taking 5 bar, 4 of them are getting cancelled. So basically A XOR B, XOR C, XOR D, XOR E, XOR F, XOR G. So this is equivalent to this only. Right, and for the C1 only 1 bar I need to take. So A XOR B, XOR C, XOR D, XOR E, XOR F, XOR G. So only 1 dot is there, so only 1 bar I need to take. So this is also equivalent. In D, how many dots are there? How many dots are there? 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. 6 dots are there. That means I will take 6 bar. And if I am taking 6 bar, that means this will be equivalent to A XOR B XOR C. 6 bar means same only. D XOR E XOR F XOR G. So it will be coming out to be same only. Because if I am taking 6 bar, it is coming out to be same. 6 bar will cancel each other. 2 cancel each other, 2 cancel each other, 2 cancel each other. So this is coming out to be this, but this is the bar of that. So if there is bar of that, that means both are different thing. So that is our correct answer, A, B and C. So in that manner we can solve. So yeah, a lot of new things we got to understand in this lecture. We got to understand about 5 variable K-maps. We got to understand how to plot them in K-maps, how to write down the reduced expression. So these 2 lectures are there, would be of around 2.5 hours. Now we are going to study about implicants, prime implicant, essential prime implicants, redundant prime implicants, selective prime implicants. These implicants we are going to study in the next lecture. So let's meet you in the next lecture.